exploring the universe. On a fine bright night, when you look up at the sky, it seems to be studded with stars. Little do you realize that each of the stars is far bigger than the Earth on which we live. Some of the larger ones have been estimated to be many millions of times the size of the Earth. These stars are not scattered regularly in space. They occur in clusters, better described as galaxies or nebulas. Each galaxy may contain as many as 100 million stars. It is believed that the Earth's own galaxy, the Milky Way, alone contains as many as 100,000 million stars. The stars appear small to us even through a telescope because they are so far away. The light from the nearest star traveling at the speed of light, i.e. 186,000 miles per second or 299,792 kilometers per second, takes something like 4 years to reach us. A ray of light from the sun takes about 8 minutes to reach the Earth. Light takes only a second to reach us from the moon. The solar system. The solar system comprises the sun and its 8 planets, figure 1, which are believed to have been developed from the condensation of gases and other lesser bodies. All the planets revolve round the sun in elliptical orbits. Like the Earth, they shine only by the reflected light of the sun. The sun has a surface temperature of 6,000 degrees Celsius 10,800 degrees Fahrenheit and increases to 20 million degrees C, 36 million degree F, in the interior. All over its surface are fiery gases that leap up in whirls of glowing flames like a volcano in eruption. In size, the sun is almost unimaginable. It is about 300,000 times as big as the Earth. Amongst the 8 planets, Mercury is the smallest and closest to the sun, only 36 million miles, 57.9 million miles away. It thus completes its orbit in a much shorter space of time than does Earth. A year in Mercury is only 88 days. Venus, twice the distance away from the sun, is the next closest planet. It is often considered as Earth's twin because of their close proximity in size, mass, weight, and density. But no other planet is in any way comparable to Earth, which is life and all the living things we see around us. Like many other planets, the Earth has a natural satellite, the Moon, 238,900 miles, 384,000 kilometers away, that revolves eastward around the Earth once in every 27 days. Figure 1. The solar system, the sun and the 8 planets. 2. Part 1. Physical geography. The 4th planet from the sun is Mars, which has dark patches on its surface and is believed by most professional astronomers to be the next planet after Earth to have the possibility of some plant life. Much attention has been focused on Mars to explore the possibilities of extending man's influence to it. Mars has 2 tiny natural satellites. Next comes Jupiter, the largest planet in the solar system. Its surface is made up of many gases like hydrogen, helium, and methane. It is distinguished from other planets by its circular light and dark bands, and the 79 satellites that circle round it. As it is more than 485 million miles, 778 million kilometers, from the sun, its surface is very cold, probably about minus 200 degrees Fahrenheit, minus 130 degrees Celsius. Another unique planet is Saturn, which has 3 rings and 53 satellites around it. In size, it is the second largest after Jupiter. It is so far from the sun that it takes 29% years to complete its orbit. The 7th planet, Uranus, was not known to astronomers until the late 18th century when it was first seen as a faint bluish-green disk through a very powerful telescope. It is another giant planet, 50 times larger than Earth and 15 times as heavy. Unlike other planets, Uranus orbits around the sun in a clockwise direction from east to west with 27 satellites revolving round it. The outermost planet in the solar system, Neptune, is just visible with telescopes. Discovery of Neptune was the result of mathematical calculations on its irregular gravitational effects on neighboring planetary bodies. Neptune closely resembles Uranus, except that it has only 14 known satellites and is probably much colder. Dwarf planets and Plutoids. Pluto, which was considered to be a planet since its discovery in 1930, was reclassified as a dwarf planet on August 24, 2006 by the International Astronomical Union (IU). According to the IU, a dwarf planet fulfills the following criteria. It is in orbit around the sun. It has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, nearly round shape. It has not cleared the neighborhood around its orbit. It is not a satellite of a planet or other non-stellar body. 2 years after coining the term dwarf planets, the IU has decided to call trans-Neptunian DWRF planets similar to Pluto, Plutoids. While all Plutoids are dwarf planets, all dwarf planets are not Plutoids. Currently, there are 5 celestial bodies that have been redefined by the IU as dwarf planets, of which 4 belong to the subset Plutoids. Eris, Pluto, and most recently, Makemake and Haumea have been classified as Plutoids and dwarf planets, while Ceres remains in the category dwarf planet. The shape of the Earth. In the olden days, sailors feared to venture far into the distant ocean because they thought the Earth was as flat as a table. They thought that when they reached the edge of the Earth, they would slip down and perish in the bottomless ocean. This is, of course, not true. From years of accumulated knowledge, experience, and observations in different parts of the world, we know that the Earth is round. Its spherical shape is an established fact, proved and accepted by all. There has been so much research done on Earth science that its various dimensions have been accurately found. It has an equatorial circumference of 24,874 miles, 40,030 kilometers, and its polar circumference is less by 83 miles. Its equatorial diameter is 7,918 miles, 12,742 kilometers, and its polar diameter is shorter by 26 miles, 42 kilometers. This simply shows that the Earth is not a perfect sphere. It is a little flattened at both ends like an orange. It can, in fact, be called a geoid, Earth-shaped. The spherical shape of the Earth is also masked by the intervening highlands and oceans on its surface. Evidence of the Earth's sphericity. There are many ways to prove that the Earth is spherical. The following are some of them. 1. Circumnavigation of the Earth. The first voyage around the world by Ferdinand Magellan and his crew, from 1519 to 1522, proved beyond doubt that the Earth is spherical. No traveler going round the world by land or sea has ever encountered an abrupt edge over which he would fall. Modern air routes and ocean navigation are based on the assumption that the Earth is round, Figure 2. The Earth and the Universe 3. Figure 2. A. Circumnavigation of the Earth. 2. The circular horizon. The distant horizon viewed from the deck of a ship at sea or from a cliff on land is always and everywhere circular in shape. This circular horizon widens with increasing altitude and could only be seen on a spherical body. This is illustrated in Fig. 3. 3. Ship's visibility. When a ship appears over the distant horizon, the top of the mast is seen first before the hull. In the same way, when it leaves harbor, its disappearance over the curved surface is equally gradual. If the Earth were flat, the entire ship would be seen or obscured all at once. This is apparent from Fig. 4. B. Abrupt drop at the edge of a table like Earth. Figure 4. A. The mast of a ship is seen before the hull on curved horizon. B. A flat Earth. The entire ship is seen at once on a flat surface. Figure 3. A. Increasing altitude widens the circular horizon. Viewed from Y, the horizon would be AB, but from a higher viewpoint, X, a wider horizon, C, D, would be seen. B. Visible horizon remains the same regardless of altitude. If the Earth were flat, the horizon seen from either Y or X would be the same. Sunrise and sunset. The sun rises and sets at different times in different places. As the Earth rotates from west to east, places in the east see the sun earlier than those in the west. If the Earth were flat, the whole world would have sunrise and sunset at the same time. But we know this is not so. RG 5 illustrates this. 5. The lunar eclipse. The shadow cast by the Earth on the moon during the lunar eclipse is always circular. It takes the outline of an arc of a circle. Only a sphere can cast such a circular shadow. Part 1. Physical geography. Figure 5. A. Sun rises and sun sets at different times for different places. The Earth, as illustrated in Fig. 6. Surveyors and field engineers therefore have to make certain corrections for this inevitable curvature, i.e. 8 inches to the mile. B. The whole world will have sunrise or sunset at the same time. Center pole projects above others level. Figure 6. A. The center pole projects well above the poles at either end on a curved surface. B. All the 3 poles have identical heights on a flat surface. 8. Aerial photographs. Pictures taken from high altitudes by rockets and satellites show clearly the curved edge of the Earth. This is perhaps the most convincing and the most up-to-date proof of the Earth's sphericity. 6. Planetary bodies are spherical. All observations from telescopes reveal that the planetary bodies, the sun, moon, satellites, and stars have circular outlines from whichever angle you see them. They are strictly spheres. Earth, by analogy, cannot be the only exception. 7. Driving poles on level ground on a curved Earth. Engineers, when driving poles of equal length at regular intervals on the ground, have found that they do not give a perfect horizontal level. The center pole normally projects slightly above the A less at either end because of the curvature of the Earth's movement. Man is always conscious of the apparent movement of the sun and little realizes that the Earth on which he stands is constantly in motion. When the sun disappears, he says that the sun sets, and when it emerges, he says that the sun rises. He is not the least aware that the sun, in fact, does not rise or set. It is we who rise and we who set. The Earth moves in space in 2 distinct ways. It rotates on its own axis from west to east once in every 24 hours, causing The Earth and the Universe 5. The Earth viewed from the Moon. The picture was taken on the Apollo 8 mission of 1968, which prepared the way for the moon landing. Day and night. It also revolves round the sun in an orbit once in every 365 carat days, causing the seasons and the year. Day and night. When the Earth rotates on its own axis, only one portion of the Earth's surface comes into the rays of the sun and experiences daylight. The other portion, which is away from the sun's rays, will be in darkness. As the Earth rotates from west to east, every part of the Earth's surface will be brought under the sun at some time or other. A part of the Earth's surface that emerges from darkness into the sun's rays experiences sunrise. Later, when it is gradually obscured from the sun's beams, it experiences sunset. The sun is, in fact, stationary, and it is the Earth which rotates. The illusion is exactly the same as when we travel in a fast-moving train. The trees and houses around us appear. Figure 7a. Kuala Lumpur emerges from darkness into daylight at sunrise when the Earth rotates into the sun's rays. BJ, the sun is directly overhead at Kuala Lumpur or midday. C. Kuala Lumpur passes from daylight into darkness at sunset when the Earth rotates away from the sun. D. Kuala Lumpur is directly away from the sun at midnight. 6. Part 1. Physical geography. To move, and we feel that the train is stationary. Figure 7 explains the Earth's rotation and the causes of day and night. The Earth's revolution. When the Earth revolves round the sun, it spins on an elliptical orbit at a speed of 18.5 miles, 29.77 km per second, or 66,600 miles, 107,182 kilometers per hour. One complete revolution takes 365 carat days, or a year. As it is not possible to show a quarter of a day in the calendar, a normal year is taken to be 365 days, and an extra day is added every 4 years as a leap year. 1. Varying lengths of day and night. The axis of the Earth is inclined to the plane of the ecliptic, the plane in which the Earth orbits round the sun, at an angle of 66 carat degree, giving rise to different seasons and varying lengths of day and night. Figure 8. If the axis were perpendicular to this plane, all parts of the globe would have equal days and nights at all times of the year, but we know this is not so. In the Northern Hemisphere. In winter, December, as we go northwards, the hours of darkness steadily increase. At the Arctic Circle, in, the sun never rises, and there is darkness for the whole day in midwinter on December 22nd. Beyond the Arctic Circle, the number of days with complete darkness increases, until we reach the North Pole, 90 degrees north, when half the year will have darkness. In the summer, June, conditions are exactly reversed. Daylight increases as we go polewards. At the Arctic Circle, the sun never sets at midsummer, June 21st, and there is a complete 24-hour period of continuous daylight. In summer, the region north of the Arctic Circle is popularly referred to as Land of the Midnight Sun. At the North Pole, there will be 6 months of continuous daylight. Figure 8a illustrates the revolution of the Earth and its inclination to the plane of the ecliptic, which caused the variation in the length of day and night at different times of the year. In the Southern Hemisphere, the same process takes place, except that the conditions are reversed. When it is summer in the Northern Hemisphere, the southern continents will experience winter. Equal day and night. Equal day and night. Figure 8. O. The revolution of the Earth and its effects on seasons and the variations of lengths of day and night. The Earth and the Universe 7. December 22nd. B. A simplified diagram showing the annual movement of the sun and the causes of the seasons. Midsummer at the North Pole will be midwinter at the South Pole. 2. The altitude of the midday sun. In the course of a year, the Earth's revolution round the sun with its axis inclined at 66% degree to the plane of the ecliptic changes the apparent altitude of the midday sun. The sun is vertically overhead at the equator on 2 days each year. These are usually March 21st and September 21st, though the date changes because a year is not exactly 365 days. These 2 days are termed equinoxes, meaning equal nights, because on these 2 days all parts of the world have equal days and nights. After the March equinox, the sun appears to move north and is vertically overhead at the Tropic of Cancer, 231/2 degree in, on about June 21st. This is known as the June or summer solstice, when the Northern Hemisphere will have its longest day and shortest night. By about December 22nd, the sun will be overhead at the Tropic of Capricorn, 23% degree S. This t's feet carat white t carat so size when th. Southern Hemisphere will have its longest day and shortest night. The tropics thus mark the limits of the overhead sun, for beyond these, the sun is never overhead at any time of the year. Such regions are marked by distinct seasonal changes: spring, summer, autumn, and winter. Beyond the Arctic Circle, 661/2 degree in, and the Antarctic Circle, 661/2 degree S, where darkness lasts for 6 months and daylight is continuous for the remaining half of the year, it is always cold, for even during the short summer the sun is never high in the sky. Within the tropics, as the midday sun varies very little from its vertical position at noon daily, the four seasons are almost indistinguishable. Days and nights are almost equal all the year round. Figure 8b. 3. Seasonal changes and their effects on temperature. Summer is usually associated with much heat and brightness, and winter with cold and darkness. Why should this be so? In summer, the sun is higher in the sky than in winter. When the sun is overhead, its rays fall almost vertically on the earth, concentrating its heat on a small area. Temperature therefore rises, and summers are always warm. In winter, the oblique rays of the sun come through the atmosphere less directly and have much of their heat absorbed by atmospheric impurities and water vapor. The sun's rays fall tatntly and spread over a great area. There is thus little heat, and temperatures remain low. In addition, days are longer than nights in summer, and more heat is received over the longer daylight duration. Nights are shorter and less heat is lost. There is a net gain in total heat received, and temperature rises in summer. Shorter days and longer nights in winter account for the reverse effects. Dawn and twilight. The brief period between sunrise and full daylight is called dawn, and that between sunset and complete darkness is termed twilight. This is caused by the fact that during the periods of dawn and twilight the earth receives diffused or refracted light from the sun whilst it is still below the horizon. Since the sun rises and sets in a vertical path at the equator, the period during which refracted light is received is short. But in temperate latitudes, the sun rises and sets in an oblique path, and the period of refracted light is longer. It is much longer still at the poles, so that the winter darkness is really only twilight most of the time. Figure 9. 8 Part 1. Physical Geography. A. Figure 9. Dawn and twilight. A. At the equator. B. In temperate latitude. The time it takes to pass through the twilight zone, A, B, will be shorter than for temperate latitudes where the sun rises and sets obliquely. Here the time taken to pass through the twilight zone, C, D, is longer. Mathematical location of places on the globe. The Earth's surface is so vast that unless a mathematical method can be used, it is impossible to locate any place on it. For this reason, imaginary lines have been drawn on the globe. One set running east and west, parallel to the equator, are called lines of latitude. The other set runs north and south passing through the poles and are called lines of longitude. Figure 10. The intersection of latitude and longitude pinpoints any place on the Earth's surface. Figure 11c. For example, Delhi is 28 degrees 38 minutes north and 77 degrees 12 minutes east. London is 51 degrees 30 minutes north and 0 degrees 5 minutes west, and Sydney is 33 degrees 52 minutes south and 151 degrees 12 minutes east. We shall examine more closely how latitude and longitude are determined and the role they play in mathematical geography. A. B. Figure 10. A. Parallels of latitude. B. Meridians of longitude. Latitude. 7 happy face dash caret. Happy face. Latitude is the angular distance of a point on the Earth's surface, measured in degrees from the center of the Earth as shown in Figure 10. A. It is parallel to a line, the equator, which lies midway between the poles. These lines are therefore called parallels of latitude, and on a globe are actually circles, becoming smaller polewards. The equator represents 0 degrees, and the north and south poles are 90 degrees north and 90 degrees south. Between these points, lines of latitude are drawn at intervals of 1 degree. For precise location on a map, each degree is subdivided into 60 minutes and each minute into 60 seconds. The most important lines of latitude are the equator, the Tropic of Cancer, 23 yin 2 degree N, the Tropic of Capricorn, 23 yin 2 degree S, the Arctic Circle, 661/2 degree N, and the Antarctic Circle, 661/2 degree S. As the Earth is slightly flattened at the poles, the linear distance of a degree of latitude at the pole is a little longer than that at the equator. For example, at the equator, 0 degrees, it is 68.704 miles, 110.57 kilometers. At 45 degrees, it is 69.054 miles, 111.13 kilometers. And at the poles, it is 69.407 miles. 62 caret IC, UR, LF caret. I caret SSISV caret U caret VT, backslash E caret. IO caret the Earth, and IHE universe. 111.70 kilometers. The average is taken as 69 miles. 111 kilometers. This is a useful figure and can be used for calculating distances to any place. Mumbai is 18 degrees 55 minutes north. It is therefore 18.55 by 69 or 1,280 miles, 18.55 by 111 or 2,059 kilometers from the equator. With the aid of your atlas, find the approximate distance of the following places from the equator: Singapore, Kolkata, Paris, New York, Buenos Aires, and Auckland. Figure 11. A. The latitude of 38 degrees north is the angular distance of a point on the Earth's surface north of the center of the Earth. B. The longitude of 135 degrees west is the angular distance west of the prime meridian. C. The precise location of place X is latitude 52 degrees north and longitude 27 degrees west where they intersect. Longitude. Longitude is an angular distance, measured in degrees along the equator east or west of the prime, or first, meridian, as indicated in Figure 11b. On the globe, longitude is shown as a series of semicircles that run from pole to pole passing through the equator. Such lines are also called meridians. Unlike the equator, which is centrally placed between the poles, any meridian could have been taken to begin the numbering of longitude. It was finally decided in 1884, by international agreement, to choose as the zero meridian, the one which passes through the Royal Astronomical Observatory at Greenwich, near London. This is the prime meridian, 0 degrees, from which all other meridians radiate eastwards and westwards up to 180 degrees. Since the Earth is spherical and has a circumference calculated at 24,901 miles, 40,075 kilometers, in linear distance, each of the 360 degrees of longitude is 24,901 to the power of 360 or 69.17 miles, 40,075-360 or 111.32 kilometers. As the parallels of latitude become shorter polewards, so the meridians of longitude, which converge at the poles, enclose a narrower space. The degree of longitude, therefore, decreases in length. It is longest at the equator, where it measures 69.17 miles, 111.32 kilometers. At 25 degrees, it is 62.73 miles, 100.95 kilometers. At 45 degrees, it is 49 miles, 78.86 kilometers. At 75 degrees, it is 18 miles, 28.97 kilometers. And at the poles, it is 0 mile, 0 kilometers. There is so much difference in the length of degrees of longitude outside the tropics that they are not used for calculating distances, as in the case of latitude. But they have one very important function. They determine local time in relation to GMT, or Greenwich Mean Time, which is sometimes referred to as world time. Longitude and time. Local time. Since the Earth makes one complete revolution of 360 degrees in 1 day, or 24 hours, it passes through 15 degrees in 1 hour, or 1 degree in 4 minutes. The Earth rotates from west to east, so every 15 degrees we go eastwards, local time is advanced by 1 hour. Conversely, if we go westwards, local time is retarded by 1 hour. We may thus conclude that places east of Greenwich see the sun earlier and gain time, whereas places west of Greenwich see the sun later and lose time. If we know GMT, to find local time, we merely have to add or subtract the difference in the number of hours from the h to the power of negative b plus s dot jo equals s. X is 75.4 to 7 dash caret. T section 7. Caret. OA 30 caret is pound Q 5 caret caret caret. Happy face, slash caret. 10 part 1. Physical geography. Figure 1-2 longitude and time when it is noon in London. It is 5:20 p.m. in Chennai, 80 degrees east, and 7:04 a.m. in New York, 74 degrees west. GJ caret. 1. O caret. Given longitude, as illustrated below. A simple memory aid for this will be east gain add, EGA, and west lose subtract, WLS. You could coin your own rhymes for the abbreviations. Hence when it is noon in London, longitude 0 degrees 5 minutes west, the local time for Chennai, 80 degrees east, will be 5 hours 20 minutes ahead of London, or 5:20 p.m. But the local time for New York, 74 degrees west, will be 4 hours 56 minutes behind London, or 7:04 a.m. We can put it in another way. When Londoners are having lunch, Indians will have dinner, and New Yorkers will have breakfast. Figure 12. This is difficult to believe, but it is true. The rotation of the Earth around the sun means that at any point in time, different places will experience a different time of day. There are many ways of determining the longitude of a place. The simplest way is to compare the local time with GMT. For example, the captain of a ship in the midst of the ocean wants to find out in which longitude his ship lies. If GMT is 8 o'clock a.m. and it is noon in the local region, it means that he is 4 hours ahead of Greenwich and must be east of Greenwich. His longitude is 4 by 15 degrees, or 60 degrees east. I. Standard time and time zones. If each town were to keep the time of its own meridian, there would be much difference in local time between one town and the other. 10 a.m. in Georgetown, Penang would be 10.10 in Kota Baru, a difference of 272 degrees in longitude. In larger countries such as Canada, USA, China, India, and Russia, the confusion arising from the differences alone would drive the people mad. Travelers going from one end of the country to the other would have to keep changing their watches if they wanted to keep their appointments. This is impracticable and very inconvenient. To avoid all these difficulties, a system of standard time is observed by all countries. Most countries adopt their standard time from the central meridian of their countries. The Indian government has accepted the meridian of 82 degrees 30 minutes east for the standard time, which is 5 hours 30 minutes ahead of Greenwich Mean Time. The whole world has, in fact, been divided into 24 standard time zones, each of which differs from the next by 15 degrees in longitude, or 1 hour in time. Most countries adhere to this division, but due to the peculiar shapes and locations of some countries, reasonable deviations from the standard time zones cannot be avoided. Figure 13. Larger countries like USA, Canada, and Russia, which have a great east-west stretch, have to adopt several time zones for practical purposes. Russia, the largest country, which extends through almost 165 degrees of longitude, is divided into 11 time zones. When it is 10 o'clock p.m. on a Monday night in Leningrad, it will be almost 7 o'clock a.m. the FO11 owing Tuesday morning in Vladivostok. Travelers along the Trans-Siberian Railway have to adjust their watches almost a dozen times before they reach their destination. Both Canada and USA have the Earth and the Universe 11. Fig. I3 the 5 time zones of North America. 5 time zones: the Atlantic, Eastern, Central, Mountain, and Pacific time zones. The difference between the local time of the Atlantic and Pacific coasts is nearly 5 hours. Figure 13. The International Date Line. A traveler going eastwards gains time from Greenwich until he reaches the meridian 180 degrees east, when he will be 12 hours ahead of GMT. Similarly, in going westwards, he loses 12 hours when he reaches 180 degrees west. There is thus a total difference of 24 hours, or a whole day, between the two sides of the 180 degrees meridian. This is the international date line, where the date changes by exactly 1 day when it is crossed. A traveler crossing the date line from east to west loses a day because of the loss in time he has made, and while crossing the date line from west to east he gains a day because of the gain in time he encountered. Thus, when it is midnight, Friday on the Asiatic side, by crossing the line eastwards, he gains a day. It will be midnight Thursday on the American side, i.e. he experiences the same calendar date twice. When Magellan's ship eventually arrived home in Spain in 1522, after circumnavigating the world from the Atlantic Ocean to the Pacific Ocean and westwards across the international date line, the crew knew nothing about adding a day for the one they had missed. They thought they had arrived on the 5th of September. They were shocked to be told that the date was September 6th. A modern aircraft leaving Wellington at 5 o'clock p.m. on Friday reaches Hawaii 4,100 miles, 6,598 kilometers, away at 2 o'clock p.m. the same Friday. The same aircraft on its return journey from Hawaii leaves at 6 o'clock p.m. on Friday, but arrives at Wellington at 11 o'clock a.m. on Sunday. Can you explain this? The international date line in the mid-Pacific curves from the normal 180 degrees meridian at the Bering Strait, Fiji, Tonga, and other islands to prevent confusion of day and date in some of the island groups that are cut through by the meridian. Some of them keep Asiatic or New Zealand Standard Time, others follow the American date and time. The international date line is shown in Fig. 14. Lose 1 day 150 * E 165 degrees, east 180 inch 165 foot W 150 W. 150 * E 165 * E ISO 16S W ISDFW. Gain 1 day. Figure 1 for the international date line. 12 Part 1 Physical Geography. Questions and exercises. 1. With the aid of annotated diagrams, attempt to prove that the Earth is spherical. Give as many reasons as you can. 2. Explain with the aid of fairly accurate diagrams how the tilt of the Earth's axis on its orbital plane around the Sun causes a. the seasons, b. the variations in the length of day and night, c. the altitude of the midday sun to change at different times of the year. 3. Explain the differences between any 3 of the following: a. perihelion and aphelion, b. parallels of latitude and meridians of longitude, c. the Earth's rotation and the Earth's revolution, d. solstice and equinox, e. standard time and Greenwich Mean Time. 4. Explain any 3 of the following terms connected with the Earth and its planetary relations: I. Galaxy. 2. Pi meridian. 3. Elliptical orbit. 4. International date line. 5. Either give an explanatory account of the following: a. Daylight increases as we go polewards in summer in the northern hemisphere. b. The period of twilight in United Kingdom is longer than in Malaysia. c. A ship crossing the international date line at midnight on Wednesday eastwards finds that it is midnight Tuesday on the American side. Or, work out the following. I. What is the approximate distance in a straight line between Cairo, lat. 30 degrees 0 minutes north, long, 3105 foot e, and Durban, lat. 29 degrees 57 minutes south, long, 30 degrees 59 minutes east. 2. When it is 2 o'clock p.m. in Greenwich, what is the local time of a. Sydney, long, 151 e, b. Chicago, long, 87 degrees 30 minutes west, c. Mumbai, long, 73 degrees east. 3. The captain of a ship observed that it was local noon. He turned on the radio and listened to the 7 o'clock a.m. BBG News. What was his longitude? 6. A. Explain the meaning of the terms equinox and solstice. B. With the aid of diagrams, show how they are related to the movements of the Earth. 7. Answer the following. A. Describe any 3 experiments or observations which support the belief that the Earth is roughly a sphere. B. Explain why mean temperatures for London are lowest in winter. C. Explain why the local clock time in the Samoa Islands, 171 foot W, was noon on November 1st when in the Fiji Islands, 178 degrees east, it was 11 o'clock a.m. on November 2nd. The Earth's crust. The structure of the Earth. In order to understand the geography of the external landforms of the Earth, it is essential that we have some idea of what lies within the Earth's crust. It is not possible to know exactly how the Earth was formed about 4,500 million years ago, but from the evidence of volcanic eruptions, earthquake waves, deep mine operations, and crustal borings, the following facts are quite clear. Continent. Upper mantle. Figure 16a section showing how the continent, SIL, floats on the denser SEMA. XH, atmosphere. Earth's crust, lithosphere. Oceans, hydrosphere. Figure 15a section showing the structure and composition of the Earth. The Earth is made up of several concentric layers, figure 15. The outer layer is the Earth's crust, the lithosphere, which comprises 2 distinct parts. The upper part consists of granitic rocks and forms the continents. Its main mineral constituents are S/Leica and A/Yamana, so it is collectively referred to as the SIL. It has an average density of 2.7. The lower part is a continuous zone of denser basaltic rocks forming the ocean floors, comprising mainly silica, iron, and magnesium. It is therefore called SEMA and has an average density of 3.0. The SIL and the SEMA together form the Earth's crust, which varies in thickness from only 3 to 4 miles beneath the oceans to as much as 30 miles under some parts of the continents. Since the SIL is lighter than the SEMA, the continents can be said to be floating on a sea of denser SEMA. This is illustrated in Fig. 16. Immediately beneath the crust or lithosphere is the mantle or mesosphere, about 1,800 miles thick, composed mainly of very dense rocks rich in olivine. The interior layer is the core or barosphere, 2,160 miles, 3,476 kilometers in radius, and is made up mainly of iron, Fe, with some nickel, and is called knife. The temperature here is estimated to be as high as 3,500 degrees Fahrenheit, 1,927 degrees Celsius, and the core is subject to extremely high pressure. Under such conditions, the core could be expected to be in a liquid state. But recent studies through earthquake waves have suggested that the innermost part of the core is probably a crystalline or solid mass. Parts of the Earth's crust are immersed by oceans and seas. These oceans and seas form the hydrosphere. Extending skywards for over 15 miles from the surface of the Earth, there is an envelope of gases which make up the atmosphere. The classification of rocks. The Earth's crust is made up of various types of rocks, differing from one another in texture, structure, color, permeability, mode of occurrence, and degree of resistance to denudation. A knowledge of these rocks is of paramount importance to geologists who study the composition and physical history of the Earth, but the geographer, too, needs a basic knowledge of the most common rocks and their relationship with landforms. Rocks also form. 14. Part 1. Physical geography. The basis for soil, and determine to some extent the type of natural vegetation and land use, so we must have a fair acquaintance with the rocks around us. Generally speaking, all rocks may be classified into 3 major groups: igneous, sedimentary, and metamorphic, according to their origin and appearance. Igneous rocks. Igneous rocks are formed by the cooling and solidification of molten rock, magma, from beneath the Earth's crust. They are normally crystalline in structure. They do not occur in strata, layers, nor do they contain fossils. Igneous rocks may be subdivided on the basis of mineral composition. When they contain a high proportion of silica, they are said to be acid. Acid igneous rocks, such as granite, are less dense and are lighter in color than basic rocks. These contain a greater proportion of basic oxides, e.g. of iron, aluminium, or magnesium, and are thus denser and darker in color. In terms of origin, there are 2 main classes of igneous rocks. 1. Plutonic rocks. These are igneous rocks, formed at some depth in the Earth's crust. They have cooled and solidified slowly so that large, easily recognized crystals have been able to form. These intrusive rocks, such as granite, diorite, and gabbro, are exposed at the surface by the processes of denudation and erosion. 2. Volcanic rocks. These are molten rocks poured out of volcanoes as lavas. They solidify rapidly on the Earth's surface, and the crystals are small. Basalt is a common volcanic or extrusive rock and forms lava flows, lava sheets, and lava plateaus, e.g. those of Antrim in Northern Ireland, the Deccan Plateau in India, and the Columbia Snake Plateau in USA. Some kinds of basalt solidify in a very peculiar manner to form long polygonal columns. A well-known example is the columnar basalt of the Giant's Causeway in Antrim. Some of the molten lava may push its way to the surface through clefts and passages, solidifying as vertical dikes or horizontal sills. Their origin and occurrence will be discussed in greater detail in Chapter 3. Most igneous rocks are extremely hard and resistant. For this reason, they are quarried for iode making and polished as monuments and gravestones. Sedimentary rocks. Sedimentary rocks are formed from sediment accumulated over long periods, usually underwater. They are distinguished from the other rock types in their characteristic layer formation and are termed stratified rocks. The strata may vary in thickness, from a few inches to many feet. The rocks may be coarse or fine-grained, soft or hard. The materials that form sedimentary rocks may be brought by streams, glaciers, winds, or even animals. They are non-crystalline and often contain fossils of animals, plants, and other microorganisms. Sedimentary rocks are thus the most varied in their formation of all rocks. These rocks are classified according to their age, and different kinds of rocks formed during the same period are grouped together. It is more useful to know the characteristics of the various kinds of rocks. Sedimentary rocks may be classified under three major categories in accordance with their origin and composition. 1. Mechanically formed sedimentary rock. 1. Mechanically formed sedimentary rocks. These rocks have been formed from the accumulation of materials derived from other rocks which have been cemented together. Sandstones are probably the most familiar sedimentary rocks. They are made from sand grains, often quartz fragments derived from granites. Their texture, composition, and color vary tremendously. Many types of sandstones have been quarried for building purposes or for making grindstones. A coarser type of sandstone is known as grit. When larger pebbles are firmly cemented to form a rock, it is called conglomerate when the pebbles are rounded, or breccia when the fragments are angular. The finer sedimentary materials form clay, widely used for brickmaking, shale, or mudstone. Sand and gravel may occur in uncemented form. 2. Organically formed sedimentary rocks. These rocks are formed from the remains of living organisms such as corals or shellfish, whose fleshy parts have been decomposed, leaving behind the hard shells. The most common rocks formed in this way are the calcareous type. They include limestones and chalk. The carbonaceous rocks are also organically formed but from vegetative matter, swamps, and forests. The pressure of overlying sediments has compressed the plant remains into compact masses of carbon which eventually become peat. The Earth's crust. 15. Lignite or coal, all of which bear great economic value. 3. Chemically formed sedimentary rocks. Such rocks are precipitated chemically from solutions of one kind or another. Rock salts are derived from strata which once formed the beds of seas or lakes. Gypsum or calcium sulfate is obtained from the evaporation of salt lakes, such as the Dead Sea, which have a very high salinity. In similar ways, potash and nitrates may be formed. A prehistoric limestone hill near Kuala Lumpur. Compare this hill with the limestone features shown in Chapter 7. Metamorphic rocks. All rocks, whether igneous or sedimentary, may become metamorphic or changed rocks under great heat and pressure. Their original character and appearance may be greatly altered by such forces, particularly during intense earth movements. In this manner, clay may be metamorphosed into slate, limestone into marble, sandstone into quartzite, granite into gneiss, shale into schist, and coal into graphite. The influence of rock types on landscape. The appearance and characteristic features of landforms are greatly influenced by the underlying rock type. Softer rocks like clay and shale are worn down much faster than harder rocks like granite. Within West Malaysia, the resistant granites form the high ground of the main range and the eastern range, where several peaks rise to over 2,000 feet. The landscape is one of smooth slopes and rounded hilltops. The highest peak in West Malaysia, Gunung Tayan, 7,186 feet, is composed of even more resistant quartzite. Shales, schists, and sandstones, being less resistant, form the much lower, rounded hills. Recent river sediments form flat plains. The limestones, resistant because of their permeability, form prominent steep-sided hills such as those near Ipoh and in Perlis. Earth movements and the major landforms. The face of the Earth is constantly being reshaped by the agents of denudation, running water, rain, frost, sun, wind, glaciers, and waves, so that our present landforms are very varied and diverse. But these agents only modify the pattern of mountains, plateaus, and plains which have been modeled by movements of the Earth's crust. Since the dawn of geological time, no less than 9 orogenic or mountain-building movements have taken place, folding and fracturing the Earth's crust. Some of them occurred in Precambrian times between 600 to 3,500 million years ago. The three more recent orogenes are the Caledonian, Hercynian, and Alpine. The Caledonian about 320 million years ago raised the mountains of Scandinavia and Scotland, and is represented in North America. These ancient mountains have been worn down and no longer exhibit the striking forms that they must once have had. In a later period, during the Hercynian earth movements about 240 million years ago, were formed such ranges as the Ural Mountains, the Pennines and Welsh Highlands in United Kingdom, the Harz Mountains in Germany, the Appalachians in North America, as well as the high plateaus of Siberia and China. These mountains have also been reduced in size by the various sculpturing forces. We are now living in an era very close to the last of the major orogenic movements of the Earth, the Alpine, about 30 million years ago. Young fold mountain ranges were buckled up and overthrust on a gigantic scale. Being the most recently formed, these ranges, such as the Alps, Himalayas, Andes and Rockies, shown in Figure 17, are the loftiest and the most imposing. Their peaks are sometimes several miles high. But the time will come when these lofty ranges will be lowered like those that existed before them. From the eroded materials, new rocks will be foamed, later to be uplifted to form the next generation of mountains. 16 Part T Physical Geography. Figure 17 Structural divisions of the Earth. Types of mountains. Mountains make up a large proportion of the Earth's surface. Based on their mode of formation, 4 main types of mountains can be distinguished. 1. Fold mountains. These mountains are by far the most widespread and also the most important. They are caused by large-scale earth movements. When stresses are set up in the Earth's crust, such stresses may be due to the increased load of the overlying rocks, flow movements in the mantle, magmatic intrusions into the crust, or expansion or contraction of some part of the Earth. When such stresses are initiated, the rocks are subjected to compressive forces that produce wrinkling or folding along the lines of weakness. As illustrated in Figures 18, A and B, folding effectively shortens the Earth's crust, creating from the original level surface a series of waves. The upfold waves are called anticlines, and the troughs or downfolds are synclines. The formation of up and down folds closely resembles that of the wrinkles of a tablecloth when it is pushed from either one or both sides of the table. In the great fold mountains of the world, such as the Himalayas, Rockies, Andes, and Alps, do. Figure 1.8a, the horizontal strata of the Earth's crust. Before folding B, compression shortens the crust-forming fold. Mountains. Anticline. Shorten crust -B. To the complexity of the compressional forces, the folds developed much more complicated form /. When the crest of a fold is pushed too far, an overfold is formed, Figure 19. If it is pushed still further, it becomes a recumbent fold, Figure 19. In extreme cases, fractures may occur in the crust, so that the upper part of the recumbent fold slides forward over the lower part along a thrust plane, forming an overthrust fold. The overriding portion of the thrust fold is termed a nap, Figure 19. Since the rock strata have been elevated to great, the Earth's crust 17 heights, sometimes measurable in miles, fold mountains may be called mountains of elevation. The fold mountains are also closely associated with volcanic activity. They contain many active volcanoes, especially in the Circum-Pacific Fold mountain system. They also contain rich mineral resources such as tin, copper, gold, and petroleum. 2. Block mountains. When the Earth's crust bends, folding occurs, but when it cracks, faulting takes place, Figure 20. Faulting may be caused by tension or compression, forces which lengthen or shorten the Earth's crust, causing a section of it to subside or to rise above the surrounding level. Figures 21a and B explain how faulting causes horst or block mountains and their counterparts, graben or rift valleys. Minor faulting in sedimentary rocks of the Kenny Hill series. 2 small faults have distorted the strata GC. Morgan Figure 20 normal, reverse, and transcurrent faults. 18 Part 1 Physical Geography. In Figure 21a, Earth movements generate tensional forces that tend to pull the crust apart, and faults are developed. If the block enclosed by the faults remains as it is or rises, and the land on either side subsides, the upstanding block becomes the horst or block mountain. The faulted edges are very steep, with scarp slopes, and the summit is almost level, e.g. the Hunsrück Mountains, the Vosges and Black Forest of the Rhineland. Tension may also cause the central portion to be let down between 2 adjacent fault blocks, forming a graben or rift valley, which will have steep walls. The East African Rift Valley system is 3,000 miles, 4,828 kilometers, long, stretching from East Africa through the Red Sea to Syria. FFF. Figure 21. A. Block mountain, horst, formed by tension when faults develop. B. Rift valley formed by compression when faults develop. C. Later stage when overhanging sides are worn back. Compressional forces set up by Earth movements may produce a thrust or reverse fault and shorten the crust. A block may be raised or lowered in relation to surrounding areas. Figure 21b illustrates a rift valley formed in this way. In general, large-scale block mountains and rift valleys are due to tension rather than compression. The faults may occur in series and be further complicated by tilting and other irregularities. Denudation through the ages modifies faulted landforms. 3. Volcanic mountains. These are, in fact, volcanoes which are built up from material ejected from fissures in the Earth's crust. The materials include molten lava, volcanic bombs, cinders, ashes, dust, and liquid mud. They fall around the vent in successive layers, building up a characteristic volcanic cone, figure 22. Volcanic mountains are often called mountains of accumulation. They are common in the Circum-Pacific Belt and include such volcanic peaks as Mt. Fuji, Japan, Mt. Mayon, Philippines, Mt. Merapi, Central Java, Mt. Agung, Bali, and Mt. Cotopaxi, Ecuador. Further details are given in Chapter 3. Figure 22, a volcano or mountain of accumulation with successive layers of lava. 4. Residual mountains. These are mountains evolved by denudation. Where the general level of the land has been lowered by the agents of denudation, some very resistant areas may remain, and these form residual mountains, e.g. Mt. Monadnock in USA. Residual mountains may. The Earth's crust 19. Original almost downcutting by rivers, flat plateau surface, or glaciers. Figure 23, residual mountains, or mountains of denudation. Also evolved from plateaus which have been dissected by rivers into hills and valleys like the ones illustrated in Fig. 23. Here the ridges and peaks are all very similar in height. Examples of dissected plateaus, where the downcutting streams have eroded the uplands into mountains of denudation, are the highlands of Scotland, Scandinavia, and the Deccan Plateau. Types of plateaus. Plateaus are elevated uplands with extensive level surfaces and usually descend steeply to the surrounding lowland. They are sometimes referred to as tablelands. Like all highlands, plateaus are subjected to erosional processes. As a result, their original characteristics may be greatly altered. According to their mode of formation and their physical appearance, plateaus may be grouped into the following types. 1. Tectonic plateaus. These are formed by earth movements which cause uplift, and are normally of a considerable size and fairly uniform altitude. They include continental blocks like the Deccan Plateau in India. Some of the tectonic plateaus may be tilted like the Meseta of central Iberia, or faulted like the Harz of Germany. When plateaus are enclosed by fold mountains, they are known as interment plateaus. Examples are the Tibetan Plateau between the Himalayas and the Kunlun, and the Bolivian Plateau between two ranges of the Andes. Intermont plateaus are some of the highest and the most extensive plateaus in the world. 2. Volcanic plateaus. Molten lava may issue from the Earth's crust and spread over its surface to form successive sheets of basaltic lava. These solidify to form a lava plateau. Some of the better known volcanic plateaus are the Antrim Plateau of Northern Ireland and the northwestern part of the Deccan Plateau. The most remarkable plateau built by lava is the Columbia Snake Plateau, which covers an area almost twice as big as Malaysia. Each layer of the lava flow is over 100 feet, or about 30 meters thick, and the entire depth of successive lava layers is estimated to be almost a mile. 3. Dissected plateaus. Through the continual process of weathering and erosion by running water, ice and winds, high and extensive plateaus are gradually worn down, and their surfaces made irregular. In the humid highlands, stream action and sometimes glaciation cut deep, narrow valleys in the plateaus, which are then described as dissected plateaus. An example is the Scottish Highlands. In drier countries, vertical corrosion by rivers and abrasion by winds will dissect the plateau into steep-sided tabular masses, termed mesas and buttes, intersected by deep canyons. This is a common feature of arid and semi-arid areas, e.g. in the southwestern USA. Many of the world's plateaus have rich mineral resources and have been actively mined. The African plateau yields gold, diamonds, copper, manganese, and chromium. In the Brazilian plateau, there are huge resources of iron and manganese, particularly in the Minas Gerais area. The Deccan Plateau has deposits of manganese, coal, and iron, and the plateau of Western Australia is rich in gold and iron. Types of plains. A plain is an area of lowland, either level or undulating. It seldom rises more than a few hundred feet above sea level. There may be low hills which will give a typical rolling topography. The plains usually form the best land of a country and are often intensively cultivated. Population and settlements are normally concentrated here, and when plains are traversed by rivers, as most of them are, their economic importance may be even greater, e.g. the Indo-Gangetic Plain, the Mississippi Plain, and the Yanzu Plain. Some of the most extensive temperate plains are grasslands like the Russian steppes, the North American prairies, and the Argentinian pampas. Plains may be grouped into three major types based on their mode of formation. 20 Part 1 Physical Geography. 1. Structural plains. These are the structurally depressed areas of the world that make up some of the most extensive natural lowlands on the Earth's surface. They are formed by horizontally bedded rocks, relatively undisturbed by the crustal movements of the Earth. They include such great plains as the Russian Platform, the Great Plains of USA, and the central lowlands of Australia. 2. Depositional plains. These are plains formed by the deposition of materials brought by various agents of transportation. They are comparatively level but rise gently towards adjacent highlands. Their fertility and economic development depend greatly on the types of sediments that are laid down. Some of the largest depositional plains are due to deposition by large rivers. Active erosion in the upper course results in large quantities of alluvium being brought down to the lower course and deposited to form extensive alluvial plains, floodplains, and deltaic plains. They form the most productive agricultural plains of the world, intensively tilled and very densely populated. The Nile Delta of Egypt is noted for rice and cotton cultivation, the Ganga Delta for rice and jute growing, while the plain of North China, where the Huanghe, Yellow River, has spread out a thick mantle of alluvium, supports a wide range of crops. Glaciers and ice sheets may deposit a widespread mantle of unsorted fluvio-glacial sands and gravels in the outwash plain, or may drop boulder clay, a mixture of various sizes of boulders and clay, to form a till plain or drift plain. Outwash plains are usually barren lands, e.g. some parts of the Netherlands and northern Germany. But boulder clay may be very valuable farming land, e.g. the Midwest of USA and East Anglia in England. In coastal regions, waves and winds often drive beach materials, mud, sand, or shingle, landwards and deposit them on the coastal plain to form marine swamps, mudflats, tidal, and estuarine lowlands, an appreciable portion of the coastal lowlands of Belgium, the Netherlands, and the Gulf Coast of USA were formed in this way. Uplift may raise the coastal lowlands slightly, and they then form an emergent coastal plain, e.g. the coastal margins from Florida to Texas. Winds may blow aeolian deposits, very fine particles known as loess. Winds may blow aeolian deposits, very fine particles known as loess, from interior deserts or barren surfaces and deposit them upon hills, valleys, or plains, forming a loess plateau, as in northwest China, or a loess plain, as in the Pampas of Argentina. The loess helps to level an undulating plain by filling up grooves and depressions. Many of the loess-covered plains in the world are fertile agricultural regions. 3. Erosional plains. These plains are carved by the agents of erosion. Rain, rivers, ice, and wind help to smooth out the irregularities of the Earth's surface, and in terms of millions of years, even high mountains can be reduced to low undulating plains. Such plains of denudation are described as peneplains, a word meaning almost plains. Rivers, in their course from source to sea, deepen their valleys and widen their banks. The projecting spurs are cut back so that the level ground bordering the river is constantly widened. At the same time, the higher land between the rivers is gradually lowered. Figure 24. Figure 24. Peneplain. In the formation of a peneplain in humid conditions, the hills are both lowered and worn back to give an undulating lowland. In glaciated regions, glaciers and ice sheets scoured and leveled the land, forming ice-scoured plains. Hollows scooped out by the ice are now filled by lakes. There are extensive ice-scoured plains in northern Europe and northern Canada. Finland is estimated to have over 180,000 lakes, occupying 10% of the total land surface of the country. In arid and semi-arid regions, wind deflation sweeps away much of the eroded desert materials, lowering the level of land and forming extensive plains, e.g. the gravelly or stony desert plains called Reg in Africa. Mechanical weathering in arid and semi-arid areas wears back the mountain slopes to leave a gently sloping pediments or pedoplains. Figure 25. Figure 25. Pedoplain. In the formation of a pedoplain in arid or semi-arid conditions, the hills are worn back to form a gently sloping plain, but some steep hills remain. These are called inselbergs. The Earth's crust. 21. Questions and exercises. 1. Either attempt a classification of mountains according to their mode of formation, or explain why a knowledge of rocks and their structures is essential in the interpretation of landforms. 2. With the aid of diagrams, explain the difference in appearance and formation of any three of the following: A. Folds and faults. B. Dissected plateau and interment plateau. C. Alluvial plain and peneplain. D. Sima and Sial. E. Lithosphere and mantle. 3. What is a sedimentary rock? In what way is it different from igneous rocks? Describe the various sources from which sedimentary rocks may be derived. Quote actual examples of sedimentary rocks to support your answer. 4. For each of the following: a young fold mountain, a rift valley, a loess plain. A. Draw a simple diagram to show its characteristic relief. B. Explain its origin. C. Name and locate a region where such a feature may be found. 5. Either describe and explain the following selected landforms: A. Antrim Plateau. B. Russian Platform. C. Scottish Highlands. Or explain the meaning of any four of the following terms connected with the study of landforms in the Earth's crust: basalt, orogenesis, recumbent fold, fossiliferous rocks, horst, syncline, volcanism, and earthquakes. Landforms associated with volcanic activities. Volcanic activities have a profound influence on the Earth's landforms. Solid, liquid, or gaseous materials may find their way to the surface from some deep-seated reservoir beneath. Molten magma is mobile rock that forces its way into the planes of weakness of the crust to escape quietly or explosively to the surface. The resultant landforms depend on the strength and fluidity of the magma, the types of cracks, faults, and joints that it penetrates, and the manner in which it escapes to the surface. Magma, while thrusting its way up to the surface, may cool and solidify within the crust as plutonic rocks assaulting and intrusive landforms. Magmas that reach by surface and solidify form extrusive landforms. Rocks formed by either plutonic or volcanic activity recalled igneous rocks. Landforms of igneous intrusions. Perhaps the commonest intrusive landforms are sills and dikes. When an intrusion of molten magma is made horizontally along the bedding planes of sedimentary rocks, the resultant intrusion is called a sill. Denudation of the overlying sedimentary strata will expose the intrusion, which will resemble a lava flow or form a bold escarpment like the Great Wind Sill of England. Similar intrusions, when injected vertically as narrow walls of igneous rocks within the sedimentary layers, are termed as dikes. Because of their narrowness, dikes seldom dominate the landscape. When exposed to denudation, they may appear as upstanding walls or shallow trenches, depending on whether they are more or less resistant than the rocks in which they are emplaced. Examples of dikes are the Cleveland Dike or Armathwaite Dike of parasitic cone. Lava plateau built up by successive flows. Dike less resistant than surrounding rocks. Overlying rocks arched up by laccolith. Sill forming a bold escarpment dike more resistant than surrounding rocks. Volcano. SW. XX. 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 Sill. XX. XX. Sedimentary, ES and synclines rocks below a coath. Fa. Figure 26. Intrusive landforms of igneous intrusions in volcanic regions, showing sill, dike, laccolith, lopolith, faccolith, and batholith. Formed in undisturbed NTI C/INI. Volcanism and earthquakes 23. North Yorkshire, England, and hundreds of others in the Isles of Mull and Arran in Scotland. A large, very resistant dike of quartzite forms a long ridge to the north of Kuala Lumpur. Igneous intrusions on a larger scale are the various types of liths, laccoliths, lopoliths, faccoliths, and batholiths, figure 26. The names may sound difficult. They are, in fact, all variations of igneous intrusions placed differently in the Earth's crust and solidifying within the upper layers of the crust. A laccolith is a large blister or igneous mound with a dome-shaped upper surface and a level base, fed by a pipe-like conduit from below. It arches up the overlying strata of sedimentary rocks, e.g. the laccoliths of the Henry Mountains in Utah, USA. A lopolith is another variety of igneous intrusion with a saucer shape. A shallow basin is formed in the midst of the country rocks. The Bushveld lopoliths of Transvaal system, South Africa, are good examples. A faccolith is a lens-shaped mass of igneous rocks occupying the crest of an anticline or the bottom of a syncline and being fed by a conduit from beneath. An example of a faccolith is Corndon Hill in Shropshire, United Kingdom. A batholith is a huge mass of igneous rocks, usually granite, which after removal of the overlying rocks forms a massive and resistant upland region such as the Wicklow Mountains of Ireland, the uplands of Brittany, France, and the main range of West Malaysia. Their precise mode of origin is still a matter of controversy. It is generally believed that large masses of magma rising upwards metamorphosed the country rocks with which they came into contact. These metamorphosed rocks together with the solidified magma give rise to extensive batholiths, sometimes hundreds of miles in extent. They are the most spectacular of the intrusive landforms. The origin of volcanoes. The ancient Greeks believed that volcanic eruptions occurred when Vulcan, the god of the underworld, stoked his subterranean furnace beneath Volcano, a small volcanic island off Sicily, from which the present word volcano is derived. Of course, we no longer believe this is true. Geologists and volcanologists have ascertained that volcanic activity is closely connected with crustal disturbances. Mt. Mayon, Philippines, an eruption, particularly where there are zones of weakness due to deep faulting or mountain folding. As temperature increases with increasing depth below the Earth's crust at an average rate of about 1 degree Fahrenheit for every 65 feet of descent, the interior of the Earth can be expected to be in a semi-molten state, comprising solid, liquid, and gaseous materials, collectively termed magma. The magma is heavily charged with gases such as carbon dioxide, sulfurated hydrogen, and small proportions of nitrogen, chlorine, and other volatile substances. The gases and vapor increase the mobility and explosiveness of the lavas which are emitted through the orifice or vent of a volcano. During a volcanic eruption, there are two main types of lavas. 1. Basic lavas. These are the hottest lavas, about 100 degrees C, 1832 degrees Fahrenheit, and are highly fluid. They are dark colored like basalt, rich in iron and magnesium but poor in silica. As they are poured out of the volcano, they flow Chu/Et/Y and are not very explosive. Due to their high fluidity, they flow readily with a speed of 10 to 30 miles, 16 to 48 kilometers per hour. They affect extensive areas, spreading out as thin sheets over great distances before they solidify. 24 Part 1. Physical Geography. Figure 27 Lava dome or shield volcano. The resultant volcano is gently sloping with a wide diameter and forms a flattened shield or dome. Figure 27. 2. Acid lavas. These lavas are highly viscous with a high melting point. They are light-colored, of low density, and have a high percentage. Of silica. They flow slowly and seldom travel far before solidifying. The resultant cone is therefore steep-sided. The rapid congealing of lava in the vent obstructs the flow of the outpouring lava, resulting in loud explosions, throwing out mini volcanic bombs. Or pyroclasts, figure 28. Sometimes the lavas are viscous that they form a spine or plug at the éter like that of Mt. Pelee in Martinique, figure 29. Crater. 28. Acid lava cone. To erosion. The plug is more resistant and genes after most of the volcanic materials have worn away. Some spines are very resistant, and while most of the material of very old volcanoes is removed by erosion, the spine may remain, e.g. Puy de Dôme, France. Types of volcanoes. There are 3 types of volcanoes: active, dormant, and extinct. Volcanoes are said to be active when they frequently erupt, or at least when they have erupted within recent time. Those that have been known to erupt and show signs of possible eruption in the future are described as dormant. Volcanoes that have not erupted at all in historic times, but retain the features of volcanoes, are termed extinct. All volcanoes pass through active, dormant, and extinct stages, but we can never be thoroughly sure when they are extinct. Mt. Vesuvius, Italy, and Mt. Krakatau, Indonesia, were once thought by people to be extinct, and yet both erupted most violently. Extrusive landforms. Extrusive landforms are determined by the nature and composition of the lava and other ejected materials that reach the surface of the Earth. The fluid basic lava, flowing for long distances, produces extensive lava plains and basalt plateaus, such as the Great Lava Plains of the Snake River Basin, USA. The basalt plateaus are found in many continents, e.g. the northwestern part of the Deccan Plateau in India, Asia, and in Iceland, Europe. Volcanic cones are most typical of the extrusive features. The highly fluid lavas build up lava domes, or shield volcanoes with gently rising slopes and broad, flattened tops. The volcanoes of Hawaii have the best developed lava domes. The spectacular Mauna Loa and Kilauea are so accessible that they have been closely studied. Kilauea has a very steep, walled caldera into which the active vent pours red-hot lava, forming the lava pit of Halong-Mau, also Halim-Miu. Thousands of lava fountains rise and fall in the dazzling pit. The less fluid lavas that explode more violently form ash and cinder cones with large central craters and steep slopes. They are typical of small volcanoes, occurring in groups and seldom exceeding 1,000 feet or 300 meters in height, such as Mt. Nuovo, near Naples, Italy, and Mt. Paracutin. Volcanism and earthquakes, 25. In Mexico, the lava flows are so viscous that they solidify after a short distance. When they are confined in valleys, they form lava tongues and lava dammed lakes when they dam a river valley. Other minor features that may be associated with lava obstructions include lava bridges and lava tunnels. A volcanic region may be strewn with solid materials that were hurled from the vent of the volcano. The very fine particles are the volcanic dust, which may be shot so high into the sky that it travels round the world several times before it eventually comes to rest. The dust or ash falls as black snow and can bury houses and people. The coarser fragmental rocks are collectively called pyroclasts and include cinders or lapilli, scoria, pumice, and volcanic bombs. The highest and most common volcanoes have composite cones. They are often called stratovolcanoes. The cones are built up by several eruptions of lava, ashes, and other volcanic materials. From the main conduit, which leads down a reservoir of magma, each new eruption adds new layers of ashes or lava to the sides of the volcano, which grows steadily in height. From the main conduit, subsidiary dikes or pipes may reach the surface as feeders to parasitic cones. Lava escapes through them to the sides of the main cones, figure 30. Mt. Etna in Sicily, Italy, has hundreds of such parasitic cones. Another interesting composite volcano is Mt. Stromboli, Italy, whose frequent eruptions that make the summit glow have earned for it the name Lighthouse of the Mediterranean. Other well-known. Figure 30, a composite cone. Composite volcanoes include Mt. Vesuvius, Italy, Mt. Fuji, Japan, Mt. Popocatépetl, Mexico, and Mt. Chimborazo, Ecuador. During an eruption, material from the top of the cone is blown off or collapses into the vent, widening the orifice into a large crater. Some volcanoes may have greatly enlarged depressions called calderas, which may be several miles across. These are the result of violent eruptions accompanied by the subsidence of much of the volcano into the magma. Beneath, figure 31. Water may collect in the crater or the caldera, forming crater or caldera lakes, e.g. Lake Toba in Sumatra. Outline of figure 3.1. A caldera. A violent eruption weakens the structure of the volcano, and after eruption has ceased, much of the volcano subsides into the magma reservoir beneath. The depression may later be filled with water to form a lake. Some volcanic eruptions. In the history of mankind, perhaps the most Disastrous eruptions were those of Mt. Vesuvius, Mt. Krakatoa, and Mt. Pelee. Mt. Vesuvius, Italy. Mt. Vesuvius, standing about 4,000 feet or 1,220 meters above the Bay of Naples, erupted violently. On August 24, CE79, taking the people who lived around it by complete surprise. White-hot lava flowed from parasitic cones. In the midst of a thundering explosion, the highly gaseous magma escaped as gigantic luminous clouds in cauliflower form and shot up to great heights before it fell to earth as pyroclasts and ashes. The city of Pompeii, located to the southwest, was buried beneath 20 feet of volcanic ashes which were later cemented by the torrential downpours of heavy rain that accompanied the violent eruption. In a similar way, the city of Herculaneum on the west was completely overwhelmed by a mud flow of ashes and cinders. 26 Part 1, Physical Geography. Almost 50 feet thick, washed down by torrential rain from the slopes of Vesuvius. Almost the entire population of the two cities was buried alive. After this, minor eruptions occurred from time to time, but the fertility of the solidified volcanic ashes tempted many farmers to begin anew on the slopes of Vesuvius. Then came the catastrophic eruption of December 1631, when an avalanche comprising red hot volcanic debris, pasty lava, and highly energized gases ruined 15 towns and killed about 4,000 inhabitants. The ashes that descended on Naples were estimated to be a foot thick. Mt. Krakatoa, Indonesia. The greatest volcanic explosion known to men is perhaps that of Mt. Krakatoa in August 1883. Krakatoa is a small volcanic island in the Sunda Straits, midway between Java and Sumatra. Dense black clouds of ashes shot 20 to 50 miles high and were brought down as mud by the torrential rain which fell over the adjacent islands. So much magma was ejected from the underlying reservoir that 2/3 of the island collapsed and disappeared, forming a huge submarine caldera. The explosion could be heard in Australia, almost 3,000 miles, 4,828 kilometers, away. The fine dust that was thrown into the upper sail of the atmosphere traveled several times around HP world, causing brilliant sunsets and glowing sky in many parts of the globe. Though Krakatoa itself was not inhabited and nobody was killed by the lava flows, the vibration set up enormous waves over 100 feet high, which drowned was not inhabited and nobody was killed by the lava flows. The vibration set up enormous waves over 100 feet high, which drowned 36,000 people in the coastal districts of Indonesia. After remaining dormant for almost half a century, an eruption in 1927 pushed up a cinder cone from the submarine floor, culminating in a summit of 220 feet above sea level by 1952. This new volcanic island was named Anak Krakatoa, meaning the child of Mt. Krakatoa. Mt. Pelee, Martinique. The eruption of Mt. Pelee of the West Indies in May 1902 was the most catastrophic of modern times. The volcano erupted white-hot lava and superheated steam which swept down the slope at an amazing speed as a new ardent, glowing avalanche. Saint-Pierre, the capital of Martinique, lying on the path of the lava, was within minutes. Its entire population of 30,000, except 2 of them, was killed almost instantly. Even the sea was boiling and all the ships in the harbor were wrecked. The ejection of volcanic materials continued for several months until a vertical spine rose from the crater, almost 1,000 feet high by the middle of 1903. The spine was formed by the pasty lava, partially solidified in the neck of the volcano. Part of the spine, however, crumbled under continual weathering as well as internal forces. Mt. Mayon is viewed from the town of Legazpi, southern Luzon, Philippines. Hot lava and steam violently erupted from the crater of Moyon volcano during the eruption on the morning of July 16, 2006. Volcanism and earthquakes 27. The distribution of volcanoes in the world. Volcanoes are located in a fairly clearly defined pattern around the world, closely related to regions that have been intensely folded or faulted. There are well over 500 active volcanoes and thousands of dormant and extinct ones. They occur along coastal mountain ranges, as offshore islands and in the midst of oceans, but there are few in the interiors of continents. The greatest concentration is probably that in the Circum-Pacific region, popularly termed the Pacific Ring of Fire, which has been estimated to include 2/3 of the world's volcanoes, figure 32. The chain of volcanoes extends for almost 2,000 miles, about 3,200 kilometers, from the Aleutian Islands into Kamchatka, Japan, the Philippines, and Indonesia, Java and Sumatra in particular, southwards into the Pacific Islands of Solomon, New Hebrides, Tonga and North Island, New Zealand. On the other side of the Pacific, the chain continues from the Andes to Central America, particularly Guatemala, Costa Rica and Nicaragua, Mexico, and right up to Alaska. It is said that there are almost 24 active volcanoes in the Philippines out of around 300 volcanoes, 44 in the Andes, 110 in Japan, and more than 70 in Indonesia. In contrast, the Atlantic coasts have comparatively few active volcanoes but many dormant or extinct volcanoes, e.g. Madeira, Ascension, St. Helena, Cape Verde Islands, and Canary Islands, but those of Iceland and the Azores are active. Volcanoes of the Mediterranean region are mainly associated with the alpine folds, e.g. Vesuvius, Etna, Stromboli, Volcano, and those of the Aegean Islands. A few continue into Asia Minor, Mt. Ararat, Mt. Elbrus. The Himalayas have, surprisingly, no active volcano at all. In Africa, some volcanoes are found along the East African Rift Valley, e.g. Mt. Kilimanjaro and Mt. Kenya, both probably extinct. The only active volcano of West Africa is Mt. Cameroon. There are some volcanic cones in Madagascar, but active eruption has not been known so far. The West Indian Islands. Figure 32 World distribution of volcanoes, lava plateaus, and earthquakes. 28 Part 1. Physical geography. Have experienced some violent explosions in recent times, e.g. Mt. Pelee in Martinique, and in St. Vincent further south. The Lesser Antilles are made up mainly of volcanic islands, and some of them still bear signs of volcanic liveliness. Elsewhere in the interiors of continents, Asia, North America, Europe, and Australia, active volcanoes are rare. Geysers and hot springs. Geysers are fountains of hot water and superheated steam that may spout up to a height of 150 feet from the earth beneath. The phenomena are associated with a thermal or volcanic region in which the water below is being heated beyond boiling point, 100 degrees Celsius, or 212 degrees east. The jet of water is usually emitted with an explosion, and is often triggered off by gases seeping out of the heated rocks, figure 33. Almost all the world's geysers are confined to three major areas: Iceland, the Rotorua district of North Island, New Zealand, and Yellowstone Park of USA. The world's best-known geyser is perhaps Old Faithful in Yellowstone National Park, Wyoming, which erupts at regular intervals, every 63 minutes on the average. Hot springs. A carrot steam and water erupt to the surface. 4. Geysers. Water heated at depth rises gently to surface. Less of gas would trigger eruptflow. Water heated by underground POSAG contain in contact with rocks water at depth. Figure 33 Hot springs and geysers. Hot springs or thermal springs are more common, and may be found in any part of the earth where water sinks deep enough beneath the surface to be heated by the interior forces. The water rises to the surface without any explosion. Such springs contain dissolved minerals which may be of some medical value. Iceland has thousands of hot springs. Some of them have been harnessed to heat houses, swimming pools, and for other domestic purposes. Hot springs and geysers have become tourist attractions, e.g. in Japan and Hawaii. Earthquakes. The Earth is never free from earthquakes for long, and more than 50,000 of them are recorded annually. Minor earth tremors caused by gentle waves of vibration within the Earth's crust occur every minutes. Major earthquakes, usually caused by movement along faults, can be very disastrous, particularly in densely populated areas. Earthquakes themselves may cause only restricted damage in the regions of occurrence, but their after effects can be very catastrophic. They produce gigantic tidal waves, called tsunamis by the Japanese, which flood towns. Andronthau Sansoft people. Fires break out beyond control as gas mains are shattered and buildings collapse. In severe earthquakes, fissures gape open, and the ground rise and undulates in the passage of the surface waves. A wave height of 1/4 of an inch in the upheaval is sufficient to bring down most ordinary buildings. Roads, railways, and bridges are buckled and twisted. Telecommunications are cut when the cables are snapped. Hills are so shaken that landslides are widespread. As the vibration thins out at the edges, like the series of waves set up by a stone thrown into the water, damage is greatly reduced. Only the highly sensitive seismograph can record the movements of earthquake waves. Some major earthquakes. One of the greatest earthquakes ever known was the Great Lisbon Earthquake on November 1, 1755. It originated in an abrupt subsidence of the ocean floor in the Atlantic west of Lisbon. Tidal waves as high as 35 feet were set up, which swept across the coastal districts of Lisbon, drowning thousands. Most of the buildings collapsed completely, and it was estimated that 60,000 inhabitants died. The effects of the earthquake were felt within a 400 miles, about 640 kilometers, radius of Lisbon, in North Africa and Europe. The earthquake on September 1, 1923 that shook Tokyo and Yokohama was equally shocking. A fracture that occurred in the Earth's crust off the coast of Japan caused the earthquake. The fragile buildings of the densely populated twin cities were mostly ruined. More than 500,000 houses collapsed. Widespread fires from factories, gas mains, oil installations, and kitchens killed 250,000 people, and many more were injured. Volcanism and earthquakes. 29. Other disastrous earthquakes include that of San Francisco in 1906, which ruined the greater part of the heart of San Francisco. In the Lus region of Kansu in China, the 1920 earthquake claimed 200,000 lives, and again in 1927 when 100,000 cave dwellers were buried alive. In 1960, the earthquake at Agadir, Morocco sealed the fate of 10,000 inhabitants, besides causing untold damage, and in 1968 there was a disastrous earthquake in eastern Iran, with its epicenter at Kok. The 2004 Indian Ocean tsunami was one of the deadliest disasters in modern history, causing widespread destruction and a significant loss of life. It resulted in the deaths of approximately 230,000 people and left millions displaced in countries such as Indonesia, Sri Lanka, India, Maldives. In Thailand, this catastrophic event occurred on December 26, 2004, at 7:59 a.m. local time when a powerful earthquake measuring 9.1 magnitude struck off the coast of Sumatra, Indonesia. The ensuing tsunami, a series of massive ocean waves, spread across the Indian Ocean over the next 7 hours, causing extensive damage even as far as East Africa. In some areas, the waves reached heights of 30 feet, 9 meters, or more upon reaching the shore. Post-tsunami debris in Banda Aceh, Indonesia, 2004. The distribution of earthquakes. The world's distribution of earthquakes coincides very closely with that of volcanoes. Regions of greatest seismicity are circum-Pacific areas, with the epicenters in the most frequent occurrences along the Pacific Ring of Fire. It is said that as many as 70% of earthquakes occur in the circum-Pacific belt. Another 20% of earthquakes take place in the Mediterranean Himalayan belt, including Asia Minor, the Himalayas, and parts of northwest China. Elsewhere, the Earth's crust is relatively stable and is less prone to earthquakes, though nowhere can be said to be immune to earth tremors. Questions and exercises. 1. With the aid of annotated diagrams, write a comparative account of landforms resulting from intrusive and extrusive igneous activities. 2. Distinguish the difference in appearance and origin of any 3 of the following pairs of terms associated with volcanicity. A. Sills and dikes. B. Cinder cones and lava domes. C. Geysers and hot springs. D. Crater and caldera. E. Laccolith and lopalith. 3. Describe, with appropriate sketches, the major types of landforms originating from and basic lavas. 4. On a map of the world, locate the chief volcanic and earthquake areas. Write a descriptive account of any one major volcanic eruption or earthquake that has occurred in historical rhymes. You should include the causes, effects, and consequences of such a named occurrence. 5. The following terms are in one way or another connected with volcanoes and earthquakes. Choose one term from each of the sections A, B, and C and write what you know about them. Section A. Magma lava pyroclasts. Section B. Basalt plateau lava plain parasitic cones. Section C. Volcano tsunami, Old Faithful. Weathering, mass movement, and groundwater. The Earth's crust is constantly undergoing geological changes caused by internal forces, which create new relief features. Orogenesis build. New mountain ranges, uplift or depression of particular areas is caused by folding or faulting, and volcanic disturbances also modify the landscape. Meanwhile, external forces are working vigorously to wear away the surface, and the interaction of these constructive and destructive forces gives rise to the great diversity of present-day landforms. The process of wearing away the Earth causes a general lowering and leveling out of the surface. It is known as denudation and is carried out in 4 phases. I. Weathering, the gradual disintegration of rocks by atmospheric or weather forces. 2. Erosion, the active wearing away of the Earth's surface by moving agents like running water, wind, ice, and waves. 3. Transportation, the removal of the eroded debris to new positions. 4. Deposition, the dumping of the debris in certain parts of the Earth, where it may accumulate to form new rocks. All 4 phases of the denudation process are taking place simultaneously in different parts of the world at different rates, much depending on the nature of the relief, the structure of the rocks, the local climate, and interference by man. This chapter describes the work of weathering and the features it produces, while chapters 5 to 10 deal with erosion, transportation, and deposition by water, wind, ice, and waves. Weathering. The work of weathering and breaking up the rocks is of 2 kinds, namely chemical and physical or mechanical weathering, but the processes involved in each are closely interrelated. 1. Chemical weathering. Chemical weathering is the basic process by which denudation proceeds. It is the extremely slow and gradual decomposition of rocks due to exposure to air and water. Air and water contain chemical elements, which, though they may be in small quantities, are sufficient to set up chemical reactions in the surface layers of exposed rocks. Such reactions may weaken or entirely dissolve certain constituents of the rock, thus loosening the other crystals and weakening the whole surface. For example, in Malaysia, the surface of granite which has been exposed to the weather is found to be pitted and rough. This is because the granite is made of 3 main minerals: quartz, felspar, and mica. The felspar is more quickly weathered than the quartz, and thus the felspar crystals are worn away. The quartz crystals are eventually loosened in this way and form a coarse sandy residue. When the surface of a rock is weathered, some of the material which is loosened is removed by erosive agents such as wind or running water, thus exposing a fresh surface to weathering, but much of the weathered material or regolith remains of the rock may stay in position, forming the basis of soil. Regolith is simply the mineral remains of decomposed rocks, but soil contains organic materials, such as the roots of plants, fallen leaves, small animals such as worms, bacteria, and so on. It is the organic content of soil which makes it fertile and allows crops to be grown. When a soil cover exists, chemical weathering of the underlying rocks does not cease. On the contrary, it is usually enhanced. This is because the soil absorbs rainwater and keeps the underlying rocks in contact with this moisture. The rainwater absorbs organic acids from the soil and thus becomes a stronger weathering agent than pure rainwater acting on bare rock. There are 3 major chemical weathering processes. A. Solution. Many minerals are dissolved by water, especially when, as with rainwater, it contains enough carbon dioxide to make it a weak acid. Solution is the most potent weathering process in limestone regions because the rainwater attacks and dissolves the calcium carbonate of which the rock I5. Weathering, mass movement, and groundwater 31. Chiefly formed. The dissolved calcium carbonate is carried away by the water joints and cracks in the rock. Are quickly widened in whole systems of caves and passages are worn out. See Chapter 8. Limestone, however, is by no means the only rock to suffer from solution. All rocks are subject to solution to some extent, but the process is much slower than with limestone. The rate at which solution takes place is affected not only by the mineral composition of the rock but also by its structure. Sedimentary rocks often have pore spaces between the grains in which air and water can lodge and thus attack the rock. The density of joints or cracks in the rock is also crucial to the speed of weathering. This factor is very clearly seen in Malaysia and Kazakhstan in the weathering of granite. Mostly, in tropical countries, where the heavy rainfall and warm climate both promote rapid chemical reactions, weathering often proceeds very rapidly. This produces the very deep regoliths or soils overlying the solid rocks. Often these regoliths contain core stones. These are pieces of solid rock which have resisted weathering while all the surrounding rock has been weathered. They are more resistant because they have fewer joints or cracks to harbor moisture and are thus more slowly weathered by solution processes, Figure 34 and Plate 4.a. Rock easily rock still. Pattern of joints. Figure 34 differential weathering in a rock such as granite where unevenly spaced joints may give rise to core stones and certain blocks remain unweathered. In jointed rocks, temperature change cracks up rectangular blocks. For a solid core stone embedded in weathered material which has been created by chemical weathering or spheroidal solution processes, Torish, Mangista, Kazakhstan. Rates of weathering are also affected by climate. Warm wet climates promote rapid chemical weathering, while dry climates inhibit chemical weathering. Dry climates, however, provide good conditions for physical or mechanical weathering. B. Oxidation. Oxidation is the reaction of oxygen in air or water with minerals in the rock. For example, most rocks contain a certain amount of iron, which, when it comes in contact with air, is changed to iron oxide, familiar brownish crust or rust iron oxide. Crumbles easily and is fat more easily eroded than the original iron. It is thus removed, loosening the overall structure of the rocks and weakening them. C. Decomposition by organic acids. Within the soil which covers most rocks are bacteria which thrive on decaying plant or animal material. These bacteria produce acids which, when dissolved in water, help to speed up the weathering of the underlying rocks. In some cases, microorganisms and plants like mosses or lichens can live on bare rock, so long as the surface is damp. These absorb chemical elements from the rocks as food and also produce organic acids. They are thus agents of both chemical and mechanical weathering. 2. Physical or mechanical weathering. Mechanical weathering is the physical disintegration of a rock by the actual prizing apart of separate particles. This can happen even with completely fresh rock, but the processes of physical weathering are able to work much more easily when the surface of the rock has already been weakened by the action of chemical weathering. Mechanical weathering takes place in several ways. 32 Part 1. Physical geography. A. Repeated temperature changes. In deserts, rocks are exposed to the blazing sun during the day and are intensely heated. The outer layers expand much faster than the cooler interior of the rocks and tend to pull away from the rest. At nightfall, the temperature drops rapidly and the outer layers contract more rapidly than the interior, setting up internal stresses. Such stresses, repeated every day for months and years, cause the rocks to crack and split. Well-bedded and jointed rocks tend to split along the joints or cracks, breaking up into rectangular blocks. Shales and slates may split up into platy fragments because of their platy structure. In crystalline rocks such as granite, the crystals of the various minerals, quartz, mica, feldspa, will expand and contract at different rates, enhancing the stresses and accelerating the disintegration of the rocks. Fragments broken from large rock outcrops fall by gravity. From large rock outcrops fall by gravity to the foot of the slope. They may form screes or may form a litter of angular chips and small boulders on the flatter ground. Stresses and pressures will naturally be greatest near the surface and where there are sharp angles in the rocks. Rectangular blocks are thus gradually rounded by the splitting away of sharp corners. When the surface layers of rounded boulders gradually split off, the process is called onion peeling, because the various layers look like the layers of an onion, peeled off one after another. The technical term for this process is exfoliation, Plate 4.b. B. Repeated wetting and drying. Exfoliation is not confined to desert areas. Similar stresses may be set up in rocks by repeated wetting and drying of the surface layers. This takes place especially in tropical regions like Malaysia, where short downpours saturate the rocks, and then the hot sun quickly dries them again. Repeated wetting and drying also occurs at the coast, where rocks may be rapidly dried by sun and wind between tides. When rocks are wetted, the outer layers absorb a certain amount of moisture and expand. When they dry, this moisture evaporates and they quickly shrink. When this happens repeatedly, the outer layers split off. It should also be stressed that the wetting and drying of the rocks in deserts is probably just as important as temperature changes in mechanical weathering. The rocks dry very quickly indeed after being wetted by brief desert rainstorms. For .b, when core stones are exposed to tropical weather conditions, they are subject to repeated wetting and drying, which cause the outer layers to peel off. This sandstone boulder shows several layers have split off in some areas. G.C. Morgan. C. Frost action. In temperate latitudes, frost is a potent rock breaker. All rocks contain cracks and joints or pore spaces, and after a shower, water or snow collects in such places. When the temperature drops at night or during the winter, this water freezes. When water freezes, it expands by 1/10 its volume and exerts a bursting pressure of almost 140 kilograms per square cm, 2,000 pounds to the square inch. Repeated freezing of this kind will deepen and widen the original cracks and crevices and break the rock into angular fragments, figure 35. On mountain peaks, this process creates sharp pinnacles and angular outlines. Such peaks are described as frost-shattered peaks. Angular fragments of rock are prized from mountainsides or cliff faces and fall to the foot of the slope, where they accumulate to form screes. Water collects in rock crevices. Water freezes and expands in volume, prizing rocks apart. Figure 35. Frost action as an agent of mechanical weathering. Weathering, mass movement, and groundwater. 33. Figure 36. Plant roots as agents of mechanical weathering. D. Biotic factors. Small fragments of rock loosened by either chemical or mechanical weathering lodge in cracks and crevices in the rock, and plants may sprout in such crevices. As they grow, their roots penetrate the rocks below, usually along joints and other lines of weakness, prizing them apart. You have often come across large trees growing near roads or the courtyards of houses that finally prise open the concrete or paving stones above their roots. The process is just the same on a smaller scale in a natural setting, figure 36. Men, in the course of mining, road construction, and farming, also contribute to mechanical weathering by excavating the rocks and rendering them more vulnerable to the agents of denudation. Mass movement. Mass movement is the movement of weathered materials down a slope due to gravitational forces. The movement may be gradual or sudden, depending on the gradient of the slope, the weight of the weathered debris, and whether there is any lubricating moisture supplied by rainwater. Several kinds of mass movement are distinguished. 1. Soil creep. This is a slow, gradual, but more or less continuous movement of soil downhill slopes. The movement is not very noticeable, especially when the slope is fairly gentle or when the soil is well covered with grass or other vegetation. Soil creep is most common in damp soils where the water acts as a lubricant so that individual soil particles move over each other and over the underlying rock. It is also found where continuous trampling by animals grazing on the slopes sets up vibrations which loosen the soil and cause it to move. Though the movement is slow and cannot readily be seen in action, the gradual movement tilts trees, fences, posts, and trees. Figure 37. Evidences of soil creep. 34. Part 1. Physical geography. So on which are rooted in the soil. The soil is also seen to accumulate at the foot of slope or behind obstacles such as walls, which may eventually be burst by the weight of soil above, figure 37. 2. Soil flow, solifluction. When the soil is completely saturated with water, the individual particles are almost suspended in the water and move easily over one another and over the underlying rock. The soil acts like a liquid and a soil flow or mud flow occurs. In arid regions, a mantle of weathered debris may become saturated with rainwater after a storm and flow downslope as a semi-liquid mass. In temperate and tundra regions, soil flows occur when the surface layers of frozen ground thaw in spring. Soil and rock debris, lubricated by the meltwater, flow easily. For .ca, landslide after flood has damaged the road in a small town called Semoy in Bintang, Pahang, Malaysia, over the underlying frozen subsoil. In areas of pegged soils, the peat absorbs much moisture. However, if saturation point is reached, the peaty soil I.e. flow downslope. In Ireland, such flows are known as bog bursts. 3. Landslides, slumping or sliding. These are very rapid kinds of movement and occur when a large mass of soil or rock falls suddenly. Landslides usually occur on steep slopes such as in mountainous areas, on cliffs, or where man has artificially steepened slopes. For example, in road or rail cuttings, plate 4.c. Landslides may be caused because a steep slope is undercut by a river or the sea so that it falls by gravity. Earthquakes or volcanic disturbances may loosen rocks and start off a landslide. Man-made steepening both undercuts the slope and sets up vibrations which may loosen rocks or soil, but often landslides are caused by the lubricating action of rainwater. Water may collect in joints or bedding planes and rocks so that one layer slides over another, especially in areas of tilted strata. Slumping is particularly common where permeable debris or rock layers overlie impermeable strata such as clay. Water sinking through the permeable material is halted by the clay. The damp clay provides a smooth, slippery surface over which the upper layers easily slide, figure 38. Water may collect at the base of the regolith because it sinks readily into the weathered material but more slowly into the solid rock beneath. The water may allow the regolith to slide away from the underlying rock. Figure 38. Landslide. Weathering, mass movement, and groundwater. 35. For .da, an effective way of preventing landslide by building a concrete wall. For .d, B, currently, welded wire mesh continues to be the go-to solution for landslide mitigation and repairs. Man often enhances the possibility of landslides by clearing natural vegetation for agriculture or housing. Removal of the plant cover allows more water to penetrate the soil and rocks. In areas such as the Cameron Highlands, where steep slopes have been cleared, there is much evidence of minor slumps and slides, the old scars, showing up clearly in the tea gardens. Extensive landslides, whether natural or man-induced, can have disastrous consequences, burying villages, railway lines, or people. Spectacular landslides have taken place in many parts of the world, including South Wales, British Columbia, Hong Kong, and the Cameron Highlands, where the village of Ringlet was partially buried in 1961 and several houses were ruined. Groundwater. The whole process of the circulation of water between the land, sea, and atmosphere is known as the hydrological cycle. The movement of the water in the atmosphere and its effect on climate are dealt with in chapters 13 and 14. The seas and oceans are discussed in chapter 12. The effect of water on the land as an agent of weathering, erosion, transport, and deposition is dealt with in this and the following chapters, especially chapter 5. When rain falls on the earth, it is distributed in various ways. Some is immediately evaporated and thus returns to the atmosphere as water vapor. Some is absorbed by plants and only gradually returned to the atmosphere by transpiration from the leaves of plants. Much of it flows directly off slopes to join streams and rivers, eventually reaching the seas and oceans. This is known as runoff. A considerable proportion of the water received from rain or snow, however, percolates downwards into the soil and rocks, filling up joints and pore spaces and forming what is known as groundwater. Groundwater plays an important part in weathering and mass movement and is also important as a means of natural water storage. It re-enters the hydrological cycle by way of springs. The amount of water available to form groundwater depends to some extent on climate. In dry climates, much precipitation may be quickly evaporated into the dry atmosphere and little moisture may percolate into the ground. In very humid conditions, where the surface of the ground may already be moist, much water may be moved as runoff. In moderately humid areas, water both runs off and sinks into the ground. The proportion of the rainfall absorbed as groundwater may depend on the season of the year. More important, however, is the nature of the rocks and how easily they absorb and retain water. Various rocks and soils differ greatly in their porosity and permeability. The amount of groundwater present and the depth at which it lies are governed by these characteristics. Porous rocks are those, like sandstone, which have many pore spaces between the grains. Water is easily absorbed by such rocks and may be stored in the pore spaces. 36 Part 1. Physical Geography. Permeable or pervious rocks are those which allow water to pass through them easily, figure 39. Thus most porous rocks are also permeable. However, some rocks are porous but impermeable. Clay, for example, is highly porous since it is made up of innumerable very fine particles with pore spaces between them. It thus absorbs a great deal of water. However, the pore spaces are so small that the water does not move easily through the rock, which is thus impermeable. On the other hand, granite, which is a crystalline rock and consequently non-porous, is often pervious. Its individual crystals absorb little or no water, but the rock may have numerous joints or cracks through which the water can pass, rendering it pervious or permeable. Some granites are, however, far more pervious than others. For Dadi, substantial downpour has triggered floods and caused extreme loss in Penampang area in Malaysia. The 2014 floods have affected 40,000 people from 70 villages. Joints and faults. Figure 39. Porosity and permeability of rocks. The water table. Water which seeps through the ground moves downward under the force of gravity until it reaches an impermeable layer of rock through which it cannot pass. If there is no ready outlet for the groundwater in the form of a spring, the water accumulates above the impermeable layer and saturates the rock. The permeable rock in which the water is stored is known as the aquifer, figure 40. The surface of the saturated area is called the water table. The depth of the water table varies greatly according to relief and to the type of rocks. The water table is far below the surface of hilltops but is close to the surface in valleys and flat low-lying areas where it may cause waterlogging and swampy conditions. The depth of hilltop water table lies farther beneath. Figure 40. Groundwater table and its relationship to the curvature of the land. Weathering, mass movement, and groundwater. 37. The water table also varies greatly with the seasons. When plenty of rain is available to augment groundwater supplies, the water table may rise, but in dry periods, no new supplies are available and the water table is lowered as groundwater is lost through seepages and springs. Figure 40. Springs and wells. 1. Springs. The groundwater stored in the rock is released onto the surface at points where the water table reaches the surface. A spring is simply an outlet for such water. The water may seep gradually out of the rock or may gush out as a fountain. Springs are of several kinds. Due to the nature of the rocks and the position of the water table, the main types are described below. A. In areas of tilted strata, where permeable and impermeable rocks alternate, water emerges at the base of the permeable layers, figure 41a. B. In well-jointed rocks, water may percolate downwards until it reaches a joint which emerges at the surface. The water may come to the surface through the joint, figure 41b. C. Where a dike or sill of impermeable rock is intruded through permeable rocks, it causes the water table to reach the surface and the water issues as a spring, figure 41c. D. In limestone or chalk escarpments, where the permeable rock lies between impermeable strata, water issues at the foot of the scarp as a scarp foot spring, or near the foot of the dip slope as a dip slope spring, as illustrated in figure 41d. Figure 41, a. Spring seeps from edge of pervious rock lying above an inclined impervious strata. Figure 41, b. Spring emerges from rocks with joints. Figure 41, c. A dike spring. Figure 41, d. Scarp foot spring and dip slope spring. 38 Part 1. Physical geography. E. In karst regions, rivers often disappear underground. They then flow through passages worn in the rock by solution and may reemerge when limestone gives place to some impermeable rock. This kind of spring is sometimes called a Vauclusian spring, but is better referred to as a resurgence, figure 41e. See also Chapter 8. Figure 41e. Vauclusian spring in karst regions. Some other types of springs, e.g. hot springs, mineral springs, and geysers are described in Chapter 3. 2. Wells. Springs are the natural emergence points of groundwater, but man can make use of stored water below ground by sinking wells. A hole is bored through the earth until the water table is reached. The well must be sunk to the depth of the permanent water table, figure 42, if a constant supply of water is to be obtained. If the well is only sunk to the wet season. Figure 42, depth of wells and water table mark. Depth of the water table, water will be unobtainable when the level drops in the dry season. When a well is bored, the water usually has to be raised by hand or by mechanical pumping. Wells are particularly important in arid areas where there is little surface water, but where the underlying rocks contain groundwater. A particularly important type of well is the artesian well, which owing to the nature of its formation is quite distinctive, where rock layers have been downfolded into a basin shape. Permeable strata such as chalk or limestone may be sandwiched between impermeable layers, such as clay. The permeable rocks may only come to the surface at the edges of the basin, but water falling on them will gradually seep downwards by the force of gravity until it reaches the lowest part of the basin, figure 43. The impermeable layer. Figure 43, formation of an artesian basin where a pervious layer, aquifer, is between two impervious strata of rocks. Weathering, mass movement, and groundwater. 39. Below prevents the water from passing downwards, while the impermeable layer on top prevents any possibility of the water escaping upwards. The aquifer is thus saturated to the brim of the basin. The water is thus trapped in the aquifer under great pressure, and when a well is bored, the pressure of water downwards from all around the basin is sufficient to force the water up the borehole so that it gushes onto the surface like a fountain. After a time, the pressure decreases and it is necessary to pump up the water. The depth of artesian wells varies from place to place, from a few feet to thousands of feet. The water may be used to supply the needs of an entire village, as in the Great Plains of USA, or for sheep farming, as in Queensland and other parts of Australia. Figure 44 shows the distribution of artesian wells in Australia. But the water is sometimes unsuitable for agricultural or irrigation purposes, as it may be hot or contain an excessive amount of mineral salts. Artesian wells are most valuable to man when they can be used in desert areas, e.g. in parts of the Sahara and in Australia. The aquifers receive water in areas of higher rainfall, but the water accumulates in basins underlying arid regions. Figure 44, the distribution of artesian basins in Australia. All wells bored by man tend to deplete groundwater resources because the water is extracted faster than under natural conditions and also much faster than it can be replenished by rainfall. In many areas, groundwater supplies have been greatly reduced or even exhausted by man as a result of carelessness and overexploitation. Questions and exercises. 1. A. What do you understand by the term weathering? B. Name 4 natural forces that play a role in weathering. C. Differentiate mechanical weathering from chemical weathering and give examples of each. 2. A. Describe how gravitational forces and rainwater assist in the mass movement of weathered materials on hill slopes. B. Distinguish soil creep from landslides and locate places where such occurrences have taken place. 3. A. What is meant by the following? I. Hydrological cycle. 2. Water table. 3. Aquifer. B. For any two of the above, discuss their relationship with groundwater. 4. While the Earth's crust is undergoing constructive changes to create new relief, external forces of nature are working vigorously to level this down. Discuss. 5. Elaborate on any 3 of the following. A. Exfoliation is the result of temperature changes in deserts. B. Screes accumulate at the foot of steep mountains and temperate lands. C. There are many ways in which springs can be formed. D. Artesian wells have a distinct formation. Landforms made by running water. The development of a river system. When rain falls, part of it sinks into the ground, some is evaporated back into the atmosphere, and the rest runs off as rivulets, brooks, streams, and tributaries of rivers that flow down to the sea. This running water forms a potent agent for denuding the Earth's surface. Denudation is the general lowering of the Earth's surface. This takes place because such agents of erosion as rivers, ice, wind, and waves wear away the rocks and transport the eroded debris to lower land or right down to the sea. But erosion cannot take place unless the rocks are first weakened or shattered by exposure to the elements. Rain, frost, and wind weather the rocks so that they can be eroded more easily. Unlike glaciers and snow, which are confined to the cold and temperate latitudes, waves which act only on coastlines, winds, which are only efficient. In deserts, the effect of running water is felt all over the globe wherever water is present. In deserts, the effect of running water is felt all over the globe wherever water is present. Running water is thus the most important single agent of denudation. The source of a river may be a spring, a lake, or a marsh, but it is generally in an upland region, where precipitation is heaviest and where there is a slope down which the runoff can flow. The uplands therefore form the catchment areas of rivers. The crest of the mountains is the divide or watershed from which streams flow down the slopes on both sides to begin their journey to the oceans. The initial stream that exists as a consequence of the slope is called the consequent stream. As the consequent stream wears down the surface by deepening its channel downwards, it is joined by several tributaries either obliquely or at right angles depending on the alignment and the degree of resistance of the rocks. If the rocks are composed of homogeneous beds of uniform resistance to erosion, the tributaries will join the main valley obliquely as insequent streams. The drainage pattern so evolved will be tree-like in appearance, and is therefore described as dendritic drainage, after a Greek word dendron meaning tree, figure 45. On the other hand, if the rocks are made up of alternate layers of hard and soft rocks, the tributaries tend to follow the pattern of the rock structure. If the outcrops of the rocks occur at right angles to the main valley, the tributaries will join it at right angles as subsequent streams. The drainage pattern so developed will be rectangular in shape and is called trellis drainage, figure 46. Figure 45 dendritic or tree-like drainage pattern developed on homogeneous rock or beds of equal resistance. Figure 46 trellised or rectangular drainage pattern developed on alternating outcrops of harder and softer rocks. Landforms made by running water. 41. The mechanism of humid erosion. Humid erosion covers the entire scope of sculpturing effects of running water from the action of rainwater to that of the rivers. Mass movements of earth and weathered materials on hill slopes down to valleys are mainly due to the lubricating action of water, which allows a mass of materials to move under gravity. This is particularly acute where the slopes are steep. The slow movement of soil down a hill slope is called soil creep. A more sudden movement due to the lubricating effect or rainwater may cause widespread landslides. In mountainous districts where the roads and railway tracks are cut through steep-sided valleys, landslides may obstruct railway lines, cut off road communications, and even bury villages and people. The processes of river action. When a river flows, it carries with it eroded materials. These comprise the river's load and may be divided into three distinct types. 1. Materials in solution. These are minerals which are dissolved in the water. 2. Materials in suspension. Sand, silt, and mud are carried along suspended in the water as the stream flows. 3. The traction load. This includes coarser materials such as pebbles, stones, rocks, and boulders, which are rolled along the river bed. It has been estimated that for every square mile of the Earth's surface, more than 200 tons of solid materials in suspension and more than 50 tons of materials in solution are being carried off by running water every year. The Mississippi River, which drains an area almost half the size of the United States itself, removes more than 2 million tons of eroded material into the Gulf of Mexico daily. Consequently, the river basins are being lowered, and in the case of swift-flowing rivers like the Irrawaddy, its drainage basin is being lowered by about a foot in every 400 years. During floods, the amount of rock debris swept off by rivers is very much greater. We can see this from the mud that colors the river water during a heavy rain. The ability of a river to move the various grades of materials depends greatly upon the volume of the water, the velocity of the flow, and lastly the size, shape, and weight of the load. It is said that by doubling the velocity of a river, its transporting power is increased by more than 10 times. It is therefore not surprising to find huge boulders that are stranded in normal times, but may be moved during seasonal floods. The movement of rivers is thus intermittent, acting vigorously in certain parts of the year and remaining less active at other times. River erosion and transportation. In rivers, erosion and transportation go on simultaneously, comprising the following interacting processes. 1. Corrasion or abrasion. This is the mechanical grinding of the river's traction load against the banks and bed of the river. The rock fragments are hurled against the sides of the river and also roll along the bottom of the river. Corrasion takes place in two distinct ways. A. Lateral corrasion. This is the sideways erosion which widens the V-shaped valley. B. Vertical corrasion. This is the downward action which deepens the river channel. 2. Corrosion or solution. This is the chemical or solvent action of water on soluble or partly soluble rocks with which the river comes into contact. For example, calcium carbonate in limestones is easily dissolved and removed in solution. 3. Hydraulic action. This is the mechanical loosening and sweeping away of materials by the river water itself. Some of the water splashes against the riverbanks and surges into cracks and crevices. This helps to disintegrate the rocks. The water also undermines the softer rocks with which it comes into contact. It picks up the loose fragments from its banks and bed and transports them away. Attrition. This is the wear and tear of the transported materials themselves when they roll and collide into one another. The coarser boulders are broken down into smaller stones. The angular edges are smoothed and rounded to form pebbles. The finer materials are carried further downstream to be deposited. The course of a river. The course of a river may be divided into three distinct parts, figure 47.1. The upper, FN. Landforms made by running water. The development of a river system. When rain falls, part of it sinks into the ground, some is evaporated back into the atmosphere, and the rest runs off as rivulets, brooks, streams, and tributaries of rivers that flow down to the sea. This running water forms a potent agent for denuding the Earth's surface. Denudation is the general lowering of the Earth's surface. This takes place because such agents of erosion as rivers, ice, wind, and waves wear away the rocks and transport the eroded debris to lower land or right down to the sea. But erosion cannot take place unless the rocks are first weakened or shattered by exposure to the elements. Rain, frost, and wind weather the rocks so that they can be eroded more easily. Unlike glaciers and snow, which are confined to the cold and temperate latitudes, waves which act only on coastlines, winds, which are only efficient in deserts, the effect of running water is felt all over the globe wherever water is present. Running water is thus the most important single agent of denudation. The source of a river may be a spring, a lake, or a marsh, but it is generally in an upland region, where precipitation is heaviest and where there is a slope down which the runoff can flow. The uplands therefore form the catchment areas of rivers. The crest of the mountains is the divide or watershed, from which streams flow down the slopes on both sides to begin their journey to the oceans. The initial stream that exists as a consequence of the slope is called the consequent stream. As the consequent stream wears down the surface, by deepening its channel downwards, it is joined by several tributaries either obliquely or at right angles depending on the alignment and the degree of resistance of the rocks. If the rocks are composed of homogeneous beds of uniform resistance to erosion, the tributaries will join the main valley obliquely as insequent streams. The drainage pattern so evolved will be tree-like in appearance and is therefore described as dendritic drainage, after a Greek word dendron meaning tree, figure 45. On the other hand, if the rocks are made up of alternate layers of hard and soft rocks, the tributaries tend to follow the pattern of the rock structure. If the outcrops of the rocks occur at right angles to the main valley, the tributaries will join it at right angles as subsequent streams. The drainage pattern so developed will be rectangular in shape and is called trellis drainage, figure 46. Figure 45 dendritic or tree-like drainage pattern developed on homogeneous rock or beds of equal resistance. Figure 46 trellised or rectangular drainage pattern developed on alternating outcrops of harder and softer rocks. Landforms made by running water 41. The mechanism of humid erosion. Humid erosion covers the entire scope of sculpturing effects of running water from the action of rainwater to that of the rivers. Mass movements of earth and weathered materials on hill slopes down to valleys are mainly due to the lubricating action of water, which allows a mass of materials to move under gravity. This is particularly acute where the slopes are steep. The slow movement of soil down a hill slope is called soil creep. A more sudden movement due to the lubricating effect or rainwater may cause widespread landslides. In mountainous districts where the roads and railway tracks are cut through steep-sided valleys, landslides may obstruct railway lines, cut off road communications, and even bury villages and people. The processes of river action. When a river flows, it carries with it eroded materials. These comprise the river's load and may be divided into three distinct types. 1. Materials in solution. These are minerals which are dissolved in the water. 2. Materials in suspension. Sand, silt, and mud are carried along suspended in the water as the stream flows. 3. The traction load. This includes coarser materials such as pebbles, stones, rocks, and boulders, which are rolled along the riverbed. It has been estimated that for every square mile of the Earth's surface, more than 200 tons of solid materials in suspension and more than 50 tons of materials in solution are being carried off by running water every year. The Mississippi River, which drains an area almost half the size of the United States itself, removes more than 2 million tons of eroded material into the Gulf of Mexico daily. Consequently, the river basins are being lowered, and in the case of swift-flowing rivers like the Irrawaddy, its drainage basin is being lowered by about a foot in every 400 years. During floods, the amount of rock debris swept off by rivers is very much greater. We can see this from the mud that colors the river water during a heavy rain. The ability of a river to move the various grades of materials depends greatly upon the volume of the water, the velocity of the flow, and lastly the size, shape, and weight of the load. It is said that by doubling the velocity of a river, its transporting power is increased by more than 10 times. It is therefore not surprising to find huge boulders that are stranded in normal times, but may be moved during seasonal floods. The movement of rivers is thus intermittent, acting vigorously in certain parts of the year and remaining less active at other times. River erosion and transportation. In rivers, erosion and transportation go on simultaneously, comprising the following Acting processes. 1. Corrasion or abrasion. This is the mechanical grinding of the river's traction load against the banks and bed of the river. The rock fragments are hurled against the sides of the river and also roll along the bottom of the river. Corrasion takes place in two distinct ways. A. Lateral corrasion. This is the sideways erosion which widens the V-shaped valley. B. Vertical corrasion. This is the downward action which deepens the river channel. 2. Corrosion or solution. This is the chemical or solvent action of water on soluble or partly soluble rocks with which the river comes into contact. For example, calcium carbonate in limestones is easily dissolved and removed in solution. 3. Hydraulic action. This is the mechanical loosening and sweeping away of materials by the river water itself. Some of the water splashes against the river banks and surges into cracks and crevices. This helps to disintegrate the rocks. The water also undermines the softer rocks with which it comes into contact. It picks up the loose fragments from its banks and bed and transports them away. 4. Attrition. This is the wear and tear of the transported materials themselves when they roll and collide into one another. The coarser boulders are broken down into smaller stones. The angular edges are smoothed and rounded to form pebbles. The finer materials are carried further downstream to be deposited. The course of a river. The course of a river may be divided into three distinct parts. Figure 47. 1. The upper caret. 42 Part 1. Physical geography. 1. Upper course gorge rapids and waterfalls river capture. 2. Middle course interlocking spurs meanders river cliffs. 3. Lower course floodplains oxbow lakes deltas. Transportation. Alluvium deposition. Deposition. Vertical corrasion. Figure 47 i.e. graded long profile and typical cross-section of a river from source to mouth. Sleep, gorge-like or V-shaped valley. Very gently sloping, smooth, wide valley. Open, widening, gentle sloping valley. 1. I predominantly erosion. Valley widening, some deposition. See asterisk. Course, in the stage of youth. 2. The middle or valley course, in the stage of maturity. 3. The lower or plain course, in the stage of old age. 1. The upper or mountain course. This begins at the source of the river near the watershed, which is probably the crest of a mountain range. The river is very swift as it descends the steep slopes, and the predominant action of the river is vertical corrasion. The valley developed is thus deep, narrow, and distinctively V-shaped. Downcutting takes place so rapidly that lateral corrasion cannot keep pace. In some cases where the rocks are very resistant, the valley is so narrow, and the sides are so steep that gorges are formed, e.g. the Indus Gorge in Kashmir. In arid regions, where there is little rainfall to widen the valley sides, and the river cuts deep into the valley floor, precipitous valleys called canyons are formed, e.g. the Bryce Canyon, Utah, USA. Some of the more outstanding features that are often best developed in the upper course of a river include the following. A. River capture. This is also known as river piracy or river beheading. Its development is dependent on the different rate of back-cutting, headward erosion, into a divide. For instance, if one side of the divide is of greater gradient or receives more precipitation than the other, Stream A in Figure 48 will cut back more rapidly than Stream B. The famous Samaria Gorge on the island of Crete, Greece. A. Figure 48 River capture. A. Before capture. A. Pirating Stream. B. Pirated Stream. X elbow of capture. Y wind gap. RZ. Beheaded D stream or misfit. B. After capture. Landforms made by running water. 43. Its greater erosive power will succeed in enlarging its basin at the expense of the weaker stream. Stream A may eventually break through the divide and capture or pirate Stream B. The bend at which the piracy occurred is termed as the elbow of capture. The beheaded stream, Z, is called the misfit. The valley below the elbow is the wind gap and may be valuable as a road and rail route. Examples of river capture abound. In Myanmar, the upper Sittang has been captured by the Irrawaddy. In Northumberland, England, the Blythe and the Wansbeck are beheaded by the North Tyne. B. Rapids, cataracts, and waterfalls. These are liable to occur at any part of the river course, but they are most numerous in the mountain course where changes of gradient are more abrupt and also more frequent. Due to the unequal resistance of hard and soft rocks traversed by a river, the outcrop of a band of hard rock may cause a river to jump or fall downstream. Rapids are formed, Figure 49. Similar falls of greater dimensions are also referred to as cataracts, of which there are 5 along the Nile that interrupt smooth navigation. When rivers plunge down in a sudden fall of some height, they are called waterfalls, Figure 50. Their great force usually wears out a plunge pool beneath. Waterfalls are formed in several ways. I. When a bar of resistant rock lies transversely across a river valley, e.g. the Niagara Falls, USA, which is 167 feet, 51 meters, high, in the Kaieter Falls in Guyana, 741, 226 feet, high. 2. When a fault line scarp caused by faulting lies across river, e.g. Victoria Falls on the river Zambezi, plunging 355 feet, 108 meters. 3. When water plunges down the edge of a plateau like the River Congo, which leaps 4. 900 feet, 275 meters, through a series of more than 30 rapids as Livingstone Falls. Figure 49 rapids, cataracts. Figure 50 a waterfall with plunge pool. 4. Glaciation produces hanging valleys where tributary streams reach the main U-shaped valley below as waterfalls, e.g. the Yosemite Falls of California, with a total descent of 2,425 feet, 740 meters. 2. The middle or valley course. In the middle course, lateral corrosion tends to replace vertical corrosion. Active erosion of the banks widens the V-shaped valley. The volume of water increases with the confluence of many tributaries, and this increases the river's load. The work of the river is predominantly transportation, with some deposition. Downstream, the interlocking spurs, figure 51, that project from both sides of the valley are cut back into a line of bluffs. Rainwash, soil creep, landslides and gullying gradually widen the valley, cutting back the sides. The river's treble task of valley cutting, bed smoothing, and debris removal are being carried out in a more tranquil manner than in the mountain course, though the velocity does not decrease. Some of the load is dropped or deposited. Again, this depends on the volume of flow, for in the event of flood, the river's erosive power and its capability for load carrying is greatly increased. The more outstanding features associated with the valley course are these. A. Meanders. As water flowing under gravity seldom flows straight for any long distance, a winding course soon develops. The irregularities of the ground force the river to swing in loops, forming meanders, a term derived from the winding river meander as in Asia Minor. The mechanism of meander formation is illustrated in Fig. 52. B. River cliffs and slip-off slopes. When the flow of water PQ in Figure 52 enters the bend of the Riv. 44 Part 1. Physical geography. Figure 51 interlocking spurs. B. Figure 52 meanders. A. The development of meanders. B. Cross-section of a meander. Asterisk. Meander formed by the Arda River, Eastern Rhodopes, Bulgaria. The river swings from side to side in tight R-arm-durs. Note the sand deposited on the slip-off slope. It dashes straight into Q, eroding the outer bank into a steep river cliff at Q. The water piles up on the outside of the bend because of the centrifugal force. A bottom current RS is set up in a corkscrew motion and is hurled back into midstream in the inlet bank. Shingle is thus deposited here at S, where the slip-off slope is very gentle. The outer bank is therefore the bank of continuous erosion, and the inner bank is the bank of continual deposition. C. Interlocking spurs. As the stream flows on, the meanders migrate progressively outwards with the interlocking spurs alternating with the undercut slopes as shown in Fig. 51. It must be pointed out at this stage that meanders in the middle course are only the beginning of the downstream swing, for bends are restricted by the interlocking spurs in the lower course. The loops are enlarged across the level plain and meanders are fully developed. 3. The lower or plain course. The river moving downstream across a broad, level plain is heavy with debris brought down from the upper course. Vertical corrosion has almost ceased, though lateral corrosion still goes on to erode its banks further. The work of the river is mainly deposition, building up its bed and forming extensive floodplains. The volume of water is greatly swelled by the additional tributaries that join the mainstream. Coarse materials are dropped and the finer silt is carried down towards the mouth of the river. Large sheets of materials are deposited on the level plain and may split the river into several complicated channels so that it can be described as a braided stream. Some of the major plain course features are the following. A. Floodplain. Rivers in their lower course carry large quantities of sediments. During annual or sporadic floods, these materials are spread over the low-lying adjacent areas. A layer of sediment is thus deposited during each flood, gradually building up a fertile floodplain, Figure 53. When the river flows, normally its bed is raised through the accumulation of deposits, and material is also dropped on the sides, forming raised banks called levees. It will not be long before the water level flows dangerously close to the top of the levees. In an attempt to minimize the risk of floods, artificial embankments are erected on the natural levees, but this allows the river to rise further. When they can no longer withstand the pressure of the floodwater, the banks burst, damaging property and drowning thousands. Disastrous floods of this nature frequently occur. Landforms made by running water 45. In the Yangtze, Mississippi, and Ganges Plains. But the best-known river for floods is the Huang Ho, Yellow River, China's sorrow, where millions have perished. For example, in 1852 the Huang Ho breached its bank, killing 1 million people and did untold damage to farms and properties. The river's course was diverted over 300 miles away, draining into the Gulf of Pohe instead of the Yellow Sea. Nowadays, huge dredgers help to deepen the channels to avoid excessive sedimentation. Artificial. Figure 53 section of a floodplain with levee and artificial embankment. B. Oxbow lakes. These are also known as cut-offs or bayous in the Mississippi Basin. In the lower course of a river, a meander becomes very much more pronounced. The outside bend or concave bank is so rapidly eroded that the river becomes almost a complete circle. There will come a time when the river cuts through the narrow neck of the loop, abandoning an oxbow lake or moor lake, meaning dead lake. The river then flows straight. The oxbow lake will later degenerate into a swamp through subsequent floods that may silt up the lake. It becomes marshy and eventually dries up. Figure 54. Figure 54, the formation of an oxbow lake. C. Delta. When a river reaches the sea, the fine materials it has not yet dropped are deposited at its mouth, forming a fan-shaped alluvial area called 3. Delta takes a characteristic 2. River is obstructed by sediments. I. River reaches coast. Figure 55, the formation of deltas. A. Stages in the formation of a delta. B. Section through the lower course of a river, showing floodplain and delta. 46 Part 1. Physical Geography. A delta, a word which originated from the Greek letter A, which closely resembled the triangular delta of the Nile. Figure 55. This alluvial tract is, in fact, a seaward extension of the floodplain. Due to the obstruction caused by the deposited alluvium, the river may discharge its water through several channels called distributaries. Some deltas are extremely large. For instance, the Ganges Delta is almost as big as the whole of West Malaysia. Deltas extend sideways and seawards at an amazing rate. The river extends its delta by over 40 feet a year. The town of Adria, located nearly 15 miles inland, was a seaport in the time of Christ. Deltas differ much in their size, shape, growth, and importance. A number of factors such as the rate of sedimentation, the depth of the river and the seabed, and the character of the tides, currents, and waves greatly influence the eventual formation of deltas. For this reason, several types of delta are recognizable. The Mississippi has a bird's foot delta, with several main branches like the foot of a bird extending into the Gulf of Mexico. The Nile, Ganges, and Mekong have the fan-shaped arcuate deltas with numerous distributaries. Some other rivers such as the Amazon, Ob, and Vistula have their deltas partly submerged in coastal waters to form estuarine deltas. A few rivers like the Ebro of Spain have tooth-like projections at their mouths. These are known as cuspate deltas. The following summarizes the conditions favorable for the formation of deltas. I. Active vertical and lateral erosion in the upper course of the river to provide extensive sediments to be eventually deposited as deltas. 2. The coast should be sheltered, preferably tideless. 3. The sea adjoining the delta should be shallow, or else the load will disappear in the deep waters. 4. There should be no large lakes in the river course to filter off the sediments. V. There should be no strong current running at right angles to the river mouth, washing away the sediments. River rejuvenation. The Earth's crust is far from stable, and it is not surprising that, in the course of a river's development, parts may be uplifted or depressed, giving rise to certain characteristic features associated with rejuvenation, i.e. being young. Again, a negative movement occurs when there is an uplift of land or a fall in sea level. This will steepen the slope so that active downcutting Js renewed. A fall in sea level leaves the floodplain at an increased altitude above the sea level. The river with its renewed vigor cuts into the former floodplain, leaving behind terraces on both sides of the river. There is also a break in the graded profile of the river, often marked by a series of rapids. This point where the old and rejuvenated profile meet is called the Nick Point or rejuvenated head. Figure 56. Figure 56, river terraces and Nick Point. Due to rejuvenation, the rejuvenated river cuts down into previously deposited sediments to form a new valley, leaving terraces at either side. At the head of rejuvenation, the river falls to its new valley at a Nick Point. Landforms made by running water. 47. If rejuvenation occurs in the upper course, the river valleys are deepened and steep-sided gorges are formed. In the middle and lower course, vertical corrosion replaces lateral corrosion, and the existing meanders are vertically eroded by the rejuvenated stream. A distinct new inner trench is cut in the old valley, and the river develops a deep valley with entrenched or incised meanders. The best developed incised meanders are those of the River Colorado, USA, where the uplift of 7,000 feet in the Tertiary period renewed down cutting to a fantastic depth. In some parts of the Grand Canyon, the depth is almost a mile. It is 10 miles wide at the top and 300 miles long. Other examples are the River Moselle in Germany, the River Wear at Durham, England, and the Wye Valley, Monmouthshire. A positive movement occurs when there is a depression of land or a rise in sea level. This will submerge the lands along the coast, drown the valleys, and weaken the erosive power of the river. The flow is checked and large quantities of sediment will be dropped. The lower course of the river may be partly in the sea, and features of deposition are shifted upwards to the middle course. The upper course is little affected when there is a rise in sea level. In many areas where the sea has risen, this was probably caused by the release of water locked up in the ice masses during the Quaternary ice ages. The human aspects of rivers. In many countries, rivers form the chief highway of commerce and transport. The Yangtze Kiang is navigable up to 1,000 miles from its mouth. The Amazon, the world's greatest river, is navigable 2,300 miles upstream to the foot of the Andes, though it is less extensively used. Even the Nile with its cataracts is navigable for its first 960 miles up to the first cataract at Aswan. Other major rivers such as the Mississippi, St. Lawrence, Rhine, Danube, Congo, Murray, Darling, Mekong, and Irrawaddy all serve as important waterways for their respective countries. Some of them are useful for transporting logs to the sawmills, others are used to export bulky goods and import foodstuffs and raw materials. But all rivers undertake three closely interrelated activities: erosion, transportation, and deposition. Their work has therefore both advantages and disadvantages from a human point of view. Rapids and waterfalls interrupt the navigability of a river. By depositing large quantities of sediments in the lower course, the river silts up ports, preventing large steamers from anchoring close to the shores. Deltas are thus less satisfactory sites than estuaries for the siting of large ports. Though this can be overcome by the construction of artificial harbors or by dredging, this is expensive and, in some instances, impracticable. Some rivers change their courses from time to time, others are made difficult for navigation by their seasonal variations in the amount of water discharged, and others may suffer from ill-drained marshes and stagnant waters, leading to ill health and waterborne disease. Many rivers flood, bursting levees and causing untold damage to crops. The floods may add a layer of fertile silt to the floodplain. But excessive flooding, as in the Orinoco, may discourage people from cultivating crops at all. On the other hand, the advantages of rivers often outweigh the destruction that they cause. In the upper course, rivers with steep gorges and waterfalls provide natural sites for the generation of hydroelectric power, leading to the establishment of metallurgical industries, engineering, and aluminum smelting, which can be profitably run on cheap, abundant power. Dams constructed across rivers hold back floodwater, which, if allowed to flow downstream unchecked, may cause widespread disastrous floods in the lower course, e.g. in the Indus and Ganges plains. In regions of insufficient rainfall such as Egypt and the Chao Phraya Basin in Thailand, irrigation canals fed by the mainstream enable many crops to be successfully cultivated. The upper streams develop river captures, and the resultant wind gaps may facilitate construction of upland roads and railways. The river valleys provide a convenient means of land communication. The floodplains of large rivers with their thick mantles of fine silt are some of the richest agricultural areas of the world. They may support very dense populations, and a chain of large cities may be strung along their banks. Many deltas are equally fertile, e.g. the Ganges Delta accounts for almost all the jute grown for world consumption. The Nile Delta produces superior quality cotton and several crops of rice a year. The productive hinterlands are able to support ports such as New Orleans for the Mississippi Basin, Rotterdam for the Rhineland, and Calcutta for the Indo-Gangetic Plain. 48 Part 1. Physical Geography. Freshwater fishing is important along many rivers and lakes. The organic matter brought down by the river waters provides valuable food for fish and for spawning purposes. Rivers supply water for domestic consumption, sewerage, and other industrial purposes. In Lancashire, the soft water from the Millstone Grid is used for washing, dye, and bleaching textiles. Rivers form the politic boundaries between many countries. The Mekong separates Laos from Thailand, and the Yalu form a well-defined border between North Korea and Eastern Russia. Questions and exercises. 1. What are the characteristic features you would expect to find in a river valley at the stage of youth, maturity, and old age? Illustrate some of the more outstanding features with diagrams and examples. 2. By reference to specific examples, describe the major constructive and destructive processes at work along the course of a river from its source to its mouth. 3. With the aid of annotated diagrams, explain the contrasting features of any three of the following perso features of a river: A. Dendritic and trellis drainage pattern. B. Rapids and waterfalls. C. Estuary and delta. D. Tributaries and distributaries. E. River capture and river cliff. 4. Explain any three of the following statements briefly. A. Mass movement of Earth is mainly due to the lubricating action of rainwater and gravitational forces. B. Vertical corrosion is dominant in the upper course of a river. C. The work of the river in the lower course is mainly depositional. D. Ports are better sited on estuaries than on deltas. E. Incised meanders are features of river rejuvenation. 5. Either describe and explain with relevant sketches the various types of river deltas, or explain the ways in which river erosion occurs. Landforms of glaciation. The Ice Age and types of ice masses. During the Pleistocene period or the Ice Ages, about 30,000 years ago, great continental ice sheets covered much of the temperate latitudes. It is estimated that more than 12 million square miles of the northern hemisphere were buried by ice, half of which was in North America and the rest in Europe, Greenland, and the high mountains of Eurasia. Figure 57. The warmer climate that followed caused the ice sheets to retreat. Today, only two major ice caps are still present, in Greenland and Antarctica. The former covers an area of 720,000 square miles, while the latter is more than 5 million square miles. They are made up of compact sheets of ice, hardened and crystallized to a depth of over a mile. In Marie Byrd Land, Antarctica, the ice cap was measured and found to be more than 14,000 feet thick. Under such a colossal weight, the land sinks gradually. From the central dome of the ice cap, the ice creeps out in all directions to escape as glaciers. The peaks of the loftier mountains project above. The surface is nunatax. When the ice sheets reach right down to the sea, they often extend outwards into the polar waters and float as ice shelves. They terminate in precipitous cliffs. When they break into individual blocks, these are called icebergs. While afloat in the sea, icebergs assume tabular or irregular shape and only 1/9 of the mass is visible above the surface. They diminish in size when approaching warmer waters and are eventually melted, dropping the rock debris that was frozen inside them on the seabed. Apart from Greenland and Antarctica, glaciation is still evident on the highlands of many parts of the world, which lie above the snow line. This varies from sea level in the polar regions to 9,000 feet in the Alps and 17,000 feet at the equator, as on Mt. Kilimanjaro. Permanent snowfields are sustained by heavy winter snowfall and ineffective summer melting and evaporation. Where the slopes are gentle and the hollows are sheltered from both direct sunlight and strong winds, any snow that falls is rapidly accumulated. Part of the surface. Snow may melt during the day, but by nightfall it is refrozen. This process is repeated until it forms a hard, granular substance known as neve in French or Föhren in German. Owing to gravitational forces, the neve of the upland snowfield is drawn towards the valley below. This is the beginning of the flow of the glacier, river of ice. It normally assumes a tongue shape, broadest at the source but becoming narrower downhill. Though the glacier is not a liquid, under the continual pressure from the accumulated snow above, it moves. The rate of movement is greatest in the middle where there 50 Part 1. Physical geography is little obstruction. The sides and the bottom are held back by friction with the valley side spurs and the valley floor. If a row of stakes is planted across a glacier in a straight line, they will eventually take a curved shape down the valley, showing that the glacier moves faster at the center than the sides, figure 58. In the Alps, the average rate of flow is about 3 feet a day. In Greenland, it may be more than 50 feet, but in Antarctica, where there is little heat to melt the ice, glaciers move only a few inches a day. The Aletsch Glacier in the Bernese Oberland of Switzerland is 10 miles long, affording some spectacular sights to alpine tourists. Though it is the longest glacier in Europe, it is short compared with those of Alaska and the Himalayas, which measure more than 5 times that length. Figure 58. The different rate of glacial movement. A glacier moves faster in the center than the sides. At the foot of mountain ranges, several glaciers may converge to form an extensive ice mass called a Piedmont Glacier. The best-known Piedmont Glacier is the Malaspina Glacier of Alaska, which is 65 miles long and 25 miles wide, covering an area of more than 1,600 square miles. Combined glaciers of such dimensions are now rare, and in most continents, only valley or alpine glaciers are seen. Landforms of highland glaciation. Glaciation generally gives rise to erosional features in the highlands and depositional features on the lowlands, though these processes are not mutually exclusive because a glacier plays a combined role of erosion, transportation, and deposition throughout its course. A glacier erodes its valley by 2 processes: plucking and abrasion. By plucking, the glacier freezes the joints and beds of the underlying rocks, tears out individual blocks, and drags them away. By abrasion, the glacier scratches, scrapes, polishes, and scours the valley floor with the debris frozen into it. These fragments are powerful tools of denudation. Large angular fragments cut deep into the underlying rock, so all glaciated floors bear evidence of striation or scratching. The finer materials smooth and polish the rock surfaces and produce finely ground rock flour. The rate of erosion is determined by several factors such as the velocity of flow, gradient of the slope, the weight of the glacier, the temperature of the ice, and the geological structure of the valley. The characteristic features of a glaciated highland are as follows. 1. Corrie, cirque, or combe. The downslope movement of a glacier from its snow-covered valley head and the intensive shattering of the upland slopes tend to produce a depression where the Föhren or neve accumulates. The process of plucking operates on the back wall, steepening it, and the movement of the ice abrades the floor, deepening the depression into a steep, horseshoe-shaped basin called a cirque in French. It is also known as a corrie in Scotland and a combe in Wales, figure 59. There is a rocky ridge at the exit of the corrie, and, when the ice eventually melts, water collects behind this barrier to form a corrie lake or tarn. Figure 59. Development of a corrie. 2. Arates and pyramidal peaks. When 2 corries cut back on opposite sides of a mountain knife, edged ridges are formed called arates, a French word. A well-known British example of an arate. Landforms of glacial ion 51. A glacial landscape in Switzerland's Swiss National Tourist Office. Figure 60. Cirque, arate, and pyramidal peak is the striding edge on Helvellyn in Westmoreland. Where 3 or more cirques cut back together, their ultimate recession will form an angular horn or pyramidal peak. The Matterhorn of Switzerland is a classic example, figure 60. 3. Bergschrund. At the head of a glacier, where it begins to leave the snowfield of a corrie, a deep vertical crack opens up called a Bergschrund in German, or Rimei in French. This happens in summer when, although the ice continues to move out of the corrie, there is no new snow to replace it. In some cases not one, but several such cracks occur. The bergschrund presents a major obstacle to climbers. Further down were the glaciers. 52 Part 1, Physical Geography. A U-shaped valley in Switzerland. The valley sides are steep, but the floor is flat. Negotiates a bend or a precipitous slope, more crevasses or cracks are formed, figure 59. 4. U-shaped glacial trough. The glacier on its downward journey, fed by ice from several quarries like tributaries that join a river, begins to wear away the sides and floor of the valley down which it moves. It scratches and grinds the bedrock, removing any rock debris and surface soil. It tends to straighten any protruding spurs on its course. The interlocking spurs are thus blunted to form truncated spurs and the floor of the valley is deepened, figure 61. A valley which has been glaciated takes a characteristic U shape, with a wide, flat floor and very steep sides. After the disappearance of the ice, the deep sections of these long, narrow glacial troughs may be filled with water-forming ribbon lakes, such as Loch Ness and Lake Ullswater in Great Britain. They are sometimes referred to as trough lakes or finger lakes. 5. Hanging valleys. The main valley is eroded much more rapidly than the tributary valleys as it contains a much larger glacier. After the ice has melted, a tributary valley therefore hangs above the main valley so that its stream plunges down as a waterfall, figure 61. Such tributary valleys are termed hanging valleys and may form a natural head of water for generating hydroelectric power. Figure 61. A glaciated upland. 6. Rock basins and rock steps. A glacier erodes and excavates the bedrock in an irregular manner. The unequal excavation gives rise to many rock basins later filled by lakes in the valley trough. Where a tributary valley joins a main valley, the additional weight of ice in the main valley cuts deeper into the valley floor at the point of convergence, forming a rock step. A series of such rock steps may also be formed due to different degrees of resistance to glacial erosion of the bedrocks. Landforms of glaciation. 53. 7. Moraines. Moraines are made up of the pieces of rock that are shattered by frost action, embedded in the glaciers, and brought down the valley. Those that fall on the sides of the glacier, mainly screes, form lateral moraines. When two glaciers converge, their inside lateral moraines unite to form a medial moraine. The rock fragments which are dragged along beneath the frozen ice are dropped when the glacier melts and spread across the floor of the valley as ground moraine. The glacier eventually melts on reaching the foot of the valley and the pile of transported materials. Left behind at the snout is the terminal moraine or end moraine, figure 62. The deposition of the end moraines may be in several succeeding waves, as the ice may melt back by stages so that a series of recessional moraines are formed. Sides. Medial moraine. Lateral moraine. Snout melts at valley foot. Figure 62. The glacial moraines. NAL moraine. If the glacier flows right down to the sea, it drops its load of moraine in the sea. If sections break off as icebergs, morainic material will only be dropped when they melt, figure 63. Where the lower end of the trough is drowned by the sea, it forms a deep, steep-sided inlet called a fjord, typical of the Norwegian and South Chilean coasts. Containing moraine. H. High. Melting iceberg dropping moraine. Glacier. Moraine dropped as glacier enters sea. Rune moraine. Figure 63. A glacier ending at the sea. Landforms of glaciated lowlands. Landforms of glaciated lowlands are mainly depositional in nature, brought about by both valley glaciers and continental ice sheets. The former leaves behind the eroded materials in only restricted areas. The imprint of ice sheets on the landscape is far more widespread because they advanced through large areas during the ice ages, scouring and removing any surface soil and rock debris on their way. As a result, it has been estimated that almost a third of the total land surface of Europe and North America is littered with glacial and fluvio-glacial materials of all descriptions: moraines, boulder clay, tills, drifts, rock flour, gravels, and sands. Many of them are being re-eroded, resorted, and redeposited elsewhere by present-day rivers. Most of the glaciated lowlands have depositional features, but where rock masses project above the level surface, they result in striking features of erosion, such as the roche moutonné and crag and tail. 1. Roche moutonné. This is a resistant residual rock hummock. The surface is striated by ice movement. Its upstream side is smoothed by abrasion and its downstream side is roughened by plucking and is much steeper. The term roche moutonné is used to describe such a feature because it resembles a sheepskin wig once worn in France, figure 64. Worn in France, figure 64. Roches moutonnées are found in both highland and lowland glaciated regions. Direction of figure 64. Roche moutonné. 2. Crag and tail. The crag is a mass of hard rock with a precipitous slope on the upstream side, which protects the softer leeward slope from being completely worn down by the oncoming ice. It therefore has a gentle tail, strewn with the eroded rock debris. The classic example is the Castle Rock of Edinburgh, Scotland. Edinburgh Castle is located on the crag and the High Street on the tail. Figure 65. The remaining glaciated lowland features are of a depositional nature. Figure 66. The following are the typical ones. 54 Part 1. Physical geography. Direction of ice movement. 3. Boulder clay or glacial till. This is an unsorted glacial deposit comprising a range of eroded materials. Boulders, angular stones, sticky clay, and fine rock. Flour. It is spread out in sheets, not mounds, and forms gently undulating till or drift plains. The landform is rather monotonous and featureless. The degree of fertility of such glacial plains depends very much on the composition of the depositional materials. Some of the boulder clay plains such as East Anglia and Chile northern Midwest of USA form rich arable lands. 4. Erratics. These are boulders of varying sizes that were transported by ice. They came with the advancing glaciers or ice sheets, but when the ice melted, they were left stranded in the regions of deposition. They are called erratics because they are composed of materials entirely different from those of the region in which they are found. Such erratics are thus most useful in tracing the source and direction of the ice movement sometimes. The erratics may be found perched in precarious positions just as the ice dropped them, and they are then termed perch blocks. Examples of such blocks are commonly encountered in both lowland and highland areas in Europe, e.g. Silurian grits are found perched on the carboniferous limestone of the Pennines. Their presence in large numbers is a hindrance to farming. 5. Drumlins. These are swarms of oval, elongated, whaleback hummocks composed wholly of boulder clay, with their elongation in the direction of the ice flow, that is on the downstream side. They are low hills varying from a few yards to 400 feet in height and maybe a mile or two long. They appear a little steeper at the onset side and taper off at the leeward end. They are arranged diagonally and so are commonly described as having a basket of eggs. Topography. Large numbers of them are found in County Down in Northern Ireland and the glaciated plain around the Great Lakes in North America. 6. Escos. These are long, narrow, sinuous ridges, composed of sand and gravel which mark the former sites of subglacial meltwater streams. They vary from a few feet to 200 feet in height and may be several miles long. In some parts of Maine, USA, the outstanding Escos form a continuous ridge of 100 miles. They are very numerous in Scandinavia, e.g. the Punkaharju Esker of Finland. As Escos are made up of highly porous sand and gravel, water is rapidly drained off from their crests and they may a drumlin field. Landforms of glaciation. 55. Asterisk direction of ice movement. Figure 66. Glacial depositional features in the outwash plain not support many trees, though in Finland they often form tree-covered ridges between lakes. 7. Terminal moraines. These are made up of the coarse debris deposited at the edge of the ice sheet to form hummocky and hilly country such as the Baltic heights of the North European plain. Figure 66. 8. Outwash plains. These are made up of fluvio-glacial deposits washed out from the terminal moraines by the streams and channels of the stagnant ice mass. The meltwaters sort and redeposit the material in a variety of forms from the low hilly heathlands, such as the Lüneburg Heath of the North European plain, to undulating plains, where terraces, alluvial fans and deltaic deposits of the meltwater streams make up the landscape. Kames, small rounded hillocks of sand and gravel may cover part of the plain. Where the deposition takes the form of alternating ridges and depressions, the latter may contain kettle lakes and give rise to characteristic knob and kettle topography. The human aspects of glaciated landforms. Though the ice ages were at their height over 30,000 years ago, the effects of glaciation on both landforms and human activities have profound influence in many parts of the world today. Their most striking impact is felt in the temperate regions of Europe and North America, which were once under continental ice sheets. Further south and on the high mountains all over the world, slow-moving glaciers are still shaping the landscape in the Alps, Andes, Rockies, and Himalayas. Glacial influences on man's economic activities are both favorable and unfavorable, depending on the intensity of glaciation, the relief of the region, and whether the effects are of an erosional or depositional nature. In hilly regions such as the mountain slopes of Scandinavia, ice sheets and glaciers have removed most of the topsoil, leaving them quite bare of vegetation. Soils that do exist are so thin that they are incapable of supporting effective agriculture. Glacial drifts in the valleys and benches or Alps, which were not affected by glaciers, have good pastures during summer. Cattle are driven up to graze on the grass and return to the valley bottom in winter. This form of animal migration type of farming is called transhumance. Extensive boulder clay plains such as those of East Anglia and the Midwest of USA are some of the most fertile agricultural plains known. The lush plains of Europe and central USA, with a high proportion of humus, are good farming land too. On the other hand, the sandy or gravelly outwash plains, e.g. the heath-covered geest of northern Germany, the marshy boulder clay deposits of central Ireland, the barren ice-scoured surfaces of the Canadian and Baltic shields are infertile. The presence or numerous erratic and perch blocks in part of Britain and in Alberta, Canada, many of their 56 Part 1. Physical geography. Of gigantic size obstruct farming and the use of machines. Morainic deposits may dam or glaciers may hollow out, lakes which greatly inconvenience large-scale farming or land development. But when the lakes are eliminated, the old glacial lake beds, with their rich alluvium, support heavy cropping. Large lakes formed by former glaciation, e.g. the Great Lakes of North America, make excellent waterways. They may also cut deep overflow channels while draining off, making natural routeways across a mountainous terrain, e.g. the Hudson-Mohawk Gap that links the interior with the Atlantic seaboard of USA. On the other hand, in regions where drumlins are dominant, the drainage is either poor or much confused. Terminal and recessional moraines comprise coarse materials of little use to man, but fluvio-glacial deposits are not without their economic significance. In the outwash plains, eskers and kames have been excavated to provide sand, and gravels for highway and building construction. The purest sands are extracted to make molds for metal castings. The lake basins, glaciated mountains provide natural reservoir in places like Scandinavia, Norway, Sweden, and Denmark, Switzerland, and Canada, where then is little available coal. Streams and waterfall that plunge down from hanging valleys or OTW glaciated uplands are being harnessed to provide hydroelectric power. This has helped to develop many of the chemical and metallurgical industries. With the magnificent scenery provided by glaciated mountains, e.g. the French, Italian, and Swiss Alps, large numbers of tourists are attracted to them annually. Skiing, mountain climbing, and sightseeing are all popular with alpine tourists. Questions and exercises. 1. Choose any 3 of the following glacial features: Corey, Errate, Erratic, Hanging Valley, Kettle Lake, Nunatak for each of them. A. Describe its physical appearance. B. Account for its mode of formation. C. Locate and name an area where an example could be seen. 2. A. Distinguish between valley glaciers and continental ice sheets. B. Explain why glaciation in the uplands produced erosional features while that of the lowlands produce mainly depositional features. 3. The following lowland glacial features are all, in fact, small ridges, but are quite different in their process of formation. A. State which of them are of erosional or depositional nature. B. Pick out their distinctive differences in both appearance and formation. Roche Moutonne, drumlin, esker, crag and tail, kames. 4. Briefly explain any 3 of the following. A. Glaciated valleys assume a characteristic U-shaped. B. The middle of a glacier moves faster than the sides. C. In glaciated lowlands, eskers, kames, and other morainic deposits are extensively quarried. D. Glacial soils vary greatly in their fertility. E. Erratics and perch blocks are the best indicators of the source and direction of ice movement. 5. With the aid of diagrams, attempt to explain the difference between any 3 of the following pairs of terms connected with glaciation. A. Valley Glacier and Piedmont Glacier. B. Bergschrund and crevasses. C. Corey Lake and Ribbon Lake. D. Interlocking spurs and truncated spurs. E. Terminal moraine and recessional moraine. Arid or desert landforms. Types of deserts. About a fifth of the world's land is made up of deserts, some rocky, others stony, and the rest sandy. Deserts that are absolutely barren and where nothing grows at all are rare, and they are better known as true deserts. If you look at the world map carefully, you will find that there is a certain definite pattern to the location of the world's deserts, figure 67. You will realize that almost all the deserts are confined within the 15 degrees to 30 degrees parallels of latitude north and south of the equator. They lie in the trade wind belt on the western parts of the continents where trade winds are offshore. They are bathed by cold currents which produce a desiccating effect, so that moisture is not easily condensed into precipitation. Dryness or aridity is the keynote. Such deserts are tropical hot deserts or trade wind deserts. They include the Great Sahara Desert, Arabian, Iranian and their deserts, Kalahari, Namib, and Atacama deserts, the Great Australian Desert, and the deserts of southwest USA and northern Mexico. In the continental interiors of the mid-latitudes, the deserts such as the Gobi and Turkestan are characterized by extremes of temperatures, the work of winds and water in eroding elevated uplands, transporting the worn-off materials and depositing them elsewhere, has given rise to 5 distinct kinds of desert landscape. Hamada or rocky desert. This consists of large stretches of bare rocks, swept clear of sand and dust by the wind. The exposed rocks are thoroughly smoothed and polished. The region is bare and sterile. Fig. 67 World Distribution of Major Deserts. 58 Part 1, Physical Geography. A sandy desert area, Erg, in Death Valley, California. The best-known rocky deserts are those of the Sahara Desert, e.g. the Hamada El Hamra, in Libya, which covers an area of almost 20,000 square miles or 51,800 square kilometers. 2. Reg or Stony Desert. This is composed of extensive sheets of angular pebbles and gravels which the winds are not able to blow off. Such stony deserts are much more accessible than the sandy deserts, and large herds of camels are kept there. In Libya and Egypt the term Sarir is used. Elsewhere in Africa, stony deserts are called Reg. 3. Erg or Sandy Desert. This is a sea of sand which typifies the popular idea of desert scenery. Winds deposit vast stretches of undulating sand dunes in the heart of the deserts. The intricate patterns of ripples on the dune surfaces indicate the direction of the winds. The Kalanchio Sand Sea in Libya is characteristic of a sandy desert. In Turkestan, sandy deserts are also known as comb. 4. Badlands. The term badlands was first given to An arid area in South Dakota, USA, where the hills were badly eroded by occasional rainstorms into gullies and ravines. The extent of water action on hill slopes and rock surfaces was so great that the entire region was abandoned by the inhabitants. Deserts with similar features are now referred to as Badlands, e.g. the Painted Desert of Arizona, which lies southeast of the Grand Canyon of the Colorado River. 5. Mountain deserts. Some deserts are found on highlands such as plateaus and mountain ranges. Erosion has dissected the desert highlands into harsh, serrated outlines of chaotic peaks and craggy ranges. Their steep slopes are cut by wadis, steep-sided, often dry, valleys, and the action of frost has carved out sharp, irregular edges. In the Sahara Desert, the Ahagar, also known as the Hagar Mountains and the Dabesti Mountains are good examples of desert mountains. The mechanism of arid erosion. Arid landforms are the results of many combined factors, one reacting upon the other. Insufficient rainfall, often less than 5 inches, coming out most irregular periods, coupled with very high arid or desert landforms. 59. Temperatures 87 degrees Fahrenheit or 30 degrees Celsius is the average. And a rapid rate of evaporation are the chief causes of aridity. Subaerial denudation through the processes of weathering, mechanical and chemical, wind action, and the work of water have combined to produce a desert landscape that is varied and distinctive. Weathering. This is the most potent factor in reducing rocks to sand in arid regions. Even though the amount of rain that falls in the desert is small, some manage to penetrate into the rocks and sets up chemical reactions in the various minerals. Intense heating during the day and rapid cooling at night by radiation set up stresses in the already weakened rocks so that they eventually crack. As heat penetrates rocks slowly when the outer surface of rocks is being heated by the hot sun, the inner rocks remain quite cool. The heating of the rocks causes the outer surface to expand and so prise itself off from the interior rocks so that it peels off in successive very thin layers. Such an onion peeling process of mechanical weathering is called exfoliation. Angular rock debris is found in abundance as screes at the foot of upstanding rocks. Similarly, when water gets into the cracks and joints of rocks and the temperature at night suddenly drops to below freezing point, the water freezes and therefore expands by 10% of its volume. Successive freezing will prise off fragments of rock which accumulate as screes. These rock fragments become the teeth or tools of wind erosion. Action of winds in deserts. The wind, though not the most effective agent of erosion, transportation, and deposition, is more efficient in arid than in humid regions. Since there is little vegetation or moisture to bind the loose surface materials, the effects of wind erosion are almost unrestrained. Wind erosion is carried out in the following ways. 1. Deflation. This involves the lifting and blowing away of loose materials from the ground. Such unconsolidated sands and pebbles may be carried in the air or rolled along the ground depending on the grain size. The finer dust and sands may be removed miles away from their place of origin and be deposited even outside the desert margins. Deflation results in the lowering of the land surface to form large depressions called deflation hollows. The Katara Depression of the Sahara Desert lies almost 450 feet, 137 meters, below sea level. 2. Abrasion. The sandblasting of rock surfaces by winds when they hurl sand particles against them is called abrasion. The impact of such blasting results in rock surfaces being scratched, polished, and worn away. Abrasion is most effective at or near the base of rocks, where the amount of material the wind is able to carry is greatest. This explains why telegraph poles in the deserts are protected by a covering of metal for a foot or two above the ground. A great variety of desert features are produced by abrasion. 3. Attrition. When windborne particles roll against one another in collision, they wear each other away so that their sizes are greatly reduced and grains are rounded into millet seed sand. This process is called attrition. Landforms of wind erosion in deserts. In the combined processes of abrasion, deflation, and attrition, a wealth of characteristic desert landforms emerge. 1. Rock pedestals or mushroom rocks. The sand blasting effect of winds against any projecting rock masses wears back the softer layers so that an irregular edge is formed on the alternate bands of hard and soft rocks. Grooves and hollows are cut in the rock surfaces, carving them into fantastic and grotesque-looking pillars called rock pedestals. Figure 68. Such rock pillars will be further eroded near their bases where the friction is greatest. This process of undercutting produces rocks of mushroom shape called mushroom rocks or gore in the Sahara. Figure 68. Rock pedestals or gore. 60. Part 1. Physical geography. 2. Zugin. These are tabular masses which have a layer of soft rocks lying beneath a surface layer of more resistant rocks. The sculpting effects of wind abrasion wear them into a weird-looking ridge and furrow landscape. Mechanical weathering initiates their formation by opening up joints of the surface rocks. Wind abrasion further eats into the underlying softer layer so that deep furrows are developed. The hard rocks then stand above the furrows as ridges or zugin, figure 69a, and many even overhang. Such tabular blocks of zugin may stand 10 to 100 feet above the sunken furrows. Continuous abrasion by wind gradually lowers the zugin and widens the furrows. 59-69a zugin, with horizontal strata of hard and soft rocks. Direction. Figure 69b, Yordangs with vertical bands of hard and soft rocks. 3. Yardogs. Quite similar to the ridge and furrow landscape of Zhejiang are the steep-sided yardogs. Instead of lying in horizontal straight up on one another, the hard and soft rocks of yardogs are vertical bands and are aligned in the direction of the prevailing winds. Wind abrasion excavates the bands of softer rocks into long, narrow corridors, separating the steep-sided overhanging ridges of hard rocks, called yardogs. Figure 69b. They are only found in the Atacama Desert, Chile, but the more spectacular ones with yardogs read to 25 to 50 feet are best developed in the and deserts of Central Asia where the name original. 4. Mesas and buttes. Mesa is a Spanish meaning table. It is a flat, table-like land mass in a very resistant horizontal top layer and varist sides. The hard stratum on the surface denudation by both wind and water, and thus prot the underlying layers of rocks from being eroded away. Mesas may be formed in canyon regions, Arizona, or on fault blocks, e.g. the Table Mounts of Cape Town, South Africa. Continued denudity through the ages may reduce mesas in areas soft. They become isolated flat-topped hills called butte. Many of them in arid countries are separated deep gorges or canyons. Figure 70. Mesa. Figure 70 Mesa and butte. 5. Inselberg. This is a German word meaning island mountain. They are isolated residua. Hills rising abruptly from the level ground. TM are characterized by their very steep slopes on rather rounded tops. They are often composed sea granite or gneiss, and are probably the relics of Al. Figure 71 round-topped, steep-sided Inselbergs. Arid or desert landforms. Ayers Rock, an Inselberg in the Australian desert. Original plateau which has been almost entirely eroded away. Inselbergs are typical of many desert and semi-arid landscapes in old age, e.g. those of northern Nigeria, Western Australia, and the Kalahari Desert. Figure 71. 6. Vinifacts or Drakener. These are pebbles faceted by sandblasting. They are shaped and thoroughly polished by wind abrasion too. Shapes resembling Brazil nuts. Rock fragments, mechanically weathered from mountains and upstanding rocks, are moved by wind and smoothed on the windward side. If wind direction changes, another facet is developed. Such rocks have characteristic flat facets with sharp edges. Amongst the vinifacts, those with 3 wind-faceted surfaces are called Drakener. These wind-faceted pebbles form the desert pavement, a smooth, mosaic-like region, closely covered by the numerous rock fragments and pebbles. 7. Deflation hollows. Winds lower the ground by blowing away the unconsolidated materials, and small depressions may form. Similarly, minor faulting can also initiate depressions, and the eddying action of oncoming winds will wear off the weaker rocks until the water table is reached. Water then seeps out, forming oases or swamps in the deflation hollows or depressions. The Fayum, or Fayum, depression in Egypt lies 130 feet, 40 meters, below the sea level. Large areas in the western USA, stripped of their natural vegetation for farming, were completely deflated when strong winds moved materials as dust storms, laying waste crops and creating what is now known as the Great Dust Bowl. In a dust storm, winds may lift dust hundreds of feet high and carry it thousands of miles away. Landforms of wind deposition in deserts. Materials eroded and transported by winds must come to rest somewhere. The finest dust travels enormous distances in the air and may be moved completely out of the desert. It has been estimated that some dust grains travel as far as 2.300 in Le Carrot. 62 Part 1. Physical Geography. 3,700 kilometers before they are finally deposited on land or sea. The dust from the Sahara Desert is sometimes blown across the Mediterranean to fall as blood rains in Italy or on the glaciers of Switzerland. Dust that settles in the Huang Ho, or Huanghe Basin from the Gobi Desert, has accumulated over past centuries to a depth of several hundred feet. As windborne materials are sifted according to their coarseness, it can be expected that the coarser sands will be too heavy to be blown out of the desert limits. They remain as dunes or other depositional landforms within the deserts themselves. Since they are rarely static, their migration pattern depends on a number of factors: the size of the particles they carry, the direction and velocity of the winds, the location and nature of the surfaces over which the particles are transported, in the presence or absence of water and natural vegetation. The following are some of the major features of wind deposition. 1. Dunes. Dunes are, in fact, hills of sand formed by the accumulation of sand and shaped by the movement of winds. They may be active or live dunes, constantly on the move, or inactive fixed dunes, rooted with vegetation. Dunes are most well represented in the Erg Desert, where a sea of sand is being continuously moved, reshaped, and redeposited into a variety of features. Because of their great contrast in shape, size, and alignment, they have been given a long list of fanciful names, such as attached dune or head dune, tail dune, advanced dune, lateral dune, wake dune, star dune, pyramidal dune, sword dune, parabolic blowout dune, hairpin dune, smoking dune, and transverse dune. However, the following 2 types of common dunes, barcons and seefs, will be described in more detail. A. Barcon. These are crescentic or moon-shaped dunes which occur individually or in groups. They are live dunes which advance steadily before winds that come from a particular prevailing direction. They are most prevalent in the deserts of Turkestan and in the Sahara. Barkhans are initiated probably by a chance accumulation of sand at an obstacle, such as a patch of grass or a heap of rocks. They occur transversely to the wind, so that their horns thin out and become lower in the direction of the wind due to the reduced frictional retardation of the winds around the edges. The windward side is convex and gently sloping, while the U side, being sheltered, is concave and steep slip face, figure 72. The crest of the sand J moves forward as more sand accumulates the prevailing wind. The sand is driven up windward side and, on reaching the crest, down the leeward side, so that the dune advano the rate of advancement varies from 25 feet a year for the high dunes measuring up to loof high, to 50 feet a year. For the lower dunes WH may be only a dozen feet high. Ho. Future position of the Barkhan. Figure 72 crescentic sand dune, Barkhan. The migration of the Barkhans may be a THRE to desert life, for they may encroach on an OAS burying palm trees or houses. Long-rooted sand-holding trees and grasses are therefore planted to halt the advance of the dunes, thus prevent areas of fertile land from being devastated. UW. The action of winds, Barkhans take a Choujay changing pattern. Several Barkhans may coalesce into a line of irregular ridges, ever-changing with LB direction of the winds. Ergs are sandy deserts thus most difficult to cross. B. Seefs or longitudinal dunes. Seef is a Arabic word meaning sword. They are loady narrow ridges of sand, often over 100 miles long, lying parallel to the direction of TW prevailing winds. The high, serrated ridges M attain a height of over 200 feet. The crestlet of the Seef rises and falls in alternate peaks, AP saddles in regular successions like the teal of a monstrous saw. The dominant winds bio** straight along the corridor between the lines O dunes, so that they are swept clear of sand and remain smooth. The eddies that are set up BLO caret towards the sides of the corridor, and, having less power, drop the sand to form the dune 5. Arid or desert landform 63. In this manner, the prevailing winds increase the length of the dunes into tapering linear ridges, while the occasional cross winds tend to increase their height and width. Extensive Seef dunes are found in the Sahara Desert, south of the Qattara Depression, the Thar Desert, and the West Australian Desert, figure 73. Figure 73 longitudinal dunes, Seefs. 2. Loess. The fine dust blown beyond the desert limits is deposited on neighboring lands as loess. It is a yellow, friable material and is usually very fertile. Loess is in fact fine loam, rich in lime, very coherent and extremely porous. Water sinks in readily, so that the surface is always dry. Streams have cut deep valleys through the thick mantle of soft loess, and badland topography may develop. It is so soft that roads constructed through a loess region soon sink and their walls rise steeply. The most extensive deposit of loess is found in northwest China in the Loess Plateau of the Huanghe Basin. It is estimated to cover an area of 290,000 square miles, 750,000 square km, and the deposits have accumulated to a depth of 200 to 500 feet, about 60 to 150 m. In China, such yellowish windborne dust from the Gobi Desert is called Wangtu, the yellow earth. But the original term loess actually comes from a village in Alsace, France, bearing that name, where such deposits occurred. Similar deposits also occur in some parts of Germany, France, and Belgium, and are locally called limon. They're also windborne, but were blown from material deposited at the edge of ice sheets during the ice ages. In parts of the Midwest, USA, loess was derived from the ice sheets which covered northern North America and is termed adobe landforms due to water action in deserts. Few deserts in the world are entirely without rain or water. The annual precipitation may be small, 5 to 10 inches, and comes in irregular showers. But thunderstorms do occur in the rainfalls. In torrential downpours, producing devastating effects. A single rainstorm may bring several inches of rain within a few hours, drowning people who camp in dry desert streams and flooding mud-baked houses in the oases. As deserts have little vegetation to protect the surface soil, large quantities of rock waste are transported. In the sudden raging torrents or flash floods, loose gravels, sand, and fine dust are swept down the hillsides. They cut deep gullies and ravines, forming badland topography. Subsequent downpours widen and deepen the gullies when they wash down more soft rocks from the surface. There is so much material in the flash floods that the flow becomes liquid mud. When the masses of debris are deposited at the foot of the hill or the mouth of the valley, an alluvial cone or fan or dry delta is formed, over which the temporary stream discharges through several channels, depositing more material. The pasty alluvial deposits are subjected to rapid evaporation by the hot sun and downward percolation of water into the porous ground, and soon dry up, leaving mounds of debris. Apart from gullies, there are many larger dry channels or valleys. These are deepened by vertical corrosion by raging torrents during the occasional cloudbursts. These are the wadis and are dry for most of the time. Some desert streams are fed by the melting snow of the distant mountains outside the deserts, and rivers flow as exotic streams. The water carves out steep walls, which rise abruptly from the stream bed. In Algeria, such gorges are termed chebka. In arid and semi-arid areas, the outflowing streams from the upland regions are both short and intermittent. They drain into the lower depressions so that drainage is almost entirely internal. Sometimes water collected in a depression or a desert basin does. 64 Part 1. Physical Geography. Figure 74 in Fairmont Desert Basin. Completely disappear by evaporation or seepage, and a temporary lake is formed. Such lakes contain a high percentage of salts because of high evaporation and are glistening white when they dry up. The lakes and the alluvial plains formed by them are called playas, salinas or salas in the United States and Mexico, and shots in northern Africa. Figure 74. The floor of the depression is made up of two features, the bahada and the pediment. The bahada is a depositional feature made up of alluvial material laid down by the intermittent streams. The pediment is an erosional plain formed at the base of the surrounding mountain scarps. Questions and exercises. 1. Draw annotated diagrams and explain very briefly any three of the following desert features. A. Yardongs. B. Barkants. C. Pediments. D. Inselbergs. E. Wadis. 2. Attempt a simple classification of deserts. Justify your basis of classification by bringing out their distinct differences in appearance, formation, and outstanding features. With the aid of diagrams, explain the major differences between any three of the following pairs of desert landforms. A. Zildjian and Yardongs. B. Mesas and Inselbergs. C. Crescentic Barkants and longitudinal seefs. D. Bahadas and pediments. E. Vinifacts and Drakener. 4. Explain concisely the processes of deflation, abrasion, and deposition by winds. With the aid of diagrams, explain two topographical features formed by any two of the above processes. 5. The following terms are closely related to desert landforms. For any four of them, define with reference to examples what the terms mean. A. Erg landscape. B. Lus deposits. Icy, badland topography. D. Rock pedestals. 1. Great dust bowl flash floods. Limestone and chalk landform. Limestone and chalk. Limestone and chalk are sedimentary rocks of organic origin derived from the accumulation of corals and shells in the sea. In its pure state, limestone is made up of calcite or calcium carbonate, but where magnesium is also present, it is termed dolomite. Chalk is a very pure form of limestone, white, and rather soft. Limestone is soluble in rainwater, which, with carbon dioxide from the air, forms a weak acid. A region with a large stretch of limestone, therefore, possesses a very distinct type of topography. It is then termed a karst region, a name derived from the Karst district of former Yugoslavia where such topography is particularly well developed. In the present geographical scenario, karst remains a remarkable karst plateau region that stretches across the border of southwestern Slovenia and northeastern Italy. Characteristic features of a karst region. Generally speaking, karst regions have a bleak landscape, occasionally broken by precipitous slopes. There is a general absence of surface drainage as most of the surface water has gone underground. Streams rising on other rocks only flow over limestone for a short distance and then disappear underground. For the greater part of their course, they cut their way along the joints and fissures of the rock, wearing out a system of underground channels. The surface valleys are therefore dry. When the water penetrates to the base of the limestone and meets non-porous rocks, it re-emerges onto the surface as a spring or resurgence. Limestones are well jointed, and it is through these joints and cracks that rainwater finds its way into the underlying rock. Progressive widening by solution enlarges these cracks into trenches, and a most intriguing feature called limestone pavement is developed. The enlarged joints are called grikes, and the isolated, rectangular blocks are termed clints. The limestone pavements may have been formed beneath the soil and are now exposed by the removal of the soil cover. Figure 75. Rainwater charged with carbon dioxide forms a dilute acid I. Rainwater or mild acid. Figure 75. Limestone pavement. A limestone escarpment overlooking the beautiful Life Valley in Cumbria, UK. Notice that the valley is colorful, but the limestone is bleak and treeless. 64 Part 1. Physical Geography. Figure 74. Interment Desert Basin. Completely disappear by evaporation or seepage, and a temporary lake is formed. Such lakes contain a high percentage of salts because of high evaporation and are glistening white when they dry up. The lakes and the alluvial plains formed by them are called playas, salinas or salas in the United States and Mexico, and shots in northern Africa. Figure 74. The floor of the depression is made up of two features, the bahada and the pediment. The bahada is a depositional feature made up of alluvial material laid down by the intermittent streams. The pediment is an erosional plain formed at the base of the surrounding mountain scarps. Questions and exercises. 1. Draw annotated diagrams and explain very briefly any three of the following desert features. A. Yardongs. B. Barkants. C. Pediments. D. Inselbergs. E. Wadis. 2. Attempt a simple classification of deserts. Justify your basis of classification by bringing out their distinct differences in appearance, formation, and outstanding features. 3. With the aid of diagrams, explain the major differences between any three of the following pairs of desert landforms. A. Zildjian and Yardongs. B. Mesas and Inselbergs. C. Crescentic Barkants and longitudinal seefs. D. Bahadas and pediments. E. Vinifacts and Drakener. 4. Explain concisely the processes of deflation, abrasion, and deposition by winds. With the aid of diagrams, explain two topographical features formed by any two of the above processes. 5. The following terms are closely related to desert landforms. For any four of them, define with reference to examples what the terms mean. A. Erg landscape. B. Loess deposits. C. Badland topography. D. Rock pedestals. E. Great dust bowl. F. Flash floods. Limestone and chalk landform. Limestone and chalk. Limestone and chalk are sedimentary rocks of organic origin derived from the accumulation of corals and shells in the sea. In its pure state, limestone is made up of calcite or calcium carbonate, but where magnesium is also present, it is termed dolomite. Chalk is a very pure form of limestone, white, and rather soft. Limestone is soluble in rainwater, which, with carbon dioxide from the air, forms a weak acid. A region with a large stretch of limestone, therefore, possesses a very distinct type of topography. It is then termed a karst region, a name derived from the Karst district of former Yugoslavia where such topography is particularly well developed. In the present geographical scenario, karst remains a remarkable karst plateau region that stretches across the border of southwestern Slovenia and northeastern Italy. Characteristic features of a karst region. Generally speaking, karst regions have a bleak landscape, occasionally broken by precipitous slopes. There is a general absence of surface drainage as most of the surface water has gone underground. Streams rising on other rocks only flow over limestone for a short distance and then disappear underground. For the greater part of their course, they cut their way along the joints and fissures of the rock, wearing out a system of underground channels. The surface valleys are therefore dry. When the water penetrates to the base of the limestone and meets non-porous rocks, it re-emerges onto the surface as a spring or resurgence. Limestones are well jointed, and it is through these joints and cracks that rainwater finds its way into the underlying rock. Progressive widening by solution enlarges these cracks into trenches, and a most intriguing feature called limestone pavement is developed. The enlarged joints are called grikes, and the isolated, rectangular blocks are termed clints. The limestone pavements may have been formed beneath the soil and are now exposed by the removal of the soil cover. Figure 75. Rainwater charged with carbon dioxide. Figure 75. Limestone pavement. A limestone escarpment overlooking the beautiful Life Valley in Cumbria, UK. Notice that the valley is cultivated, but the limestone is bleak and treeless. 66. Part 1. Physical geography. On the surface of the limestone are numerous swallow holes, which are small depressions carved out by solution where rainwater sinks into the limestone at a point of weakness. They are also known as sinkholes. Gaping Gill in Yorkshire is a fine example. These holes grow in size through continuous solvent action. Once water has sunk into the limestone, it etches out caverns and passages along joints or bedding planes. When the roof of an underground tunnel collapses, a precipitous limestone gorge, such as the Cheddar Gorge, is formed. Where a number of swallow holes coalesce, a larger hollow is formed and is called a doline. Figure 76. Several dolina may merge. Cave collapsed. Swallow holes or sink dry valley forming a gorge holes where stream goes underground. G. N. D. EQCL. D. Grike. Clint limestone pavement. Co-O. O. CO. Co. D. Alternating scar and scree, /S cree slopes developed on bands of different resistance. J scan. Resurgence where stream reappears on surface. P river flow on. QO. Figure 76. Limestone scenery. Doline barren limestone surface with no rivers. Cave with stalactites and stalagmites underground. Course of stream. A limestone pavement. Limestone and chalk landform. 67. As a result of subsidence to form a larger depression, called an uvula. Some of them are a mile across, containing much clayey soil from the limestones, weathered after their subsidence. In Slovenia, some very large depressions called Polj may be as large as 100 square miles, but these are partly due to faulting. During the rainy season, parts of the floor which are at or near the water table may become temporary lakes, but the drier areas are fertile and may support large villages, where subterranean streams descend through swallow holes to underground passages. The region may be honeycombed with caves and caverns, some containing ponds and lakes. The most spectacular underground features that adorn the limestone caves are stalactites, stalagmites, and pillars. Stalactites are the sharp, slender, downward-growing pinnacles that hang from the cave roofs. The water carries calcium in solution, and when this lime-charged water evaporates, it leaves behind the solidified crystalline calcium carbonate. As moisture drips from the roof, it trickles down the stalactite and drops to the floor where calcium is deposited to form stalagmites. They are shorter, fatter, and more rounded. Over a long period, the stalactite hanging from the roof is eventually joined to the stalagmite growing from the floor to form a pillar. Figure 77. Such features are commonly seen in any V/L developed limestone caves, e.g. Bata Caves, Selangor in Malaysia, Mammoth Cave, Kentucky, and Carlsbad Caverns, New Mexico, both in USA, and Postojna Cave, Slovenia. Figure 77. Limestone cave. The major limestone regions of the world. The most characteristic stretch of limestone occurs in Slovenia. Other regions include the Caucasus district of southern France, the Pennines of the United Kingdom, Yorkshire and Derbyshire in particular, the Kentucky region of the USA, the Yucatan Peninsula of Mexico, the Cockpit country of Jamaica, and the limestone hills of Perlis, Malaysia. Human activities of karst regions. Karst regions are often barren and at best carry a thin layer of soil. The porosity of the rocks and the absence of surface drainage make vegetative growth difficult, so that limestone can usually support only poor grass and short turf. Some sheep grazing is possible. Limestone vegetation in tropical regions, however, is luxuriant because of the heavy rainfall all the year round. Settlements are scattered and the population is often sparse. The only mineral of importance is lead, which occurs in veins in association with limestone. Besides this, good quality limestones are often used as building materials or quarried for the cement industry. In West Malaysia, the limestone outcrops of the Kladang Range and the main range are quarried. 68 Part 1. Physical Geography. The Buin region, Clare, Ireland. The limestone landscape of the Buin is well known for the old tradition of winterage, allowing cattle to graze the hills in winter. For the Pamelation and Taysec cement works, currently, Taysec Corporation Bearhood. Chalk. The landforms of chalk are rather different from those of other limestones. There is little or no surface drainage, and valleys which once contained rivers are now dry. These are often called combes. The chalk forms low rounded hills in southern and southeastern England, where they are called downs, and in northern France. The chalk is covered with short turf, and in places with woodland, and is used for pasture and sometimes for arable farming. Because of the friable nature of the rock, swallow holes and underground cave networks do not generally develop. Questions and exercises. 1. Choose 3 outstanding features of a karst region. With the aid of diagrams, describe their appearance and explain how they have been formed. 2. The following features are associated with karst topography. A. Clints and grikes. B. Dolines and uvulas. C. Stalactites and stalagmites. For any 2 of them, with the aid of annotated diagrams, explain their origin and locate an actual example of each. 3. Explain why. A. Karst regions have very little surface drainage. B. Subterranean streams produce a magnificent underground scenery. C. Limestone areas have little agriculture and are sparsely peopled. 4. With the aid of labeled diagrams, describe and account for the development of physical features which result from the action of water in A. Limestone regions. B. Arid deserts. C. Granite uplands. To draw a large diagram of a karst region and indicate the following swallow holes, limestone gorge, dry valleys, limestone pavement with clints and grikes. Describe briefly how any 2 of them have been formed. Lakes. General the formation and origin of lakes. Lakes are amongst the most varied features of the Earth's surface. They occupy the hollows of the land surface in which water accumulates. They vary tremendously in size, shape, depth, and mode of formation. The tiny ones are no bigger than ponds or pools, but the large ones are so extensive that they merit the name of seas, e.g. the Caspian Sea, which is 760 miles long, 1,220 kilometers, as much as 3,360 feet, 1,025 meters, deep, with a total area of 149,200 square miles, 386,400 square kilometers, and is bigger than the whole of Malaysia. Lakes may exist temporarily, filling up the small depressions of undulating ground after a heavy shower. But those which are deep and carry more water than could ever be evaporated remain permanent. Most of the lakes in the world are freshwater lakes fed by rivers and with outflowing streams, e.g. Lake Geneva, Switzerland, Lake Poyang, China, and the Great Lakes of North America. In regions of low precipitation and intense evaporation where there are few rivers strong enough to reach the sea, streams drain into a lake, forming a basin of inland drainage. Because of the intense evaporation, these lakes are saline. For example, the Dead Sea has a salinity, salt content, of 250 parts per thousand, and the Great Salt Lake of Utah, USA, has a salinity of 220 parts per thousand. But the Black Sea, into which drain many large rivers, has a salinity of less than 17 parts per thousand. Playas or salt lakes are a common feature of deserts. It must be pointed out that lakes are only temporary features of the Earth's crust. They will eventually be eliminated by the double process of draining and silting up. In regions of unreliable rainfall, lakes dry up completely during the dry season. In the hot deserts, lakes disappear altogether by the combined processes of evaporation, percolation, and outflow. Though the process of lake elimination may not be completed within our span of life, it takes place relatively quickly in terms of geological time. The following are the various ways in which lakes can be formed. Each of them is placed in a specific category, though in a few cases the lakes could have been formed by more than one single factor. 1. Lakes formed by earth movement. A. Tectonic lakes. Due to the warping, sagging, bending, and fracturing of the Earth's crust, tectonic depressions occur. Such depressions give rise to lakes of immense sizes and depths. They include Lake Titicaca, occupying a huge depression in the Intermont Plateau of the Andes, 12,500 feet, 3,810 meters, above sea level, the highest lake in the world, and the Caspian Sea, 149,200 square miles, 386,400 square kilometers, the largest lake, almost 5 times larger than its nearest rival, Lake Superior. B. Rift Valley lakes. Due to faulting, a rift valley is formed by the sinking of land between two parallel faults, deep, narrow, and elongated in character. Water collects in these troughs and their floors are often below sea level. The best known example is the East African Rift Valley, which runs through Zambia, Malawi, Tanzania, Kenya, and Ethiopia, and extends along the Red Sea to Israel and Jordan over a total distance of 3,000 miles, 4,828 kilometers. It includes such lakes as Lakes Tanganyika, 4,710 feet, or 1,436 m deep, the world's second deepest lake, Malawi, Rudolph, Edward, Albert, as well as the Dead Sea, 1,286 feet, 392 meters, below mean sea level, the world's lowest lake, figure 78. Water collects Rift Valley lakes. 70 Part 1. Physical geography. 2. Lakes formed by glaciation. A. Cirque lakes or tarns. A glacier on its way down the valley leaves behind circular hollows in the heads of the valleys up in the mountains. Such hollows are the armchair-shaped cirques or corries. They're over-deepened. Floors may be filled with water to become cirque lakes, e.g. Red Tarn in the English Lake District, figure 79. Those that occupy glacial troughs are cirque lakes. Figure 79 glaciation. Long and deep and are termed ribbon lock carrot, e.g. Lake Ullswater. B. Kettle lakes. These are depressions the outwash plain left by the melting of masses of stagnant ice. They are irregular because of uneven morainic surface and are never of a nigrial size or depth, e.g. the Meres of Shropshire, IR England, and the Kettle Lakes of Orkney in Scotland. C. Rock hollow lakes. These are formed ice scouring when valley glaciers or ice sheets scoop out hollows on the surface. Such lakes of glacial origin are abundant in Finland. Indeed, the Finns call their country Suomi, the land of lakes. It is said that there are over 35,000 glacial lakes in Finland. D. Lakes due to morainic damming of valleys. Valley glaciers often deposit morainic debris across a valley so that lakes are formed when water accumulates behind the barrier. Both lateral ono-terminal moraines are capable of damming valleys, e.g. Lake Windermere of the Lake District, England. E. Lakes due to the deposition of glacial drifts and glaciated lowlands with a predominant drumulk. Lee Wafer in Westmoreland, England, a typical quarry lake. Lake 71. Landscape. Where drainage is poor, there are intervening depressions. These depressions are often waterlogged, forming small lakes like those of County Down in Northern Ireland. 3. Lakes formed by volcanic activity. A. Crater and caldera lakes. During a volcanic explosion, the top of the cone may be blown off, leaving behind a natural hollow called a crater. This may be enlarged by subsidence into a caldera. These depressions are normally dry, bounded by steep cliffs, and roughly circular in shape. In dormant or extinct volcanoes, rain falls straight into the crater or caldera, which has no superficial outlet and forms a crater or caldera lake. The outstanding ones are the Crater Lake in Oregon, USA, which in fact occupies a caldera, Lake Toba in northern Sumatra, and Lake Avernus near Naples, figure 80. Figure 80 volcanic activity. B. Lava block lakes. In volcanic regions, a stream of lava may flow across a valley, become solidified, and thus dam the river, forming a lake, e.g. a lava flow blocks the Jordan Valley, forming the Sea of Galilee, also called Lake Tiberias or Kinneret, which is an inland lake, rather elongated in shape. C. Lakes due to subsidence of a volcanic land surface. The crust of a hollow lava flow may collapse. The subsidence leaves behind a wide and shallow depression in which a lake may form, e.g. Maivan of Iceland. 4. Lakes formed by erosion. A. Karst lakes. The solvent action of rainwater on limestone carves out solution hollows. When these become clogged with debris, lakes may form in them. The collapse of limestone roofs of underground caverns may result in the exposure of long, narrow lakes that were once underground, e.g. the Lac de Chalexin, French name, or the Lac de Brunetz, Swiss name, in the Jura Mountains. The large depressions called polges, which normally do not have surface outlets, may contain lakes. During wet periods, these may cover most of the polge floor, but they shrink during dry periods due to seepage, figure 81. An example is Lake Scutari that lies on the border of Albania and Montenegro in southern Europe. Limestone hills with figure 81a karst lake formed above the groundwater table in a limestone region. Solution is important in other rocks such as rock salt. Local subsidence may occur when the underlying beds of rock salt are gradually removed in solution. Many of the meres of Cheshire, England, were probably caused by this, and are also the result of salt mining operations. B. Wind-deflated lakes. The deflating action of winds in deserts creates hollows. These may reach groundwater, which seeps out, forming small, shallow lakes. Excessive evaporation causes these to become salt lakes and playas. These are found in the Qattara Depression in Egypt, in the Great Basin of Utah, USA. 5. Lakes formed by deposition. A. Lakes due to river deposits. A river may shorten its course during a flood by cutting across its meandering loops, leaving behind a horseshoe-shaped channel as an oxbow lake, e.g. those that occur on the floodplains of lower Mississippi, USA, and Rio Grande, Mexico. B. Lakes due to marine deposits. The action of winds and waves may isolate lagoons along coasts by building spits or bars. As these lagoons of shallow water are enclosed only by a narrow spit, 72 Part 1. Physical Geography. Of land, comprising mud, sand and shingle, they may drain away at low tide. They are commonly found off the deltas of large rivers such as the Nile and the Ganges. In East Germany and Poland, lagoons are called hafs. Strong onshore winds are capable of pushing coastal sand dunes landwards, and these may enclose marshy lagoons. This type of lagoon is well developed in the landes of South West France. C. Lakes due to landslides, screes and avalanches. Lakes formed by these processes are also known as barrier lakes. Landslides or screes may block valleys so that rivers are dammed. Figure 82 Deposition, a barrier lake formed by the deposition of an obstacle. Such lakes are short-lived because the Lu carat fragments that pile across the valley soon g carat way under the pressure of water. When th carat suddenly give way, the dammed water rush down, causing floods. Examples of lakes of this type are Lake Gormire in Yorkshire, England, blocked by landslides. Finn and Lugwai on Snowdon blocked by screes. Figure 82. 6. Lakes formed by human and biological activities. A. Man-made lakes. Besides the natural lakes, man has now created artificial lakes by erecting concrete dam across a river valley so that the rivet water can be kept back to form reservoirs. Figure 83. Amongst such man-made lakes, the most imposing is Lake Mead above the Hoover Dam in the Colorado River, USA. B. Lakes made by animals. Animals like beavers are particularly interesting. They live in communities and construct dams across the rivers with timber. Such beaver dams are quite permanent and are found in North America, e.g. Beaver Lake in Yellowstone National Park, USA. C. Other types of lakes. These include ornamental lakes, especially made to attract tourists, e.g. Lake Gardens, Kuala Lumpur, Taiping Lakes. Man's mining activities, e.g. tin mining in West Malaysia, have created numerous lakes. Inland fish culture has necessitated the creation of many fishing lakes. HG 83 Human activities, a lake made by constructing a concrete dam across a river valley. Lake 73. Lakes and man. A careful examination of the lakes of the world will reveal their immense human significance. In countries where they are found in abundance, such as Finland, Canada, USA, Sweden, and the East African states, lakes, together with other inland waterways, have played a dominant role in the human, economic, social, and cultural life of the people. The pattern of settlement, commerce, and communication is very closely related to the distribution of the water features. The following are the major uses of lakes and their associated human activities. 1. Means of communication. Large lakes like the Great Lakes of North America provide a cheap and convenient form of transport for heavy and bulky goods such as coal, iron, machinery, grains, and timber. The Great Lakes St. Lawrence waterways penetrate more than 1,700 miles into the interior. They are thus used as the chief arteries of commerce. It is estimated that the annual tonnage passing through the Sault Ste. Marie Canal or the Soo Canal between Lake Huron and Lake Superior is greater than the combined annual tonnage of the Suez and Panama Canals. 2. Economic and industrial development. Early settlements and town sites are very much influenced by the presence of lakes. Lakes are an even more decisive factor when they are drained by large rivers with outlets to the sea. The Great Lakes St. Lawrence waterways were responsible for the development of the interior wheat farms and lakeside industries. Raw materials, minerals, and fuels were economically handled and assembled in the Holmes District, Lakes Huron, Ontario, Michigan, Erie, and Superior, which has since become one of the greatest industrial districts of the world. Similarly, Lakes Poyang, Tung Ting, and other lakes of the central Yangtze Basin have greatly assisted in the commercial and industrial development of Wuhan, Wuchang, Hanyang, and Hankow. Some of the lakes of Finland scoured out by ice action. 74 Part 1. Physical Geography. 3. Water storage. Lakes of either natural or artificial origin are vital sources of domestic water supply to surrounding towns and industrial cities. For example, Lake Thirlmere in England supplies water to Manchester, Loch Katrine in Scotland, to Glasgow, Lake Vyrnwy in Wales, to Liverpool. The Okla Reservoir supplies Delhi, and the Vatarna, Vihar, and Tulsi lakes supply Mumbai. 4. Hydroelectric power generation. In mountainous districts, lakes or man-made reservoirs are used to furnish a good head of water to generate hydroelectric power. Natural lakes are preferred to artificial reservoirs because the volume of water that flows from them varies very little throughout the year. For instance, the Niagara River flowing from Lake Erie to Lake Ontario has a very regular supply of water for its power stations, whereas the Catawba River in the Carolinas, which does not flow from a lake, has very little water during the dry season. Cotton mills have been forced to close down during the period of drought due to insufficient power supplies to run the mills. The Aswan Dam on the Nile in Egypt and the Sucker Barrage, previously known as Lloyd Barrage, on the Indus at Sucker suffer from similar defects. The Abu Bakar Dam of the Cameron Highlands supplies much hydroelectricity for central West Malaysia. 5. Agricultural purposes. As mentioned earlier, most lakes will eventually be eliminated, and when they dry up, their former beds are covered with thick layers of fertile alluvium. They make excellent agricultural land like the fertile Vale of Pickering in Yorkshire or the rich Red River Valley of Canada, which was in fact the former site of Lake Agassiz. Modern multipurpose dams, besides generating hydroelectric power, also supply water for irrigation, e.g. the Sinnar Dam on the Blue Nile in Sudan, the Burrinjuck Dam on the Murrumbidgee in Australia, and the Hirakud Dam, Odisha, on the Mahanadi in India. 6. Regulating river flows. A river with large lakes in its basin seldom experiences serious floods or lack of water. By absorbing the excess water during heavy rain, a lake reduces the effects of serious flooding. Downstream, in the dry season, it releases its water, so that a steady flow of the river is maintained. Because lakes retain part of the sediment load, rivers leaving lakes have clearer water. Lakes that have such functions include the Poyang and Tong Ting on the Yangtze Kiang, Tunnel Sap on a tribute of the Mekong, and Lake Constance on the up Rhine. Where such lakes are not available, flooding is a serious problem. Artificial reservoirs are constructed, e.g. the Hoover Dam on the Ree, Colorado, and the Bakra and Nungal Dams off Satluj in India. 7. Moderation of climate. Large and deep lakes WHJ are heated more slowly than the land by day, cooled more slowly than the land by night, exercles. An appreciable effect in moderating the climate of region in the same way as oceans affect adjoining land masses. Water in the lakes cools the air in summer, absorbing part of the heat, and warms it in winters, releasing the heat. For example, the eastern shores of Lakes Erie, Ontario, and Huron have a much milder winter than those of the west, because the oncoming breezes are warmed and early frosts are minimized. This part of the Lake Peninsula is therefore important for grapes and fruit farming. Large lakes like Lake Michigan and the Caspian Sea also exert a slight influence on the cloudiness and precipitation of the region. Their large expanse of water acts almost like part of the ocean and helps to precipitate atmospheric moisture into rain. The leeward side of Lake Michigan records a little more precipitation than the windward side, though the actual amount is often not easily noticeable. Small lakes have practically no effect at all on either temperature or rainfall. 8. Source of food. Many large lakes have important supplies of protein food in the form of freshwater fish. Sturgeon is commercially caught in the Caspian Sea, salmon and sea trout in the Great Lakes, and in Tunnel Sap in Cambodia. Fishing is a leading occupation. Amateur fishermen have found fishing in lakes and rivers a most rewarding pastime. In many countries, artificial lakes have been created for inland fish breeding. This is particularly important in China and Japan. 9. Source of minerals. Salt lakes provide valuable rock salts. In the Dead Sea, the highly saline water is being evaporated and produces common salt, almost indispensable for human well-being. Borax is mined in the salt lakes of the Mojave Desert. Gypsum is mined in Cheshire, and Stassfurt, a small distance from Berlin, is so rich in potash and other chemical deposits that they have given rise to a wide range of chemical industries. In both these areas, the salts are obtained from deposits formed in earlier geological period. Lakes 75. 10. Tourist attraction and health resorts. Some of the world's best frequented holiday and health resorts are located on lakesides, for example, Lake Geneva, Lake Lucerne, Lake Lugano, Lake Como, Lake Placid, New York, Lake Vänern and Lake Vader, Sweden, the English Lake District, UK, and Taiping Lakes, Malaysia. The glacier-formed lakes of the Alps have made the tourist industry a national occupation of the Swiss. Questions and exercises. 1. Locate the following lakes on an outline map of the world. Lake Tanganyika, Great Salt Lake, Lake Toba, Lake Como, Lake Victoria, Lake Scutari, and Lake Mead. Also, A. With the aid of sketch maps, explain their mode of formation. B. State their specific value to the countries they serve. C. Name another lake outside that country which has fairly similar origins. 2. Explain how each of the following types of lakes are formed. Quote an example of each and locate them in clear sketch maps. A. Oxbow Lake. C. Crater Lake. B. Kettle Lake. D. Karst Lake. 3. A. With the help of large, labeled diagrams, explain how lakes may be formed by any three of the following. I. Glaciation. 2. Earth movement. 3. Volcanic activity. 4. Erosion. V. Deposition. B. Quote 3 actual examples of each. C. State 3 uses of man-made lakes. 4. Rivers may be dammed. 4. A. Generating hydroelectricity. D. Supplying drinking water. B. Controlling floods. E. Assisting inland water transport. C. Irrigating crops. For any/hour of them, locate a dam and a river in which the damming has taken place. Explain briefly how each of the above purposes has been successfully achieved. 5. Each of the following terms are in one way or another connected with lake formation and uses. For any jive of them, give a concise explanation of their implications and give a good example of each. A. Basin of inland drainage. E. Playas. B. Tectonic lakes. F. Barrier lakes. C. Hafts. G. Torrents. D. Beaver dams. Coastal landforms. The action of waves, tides, and currents. The coast giant, under the constant action of the waves, tides, and currents, is undergoing changes. From day to day, on calm days, when winds are slight, waves do little damage to the shoreline and may instead help to build up beaches and other depositional features. It is in storms that the ravages of the waves reach their greatest magnitude. The average pressure of Atlantic waves on adjacent coasts is about 600 pounds per square foot in the summer and treble that in winter. During storms, the pressure exerted is more than 6,000 pounds or 3 tons per square foot. Movements of such intensity will wear down not only the cliffs but also sea walls and buildings. Tides and currents, on contact with the shores, make very little direct attack on the coastline. Tides affect marine erosion mainly by extending a line of erosion into a zone of erosion. This zone corresponds to the area between the low water level and the high water level. Currents help to move eroded debris and deposit it as silt, sand, and gravel along the coasts. The mechanism of marine erosion. The most powerful agents of marine erosion are waves. Their origin is due to the sweeping of winds over the water surface, which sets a series of undulating swells surging forward. These become higher and swifter. A normal wave in an open ocean may measure 20 feet or 6 meters high, the vertical height between the crest and the trough, and 400 feet or 122 meters long, the wave length or the horizontal distance between one crest and another. During storms, this is greatly increased, depending on the speed and duration of the winds. On approaching shallow water near the shores, their speed is reduced and the waves are curved or refracted against the alignment of the coast. Shallow water, when it is less than the height of the waves, checks their forward movement. The crests curl over and break into the shores in a massive roam as breakers. The water that finally rushes up the beach and hurls rock debris against the land is termed swash. The water is sucked back and retreats as backwash. Another element in offshore drift is the undertow, which flows near the bottom away from the shore. This current exerts a pulling effect which can be dangerous to sea bathers. Figure 84. Wind turbulences. FISEAFI. Wind direction. Wavelength asterisk indicating the rotation of individual particles in a wave advance. X equals friction at the base of the wave swash. Y equals wave breaking backwash. Figure 84. The mechanism of wave mow-on. Marine agents of erosion operate in the following ways to transform the coastal landscape. 1. Corrasion. Waves armed with rock debris of all sizes and shapes charge against the base of the cliffs and wear them back by corrasion. Oncoming currents and tides complete the work by sweeping the eroded material into the sea. 2. Attrition. The constantly moving waves that transport beach materials such as boulders, pebbles, shingle, and fine sand also hurl these fragments against one another until they are broken down by attrition into very small pieces. The coastal landforms. 77. Grinding and polishing of such fragmental materials against cliff faces and against each other is largely responsible for the fine sand which forms the beaches that are so typical of the seaside resorts. 3. Hydraulic action. In their forward surge, waves splashing against the coast may enter joints and crevices in the rocks. The air imprisoned inside is immediately compressed. When the waves retreat, the compressed air expands with explosive violence. Such action repeated again and again soon enlarges the cracks and rock fragments are prized apart. 4. Solvent action. On limestone coasts, the solvent action of seawater on calcium carbonate sets up chemical changes in the rocks and disintegration takes place. This process is limited to limestone coasts. The rate of marine erosion depends on the nature of the rocks, the amount of rock exposed to the sea, the effects of tides and currents, and human interference in coast protection. Other effects, such as volcanicity, glaciation, earth movement, and organic accumulations have also to be considered. Coastal features of erosion. 1. Capes and bays. On exposed coasts, the continual action of waves on rocks of varying resistance causes the coastline to be eroded irregularly. This is particularly pronounced where hard rocks, e.g. granites and limestones, occur in alternate bands with softer rocks, e.g. sand and clay. The softer rocks are worn back into inlets. Coves or bays and the harder ones persist as headlands, promontories, or capes. Figure 85. Along the Dorset coast of southern England, Swanage. Figure 85. Coastal features of differential erosion. Bay and Dalston Head are examples. Even where the coast is of one rock type, irregularities v/ill be caused by variation within the rock. Thus, Penang Island, Malaysia, made of granite, has many bays and headlands. Very large indentations such as the Persian Gulf or the Bay of Bengal are due to other causes such as submergence or earth movement. 2. Cliffs and wave-cut platforms. Generally, any very steep rock face adjoining the coast forms a cliff. The rate of recession will depend on its geological structure, that is the stratification and jointing of the rocks and their resistance to wave attack. If the beds dip seawards, large blocks of rock will be dislodged and fall into the sea. The cliff will rise in a series of steps as shown in Figure 86. On the contrary, if the beds dip landwards, as illustrated in Figure 87, the cliff will be more resistant to wave erosion. Some of the best-known cliffs are the chalk cliffs of the English Channel and include Beachy Head, which is 500 feet or 152 meters high, the Seven Sisters near the mouth of the Cuckmere, and the White Cliffs of Dover. Figure 86. Cliff beds dipping seawards. Figure 87. Cliff beds dipping landwards. At the base of the cliff, the sea cuts a notch, which gradually undermines the cliff so that it collapses. As a cliff recedes landwards under the pounding of waves, an eroded base is left behind, called the wave-cut platform. The platform, the upper part of which is exposed at low tide, slopes gently. A wave-cut platform at the shoreline in South Wales, UK. Seawards, and its surface is strewn with rock debris from the receding cliff. Further abrasion continues until the pebbles are swept away into the sea. The eroded materials are deposited on the offshore terrace, figure 88. When the platform attains a greater width, e.g. 30 miles in the case of the wave-cut platform of Strandflat off western Norway, it is entirely covered with water and further erosion of the cliffs is negligible. 3. Cave, arch, stack, and stump. Prolonged wave attack on the base of a cliff excavates holes in regions of local weakness called caves, e.g. at Edinburgh Head, England. When two caves approach one another from either side of a headland and unite, they form an arch, e.g. the Dye near Wick, Scotland. Further erosion for waves will ultimately lead to the total collapse of E-arch. The seaward portion of the headland will remain as a pillar of rock known as a stack. One of the finest examples of a stack is the Old Man of JY in the Orkneys, which is of old red sandstone and is 450 feet, 137 meters, high. Equally outstanding are the Needles, olive white, which are a group stacks cut in chalk and diminishing in size warts. In the course of time, these stubborn initial land surface zone of wave attack HTLT 1. 3 HT LT cliff with undercut base offshore terrace wave cut platform figure 88. The development of shore profile coastal landforms 79 stacks will gradually be removed. The vertical rock pillars are eroded, leaving behind only the stumps, which are only just visible above the sea level, e.g. those of the Street Kilda group off the outer Hebrides, Scotland, figure 89. Figure 89 arch, stacks and stumps. Where two caves are eroded on either side of a headland, they may eventually join to form a natural arch. If the top of the arch collapses, stacks are formed. These are gradually worn down until they become stumps exposed only at low tide. 4. Geos and gloops. The occasional splashing of the waves against the roof of a cave may enlarge the joints when compressed air is trapped inside. A natural shaft is thus formed, which may eventually pierce through to the surface. Waves breaking into the cave may force water or spray or just air out of this hole. Such a shaft is termed a gloop, from the noise made by the water gurgling inside, or blowhole, figure 90. An example is at Holborn Head in Caithness, Scotland. The enlargement of blowholes and the continued action of waves weakens the cave roof. When the roof collapses, a long, narrow inlet or creek develops. Such deep clefts, blowhole, cliffs cave, spray forced out of blowhole, figure 90 gloop, which may be 100 feet, 30.5 meters, deep and equally long, are called geos, e.g. the Wife Geo, near Duncansby Head, Scotland, figure 91. Geo. Geo is formed. Figure 91 Geo. Coastal features of deposition. 1. Beaches. Sands and gravels loosened from the land are moved by waves to be deposited along the shore as beaches. This is the most dominant form of the constructive work of the sea. The eroded material is transported along the shore in several distinct ways. The longshore drift, which comes obliquely to the coast, carries the material along the shore in the direction of the dominant wind, figure 92. At the same time, the backwash removes part of the material seawards along the bed of the sea and deposits it on the offshore terrace and even beyond. Finer materials such as silt and mud are deposited in the shallow waters of a sheltered coast. Where waves surge into a cave, they may cut a shaft to the cliff top through which air or water are forced. A wave-cut platform at the shoreline in South Wales, UK. Seawards, and its surface is strewn with rock debris from the receding cliff. Further abrasion continues until the pebbles are swept away into the sea. The eroded materials are deposited on the offshore terrace, figure 88. When the platform attains a greater width, e.g. 30 miles in the case of the wave-cut platform of Strandflat off western Norway, it is entirely covered with water and further erosion of the cliffs is negligible. 3. Cave, arch, stack, and stump. Prolonged wave attack on the base of a cliff excavates holes in regions of local weakness called caves, e.g. at Flamborough Head, England. When two caves approach one another from either side of a headland and unite, they form an arch, e.g. the Neddy near Wick, Scotland. Further erosion by waves will ultimately lead to the total collapse of the arch. The seaward portion of the headland will remain as a pillar of rock known as a stack. One of the finest examples of a stack is the Old Man of Hoy in the Orkneys, which is of old red sandstone and is 450 feet, 137 meters, high. Equally outstanding are the Needles, olive white, which are a group of stacks cut in chalk and diminishing in size. Seawards. In the course of time, these stubborn wave attack. Figure 88. The development of shore profile. Coastal landforms 79. Stacks will gradually be removed. The vertical rock pillars are eroded, leaving behind only the stumps, which are only just visible above the sea level, e.g. those of the Street Kilda group off the outer Hebrides, Scotland, figure 89. Figure 89 arch, stacks and stumps. Where two caves are eroded on either side of a headland, they may eventually join to form a natural arch. If the top of the arch collapses, stacks are formed. These are gradually worn down until they become stumps exposed only at low tide. 4. Geos and gloops. The occasional splashing of the waves against the roof of a cave may enlarge the joints when compressed air is trapped inside. A natural shaft is thus formed which may eventually pierce through to the surface. Waves breaking into the cave may force water or spray or just air out of this hole. Such a shaft is termed a gloop, from the noise made by the water gurgling inside, or blowhole, figure 90. An example is at Holborn Head in Caithness, Scotland. The enlargement of blowholes and the continued action of waves weakens the cave roof. When the roof collapses, a long, narrow inlet or creek develops. Such deep clefts, figure 90 gloop, which may be 100 feet, 30.5 meters, deep and equally long, are called geos, e.g. the Wife Geo, near Duncansby Head, Scotland, figure 91. Figure 91 Geo. Coastal features of deposition. 1. Beaches. Sands and gravels loosened from the land are moved by waves to be deposited along the shore as beaches. This is the most dominant form of the constructive work of the sea. The eroded material is transported along the shore in several distinct ways. The longshore drift, which comes obliquely to the coast, carries the material along the shore in the direction of the dominant wind, figure 92. At the same time, the backwash removes part of the material seawards along the bed of the sea and deposits it on the offshore terrace and even beyond. Finer materials such as silt and mud are deposited in the shallow waters of a sheltered coast cliff top through which air or water are forced. 80 Part 1. Physical geography. The constant action of the waves automatically sorts out the shoreline deposits in a graded manner. The coarser materials, cobbles and boulders, are dropped by the waves at the top of the beach. The finer materials, pebbles and sand grains, which are carried down the beach by the backwash, are dropped closer to the sea. On smooth lowlands, beaches may continue for miles, like those of the east coast of West Malaysia, but in upland regions where the land descends abruptly into the sea, such as the Chilean coast, long beaches are absent. 2. Spits and bars. The debris eroded by waves is continually moved by longshore drift, and where there is an indentation in the coast, such as the mouth of a river or a bay, material may continue to be deposited across the inlet. As more materials are added, they will pile up into a ridge or embankment of shingle, forming a tongue or spit, with one end attached to the land and the other end projecting into the sea, figure 93, e.g. Calshot Spit, Southampton Water, England, or those along the coast of Kelantan. Oblique waves may curve the spit into a hook or recurved spit. When the ridge of shingle is formed across the mouth of river or the entrance to a bay, it is called a bar. I.e. most remarkable example of a bar is Chesil Beach in Dorset, England, which extends for over 16 miles, 25.7 kilometers, along the coast, linking the Isle of Portland with mainland, and enclosing a lagoon called the Fleet. Such a connecting bar that joins two land masses is better known as Tombolo. In the Baltic coast of Poland and Germany, large beach material moved by drift. Figure 93 Development of spit. Waves refracted so that spit is recurved. Coast obliquely. Bodies of water are almost completely enclosed by long bars, locally termed urungs, to form marshy lagoons or halves. 3. Marine dunes and dune belts. With the force of onshore winds, a large amount of coastal sand is driven landwards, forming extensive marine dunes that stretch into dune belts. Their advance inland may engulf farms, roads, and even entire villages. The dunes of the Landis, southwest France, cover 6,000 square miles, 15,540 square kilometers. The crests of the dunes are over 130 feet, 40 meters. High dunes are common in the coastlands of Belgium, Denmark, and the Netherlands. To arrest the migration of the dunes, sand-binding species of grass and shrubs, such as marram grass and pines, are planted. Coastal landforms. 81. Types of coasts. Despite a great variety of coastal features, coastlines may be divided into two basic types. 1. Coastlines of submergence. These are due to the sinking of the land or the rise of the sea, including such coasts as Ria coasts, fjord coasts, estuarine coasts, and Dalmatian or longitudinal coasts. 2. Coastlines of emergence. These are due to the uplift of the land or fall in the sea level. They are less common and are represented by the uplifted lowland coast and the emergent upland coast. Coastlines of submergence. 1. Ria coasts. During the Ice Age, a great deal of water was locked up in ice. The warmer climate that followed melted much of the ice. Subsequently, there was an increase in the waters of the oceans and the sea level rose appreciably. In some cases, it is estimated that there was a rise of almost 300 feet, 91 m.l. In upland coastal regions where the mountains run at right angles to the sea, that is transverse or discordant to the coast, AG 94, a rise in the sea level submerges or drowns the lower parts of the valleys to form long, narrow branching inlets. Figure 94, a Ria coast, discordant, Atlantic type, separated by narrow headlands. They differ from fjords in two important respects, i.e. they are not glaciated, and their depth increases seawards. A Ria coast is typical of the Atlantic type of coast, like those of northwest France, northwest Spain, southwest Ireland, Devon, and Cornwall. As Rias are generally backed by Highland. They support few large commercial ports, though they have deep water and offer sheltered anchorage. They have been extensively used for siting fishing ports and naval bases such as Plymouth and Brest. 2. Fjord coasts. Fjords are submerged U-shaped glacial troughs. They mark the paths of glaciers that plunge down from the highlands. They have steep walls, often rising straight from the sea, with tributary branches joining the main inlet at right angles. Due to the greater intensity of ice, erosion fjords are deep for great distances inland. But there is a shallow section at the seaward end formed by a ridge of rock and called the threshold. HG 95. Off the fjord coast are numerous islands or skerries which, with the shallow thresholds, sometimes only 200 feet 61 meters deep, complicate coastal navigation. Fjord coasts are almost entirely confined to the higher latitudes of the temperate regions which were once glaciated, e.g. Norway, Alaska, British Columbia, southern Chile, and the South Island of New Zealand. Some of the large fjords are extremely long and deep. For example, the Sogn Fjord of Norway is 110 miles, 177 meters, long, for miles, 6.4 meters, wide, and almost 4,000 feet, 1,219 meters, deep in its mid-channel. Despite their deep and sheltered water, few large ports are located in fjords. Their mountainous background with 82 Part 1. Physical geography. Poor accessibility inland, attract few settlements. Agriculture is confined to the deltaic fans, built up where streams flow down to the fjords. The few towns that exist either as fishing or market centers, e.g. Trondheim, are only of local importance. 3. Dalmatian coast. This is the longitudinal coast, where mountains run parallel or concordant to the coast. The name is taken from the coast of Dalmatia, Yugoslavia, along the Adriatic Sea, where the submergence of the coastline produces long, narrow inlets with a chain of islands parallel to the coast. Narrow inlets with a chain of islands parallel to the coast. The elongated islands are the crests of former ranges, and the narrow sounds were the former longitudinal valleys, figure 96. The Dalmatian type of coast is also typical of the Pacific coast, where the ranges are parallel to the coast, e.g. western coast of North and South America, but there the coastline is more regular. Like the Ria and fjord coasts, the mountainous nature of the Dalmatian coastline hinders communication. Inland, it has deep, sheltered harbors but no distinguished ports. On the Pacific coast, however, there are some important ports such as San Francisco. 4. Estuarine coasts. In submerged lowlands, the mouths of rivers are drowned so that funnel-shaped estuaries are formed. If their entrances are not silted by moving sandbanks, they make excellent sites for ports, e.g. the estuaries of the Thames. Elba and Plate are the sites of such great seaports as London, Hamburg, and Buenos Aires. Tidal effects further enhance the value of the ports and, even when there is a little silting, modem dredges help to keep the ports open all the time. Figure 96A. Dalmatian coast, concordant, Pacific type. Coastlines of emergence. 1. Uplifted lowland coast. The uplift of part of the continental shelf produces a smooth, gently sloping coastal lowland, figure 97. The offshore waters are shallow with lagoons, salt marshes, and mudflats. Where the emergent deposits from the continental shelves are sandy and gravelly, beaches and marine dunes are formed. Ports that were once located on the former coast become inland towns. Figure 97. Lowland coastline of emergence. Coastal landforms 83. Old indented cliff. Figure 98. Upland emergent coastline. Examples of uplifted lowland coasts include the southeastern USA, western Finland, eastern Sweden, and parts of coastal Argentina south of the Rio de la Plata. 2. Emergent upland coast. Faulting in earth movement may thrust up coastal plateaus so that the whole region is raised, with consequent emergent features. A raised beach is the most prominent. The raised beach is beyond the reach of the waves, though it may still possess arches, stacks, and other coastal features. The emergent upland coast is quite straight with steep cliffs and deeper offshore water, for the waves have not yet eroded lines of weakness or carved a wave-cut platform, figure 98. It has little potential for good port sites. Examples of emergent upland coasts are found in Scotland, the western coast of the Deccan, India, and the western Arabian coast facing the Red Sea. Questions and exercises. 1. By reference to specific examples, describe some of the major coastal features resulting from the constructive and destructive work of the sea. 2. With the aid of annotated diagrams, describe the appearance and formation of any three of the following pairs of features of coastal landforms. A. Cliff and wave-cut platform. C. Arch and stack. B. Geo and blowhole. D. Spits and bars. 3. Flow. Can shorelines be classified? Describe any one method of classification and briefly explain some of the major shoreline features that you have classified. 4. With the help of diagrams, explain the distinct differences between the following coastlines of submergence. A. Ria coast. C. Dalmatian coast. B. Fjord coast. D. Estuarine coast. S. Choose any three of the following terms connected with marine landscape. Explain the meaning of each and state its role in transforming the coastline. A. Longshore drift. D. Raised beach. B. Undertow. E. Tombolo. C. Concordant coast. Islands and coral reefs. An island is a piece of land surrounded on all sides by water. It may occur individually or in a group, in open oceans or seas. Smaller ones of only local significance are found even in lakes and rivers. Generally speaking, all islands may be grouped under the following types. 1. Continental islands. These islands were formerly part of the mainland and are now detached from the continent. They may be separated by a shallow lagoon or a deep channel. Prior separation could be due to subsidence of some part of the land or to a rise in sea level, so that the lowland links are submerged by the sea. Their former connection with the neighboring mainland can be traced from the similar physical structure, flora, and fauna that exist on both sides of the channel. In the course of time, modification by men and other natural forces may give rise to different surface features. But even then, the basic structural features will remain the same. Continental islands may appear as a. Individual islands. These lie just outside the continent, very much associated with the characteristic features of the mainland of which they were once part. Some of the outstanding examples are Newfoundland, separated from the mainland by the Strait of Belle Isle, Madagascar by the Mozambique Channel, Sri Lanka by the Pak Strait, Tasmania by the Bay Strait, and Taiwan by the Taiwan Strait. B. Archipelagos or island groups. These comprise groups of islands of varying sizes and shapes, e.g. the British Isles, the Balearic Islands of the Mediterranean, and also those of the Aegean Sea. C. Festoons or island arcs. The islands form an archipelago in the shape of a loop around the edge, or phi mainland, marking the continuation of mountain ranges which can be traced on the continent, e.g. the East Indies, the Aleutian Islands, Ryukyu Islands, Kuril Islands, and other island arcs of the Pacific coasts. 2. Oceanic islands. These islands are normally small and are located in the midst of oceans. They have no connection with the mainland, which may be hundreds or thousands of miles away. They have a flora and fauna unrelated to those of the continents. The Galapagos Islands have many unique species of animals. Due to their remoteness from the major trading centers of the world, most of the oceanic islands are very sparsely populated. Some of them provide useful stops for aeroplanes and ocean steamers that ply between continents across vast stretches of water. Generally speaking, oceanic islands fall into one of the following groups. A. Volcanic islands. Many of the islands in the oceans are in fact the topmost parts of the cones of volcanoes that rise from the ocean bed. Most of them are extinct, but there are also some active ones. The best-known volcanic peak of the Pacific Ocean is Mauna Loa in Hawaii, which is 13,680 feet, 4,170 meters, above sea level. Tracing downwards, Mauna Loa is found to have been built up from the ocean floor at a depth 18,000 feet, 5,486 meters, below the water surface. Other volcanic islands have emerged from the submarine ridges of the oceans. The volcanic islands are scattered in most of the Earth's oceans. In the Pacific Ocean, they occur in several groups such as Hawaii, the Galapagos Islands, and the South Sea Islands. In the Atlantic are the Azores, Ascension, St. Helena, Madeira, and the Canary Islands. Those of the Indian Ocean are Rarotonga and the Cook Islands, a volcanic island in the Pacific. Islands and coral reefs 85. Mauritius and Reunion. In the Antarctic Ocean are the South Sandwich Islands, Bouvet Island, and many others. B. Coral Islands. Unlike the volcanic islands, the coral islands are very much lower and emerge just above the water surface. These islands, built up by coral animals of various species, are found both near the shores of the mainland and in the midst of oceans. Coral islands include the Marshall Islands, Gilbert and Ellis Islands of the Pacific, Bermuda in the Atlantic, and the Lakshadweep and Maldives of the Indian Ocean. Coral reefs. In tropical seas, many kinds of coral animals and marine organisms such as coral polyps, calcareous algae, shell-forming creatures, and lime-secreting plants live in large colonies. Though they are very tiny creatures, their ability to secrete calcium carbonate within their tiny cells has given rise to a peculiar type of marine landform. They exist in numerous species of many forms, colors, and shapes. Under favorable conditions, they grow in great profusion just below the water level. Taking coral animals as a whole, the polyps are the most abundant and also the most important. Each polyp resides in a tiny cup of coral and helps to form coral reefs. When they die, their limey skeletons are cemented into coral and limestone. There are also non-reef building species such as the precious corals of the Pacific Ocean and the red coral of the Mediterranean, which may survive in the colder and even the deeper waters. As a rule, they thrive well only in the warmer tropical seas. The reef-building corals survive best under the following conditions. 1. The water temperature must not fall below 68 degrees Fahrenheit, 20 degrees Celsius. This virtually limits the aerial distribution of corals to the tropical and subtropical zones. Again, they will not flourish where there are cold currents, because of the upwelling of the cold water from the depths that cools the warm surface water. This explains why coral reefs are generally absent on the western coast of continents. On the other hand, the warming effect of the warm currents, e.g. the Gulf Stream, means that corals are found far to the north of the West Indies and the Atlantic Ocean. The Pacific and the Indian Oceans, however, have the most numerous coral reefs. 2. The depth of the water should not exceed 30 fathoms or 180 feet, 55 meters, because beyond. This depth sunlight is too faint for photosynthesis to take place. This is essential for the survival of the microscopic algae on which the coral polyps depend. Shallow water of less than 100 feet, 30.5 meters, is ideal. But there should always be plenty of water as polyps cannot survive for too long out of water. 3. The water should be saltish and free from sediment. Corals therefore survive best in the moving ocean water well away from the silty coasts or muddy mouths of streams. The corals are best developed on the seaward side of the reef, where constantly moving waves, tides and currents maintain an abundant supply of clear, oxygenated water. They also bring an adequate supply of food in the form of microscopic organisms. An aerial view of Tapai Atoll, also called Motu Iti in Society Island Group, French Polynesia. Islands and coral reefs. An island is a piece of land surrounded on all sides by water. It may occur individually or in a group, in open oceans or seas. Smaller ones of only local significance are found even in lakes and rivers. Generally speaking, all islands may be grouped under the following types. 1. Continental islands. These islands were formerly part of the mainland and are now detached from the continent. They may be separated by a shallow lagoon or a deep channel. Their separation could be due to subsidence of some part of the land or to a rise in sea level, so that the lowland links are submerged by the sea. Their former connection with the neighboring mainland can be traced from the similar physical structure, flora and fauna that exist on both sides of the channel. In the course of time, modification by men and other natural forces may give rise to different surface features. But even then, the basic structural features will remain the same. Continental islands may appear as a. Individual islands. These lie just outside the continent, very much associated with the characteristic features of the mainland of which they were once part. Some of the outstanding examples are Newfoundland, separated from the mainland by the Strait of Belle Isle, Madagascar by the Mozambique Channel, Sri Lanka by the Pak Strait, Tasmania by the Bay Strait and Taiwan by the Taiwan Strait. B. Archipelagos or island groups. These comprise groups of islands of varying sizes and shapes, e.g. the British Isles, the Balearic Islands of the Mediterranean and also those of the Aegean. C. Festoons or island arcs. The islands form an archipelago in the shape of a loop around the edge or the mainland, marking the continuation of mountain ranges which can be traced on the continent, e.g. the East Indies, the Aleutian Islands, Ryukyu Islands, Kuril Islands and other island arcs of the Pacific coasts. 2. Oceanic islands. These islands are normally small and are located in the midst of oceans. They have no connection with the mainland which may be hundreds or thousands of miles away. They have a flora and fauna unrelated to those of the continents. The Galapagos Islands have many unique species of animals. Due to their remoteness from the major trading centers of the world, most of the oceanic islands are very sparsely populated. Some of them provide useful stops for airplanes and ocean steamers that ply between continents across vast stretches of water. Generally speaking, oceanic islands fall into one of the following groups. A. Volcanic islands. Many of the islands in the oceans are in fact the topmost parts of the cones of volcanoes that rise from the ocean bed. Most of them are extinct, but there are also some active ones. The best-known volcanic peak of the Pacific Ocean is Mauna Loa in Hawaii, which is 13,680 feet, 4,170 meters, above sea level. Tracing downwards, Mauna Loa is found to have been built up from the ocean floor at a depth 18,000 feet, 5,486 meters, below the water surface. Other volcanic islands have emerged from the submarine ridges of the oceans. The volcanic islands are scattered in most of the Earth's oceans. In the Pacific Ocean, they occur in several groups such as Hawaii, the Galapagos Islands, and the South Sea Islands. In the Atlantic are the Azores, Ascension, St. Helena, Madeira, and the Canary Islands. Those of the Indian Ocean are Rarotonga and the Cook Islands, a volcanic island in the Pacific. Islands and coral reefs 85. Mauritius and Reunion. In the Antarctic Ocean are the South Sandwich Islands, Bouvet Island, and many others. B. Coral Islands. Unlike the volcanic islands, the coral islands are very much lower and emerge just above the water surface. These islands, built up by coral animals of various species, are found both near the shores of the mainland and in the midst of oceans. Coral islands include the Marshall Islands, Gilbert and Ellis Islands of the Pacific, Bermuda in the Atlantic, in the Lakshadweep and Maldives of the Indian Ocean. Coral reefs. In tropical seas, many kinds of coral animals and marine organisms such as coral polyps, calcareous algae, shell-forming creatures, and lime-secreting plants live in large colonies. Though they are very tiny creatures, their ability to secrete calcium carbonate within their tiny cells has given rise to a peculiar type of marine landform. They exist in numerous species of many forms, colors, and shapes. Under favorable conditions, they grow in great profusion just below the water level. Taking coral animals as a whole, the polyps are the most abundant and also the most important. Each polyp resides in a tiny cup of coral and helps to form coral reefs. When they die, their limy skeletons are cemented into coralline limestone. There are also non-reef building species such as the precious corals of the Pacific Ocean and the red coral of the Mediterranean which may survive in the colder and even the deeper waters. As a rule, they thrive well only in the warmer tropical seas. The reef-building corals survive best under the following conditions. The water temperature must not fall below 68 degrees Fahrenheit, 20 degrees Celsius. This virtually limits the aerial distribution of corals to the tropical and subtropical zones. Again, they will not flourish where there are cold currents because of the upwelling of the cold V/a tear from the depths that cools the warm surface water. This explains why coral reefs are generally absent on the western coast of continents. On the other hand, the warming effect of the warm currents, e.g. the Gulf Stream, means that corals are found far to the north of the West Indies and the Atlantic Ocean. The Pacific and the Indian Oceans, however, have the most numerous coral reefs. 2. The depth of the water should not exceed 30 fathoms or 180 feet, 55 meters, because beyond this depth sunlight is too faint for photosynthesis to take place. This is essential for the survival of the microscopic algae on which the coral polyps depend. Shallow water of less than 100 feet, 30.5 meters, is ideal. But there should always be plenty of water as polyps cannot survive for too long out of water. 3. The water should be saltish and free from sediment. Corals therefore survive best in the moving ocean water well away from the silty coasts or muddy mouths of streams. The corals are best developed on the seaward side of the reef, where constantly moving waves, tides, and currents maintain an abundant supply of clear, oxygenated water. They also bring an adequate supply of food in the form of microscopic organisms. An aerial view of Tapai Atoll, also called Motu Iti in Society Island Group, French Polynesia. A fringing reef found in a remote part of the Solomon Islands. 86 Part 1 Physical Geography. Types of coral reefs. There are 3 main types of coral reefs. 1. Fringing reefs. A fringing reef is a coralline platform lying close to the shore extending outwards from the mainland. It is sometimes separated from the shore by a shallow lagoon. It is widest when fringing a protruding headland but completely absent when facing the mouth of a stream. The outer edge grows rapidly because of the splashing waves that continuously renew the supply of fresh food. The reefs may be about a mile wide, lying just above the level of low water and sloping steeply downwards on the seaward side to a depth of about 100 feet or 30.5 meters, figure 99. Fringing reef. IG. 99 Fringing reef. 2. Barrier reefs. A barrier reef is separated from Archie Coast by a much wider and deeper channel or lagoon, figure 100. The reef is partially submerged. Where it lies above the water level and sand can accumulate on it, a little vegetation is possible. Figure 100 Barrier reef. The barrier reefs have narrow gaps at several places to allow the water from the enclosed lagoon to return to the open ocean. Such gaps are very useful for shipping and provide the only entrances for ships to enter or leave the lagoon. The best-known barrier reef is the Great Barrier Reef off the coast of Queensland, Australia. It is 1,200 miles, 1,931 kilometers, long, separated from the coast by a channel 100 miles. It is 1,200 miles, 1,931 kilometers, long, separated from the coast by a channel 100 miles, 161 kilometers, wide in places, and over 200 feet. 61 m, deep. 3. Atolls. Atolls are similar to barrier reefs except that they are circular in shape, enclosing a shallow lagoon without any land in the center. The encircling ring is usually broken in a few places to allow the free flow of water, figure 101. On the inside of the reefs, sand and limestone debris collect, and palm trees like coconuts may grow. Such palm trees thrive well in the brackish water of the lagoon. The nuts fall into the water and are distributed widely by floating from one coral island to another. The calm waters are useful for fishing and canoeing. Some of the large atolls, e.g. Suvadiva in the Maldives, west of Sri Lanka, have a lagoon over 40 miles, 64 kilometers, across. A number of them provide essential air bases for trans-Pacific aircraft. Islands and coral reefs. 87. Lagoon, the probable origin of coral reefs. The subject of the origin of coral reefs has been studied and debated for over 1.5 centuries. Several theories have been suggested, but none is universally accepted. The most widely accepted theory is that put forward by the great scientist Charles Darwin after his voyage to the Pacific Islands in 1842. It is known as the subsidence theory. Darwin assumed that all coral reefs began as fringing reefs around an island or the topmost portions of extinct volcanoes that stood above the ocean bed. Due to a general downwarping of the Earth's crust, the islands gradually subsided. The corals continued to grow upwards to keep pace with the subsidence. The growth was more vigorous at the outward edge than the landward edge because of the more favorable living conditions for corals, so the encircling reef widened. It then formed a barrier reef, with a lagoon between the island and the reef. Eventually, when the land completely submerged, only the outer rims of the reefs were seen, forming an atoll. The submerged island was covered by a layer of sediment, so that the characteristic circular lagoon is generally shallow. Thus, atolls mark the position of the former islands, figure 102a. More recent researches by oceanographers have 2. Subsidence of the land leads to a barrier reef developing. Coral reef. I. A fringing reef. 3. Further subsidence matched by the growth of coral leads to an atoll. Former sea level. Fig. 102. A. Darwin's theory of subsidence. Coral reef growing upwards and outwards to keep pace with subsiding island, passing from fringing reef to barrier reef and eventually atoll. 2. Island is planed when sea is at a lower level atoll. 3. Sea level rises and coral grows upwards forming atoll. Figure 102. B. Daly's glacial control theory. 88. Part 1 Physical Geography. Revealed that the ocean floor has, in fact, been subjected to subsidence, especially in the Pacific. Darwin's explanation was therefore generally correct. Amongst the other theories, perhaps the American geographer R.A. Daly's glacial control theory, put forward in 1910, is worth consideration. During his visit to Mauna Kea in Hawaii, he noticed the close relationship between glaciation and the development of coral reefs. He believed that, during the height of the ice ages, the water was too cold for any coral growth to take place. With the absence of a coral barrier, marine erosion was able to attack and lower the islands. With the return of the warmer climate, the water that was locked up in the ice sheets melted. Consequently, there was a rise in the sea level which in some cases submerged these lower islands. On these waveplane platforms, corals began to grow upwards at the rate of a foot in a decade to keep pace with the rising water level. Figure 102b. Coral reefs, where islands still project above sea level, and atolls were thus formed. Recent evidence of boring through coral formations seems to favor Daly's explanation of a change in sea level and consequent erosion of the islands. However, the deepest borings reveal basaltic rocks. These correspond to the subsided islands envisaged by Darwin. Thus, a combination of the two theories accounts for all the important features of coral reefs and atolls. Questions and exercises. 1. Give a concise classification of the islands of the world. Quote actual examples of islands to justify your proposed classification. 2. The following are some of the islands of the world. State in which part of the globe they are found. For any three of them account for their probable origin. Sakhalin Island. Andaman Islands. Maldives, St. Helena, Hawaiian Islands, Crete. 3. What are the three general types of coral reefs formed by coral animals? Point out the distinct differences between them. 4. Explain clearly how coral reefs are formed. Under what conditions do corals thrive best? 5. With the aid of examples and diagrams, explain any three of the following terms connected with islands and coral reefs. A. Continental islands. B. Archipelagos. C. Oceanic islands. D. Coral polyps. E. Fringing reefs. F. Atolls. The oceans. Exploring the oceans. The oceans, comprising more than 70%, or 139 million square miles or 361 million square kilometers of the Earth's surface, have tremendous potential waiting to be developed. Besides being a source of food, fish, mammals, reptiles, salt, and other marine foodstuffs, the tides can be harnessed to provide power. Formal oceanographic investigation began only with the British expedition of the Challenger, 1873 to 1876, the first successful worldwide deep-sea expedition. Oceanography, the science of the oceans, has become such an important subject in recent years that researches into the deep seas have been conducted by many institutions, universities, government ministries, and other international organizations. The most famous international oceanographic research center is the International Council for the Exploration of the Sea with its headquarters in Copenhagen. Ocean exploration for the observation and recording of oceanographic data is a very expensive matter. It involves the operation and maintenance of specially equipped vessels in mid-ocean for long periods, and large-scale oceanographic researches are thus best undertaken by international bodies. The older echo sounding techniques have now been replaced by radar sounding and electrical echo devices to find the precise depths of ocean floors and map the relief of the oceans. Trained frogmen, equipped with modern breathing apparatus, are employed to gather valuable information from great depths. Deep-sea core samples are obtained by boring for the study of the oceanic deposits, the various kinds of oozes, muds, and clays. Automatic recording thermometers and other sensitive instruments can be lowered to any required depth by stationary vessels with laboratory facilities for processing any required data. For the observation, only 5% of the oceans have been explored till date. 90 Part 1 Physical Geography and measurement of current flow, various kinds of current meters using propellers, vanes, or pendulums have been designed. Sealed bottles and other floating objects containing instructions for reporting their precise time and place of discovery are released in large numbers to compute the rate and direction of drift and current flow. With all these modern techniques at the disposal of the oceanographers, our knowledge of the mysteries of the oceans is greatly increased. But there is still much to be discovered. The relief of the ocean. The ocean basins are in many ways similar to the land surface. There are submarine ridges, plateaus, canyons, plains, and trenches. A section drawn across an ocean, figure 103, illustrates the typical submarine relief features. 1. The continental shelf. This is, in fact, the seaward extension of the continent from the shoreline to the continental edge marked, approximately, by the 100 fathom, 600 feet, or 183 m, isobaths. Are contours marking depths below sea level. The continental shelf is thus a shallow platform whose width varies greatly, from a few miles in the North Pacific off the continent of North America, to over 100 miles, 161 kilometers, off northwest Europe. In some places where the coasts are extremely mountainous, such as the Rocky Mountain and Andean coasts, the continental shelf may be entirely absent. Off broad lowland coasts like those of Arctic Siberia, a maximum width of 750 miles, 1,207 kilometers, has been recorded. A width of 20 to 100 miles, 32 to 161 kilometers, is generally encountered. The angle of the slope is also variable and is normally least where the continental shelf is widest. A gradient 01 in 500 is common to most continental shelves. Many regard the continental shelf as part of the continent submerged due to a rise in sea level, e.g. at the close of the Ice Age, when the ice in the temperate latitudes melted and raised the sea level by several hundred feet. Some smaller continental shelves could have been caused by wave erosion where the land is being eroded by the sea as shown in Fig. 104. Conversely, such shelves might have been formed by the deposition of land derived or riverborne materials on the offshore. Terraces in Fig. 105. The continental shelves are of great geographical significance for the following reasons. A. Their shallowness enables sunlight to penetrate through the water, which encourages the growth of minute plants and other microscopic organisms. They are thus rich in plankton on which millions of surface and bottom-feeding fishes thrive. The continental shelves are therefore the richest fishing grounds in the world, e.g. the Grand Banks off Newfoundland, the North Sea, and the Sunda Shelf. B. Their limited depth and gentle slope keep out cold undercurrents and increase the height of tides. This sometimes hinders shipping and other marine activities since ships can only enter and leave port on the tide. Most of the world's greatest seaports, sea level, continental edge, are 300 feet. Figure 103. The relief of the ocean basin, a typical section, with oceanic deposits, mud, clay, and oozes. The ocean's 91, including Southampton, London, Hamburg, Rotterdam, Hong Kong, and Singapore, are located on continental shelves. Figure 104. Continental shelf formed by processes of erosion. Figure 105. Continental shelf formed by processes of deposition. 2. The continental slope. At the edge of the continental shelf, there is an abrupt change of gradient to about 1 in 20, forming the continental slope. 3. The deep sea plain. This is the undulating plain lying 2 to 3 miles below sea level and covering 2/3 of the ocean floor, generally termed the abyssal plain. It was once thought to be featureless, but modern sounding devices reveal that the abyssal plain is far from being level. It has extensive submarine plateaus, ridges, trenches, basins, and oceanic islands that rise above sea level in the midst of oceans, e.g. the Azores. Ascension Island. 4. The ocean deeps. These are the long, narrow trenches that plunge as great ocean deep to a depth of 5,000 fathoms or 30,000 feet or 9,144 meters. Contrary to our expectations, most of the deepest trenches are not located in the midst of oceans. They are more often found close to the continents, particularly in the Pacific Ocean, where several deep trenches have been sounded. The greatest known ocean deep is the Mariana Trench near Guam Island, which is more than 36,000 feet, 10,973 meters, deep. We can see from this that ocean trenches are greater in magnitude than the highest mountains on land. For the highest peak, Mt. Everest is only 29,031.69 feet, 8,848.86 m. Other notable ocean deeps include the Mindanao Deep, 35,000 feet or 10,668 meters, the Tonga Trench, 31,000 feet or 9,449 meters, and the Japanese Trench, 28,000 feet or 8,534 meters, all in the Pacific Ocean. The oceanic deposits of the ocean floor. Materials eroded from the earth which are not deposited by rivers or at the coast are eventually dropped on the ocean floor. The dominant process is slow sedimentation, where the eroded particles very slowly filter through the ocean water and settle upon one another in layers. The thickness of the layer of sediments is still unknown. Its rate of accumulation is equally uncertain. Generally speaking, we may classify all the oceanic deposits as either muds, oozes, or clays. 1. The muds. These are terrigenous deposits because they are derived from land and are mainly deposited on the continental shelves. The muds are referred to as blue, green, or red muds. Their coloring depends upon their chemical content. 2. The oozes. These are pelagic deposits because they are derived from the oceans. They are made of the shelly and skeletal remains of marine microorganisms with calcareous or siliceous parts. Oozes have a very fine, flour-like texture and either occur as accumulated deposits or float about in suspension. 3. The clays. These occur mainly as red clays in the deeper parts of the ocean basins and are particularly abundant in the Pacific Ocean. Red clay is believed to be an accumulation of volcanic dust blown out from volcanoes during volcanic eruptions. Salinity of the ocean. Almost every known chemical element can be found in varying proportions in the oceans, whose most characteristic feature is their salinity, in contrast to the fresh water of lakes and streams. All seawater. 92 Part 1. Physical geography. Contains large amounts of dissolved mineral matter, of which sodium chloride or common salt alone constitutes more than 77%. The other more important compounds include magnesium, calcium, and potassium, while the rest are distinguishable only in traces of very minute quantities. Due to the free movement of ocean water, the proportions of different salts remain remarkably constant in all oceans and even to great depths. But the degree of concentration of the salt solution in oceans does vary appreciably in different areas. This is expressed as salinity, the degree of saltness of water, either as a percentage or more often in parts per thousand. Variations are shown in salinity distribution maps by isohalenes, lines joining places having an equal degree of salinity. Generally speaking, the average salinity of the oceans is 35.2% O, about 35 parts of salt and 1,000 parts of water. In the Baltic Sea, where there is much dilution by fresh water and melting ice, the salinity is much lower, only about 7% O. In the Red Sea, where there is much surface evaporation and fewer rivers to bring in fresh water, the average salinity increases to 39% O. In enclosed seas, which are areas of inland drainage, such as the Caspian Sea, the salinity is very high, 180% O, and, in the Dead Sea of Palestine, a salinity of 250% OTA has been recorded. The highest salinity is perhaps that of Lake Van, in Asia Minor, with 330% O. It is a salt lake, and salts are collected from its shores. The density of the water is so high that in Lake Van, or the Dead Sea, it is almost impossible to sink. Beginner swimmers will find it much easier to float here than anywhere else. The variation of salinity in the various seas and oceans is affected by the following factors. 1. The rate of evaporation. The waters fringing the high-pressure belts of the trade wind deserts, between 20 degrees and 30 degrees north and S, have high salinity because of the high rate of evaporation caused by high temperature and low humidity. The temperate oceans have lower salinity due to the lower temperature and a lower rate of evaporation. 2. The amount of fresh water added by precipitation, streams, and icebergs. Salinity is lower than the average 35% O in equatorial waters because of the heavy daily rainfall and high relative humidity. Oceans into which huge rivers like the Amazon, Congo, Ganges, Irrawaddy, and Mekong drain have much of their saltness diluted and have a lower salinity. The Baltic, Arctic, and Antarctic waters have a salinity of less than 32% O because of the colder climate with little evaporation and because much fresh water is added from the melting of icebergs, as well as by several large poleward-bound rivers, e.g. Ob, Lena, Yenisei, and Mackenzie. 3. The degree of water mixing by currents. In wholly or partially enclosed seas such as the Caspian Sea, Mediterranean Sea, Red Sea, and Persian Gulf, the waters do not mix freely with the ocean water and they are not penetrated by ocean currents. Salinity is high, often over 37% O. In areas of inland drainage without links with the oceans, continuous evaporation under an almost cloudless sky causes the accumulation of salts around the shores. In the open oceans where currents freely flow, salinity tends to be near the average 35% O or even a little lower. The range of salinity is negligible where there is free mixing of water by surface and subsurface currents. The temperature of ocean water. Like land masses, ocean water varies in temperature from place to place both at the surface and at great depths. Since water warms up and cools down much more slowly than the land, the annual range of temperature in any part of the ocean is very much smaller. It is less than 10 degree F, minus 12 degrees Celsius, for most of the open seas. Generally, the mean annual temperature of the surface ocean water decreases from about 70 degrees Fahrenheit 21 degrees Celsius in equatorial areas to 55 degrees Fahrenheit 13 degrees Celsius at latitudes 45 degrees north and S, and drops almost to freezing point at the poles. The reduction of temperature with latitude is however never constant because of the interference by warm and cold currents, winds, and air masses. Unlike the solid Earth, ocean water is mobile and variations in the temperature between different parts of the oceans can be expected. Water flowing out from the Arctic and Antarctic is cold currents, such as the Labrador Current off northeast Canada, tends to reduce the surface water temperature. Ports of eastern Canada, even at 45 degrees north, are thus icebound for almost half the year. In the same way, coasts warmed by warm currents, such as the North Atlantic Drift, have their surface temperature raised. The Norwegian coast, even at latitudes 60 degrees to 70 degrees north, is ice-free throughout the year. The highest water temperatures are found in enclosed seas in the tropics, e.g. the Red Sea, which records a temperature of 85 degrees to 100 degrees Fahrenheit. The ocean's 93. The Arctic and Antarctic waters are so cold that their surface is permanently frozen as pack ice down to a depth of several feet. In the warmer summer, parts of the ice break off as icebergs that both dilute the water and lower the surface temperature of surrounding ice-free seas. The temperature of the oceans also varies vertically with increasing depth. It decreases rapidly for the first 200 fathoms, 366 m, at the rate of 1 degree Fahrenheit. For every 10 fathoms, 18 m, and then more slowly, until a depth of 500 fathoms, 914 m, is reached. Beyond this, the drop is scarcely noticeable, less than 1 degree Fahrenheit for every 100 fathoms, 183 m. In the ocean deeps below 2,000 fathoms, 12,000 feet or 3,657 m, the water is uniformly cold, just a little above freezing point. It is interesting to note that even in the deepest ocean trenches, more than 6 miles, 9.65 kilometers, below the surface, the water never freezes. It is estimated that over 80% of all ocean waters have a temperature between 35 degrees and 40 degrees Fahrenheit, 1.66 degrees and 4.44 degrees Celsius. The movements of ocean currents. Ocean currents are large masses of surface water that circulate in regular patterns around the oceans, as shown in the world map in Fig. 106. Those that flow from equatorial regions polewards have a higher surface temperature and are warm currents. Those that flow from polar regions equatorwards have a lower surface temperature and are cold currents. Their direction of movement is indicated by the arrows. But why should they follow such a pattern? Some of the underlying factors are explained below. 1. The planetary winds. Between the equator and the tropics blow the trade winds which move equatorial waters polewards and westwards and warm the eastern coast of continents. For example, the northeast trade winds move the North Equatorial Current and its derivatives, the Florida Current and the Gulf Stream drift to warm the southern and eastern coast of USA. Similarly, the southeast trade winds drive the South Equatorial Current which warms the eastern coast of Brazil as the warm Brazilian Current. And the temperate latitudes blow the westerlies. Though they are less reliable than the trade winds, they result in a northeasterly flow of water in the northern hemisphere, so that the warm Gulf Stream is driven to the western coast of Europe as the North Atlantic drift. In a similar manner, the westerlies of the southern hemisphere drive the west wind drift equatorwards as the Peruvian Current off South America and the Benguela Current off southern Africa. The planetary winds are probably the dominant influence on the flow of ocean currents. The strongest evidence of prevailing winds on current flows is seen in the North Indian Ocean. Here the direction of the currents changes completely with the direction of the monsoon winds which come from the northeast in winter and southwest in summer. 2. Temperatures. There is much difference in the temperature of ocean waters at the equator and at the poles. As warm water is lighter and rises, and cold water is denser and sinks, warm equatorial waters move slowly along the surface polewards, while the heavier cold waters of the polar regions creep slowly along the bottom of the sea equatorwards. 3. Salinity. The salinity of ocean water varies from place to place. Waters of high salinity are denser than waters of low salinity. Hence waters of low salinity flow on the surface of waters of high salinity, while waters of high salinity flow at the bottom towards waters of low salinity. For example, in the Mediterranean region, there is great difference in salinity between the waters of the open Atlantic and those of the partially enclosed Mediterranean. C. The less saline water of the Atlantic flows on the surface into the Mediterranean, and this is compensated for by an outflow of denser bottom water from the Mediterranean. 4. The Earth's rotation. The Earth's rotation deflects freely moving objects, including ocean currents, to the right. In the northern hemisphere, this is a clockwise direction, e.g. the circulation of the Gulf Stream drift and the Canaries Current. In the southern hemisphere, it is an anti-clockwise direction, e.g. the Brazilian Current and the west wind drift. 5. Land. A land mass always obstructs and diverts a current. For instance, the tip of southern Chile diverts part of the west wind drift northwards as the Peruvian Current. Similarly, the shoulder of Brazil at Cape São Roque divides the west-flowing equatorial currents into the Cayenne Current which flows northwestwards and the Brazilian Current which flows southwestwards. 94 Part 1. Physical Geography. The circulation of the Atlantic Ocean. Let us now study more closely the circulation of ocean currents in the Atlantic Ocean. We shall begin with the north and south equatorial current at the equator. The steady trade winds constantly drift two streams of water from east to west. At the shoulder of northeast Brazil, the protruding land mass splits the south equatorial current into the Cayenne Current which flows along the Guiana coast, and the Brazilian Current which flows southwards along the east coast of Brazil. In the North Atlantic Ocean, the Cayenne Current is joined and reinforced by the North Equatorial Current and heads northwestwards as a large mass of equatorial water into the Caribbean Sea. Part of the current enters the Gulf of Mexico and emerges from the Florida Strait between Florida and Cuba as the Florida Current. The rest of the equatorial water flows northwards east of the Antilles to join the Gulf Stream off the southeastern USA. The Gulf Stream drift is one of the strongest ocean currents, 35 to 100 miles, 56 to 161 kilometers, wide, 2,000 feet, 610 meters, deep and with a velocity of 3 miles or 5 kilometers an hour approximately. The current hugs the coast of America as far as Cape Hatteras, latitude 35 degrees north, where it is deflected eastwards under the combined influence of the westerlies and the rotation of the Earth. It reaches Europe as the North Atlantic drift. This current, flowing at 10 miles, 16 kilometers per day, carries the warm equatorial water for over 1,000 miles to the coast of Europe. From the North Atlantic, it fans out in three directions, eastwards to Britain, northwards to the Arctic, and southwards along the Iberian coast as the cool Canaries Current. Oceanographic researches show that almost two-thirds of the water brought by the Gulf Stream to the Arctic regions is returned annually to the tropical latitudes by dense, cold polar water that creeps southwards in the ocean depths. The Canaries Current flowing southwards eventually merges with the North Equatorial Current, completing the clockwise circuit in the North Atlantic Ocean. Within this ring of currents, an area in the middle of the Atlantic has no perceptible current. A large amount of floating seaweed gathers, and the area is called the Sargasso Sea. Apart from the clockwise circulation of the currents, there are also currents that enter the North Atlantic from the Arctic regions. These cold waters are blown south by the outflowing polar winds. The Erminger Current, or East Greenland Current, flows between Iceland and Greenland and cools the North Atlantic drift at the point of convergence. The cold Labrador Current drifts southeastwards between West Greenland and Baffin Island to meet the warm Gulf Stream off Newfoundland, as far south as 50 degrees north where the icebergs carried south by the warm Gulf Stream off Newfoundland, as far south as 50 degrees north where the icebergs carried south by the Labrador Current melt. The South Atlantic Ocean follows the same pattern of circulation as the North Atlantic Ocean. The major differences are that the circuit is anti-clockwise and the collection of seaweed in the still waters of the mid-South Atlantic is not so distinctive. Where the South Equatorial Current is split at Cape São Roque, one branch turns south as the warm Brazilian Current. Its deep blue waters are easily distinguishable from the yellow, muddy waters carried hundreds of miles out to sea by the Amazon further north. At about 40 degrees south, the influence of the prevailing westerlies and the rotation of the Earth propel the current eastwards to merge with the cold west wind drift as the South Atlantic Current. On reaching the west coast of Africa, the current is diverted northwards as the cold Benguela Current, the counterpart of the Canaries Current. It brings the cold polar waters of the west wind drift into tropical latitudes. Driven by the regular southeast trade winds, the Benguela Current surges equator wards in a northwesterly direction to join the South Equatorial Current. This completes the circulation of the currents in the South Atlantic. Between the North and South Equatorial Currents is the east flowing equatorial countercurrent, the circulation of the Pacific Ocean. The pattern of circulation in the Pacific is similar to that of the Atlantic except in modifications which can be expected from the greater size and the more open nature of the Pacific. The circulation can be easily followed in Fig. 106. Try to correlate it with the currents in the Atlantic. The North Equatorial Current flows westwards with a compensating equatorial countercurrent running in the opposite direction. Due to the greater expanse of the Pacific and the absence of an obstructing land mass, the volume of water is very much greater than that of the Atlantic Equatorial Current. The northeast trade winds. The oceans 95. Littoral Current, south. South Pacific Ocean. Indian Ocean. NE 66W. I Apergel TPT Turgert. Sargasso Sea. In. E Monson Drift. Winter. AV, North Pacific Ocean. Erpelkt Career IJWN. V. Y Nor Atlantic Current Ocean. Tropic of Capricorn ZWS. IEDLRX NELC Ocean / Warm currents T, 1 continental shelves, cold currents. Figure 106 Ocean currents of the world. Blow the North Equatorial Current off the coasts of the Philippines and Formosa into the East China Sea as the Kuroshio or Kuroshio or Japan Current. Its warm waters are carried polewards as the North Pacific Drift, keeping the ports of the Alaskan coast ice-free in winter. The cold Bering Current or Alaskan Current creeps southwards from the narrow Bering Strait and is joined by the Okhotsk Current to meet the warm Japan Current as the Oyashio, off Hokkaido. The cold water eventually sinks beneath the warmer waters of the North Pacific Drift. Part of it drifts eastwards as the cool Californian Current along the coast of the western USA and coalesces with the North Equatorial Current to complete the clockwise circulation. The current system of the South Pacific is the same as that of the South Atlantic. The South Equatorial Current, driven by the southeast trade winds, flows southwards along the coast of Queensland as the East Australian Current, bringing warm equatorial waters into temperate waters. The current turns eastwards towards New Zealand under the full force of the westerlies in the Tasman Sea and merges with part of the cold west wind drift as the South Pacific Current. Obstructed by the tip of southern Chile, the current turns northwards along the western coast of South America as the cold Humboldt or Peruvian Current. The cold water chills any wind that blows onshore so that the Chilean and Peruvian coasts are practically rainless. The region is rich in microscopic marine plants and animals that attract huge shoals of fish. Consequently, millions of seabirds gather here to feed on the fish. Their droppings completely whiten the coastal cliffs and islands, forming thick deposits of guano, a valuable source of fertilizer. The Peruvian Current eventually links up with the South Equatorial Current and completes the cycle of currents in the South Pacific. The Indian Ocean circulation. As in the other oceans as illustrated in Fig. 106. The currents of the South Indian Ocean form a circuit. The equatorial current, turning southwards past Madagascar as the Agulhas or Mozambique current merges with the west wind drift, flowing eastwards and turns equatorwards as the West Australian current. In the North Indian Ocean, there is a complete reversal of the direction of currents between summer and winter due to the changes. Han equatorial current. 96 Part 1. Physical geography of monsoon winds. In summer from June to October, when the dominant wind is southwest monsoon, the currents are blown from a southwesterly direction as the southwest monsoon drift. This is reversed in winter, beginning from December, when the northeast monsoon blows the currents from the northeast as the northeast monsoon drift. The currents of the North Indian Ocean demonstrate most convincingly the dominant effects of winds on the circulation of ocean currents. Questions and exercises. 1. With the aid of large sketch maps, describe and explain the circulation of currents in either the Atlantic or the Pacific Ocean. Your map should clearly differentiate the warm currents from the cold currents. 2. Explain by reference to actual examples the effects of ocean currents on A. Climate, B. Navigation, C. Economic activities. 3. What is meant by the relief of the oceans? In what ways are the structure and composition of the relief different from those of the land surface? 4. Give a reasoned explanation of any three of the following. A. The richest fishing grounds are located on continental shelves. B. The average salinity of the Baltic Sea is only 7, whereas that of the Dead Sea is 240% zero. C. The temperature of the ocean water varies both horizontally and vertically. D. The dominant influence on the circulation of ocean currents is wind. 5. Write brief notes on any three of the following terms associated with the oceans. A. Deep sea core samples. B. Mariana Trench. C. Isohelines. D. Gulf Stream drift. E. Sargasso Sea 6. Either A. In each of two continents name. I. A volcano. 2. A rift valley. You need not select L and 2. From the same continent. B. With the aid of diagrams, describe the physical features and method of formation of one of the volcanoes and one of the rift valleys you have named in A. Or choose three of the following landforms: fjord, barrier reef, delta, lagoon. For each. I. With the aid of diagrams, describe its main features and suggest how the landforms may have been formed. 2. Name an example and locate it by means of a sketch map. 7. A. With the aid of diagrams and by reference to actual examples, explain how lakes are caused by any two of the following. I. Movement of the Earth's crust. 2. Glaciation. 3. The action of man. B. Describe three ways in which lakes are useful to man. Part 2. Weather, climate, and vegetation. Weather. The difference between weather and climate. The term weather should not be confused with climate, though they are very closely related to each other in the study of meteorology and climatology. We don't hear people saying that the climate of the day is warm or cold, but we do. Talk of warm weather, a cold morning, a sunny afternoon, a rainy day, or a chilly night. Any casual remarks about the atmospheric conditions of a certain place at a certain time are about weather. It is never static, and thus cannot be generalized. In the same country, even over a small area, the weather can vary tremendously. It may be sunny in one part of the district, but raining heavily a few miles away. Strong gales may be experienced along the coast while the interior may be relatively calm. It is important to realize that any place can be subjected to haphazard changes in weather at any time. When we speak of climate, we mean the average atmospheric conditions of an area over a considerable time. For climatic averages, a minimum period of 35 years is desirable. This involves the systematic observation, recording, and processing of the various elements of climate such as rainfall, temperature, humidity, air pressure, winds, clouds, and sunshine before any standardization of the climatic means or averages can be arrived at. The climate of Malaysia is described as hot, wet, equatorial climate, which is a summing up of the average everyday climate of the country throughout the year. The degree of variability in the climate or weather of a country also differs. Generally speaking, the climate of temperate latitudes is far more variable than that of the tropics. The climate of the British Isles is so changeable that many people have commented that Britain has no climate, only weather. Conversely, the climate of Egypt is so static that it makes a good deal of sense when people say that Egypt has no weather, only climate. The importance of climate and weather. The profound influence of climate and weather over man's activities can be seen from his everyday life. Forces of nature have regulated to a very great extent the sort of food we eat, what we wear, how we live and work, our mental alertness, our physical characteristics, and even our racial differences when closely examined have at least some relationship with climate. The direction of winds once controlled the pattern of trading routes. The safety of modern air communications is closely tied to accurate meteorological reports from the ground stations. Despite the advances made in science and technology, farmers and their crops are still at the mercy of the climate and the weather. Conditions of temperature, precipitation, and humidity may promote or discourage the growth of fungus and diseases which may be injurious to both men and crops. Death rates are normally high in tropical countries and low in deserts because germs are not transmitted readily in regions of high temperature and low humidity. Cool, fresh mountain air is always good for health. Weather bureaus or meteorological stations are scattered all over the globe, including the oceans, using some of the most up-to-date weather instruments to gather a wide range of data as raw materials for the construction of weather maps or synoptic charts. Though men are still unable to tame the forces of nature such as floods, droughts, typhoons, or hurricanes, a sound knowledge of the trends or the weather systems can often help to avoid or reduce the seriousness of the calamities. Professional meteorologists are able to forecast the weather fairly accurately from local observations. A fall in the barometer, a change of cloud types, a bright sunset, or even a whisper of the wind can be very useful tips to a weather forecaster in detecting what is going to happen next. A casual glance at the sky will be sufficient for a weather expert to sum up the conditions of the atmosphere. Today, farmers are becoming more and more dependent upon meteorological services. A knowledge. 98 Part 2. Weather, climate, and vegetation. Of the likely weather of a place will be useful for a farmer to plan his work for the season or the year. Frequent agricultural bulletins issued by the Meteorological Office will assist farmers to take due precautions against frosts, hail, heavy snowfall, or a period of possible drought. Sailors at sea are warned promptly of any oncoming gale or typhoon. Modern air transport, military operations, geographical expeditions, even important games and outings often take due consideration of meteorological reports. A fair knowledge of the weather is not only useful but often essential. The elements of weather and climate. To collect various climatic data and to prepare maps and charts of them, the following elements of climate are normally observed and measured by weather instruments. 1. Rainfall. Rainfall, including other forms of precipitation, snow, sleet, and hail, is always measured by a metal instrument called a rain gauge, figure 107a. It consists of a copper cylinder with a metal funnel either 5 inches or 8 inches in diameter, which leads into a smaller copper container or a glass bottle. The hole in the funnel that leads down to the container is very small so that evaporation of the collected rain is minimized. The gauge should be at least 1 foot above the ground and firmly fastened. To avoid splashing, the instrument should be sited well away from tall buildings, high trees, and other objects which would shelter it. The measurement of the rainfall is done by removing the funnel, emptying the rain in the container into a graduated cylinder with a 172 diameter, figure 107b. The reading should be done at eye level and to an accuracy of 0.01 inch. For greater accuracy, a special kind of taper measure as shown in figure 107c, which tapers at the bottom, may be used. It gives an accuracy up to 0.005 inch. An inch of rainfall means the amount of water that would cover the ground to a depth of 1 inch, provided none evaporated, drained off, or percolated away. For meteorological recordings, a rain day is reckoned as a period of 24 hours with at least 0.01 inch or more rain being recorded. If the amount exceeds 0.04 inch, it is considered a wet day. For general reckoning, the average rainfall for Malaysia is less than 0 to 3 inch a day. Only a torrential downpour can account for more than an inch of rainfall in a day. The rain gauge must be examined every day. In temperate regions, snowfall. Figure 107a, a rain gauge. B, ordinary measuring cylinder. C, a calibrated taper measure. Weather 99 is carefully melted by warming the funnel and then measured. For all practical purposes, 10 to 12 inches of snow may be considered as equivalent to 1 inch of rain. The daily records of rainfall will be added at the end of the month to find the total rainfall for that month. The total for each month is again added at the end of the year to find the annual rainfall. The mean annual rainfall is obtained from the averages of annual rainfall taken over a long period of, say, 35 years. For plotting in rainfall maps, places having the same mean annual rainfall are joined by a line called an isohyet, as shown in many atlases. Rainfall can also be graphically depicted as shaded rainfall columns, one for each month of the year as in figure 108, or in dispersal diagrams, one dot for each year for as many years as possible as in fig. 109. The former illustrates the monthly rainfall. Figure 108, a rainfall histogram showing the monthly rainfall of Kota Kinabalu, E. Malaysia regime over a year, and the latter shows at a glance the range of dry and wet years for 35 years. 2. Pressure. Air is made up of a number of mixed gases and has weight. It therefore exerts a pressure on the Earth's surface which varies from place to place and from time to time. This force that presses on the surface of any object can be fairly accurately measured. The instrument for measuring pressure is a barometer, as shown in figure 110, invented by the scientist Galileo and his assistant Torricelli in 1643. The ordinary mercury barometer consists of a long glass tube, sealed at the upper and open at the lower end. The lower end is inverted in a bowl of mercury, whose surface is exposed to the air. Variations in the atmospheric pressure on the mercury surface are balanced by the column of mercury in the glass tube. This gives the pressure of the air and can be read off quickly from the scale on the glass tube. Any liquid could be used for this purpose, but mercury has been chosen because it is the heaviest liquid known. If ordinary water were used, the corresponding column for normal atmospheric pressure would be 34 feet. At sea level, the mercury column is 29.9 inches, or 760 millimeters. If the pressure increases, vacuum column of mercury 76 centimeters, 30 smiley face. Glass tube. Figure 109, a rainfall dispersal diagram for Gibraltar for 35 years. Weight of air, average 14.5 IB/square in. Figure 110, a mercury barometer. Container. 100 Part 2, weather, climate, and vegetation. The air pressing on the surface will force up the mercury column to about 31 inches, high pressure. When the pressure decreases as less air presses on the surface, the mercury column will drop about 28 inches, low pressure. As pressure is a force, it is more appropriate to measure it in terms of a unit of force. A new unit known as the millibar, MB, was adopted by meteorological stations in 1914. A normal atmospheric pressure, equivalent to 14 to 7 pounds per square inch in weight, or a reading of 29 to 9 inches of mercury in the column, is 1,013 millibars. On maps, places of equal pressure are joined by lines called isobars. In temperate latitudes, pressure changes are very rapid in the formation of cyclones and anticyclones. In normal circumstances, they vary from 960 MB to 1,040 MB. Pressure readings vary with a number of factors. A sea level reading of 30 inches will be halved on mountainous regions of 3 to 5 miles above sea level. This is because as one ascends there is less air above, and so the weight, or pressure, is less. The barometer is also sensitive to gravitational forces at different latitudes. The mercury itself also expands with an increase in temperature. Therefore, for professional meteorological work which requires very accurate readings, corrections have to be made in respect of altitude, latitude, and temperature. Since a mercury barometer that dips in liquid mercury is inconvenient for outdoor measurement, a more portable but less accurate type known as the aneroid barometer is used. This comprises a small metal container with most of the air driven out to form almost a vacuum. As there is practically no pressure at all inside the box, any increase in pressure on the outside of the box will cause the lid to move inwards, thus registering high pressure by an indicator on the revolving dial. When there is a decrease in pressure, the lid springs outwards, registering low pressure by the indicator, RG 111. In aeroplanes, a modified type of aneroid barometer called an altimeter is used. As pressure decreases with altitude at an approximate rate of 1 inch drop in the mercury reading for every 900 feet ascent, the altimeter gives the reading in feet for height attained instead of millibars or inches. With this, the pilot will be able to tell the altitude of the plane above sea level. For a continuous record of pressure changes, as is sometimes required, the self-recording barogram is used. 3. Temperature. Temperature is a very important element of climate and weather. The instrument for measuring temperature is the thermometer, which is a narrow glass tube filled with mercury or alcohol. The instrument for measuring temperature is the thermometer, which is a narrow glass tube filled with mercury or alcohol. It works on the principle that mercury expands when heated and contracts when cooled. On thermometers, temperatures are marked in one of two ways. In degree F Fahrenheit, the freezing point is 32 degrees Fahrenheit and the boiling point is 212 degrees Fahrenheit for most scientific purposes. The centigrade degree C scale is preferred. Its freezing point is 0 degrees C and its boiling point is 100 degrees Celsius. The mean daily temperature of Malaysia is 80 degrees Fahrenheit or 26.7 degrees Celsius. For rapid conversion of one scale into another, the following formulae may be used. To obtain Fahrenheit equals 1 to 8x degrees C plus 32 degrees Fahrenheit, e.g. to convert 20 degrees Celsius into Fahrenheit, 1 to 8x 20 degrees Celsius plus 32 degree F dash equals 36 degrees 4 to 32 degrees equals 68 degrees Fahrenheit. To obtain centigrade equals degree F, 32 for 1/8. E.g. to convert 59 degrees Fahrenheit into centigrade, 59 to 32 degrees, for 1 to 8 equals 27 for 1/8 equals 15 degrees Celsius. As the degree of hotness varies tremendously from one place to another, the sighting of the instrument is very important. A temperature taken in open daylight is very high because it measures the direct insolation of the sun. It is better described as temperature in the sun. For agricultural purposes, earth temperatures are taken at various depths in the ground. The thermometer is enclosed in a special glass tube and the bulb is embedded in paraffin wax so that they are less sensitive. Weather 101. Fig. II-A Stevenson screen. To abrupt temperature changes. To assess the possible damages done by ground frost to crops in temperate latitudes, grass temperatures are also taken. But the temperatures that we are so accustomed to in climatic graphs are shade temperatures, that is the temperatures of the air. Precautions therefore must be taken to exclude the intensity of the sun's radiant heat. This is done by placing the thermometers in a standard meteorological shelter known as the Stevenson screen, figure 112. It consists of a white wooden box raised 4 feet above the ground on stilts. The roof is double layered with an intervening airspace to exclude much of the direct rays of the sun. The sides of the box are louved like Venetian blinds to allow free circulation of the air. One side of the screen is hinged to serve as a door which can be opened and closed to give access to the instruments kept inside. The floor of the screen is also louved. The Stevenson screen normally carries maximum and minimum thermometers, dry and wet bulb thermometers. Larger ones may also contain a self-recording thermogram and hygrogram. Maximum and minimum temperatures are measured by the maximum and minimum thermometers. They are either in the form of separate thermometers or joined in a U-shaped glass tube as in the 6th thermometer. The maximum thermometer records the highest temperature reached during the day. The mercury in the closed glass tube expands when the temperature rises. It pushes a metal indicator up the tube, and this stays at the maximum level when the temperature drops. The end of the indicator nearest the mercury, as indicated in figure 113, gives the reading of the maximum temperature, which is 87 degrees Fahrenheit in this case. To reset the mercury for the next day's reading, swing it hard or draw the indicator back by a magnet. The minimum thermometer records the lowest temperature reached during the day. It probably occurs in the middle of the night or early in the morning. The glass tube is filled with alcohol. Figure 113 maximum and minimum thermometers. 102 Part 2, Weather, Climate, and Vegetation, which allows the indicator to slide freely along the tube. When the temperature drops, the alcohol contracts and drags the indicator towards the bulb by the surface tension of the indicator. When the temperature rises, the alcohol flows past the indicator, leaving it where it was. The end of the indicator farthest from the bulb gives the reading of the minimum temperature, which is 73 degrees Fahrenheit in Fig. 113. The thermometer is then reset by a magnet for the next 24 hours reading. In recording temperature, the maximum temperature is entered in the column for the previous day and the minimum temperature in the column for current day because of their respective period of probable occurrence. The mean daily temperature is the average of maximum and minimum, e.g., 87 degrees Fahrenheit plus 73 degrees Fahrenheit, T2 equals 80 degrees Fahrenheit, but an accurate mean should be the average of 24 readings taken at hourly intervals during the whole day. In practice, this is almost impossible except with a self-recording instrument. The difference between the maximum and minimum temperatures of a day gives the diurnal range of temperature. The difference between the hottest month, i.e. July in the northern hemisphere, and the coldest month, i.e. January in the northern hemisphere, gives the annual range of temperature. Statistical data of temperature of Mukden. Mean monthly temperature from January to December. Mean annual temperature is 44 CF or 6.7 degrees Celsius. HG 114A temperature graph of Mukden, Manchuria, 42 degrees north, 123 degrees east. In diagrammatic representations, monthly mean temperatures are shown in simple temperature graphs, figure 114, or in temperature distribution maps as isotherms. For these maps, temperatures are reduced to sea level, that is shown as if the recording station were at sea level. Temperatures decrease at the rate of 1 degree Fahrenheit drop in temperature for 300 feet ascent in altitude, so for highland stations a higher temperature is shown than was actually recorded. 4. Humidity. Humidity is a measure of the dampness of the atmosphere which varies greatly from place to place at different times of day. The actual amount of water vapor present in the air, which is expressed in grams per cubic meter, is called the absolute humidity. But more important from the point of view of weather studies is the relative humidity. This is the ratio between the actual amount of water vapor and the total amount the air can hold at a given temperature, expressed as a percentage. Warm air can hold more water vapor than cold air, so if it contains only half the amount it could carry, the relative humidity is 50%. In the equatorial regions, over 80% is common in the morning, which means the air contains 4/5 as much water vapor as it can carry. When the relative humidity reaches 100%, the air is completely saturated. The air temperature is said to be at dew point. Further cooling will condense the water vapor into clouds or rain. It is thus clear that when relative humidity is high, the air is moist, as in the equatorial regions. When it is low, the air is dry as in the deserts. The instrument for measuring relative humidity is the hygrometer, which comprises wet and dry bulb thermometers placed side by side in the Stevenson screen, figure 115. The dry bulb is, in fact, the ordinary thermometer that measures the shade temperature mentioned earlier. The wet bulb is kept wet by a wick that dips into a reservoir of distilled water. When the air is not saturated, evaporation, which produces a cooling effect, takes place from the moist wick. The wet bulb therefore always shows a lower reading than the dry bulb. With reference to prepared tables for calculating relative humidity, under the difference column of the dry and wet bulb reading, the relative humidity can be obtained as a percentage. Normally a weather 103. Bulb mercury and stem. Figure 115, the hygrometer consisting of wet and dry bulb thermometers. Large difference indicates a low RH and a small difference a high RH. If both have the same reading, RH is 100%, the air is saturated. 5. Winds. Wind is air in motion and has both direction and speed. Unlike other elements in climate such as rain, snow, or sleet, winds are made up of a series of gusts and eddies that can only be felt but not seen. When leaves fall, trees sway, and dust particles move, we realize that the wind is blowing. But there is nothing tangible that we can show or measure unless we make use of some conventional instruments. The instrument widely used for measuring wind direction is a wind vane or weathercock. As wind direction is always blocked by trees and tall buildings, weathercocks and wind vanes need to be erected in an exposed position to get a true direction. It is made up of two parts as shown in figure 116A and B. One part is an arrow or vane on the top, which is free to move with the prevailing wind. The other part with the 4 compass points is stationary and shows in which direction the wind is moving. Winds are always named from the direction they blow. An east wind is one that blows from east to west, and a southwest wind is one that blows from the southwest. Most of the weathercocks that we see on church spires and country buildings seldom give a correct indication of wind directions. They are either too low or are blocked by taller structures nearby. The direction of smoke drift or flag movements in fairly open spaces provides the most reliable indication of wind direction. Sometimes a piece of woven cloth with a tail is fixed to the top of a high pole and drifts freely in midair. This is another way of indicating wind direction. The speed of wind is usually measured by an anemometer, figure 117. It consists of 3 or 4 semicircular cups attached to the ends of horizontal spokes mounted on a high vertical spindle. As the concave sides of the cups offer greater resistance to the winds, the horizontal spokes will rotate, moving a central rod which transmits the velocity, speed, of the wind in miles per hour to an electrically operated dial. But the speed recorded is not absolutely accurate because after the winds have abated, the rotation continues due to its own momentum. With some figure 116 wind vanes. 104 Part 2 Weather, Climate, and Vegetation. To calibrated dial. Vertical mast. Modifications. The anemometer can also record wind directions. Since an anemometer is not easily available, a little practice of local wind observations will help us to assess the speed of winds. By seeing the way some objects move, a great deal can be said about the strength of winds. The best guide is obtainable from the Beaufort Wind Scale, which was devised by Admiral Beaufort in 1805 for estimating wind speed. Frequent reference to the table in your free time will help you to learn it quickly. Figure 117 simplified sketch to illustrate the main features of a wind anemometer. 00. Calm less than 1 smoke rises vertically. 1 / light air 1 to 3. Wind direction shown by smoke drift, but J not by wind vanes. 2 / slight breeze 4 to 7. Wind felt on face, leaves rustle, vanes moved by wind. 3 / gentle breeze 8 to 12. Leaves and twigs in constant motion. Winds extend light flags. BIM 1 titfly 3B and phi k $pound s pound phi I 2. A 8 and dollar and 2 and happy face. 4 / moderate W, breeze 13 to 18. Raises dust and loose paper, small branches moved. 5 W / T fresh breeze 19 to 24. Small trees and leaf begin to sway. Crested wavelets form on inland water. 6 / strong breeze 25 to 31. Large branches in motion, whistling heard in telegraph wires. A / WB, moderate gale 32 to 38. Whole tree in motion, walking. Inconvenienced. 8 fresh gale 39 to 46. Twigs broken off trees, progress. Generally impeded. 9 W, strong gale 47 to 54. Slight structural damage occurs. Chimney pots removed. W / 10 BL, whole gale 55 to 63. Considerable structural damage, trees uprooted. 11 BL, storm 64 to 75. Widespread damage, very rarely experienced. 12 BL, hurricane more than 75. Widespread devastation, experienced only in tropical areas. Weather 105. 6 sunshine. As mentioned in Chapter 1, the amount of sunshine a place receives depends on the seasons, a factor determined by latitude and by the position of the Earth in its revolution around the sun. Tourist resorts, particularly in the higher temperate latitudes, are most concerned about the numbers of hours of sunshine they receive. In the tropics, where sunshine is abundant, people are less interested in the amount. In the meteorological station, sunshine duration is recorded by a sundial, for inches in diameter, through which the sun's rays are focused upon a sensitized card, graduated in hours. A line is made on the card when it is sufficiently heated, but not when the rays are faint. On maps, places with equal sunshine duration are joined by isohells. 7 clouds. When air rises, it is cooled by expansion. After dew point has been reached, cooling leads to condensation of water vapor in the atmosphere. Tiny droplets of water vapor which are too small to fall as rain or snow, less than 0.001 centimeters, approximately 0.0005 inches in radius, will be suspended in the air and float as clouds. Their form, shape, height, and movements tell us a great deal about the sky conditions and the weather we are likely to experience. It is fascinating and very rewarding to know something about the clouds which we see every day. For meteorological purposes, the amount of cloud cover in the sky is expressed in eighths or octaves, e.g. 2/8 O is quarter covered, 4/8 O is half covered, 6/8 9 is 3/4 obscured, and August 8th is completely overcast. They are shown on weather maps by discs, shaded in the correct proportions. Details of Cloud type are indicated in code figures which have been internationally accepted on maps places with an equal degree of cloudiness are joined by lines known as isoneffs. As clouds vary so quickly, from time to time at any particular place, isoneff maps have little significance. The classification of clouds is based on a combination of form, height, and appearance. 4. Major cloud types and their variations can be recognized. A. High clouds, mainly cirrus, CI, of feathery form at 20 to 40,000 feet above ground. I. Cirrus, CL, this looks fibrous and appears like wisps in the blue sky. It is often called Mares tails. It indicates fair weather and often gives a brilliant sunset. 2. Cirrocumulus, CC. This appears as white globular masses, forming ripples in a mackerel sky. 3. Cirrostratus, CS. This resembles a thin white sheet or veil. The sky looks milky and the sun or moon shines through it with a characteristic halo. Cirrus cloud. Cirrocumulus cloud. 106 Part 2. Weather, climate, and vegetation. B. Medium clouds, mainly alto, alt, or middle height clouds at 7 to 20,000 feet. 4. Altocumulus, alts U. These are woolly, bumpy clouds arranged in layers and appearing like waves in the blue sky. They normally indicate tyne weather. V. Altostratus, alt ST. These are denser, grayish clouds with a watery look. They have a fibrous or striated structure, through which the sun's rays shine faintly. C. Low clouds, mainly stratus or sheet clouds below 7,000 feet. 6. Stratocumulus, STCU. This is a rough, bumpy cloud with the waves more pronounced than an altocumulus. There is great contrast between the bright and shaded parts. 7. Stratus, ST. This is a very low cloud, uniformly gray and thick, which appears like a low ceiling or highland fog. It brings dull weather with light drizzle. It reduces the visibility of aircraft and is thus a danger. 8. Nimbostratus, Ingesti. This is a dark, dull cloud, clearly layered, and is also known as a rain cloud. It brings continuous rain, snow, or sleet. D. Clouds with great vertical extent, mainly cumulus or heap clouds with no definite height. 2 to 30,000 feet. 9. Cumulus, CU. This is a vertical cloud with a rounded top and horizontal base, typical of humid tropical regions, associated with uprising convectional currents. Its great white globular masses may look gray against the sun, but it is a fair weather cloud. Cumulus cloud. X. Cumulonimbus, CUNI. This is, in fact, an overgrown cumulus cloud, extending for a tremendous vertical height from a base of 2,000 feet to over 30,000 feet. Its black and white globular masses take a fantastic range of shapes. Its cauliflower top often spreads out like an anvil. This is frequently seen in tropical afternoons. It is also referred to as a thundercloud and brings convectional ram, accompanied by lightning and thunder. 8. Other elements pertaining to visibility. Other elements affecting visibility include haze, mist. Other elements affecting visibility include haze, mist, and fog. A. Haze. This is caused by smoke and dust particles in industrial areas or may be due to unequal refraction of light and air of different densities in the lower atmosphere. The term is usually used in connection with the reduction of visibility in regions of low humidity, less than 75%. When visibility is less than 1 miles, haze is present. Altocumulus cloud, cumulonimbus cloud. Weather 107. B. Mist. The condensation of water vapor in the air causes small droplets of water to float about, forming clouds at ground level called mist. It reduces visibility to about 1,000 meters or 1,100 yards. Unlike haze, mist occurs in wet air when the relative humidity is over 75%. C. Fog. Ordinary fog is due to water condensing on dust and other particles like smoke from houses and factories. It only occurs in the lower strata of the atmosphere as a sort of dense ground cloud. The visibility in fog is even less than 1,000 meters. In industrial areas, like those of the Black Country, in northern England, very thick smoky fog is formed, called smog. The visibility may be reduced to 220 yards or even less. Fogs that occur on hills are called hilly fogs. They are most common in the morning, even in the tropics, and disperse when the sun rises. In temperate lands, when days are hot and nights are clear and still, fogs may also result from cooling of the land surface by radiation. The lower layers of the air are chilled and water vapor in the atmosphere condenses to form radiation fog, or land fog. When the cooling surface is over the sea, or when a damp air stream is brought into contact with a cold current as off Newfoundland, sea fog is formed. It varies in depth and thickness. Some sea fogs are so shallow and light that the masts of ships can be seen protruding above them. Generally speaking, fogs are more common overseas than lands, and are most prevalent over coastal areas. The dry interiors experience haze or mist. Dense fogs are more likely to occur in the high and middle latitudes rather than the tropics. Questions and exercises. 1. A. What instruments are normally kept in the school weather station? B. Why is it important that the times of observation and the method of recording should be uniform? C. Explain what precautions you would take to ensure that your observations and records from the various instruments are accurate. 2. Name the instruments you would use to measure the following elements of climate. A. Relative humidity. B. Atmospheric pressure. C. Wind velocity. For any two of the above, and with annotated diagrams, explain how the instruments work. 3. What weather elements are measured by the following apparatus? A. A rain gauge. B. The 6 maximum and minimum thermometers. C. A wind vane. Describe how the above apparatus function and state what special precautions must be taken when taking readings from them. 4. Either. Explain the following. A. Wind speed at 2,500 feet is greater than that at the surface. B. Britain has no climate, only weather. C. Fog is, in fact, cloud at ground level. Or, distinguish between mist and fog. 2. Cirrus and stratus clouds. 3. Climate and weather. 5. Define any three of the following terms or phrases in their relation to weather studies. A. Mean annual rainfall. D. Synoptic charts. B. Diurnal range of temperature. E. Lapse race. C. Beaufort scale. Climate. The atmosphere. The atmosphere is made up of gases and vapor and receives incoming solar energy from the sun, giving rise to what we call climate. We actually live at the bottom of this indefinite layer of atmosphere, where the air is densest. Higher up, the air thins out, and it is still a matter of conjecture where the atmosphere ends. One estimate puts this limit at about 600 miles, 965 kilometers, above sea level. The lowest layer, in which the weather is confined, is known as the troposphere. It extends from the Earth's surface for a height of 6 miles, 9.65 kilometers, and within it temperature normally falls with increasing altitude. The climatic elements such as temperature, precipitation, clouds, pressure, and humidity within the troposphere account for the great variations in local climate and weather that play such a great part in our daily lives. From analyses taken in different parts of the globe, it is found that the lower part of the atmosphere contains a consistent proportion of certain gases: 78% of nitrogen, 21% of oxygen, 0.03% of carbon dioxide, and minute traces of argon, helium, and other rare gases. In addition, it has an unpredictable proportion of water, existing either as a gas like water vapor, a liquid like rain, clouds, and sleet, or a solid like snow and hailstones, as well as other solid particles like smoke and dust. It is because of the variable water content of the atmosphere that we have such great contrasts in weather and climate over different parts of the world. If we were to live in a dry atmosphere, absolutely without water, there would be no weather and not even much climate. Above the troposphere lies the stratosphere, or the upper layer of the atmosphere. It extends upwards for another 50 miles or even more. It is not only very cold, but cloudless, with extremely thin air and without dust, smoke, or water vapor, but there are marked seasonal temperature changes. Beyond the stratosphere is the ionosphere, which goes several hundred miles up. It has electrically conductive layers which make shortwave radio transmission possible over long distances. Modern artificial satellites, launched in the upper strata of the atmosphere, as well as balloons, are used to transmit back to Earth valuable information regarding the conditions of the atmosphere. Insolation. The only source of energy for the Earth's atmosphere comes from the sun, which has a surface temperature of more than 10,800 degrees Fahrenheit, 5,982 degrees Celsius. This energy travels through space for a distance of 93 million miles, 150 kilometers, and reaches us as solar energy or radiant energy in the process called insolation. This radiation from the sun is made up of three parts: the visible, white, light that we see when the sun shines, and the less visible ultraviolet and infrared rays. The visible, white, light is the most intense and has the greatest influence on our climate. The ultraviolet rays affect our skin and cause sunburn when our bare body is exposed to them for too long a period. The infrared rays can penetrate even dust and fog and are widely used in photography. Only that part of the sun's radiation which reaches the Earth is called insolation. What matters most is the effect of the atmosphere upon the incoming solar radiation. It is estimated that of the total radiation coming to us, 35% reaches the atmosphere and is directly reflected back to space by dust, clouds, and air molecules. It plays practically no part in heating the Earth and its atmosphere. Another 14% is absorbed by the water vapor, carbon dioxide, and other gases. Its interception by the air causes it to be scattered and diffused, so that the visible rays of the spectrum between the ultraviolet and infrared give rise to the characteristic blue sky that we see above us. The remaining 51% reaches the Earth and warms the surface. In turn, the Earth warms the layers of air above it by direct contact or conduction, and through the transmission of heat by upward movement of air currents or convection. This radiation of heat by the climate 109. Earth continues during the night, when insolation from the sun cannot replace it. The Earth's surface therefore cools at night. The rate of heating differs between land and water surfaces. Land gets heated up much more quickly than the water. Because water is transparent, heat is absorbed more slowly, and because it is always in motion, its absorbed heat is distributed over a greater depth and area. Thus, any appreciable rise in temperature takes a much longer time. On the other hand, the opaque nature of land allows greater absorption, but all the radiant heat is concentrated at the surface, and temperature rises rapidly. Because of these differences between land and water surfaces, land also cools more quickly than water. Elements of climate and factors affecting them. Of the various climatic elements, temperature, precipitation, pressure, and winds are the most important because of their far-reaching global influences. These elements and their distribution, whether horizontal from equatorial to polar regions or vertical from ground to atmosphere, are in one way or another affected by some or all of the climatic factors: latitude, altitude, continentality, ocean currents, insolation, prevailing winds, slope and aspect, natural vegetation, and soil. Temperature. The importance of temperature. 1. Temperature influences the actual amount of water vapor present in the air and thus decides the moisture-carrying capacity of the air. 2. It decides the rate of evaporation and condensation, and therefore governs the degree of stability of the atmosphere. 3. As relative humidity is directly related to the temperature of the air, it affects the nature and types of cloud formation and precipitation. Factors influencing temperature. 1. Latitude. As explained in Chapter 1, due to the Earth's inclination, the midday sun is almost overhead within the tropics, but the sun's rays reach the Earth at an angle outside the tropics. Temperature thus diminishes from equatorial regions to the poles. This is illustrated in Fig. 118. It shows two bands of rays coming from the sun to two different latitudes on the Earth's surface. Band RI falls vertically over the equatorial latitudes. On surface E, band R2 falls obliquely over the temperate latitudes on surface T. RI travels through a shorter distance, and its concentrated solar insolation heats up a smaller surface area. Temperature is thus high. On the other hand, R2 travels through a longer distance, and much of Figure 118 the effect of latitude on solar insolation. This shows why temperatures are lower in higher latitudes than in the tropics. 110 Part 2. Weather, climate, and vegetation. Its heat is absorbed by clouds, water vapor, and dust particles. Its oblique ray has to heat up a large area. Temperature is therefore low. 2. Altitude. Since the atmosphere is mainly heated by conduction from the Earth, it can be expected that places nearer to the Earth's surface are warmer than those higher up. Thus temperature decreases with increasing height above sea level. This rate of decrease with altitude, lapse rate, is never constant, varying from place to place and from season to season. But for all practical purposes, it may be reckoned that a fall of 1 degree Fahrenheit occurs within a ascent of 300 feet or 0.6 degrees Celsius per 100 meters. It is usually more in summer than in winter. For example, in temperate latitudes, in summer, an ascent of only 280 feet, 85 meters, will cause the temperature to drop by 1 degree Fahrenheit, whereas in winter it requires, for 100 feet, 122 meters. Similarly, the lapse rate is greater by day than at night, greater on elevated highlands than on level plains. In tropical countries where the sea level temperature is 80 degrees Fahrenheit 26.6 degrees Celsius, a town that is located at a height of 4,500 feet or 1,372 meters, shown as X in Figure 119, will record a mean temperature of 65 degrees Fahrenheit 18.3 degrees Celsius. 3. Continentality. Land surfaces are heated more quickly than water surfaces because of the higher specific heat of water. In other words, it requires only 1/3 as much energy to raise the temperature of a given volume of land by 1 degree Fahrenheit as it does for an equal volume of water. This accounts for the warmer summers, colder winters, and greater range of temperature of continental interiors as compared with maritime districts. 4. Ocean currents and winds. Both ocean currents and winds affect temperature by transporting their heat or coldness into adjacent regions, Figure 120. Ocean currents like the Gulf Stream or the North Atlantic drift warm the coastal districts of Western Europe, keeping their ports ice-free. Ports located in the same latitude but washed by cold currents, such as the cold Labrador Current off northeast Canada, are frozen for several months. Cold currents also lower the summer temperature, particularly when they are carried landwards by onshore winds. On the other hand, onshore westerlies convey much tropical warm air to temperate coasts, especially in winter. The westerlies that come to Great Britain and Norway tend to be cool winds in summer and warm winds in winter, and are most valuable in moderating the climate. Local winds, e.g. Fin, Chinook, Sirocco, Mistral, also produce marked changes in temperature. 5. Slope, shelter, and aspect. A steep slope experiences a more rapid change in temperature than a gentle one. Mountain ranges that have an east-west alignment like the Alps show a higher temperature on the south-facing sunny slope than the north-facing sheltered slope. The greater insolation of the southern slope is better suited for vine cultivation and has a more flourishing vegetative cover. Consequently, there are more settlements and it is better utilized than the shady slope, Figure 121. In hilly areas, a hot day followed by a calm, cloudless night during which the air cools more rapidly over the higher ground. Figure 119 the lapse rate. The effect of altitude on mean annual temperature in a tropical area. Figure 120 the warming effect of warm ocean currents and prevailing winds on coastal regions with a maritime climate in temperate latitudes. Climate 111. Fig I2L south-facing slopes are more sunny. Figure 122 temperature inversion at valley bottom on a calm, still night, e.g. in Alpine Valley in spring, may induce cold, heavy air to flow down the slope and accumulate at the valley bottom, pushing the warmer air upwards. The temperature may then be lower in the valley than higher up as the slopes, as shown in Fig. 122. A reversal of the lapse rate has taken place. This is called a temperature inversion. 6. Natural vegetation and soil. There is a definite difference in temperature between forested regions and open ground. The thick foliage of the Amazon jungle cuts off much of the incoming insolation, and in many places sunlight never reaches the ground. It is, in fact, cool in the jungle, and its shade temperature is a few degrees lower than that of open spaces in corresponding latitudes. During the day, trees lose water by evapotranspiration so that the air above is cooled. Relative humidity increases and mist and fog may form. Light soils reflect more heat than darker soils, which are better absorbers. Such soil differences may give rise to slight variations in the temperature of the region. As a whole, dry soils like sands are very sensitive to temperature changes, whereas wet soils, like clay, retain much moisture and warm up or cool down more slowly. Precipitation. Types of precipitation. If air is sufficiently cooled below dew point, tiny drops of water vapor will condense around dust particles. When they float about as masses of minute water droplets or ice crystals at a considerable height above sea level, they form clouds, cirrus, cumulus, or stratus. When condensation occurs at ground level without necessarily resulting in rain, haze, mist, or fog are formed in higher latitudes or altitudes, where condensation of water vapor may take place in the atmosphere at temperatures below freezing point. Snow falls, either as feathery flakes or individual ice crystals. If the moist air ascends rapidly to the cooler layers of the atmosphere, the water droplets freeze into ice pellets and fall to the earth as hail or hailstones. As more and more supercooled water drops accumulate around a hailstone, it increases steadily in size. Some of them weigh as much as 2 pounds. In a severe hailstorm, the hailstones do great damage to crops and buildings. Very often, the ice pellets exist as frozen raindrops, melting and refreezing on their way down. This forms sleet. It is only when the droplets and clouds coalesce into larger drops between 0.2 millimeters and 6 millimeters that rain falls. Rainfall. Types of rainfall. There are 3 major types of rainfall. 1. Convectional rainfall. This type of rainfall is most common in regions that are intensely heated, either during the day, as in the tropics, or in the summer, as in temperate interiors. When the Earth's surface is heated by conduction, moisture-laden vapor rises because heated air always expands and becomes lighter. Air rises in a convection current after a prolonged period of intense heating, Figure 123. In ascending, its water vapor condenses into cumulonimbus clouds with a great vertical extent. This probably reaches its maximum in the afternoon when the convectional system is well developed. Hot, rising air has great capacity for holding moisture, which is abundant in regions of high relative humidity. As the air rises, it cools, and when saturation point is reached, torrential downpours occur, often accompanied by thunder and lightning. The summer showers in temperate regions are equally heavy with 112 Part 2. Weather, climate, and vegetation. Figure 123. Convection rainfall. Occasional thunderstorms. These downpours may not be entirely useful for agriculture because the rain is so intense that it does not sink into the soil but is drained off almost immediately. 2. Orographic or relief rain. Unlike convectional rain, which is caused by convection currents, orographic rain is formed wherever moist air is forced to ascend a mountain barrier. It is best developed on the windward slopes of mountains where the prevailing moisture-laden winds come from the sea. The air is compelled to rise as shown in Figure 124, and is thereby cooled by expansion in the higher altitudes and the subsequent decrease in atmospheric pressure. Further ascent cools the air until the air is completely saturated. Relative humidity is 100%. Condensation takes place, forming clouds and eventually rain. Since it is caused by the relief of the land, it is also known as relief rain. Much of the precipitation experienced on the windward slopes of the northeast of West Malaysia, western New Zealand, western Scotland, and Wales in the Assam hills of the Indian subcontinent is relief rain. On descending the leeward slope, a decrease in altitude increases both the pressure and the temperature. The air is compressed and warmed. Consequently, the relative humidity will drop. There is evaporation and little or no precipitation. The area in the lee of the hills is termed the rain shadow area. The effects of rain shadow are felt on the Canterbury Plain of South Island, New Zealand, and the western slopes of the northern and central Andes, and in many other areas. 3. Cyclonic or frontal rain. This type of rainfall is independent of relief or convection. It is purely associated with cyclonic activity, whether in the temperate regions, depressions, or tropical regions, cyclones. Basically, it is due to the convergence, meeting, of 2 different air masses with different temperatures and other physical properties. As cold air is denser, it tends to remain close to the ground. The warm air is lighter and tends to rise over the cold air, as shown in Fig. 125. In ascent, pressure decreases, the air expands and cools. Condensation takes place and light showers called cyclonic or frontal rain occur. The heavier and colder air masses eventually pushes up the warmer end. Lighter air, and the sky is clear again. Climate 113. Cumulonimbus clouds dash dash. Condensation, rain is formed. Saturation, relative humidity 100%. Cooling, temperature // J decreases, J // Pressure increases. Careta temperature increases. Expansion, pressure // decreases, /1 relief rain or orographic rain. CZ relative humidity decreases. At asterisk /O // Percent rapid evaporation pound and equals in sea rain. Mountain. Figure 124 orographic or relief rain. A. The convergence of warm and cold air. B. Warm air rises over cold air, cyclonic rain occurs. C. Cold air eventually pushes up warm air and the sky is clear again. Figure 125 cyclonic or frontal rain depression. Pressure and planetary winds. World pressure belts. In Chapter 11 we studied the circulation of waters in the oceans and noted that they follow a regular pattern, flowing from the poles equatorwards and from the equator polewards. In the same way, there is also a circulation of air over the surface of the Earth caused by the differences in pressure. Along the equator and within 5 degrees north and south is the equatorial low pressure belt, where there is intense heating, with expanding air and ascending convection currents. This equatorial belt is often termed the doldrums, because sailors in the olden days often found themselves becalmed here. It is a zone of wind convergence. About 30 degrees north and S occur the subtropical high pressure belts where the air is comparatively dry, and the winds are calm and light. It is a region of descending air currents or wind divergence and anticyclones. It is frequently referred to as the horse latitudes. Around the latitude 60 degrees north and S are 2 temperate low pressure belts which are also 114 Part 2, weather climate and vegetation. Zones of convergence with cyclonic activity. The subpolar low pressure areas are best developed over the oceans, where temperature differences between summer and winter are negligible. At the north and south poles 90 degrees north and S where temperatures are permanently low are the polar high pressure belts. Unlike the water masses of the high latitudes in the southern hemisphere, high pressures of the corresponding latitudes in the northern hemisphere are a little complicated by the presence of much land. Some pressure differences between summer and winter can be expected. The planetary winds. Within this pattern of permanent pressure belts on the globe, winds tend to blow from the high pressure belts to the low pressure belts as the planetary winds. Instead of blowing directly from one pressure belt to another, however, the effect of the rotation of the Earth Coriolis force tends to deflect the direction of the winds. In the northern hemisphere, winds are deflected to their right, and in the southern hemisphere to their left as shown in Fig. 126. This is known as Farrell's law of deflection. The Coriolis force is absent along the equator but increases progressively towards the poles. For this reason, winds blowing out from the subtropical high pressure belt in the northern hemisphere towards the equatorial low become northeast trade winds, and those in the southern hemisphere become the southeast trade winds. These trade winds are the most regular of all the planetary winds. They blow with great force and in a constant direction. They were thus helpful to early traders who depended on the wind when sailing the high seas, hence the name trade winds. Since they blow from the cooler subtropical latitudes to the warmer tropics, they have great capacity for holding moisture. In their passage across the open oceans, they gather more moisture and bring heavy rainfall to the east coast of continents within the tropics. As they are offshore on the west coast, these regions suffer from great aridity and form the trade wind hot deserts of the world, e.g. the Sahara, Kalahari, Atacama, and the Great Australian Deserts. Descending air. North Pole. South Pole. Figure 126 the distribution of world pressure belts and planetary winds. Climate 115. From the subtropical high pressure belts, winds blow towards the temperate low pressure belts as the variable westerlies. Under the effect of the Coriolis force, they become the southwesterlies in the northern hemisphere and the northwesterlies in the southern hemisphere. They are more variable in the northern hemisphere, but they play a valuable role in carrying warm equatorial waters and winds to western coast of temperate lands. This warming effect and other local pressure differences have resulted in a very variable climate in the temperate zones, dominated by the movements of cyclones and anticyclones. In the southern hemisphere, where there is a large expanse of ocean, from 40 degrees south to 60 degrees south, westerlies blow with much greater force and regularity throughout the year. They bring much precipitation to the western coast of continents. The weather is damp and cloudy, and the seas are violent and stormy. It is thus usual for seafarers to refer to the westerlies as the roaring 40s, furious 50s, and shrieking or stormy 60s, according to the varying degree of storminess in the latitudes in which they blow. It must be pointed out that not all the western coasts of the temperate zone receive westerlies throughout the year. Some of them, like California, Iberia, central Chile, southern Africa, and southwestern Australia, receive westerlies only in winter. This is caused by the shifting of the wind belts of such regions, which lie approximately between the latitudes 30 degrees and 40 degrees north and S. Due to the Earth's inclination, as explained in Chapter 1, the sun is overhead at midday in different parts of the Earth at different seasons. The entire system of pressure and wind belts follows the movement of the midday sun. In June, when the overhead sun is over the Tropic of Cancer. All the belts move about 5 to minus 10 degrees north of their average position. The Mediterranean parts of the southern continents then come under the influence of the westerlies and receive rain in June, winter in the southern hemisphere. In the same manner, when the sun is overhead at the Tropic of Capricorn in December, all the belts swing 5 to 10 degrees south of their average position. The Mediterranean parts of Europe and California then come under the influence of the westerlies and receive rain in December. Winter in the northern hemisphere. This is illustrated in Fig. 127. Lastly, mention must be made of the polar easterlies, which blow out from the polar high-pressure belts towards the temperate low-pressure belts. These are extremely cold winds as they come from the tundra and ice cap regions. They are more regular in the south than in the north. Shifting of wind belt in temperate latitude. December. Figure 127. The shifting of the pressure and wind belts in the northern hemisphere showing their positions in summer and winter and at the equinoxes. 116 Part 2. Weather, climate, and vegetation. Land and sea breezes and monsoons. Land and sea breezes are, in fact, monsoons on a smaller scale. Both are basically caused by differential heating of land and sea, the former in a diurnal rhythm and the latter in a seasonal rhythm. During the day, the land gets heated up much faster than the sea. Warm air rises, forming a region of local low pressure. The sea remains comparatively cool with a higher pressure, so a sea breeze blows in from sea to land. Its speed or strength is between 5 to 20 miles per hour, and it is generally stronger in tropical than temperate regions. Its influence does not normally exceed 15 miles from the coast. It is most deeply felt when one stands facing the sea in a coastal resort. At night, the reverse takes place. As the land cools down much faster than the sea, the cold and heavy air produces a region of local high pressure. The sea conserves its heat and remains quite warm. Its pressure is comparatively low. A land breeze thus blows out from land to sea. Fishermen in the tropics often take advantage of the outgoing land breeze and sail out with it. They return the next morning with the incoming sea breeze, complete with their catch. Land and sea breezes are illustrated in Fig. 128. In the same way, monsoons are caused. Rapid heating in the hot summer over most parts of India, for example, induces heated air to rise. The southwest monsoon from the surrounding ocean is attracted by the low pressure over the land and blows in, bringing torrential rain to the subcontinent. Similarly, in winter when the land is cold, the surrounding seas remain comparatively warm. High pressure is created over Indo-Pakistan, and the northeast monsoon blows out from the continent into the Indian Ocean and the Bay of Bengal. Figure 128, A. Sea breeze, day. Figure 128, B. Land breeze, night. Climate 117. Fin wind or Chinook wind. Both the fin and Chinook winds are dry winds, experienced on the leeward side of mountains when descending air becomes compressed with increased pressure. The fin wind is experienced in the valleys of the northern Alps, particularly in Switzerland in spring. Chinook winds are experienced on the eastern slopes of the Rockies in USA and Canada in winter. As illustrated in Figure 124, air ascending the southern slopes of the Alps expands and cools. Condensation takes place when the air is saturated. Rain and even snow fall on the higher slopes. In descending the northern slope, the wind experiences an increase in pressure and temperature. The air is compressed and warmed. Most of its moisture is lost, and the wind reaches the valley bottom as a dry, hot wind, the fin. It may raise the temperature by 15 degrees to 30 degrees Fahrenheit within an hour. It melts snow and causes avalanches. In North America, it is called Chinook, meaning the snow eater. But it has its blessings too. It hastens the growth of crops and fruits and thaws the snow-covered pastures. In the Rockies, the Chinook has been known to raise temperature by 35 degrees Fahrenheit within 15 minutes. The occurrence of frequent Chinooks means winter is mild. Cyclonic activity. Tropical cyclones, typhoons, hurricanes, and tornadoes. All these are different kinds of tropical cyclones. They are well-developed low-pressure systems into which violent winds blow. Typhoons occur in the China Sea, tropical cyclones in the Indian Ocean, hurricanes in the West Indian Islands in the Caribbean, tornadoes in the Guinea lands of West Africa, and the southern USA, in which the local name of whirlwind is often applied, and willy willies occur in northwestern Australia. Typhoons occur mainly in regions between 6 degrees and 20 degrees north and south of the equator and are most frequent from July to October. In extent, they are smaller than temperate cyclones and have a diameter of only 50 to 200 miles, but they have a much steeper pressure gradient. Violent winds with a velocity of over 100 miles per hour are common. The sky is overcast, and the torrential downpour is accompanied by thunder and lightning. In the wake of the typhoon, damage is widespread, e.g. in 1922, a typhoon that hurled huge waves onto the Swado coast drowned 50,000 people. In November 2013, Typhoon Haiyan struck Southeast Asia, especially the Philippines, causing devastating damage. It had winds reaching 195 miles, 314 kilometers per hour, making it the most powerful typhoon ever recorded. Haiyan is one of the deadliest typhoons in history, claiming the lives of at least 6,300 people in the Philippines alone. According to the Philippines government's report, some 8.7 million people were affected by the storm. The other tropical cyclones have similar characteristics and differ, perhaps, only in intensity, duration, and locality. Hurricanes have calm, rainless centers where the pressure is lowest, about 965 MB, but around this, the wind strength exceeds force 12 of the Beaufort scale, 75 miles per hour. Figure 129. Dense dark clouds gather and violent stormy weather lasts for several hours. A terrible hurricane struck Barbados in the West Indies in 1780, which nearly destroyed the whole island, tearing down buildings and uprooting trees. More than 20,000 inhabitants were reported dead. Hurricane Mitch was acknowledged as the second deadliest Atlantic hurricane ever recorded, following the Great Hurricane of 1780. In late October 1998, it brought devastating impacts to Central America, especially Honduras and Nicaragua. With peak wind speeds reaching 180 miles (290 kilometers) per hour, the storm had a catastrophic impact. The 13 OSID Typhoon Haiyan in approaches Vietnam in the 118 Part 2. Weather, climate, and vegetation. Figure 129. A tropical cyclone, a hurricane in the West Indies. Death toll surpassed 11,000 people, primarily affecting Honduras and Nicaragua, but also causing fatalities in Guatemala, El Salvador, Mexico, and Costa Rica. Additionally, thousands of individuals were reported missing after the hurricane's passage. Tornadoes are small but very violent tropical and subtropical cyclones in which the air is spiraling at a tremendous speed of as much as 500 miles per hour. A tornado appears as a dark funnel cloud 250 to 1,400 feet in diameter. As a tornado passes through a region, it writhes and twists, causing complete devastation within the limits of its passage. There is such a great difference in pressure that houses virtually explode. Tornadoes are most frequent in spring but can occur at almost any time. Fortunately, they are not common in many countries and their destructive effects are confined to a small area. Tornadoes are most typical of the USA and occur mainly in the Mississippi Basin. Cyclones. These are better known as depressions and are confined to temperate latitudes. The lowest pressure is in the center, and the isobars, as shown in climatic charts, are close together. Depressions vary from 150 to 2,000 miles in extent. They remain quite stationary or move several hundred miles in a day. The approach of a cyclone is characterized by a fall in barometric reading, dull sky, oppressive air, and strong winds. Rain or snow falls and the weather is generally bad. Winds blow inwards into regions of low pressure in the center, circulating in anti-clockwise direction in the northern hemisphere and clockwise in the southern hemisphere. Figure 130a. Precipitation resulting from cyclonic activities is due to the convergence of warm tropical air and cold polar air. Fronts are developed and condensation takes place, forming either rain, snow, or sleet. Anticyclones. These are the opposite of cyclones, with high pressure in the center and the isobars far apart. The pressure gradient is gentle and winds are light. Anticyclones normally herald fine weather. Skies are clear, the air is calm, and temperatures are high in summer but cold in winter. In winter, intense cooling of the lower atmosphere may result in thick fogs. Anticyclonic conditions may last for days or weeks and then fade out quietly. Winds in anticyclones blow outwards and are also subject to deflection, but they blow clockwise in the northern hemisphere and anti-clockwise in the southern hemisphere. Figure 130b. Chaos caused by a typhoon in Hong Kong. Climate 119. L. Figure 130d. A cyclone in the northern hemisphere, close isobars, anticlockwise winds. B. An anticyclone in the northern hemisphere, well-spaced isobars, winds blow in clockwise direction. China type. Monsoonal type. Monsoon forests. Equatorial zone. Warm temperate zone. Cool temperate zone. Tropic of Cancer. 2,372 degrees. Hot zone. Warm J wet forests. Mixed forests. Cold zone Arctic Circle, 6,672 foot. Arctic or polar type T. Tundra vegetation, mosses, lichens. Steppe temperate grassland. 90 degrees north. 65 degrees north. 30 degrees north. Evergreen coniferous forests. Western margin British type. Deciduous forests. Central continent Siberian type. Eastern margin Laurentian type. Mediterranean type. Mediterranean forest and shrubs. OT desert. Rain all year round, summer rain, winter rain. Steppe type. *5 equals JJ caret TTLF. Sudan type. Savanna, tropical grassland. 10 CN. Little rain at any time. Climate types given in black, vegetation, natural vegetation given in blue. Figure 131 scheme of the world's climatic types, with seasonal rainfall and natural vegetation also indicated. 120 Part 2, weather, climate, and vegetation. Climatic types and natural vegetation. It is necessary to divide the world into several climatic zones, each with its own climatic characteristics. Natural vegetation, forests, grasslands, or deserts, crops, animals, and human activities. Though the geographical characteristics may not be absolutely uniform in each climatic type, they have many things in common. Figure 131 gives the scheme of the world's climatic types with their seasonal Rainfall and natural vegetation. Equatorial zone. Approximate. 0°-10° N. And S. 1. Hot, wet equatorial. 2. A. Tropical monsoon. B. Tropical marine. With approximate, total. Rainfall all year round. 80 inches heavy summer rain, 60 inches. Equatorial rainforests. Monsoon forests. Hot zone 10°-30° N and S. 3. Sudan type. 4. Desert. A. Saharan type. B. Mid-latitude. Type. Much summer rain, 70 inches. Rain mainly in summer, 30 inches. Little rain, 5 inches. Savanna, tropical grassland. Desert vegetation and scrubby. Warm temperate zone. 30°-45° N and S. 5. Western margin. Mediterranean type. 6. Central continental. 6. Central continental. Steppe type. 7. Eastern margin. A. China type. B. Gulf type. C. Natal type. Winter rain, 35 inches. Light summer rain, 20 inches. Heavier summer rain, 45 inches. Mediterranean forest and shrub. Steppe or temperate. Grassland. Warm, wet forest and bamboo. Cool temperate. Zone. 45°-65° N and S. 8. Western margin, British type. 9. Central continental, Siberian type. More rain in autumn and winter, 30 inches. Light summer rain, 25 inches. Deciduous forests. Cold zone 65°-90° N and S. 10. Eastern margin. Laurentian type, 11. Arctic or polar. Moderate summer rain, 40 inches. Very light summer rain, 10 inches. Evergreen. Coniferous forests. Mixed forests. Coniferous and deciduous, tundra, mosses, lichens. Alpine zone. 12. Mountain climate, heavy rainfall, variable, alpine pastures, conifers, fern, snow. Questions and exercises. 1. There are many ways in which rain may be caused. Name any 3 of them, and with the aid of annotated diagrams, describe how each of them occurs. 2. Attempt to explain the role played by temperature in climate. What are the various factors that affect the distribution of temperature in the world? Climate 121. 3. Account for the occurrence of any 3 of the following. Make use of any relevant sketches. A. The planetary winds. B. Land and sea breezes. C. Frontal rain. D. Extremes of temperature in continental interiors. E. Horse latitudes. 4. Distinguish the differences between A. Troposphere and stratosphere. B. Steady trade winds and variable westerlies. C. Insolation and radiation. D. Tornado and hurricane. 5. Explain any 3 of the following statements. A. Anticyclones are more frequent in summer. B. Without water vapor and dust in the atmosphere, there would be no weather. C. Sleet is frozen rain. D. Temperature decreases with increasing altitude. E. Winds in the northern hemisphere are always deflected to their right. 6. A. Name 3 different types of rainfall and, with the aid of diagrams, show clearly how the rainfall is caused in each case. B. Describe the instrument used to measure the rainfall of a place, and the way in which the information so obtained is used to calculate the mean annual rainfall. 7. Give reasons for the following. A. Fog at sea often experienced near the Californian coast. B. Many of the hot deserts of the world lie on the west side of a continent, either between 20 degrees north and 30 foot in, or between 20 degrees south and 30 degrees south. C. The surface waters in the northwest Atlantic are cooler than surface waters in the northeast Atlantic. 8. With the aid of diagrams, and by reference to actual examples, describe 3 of the following and state clearly how each of the 3 has been caused. A. Land and sea breezes. B. A rain shadow area. C. Fin, Chinook. Winds. D. Hurricanes, typhoons. 120 Part 2. Weather, climate, and vegetation. Climatic types and natural vegetation. It is necessary to divide the world into several climatic zones, each with its own climatic characteristics, natural vegetation, forests, grasslands or deserts, crops, animals, and human activities. Though the geographical characteristics may not be absolutely uniform in each climatic type, they have many things in common. Figure 131 gives the scheme of the world's climatic types with their seasonal rainfall and natural vegetation. Equatorial zone. Approximate. 0°-10° N and S. 1. Hot, wet equatorial. 2. A. Tropical monsoon. B. Tropical marine. With approximate, total, rainfall all year round, 80 inches heavy summer. Rain, 60 inches. Equatorial rainforests. Monsoon forests. Hot zone 10°-30° N and S. 3. Sudan type. 4. Desert. A. Saharan type. B. Mid-latitude. Type. Much summer rain, 70 inches. Rain mainly in summer, 30 inches. Little rain, 5 inches. Savanna, tropical grassland. Desert vegetation and scrub. Warm temperate. Zone. 30°-45° N and S. 5. Western margin. Mediterranean type. 6. Central continental, steppe type. 7. Eastern margin. A. China type. B. Gulf type. C. Natal type. Winter rain, 35 inches. Light summer rain, 20 inches. Heavier summer rain, 45 inches. Mediterranean, forest and shrub, steppe or temperate, grassland, warm, wet forests, and bamboo, cool temperate, zone, 45°-65° N and S. 8. Western margin, British type. 9. Central continental, Siberian type. More rain in autumn and winter, 30 inches light. Summer rain, 25 inches. Asterisk. Deciduous forests. Cold zone 65°-90° N and S. 10. Eastern margin, Laurentian type. 11. Arctic or polar. Moderate summer rain, 40 inches. Very light summer rain, 10 inches. Evergreen coniferous forests. Mixed forests. Coniferous and deciduous, tundra, mosses, lichens. Alpine. Zone. 12. Mountain climate, heavy rainfall, variable, alpine pastures, conifers, fern, snow. Questions and exercises. 1. There are many ways in which rain may be caused. Name any 3 of them, and with the aid of annotated diagrams, describe how each of them occurs. 1. Attempt to explain the role played by temperature and climate. What are the various factors that affect the distribution of temperature in the world? Climate 121. 3. Account for the occurrence of any 3 of the following. Make use of any relevant sketches. A. The planetary winds. B. Land and sea breezes. C. Frontal rain. D. Extremes of temperature in continental interiors. E. Horse latitudes. 4. Distinguish the differences between A. Troposphere and stratosphere. B. Steady trade winds and variable westerlies. C. Insolation and radiation. D. Tornado and hurricane. 5. Explain any 3 of the following statements. A. Anticyclones are more frequent in summer. B. Without water vapor and dust in the atmosphere, there would be no weather. C. Sleet is frozen rain. D. Temperature decreases with increasing altitude. E. Winds in the northern hemisphere are always deflected to their right. 6. A. Name 3 different types of rainfall and, with the aid of diagrams, show clearly how the rainfall is caused in each case. B. Describe the instrument used to measure the rainfall of a place, and the way in which the information so obtained is used to calculate the mean annual rainfall. 7. Give reasons for the following. A. Fog at sea often experienced near the Californian coast. B. Many of the hot deserts of the world lie on the west side of a continent, either between 20 degrees north and 30 degrees north, or between 20 degrees south and 30 degrees south. C. The surface waters in the northwest Atlantic are cooler than surface waters in the northeast Atlantic. 8. With the aid of diagrams, and by reference to actual examples, describe 3 of the following and state clearly how each of the 3 has been caused. A. Land and sea breezes. B. A rain shadow area. C. Fin, Chinook. Winds. D. Hurricanes, typhoons. The hot, wet equatorial climate. Distribution. The equatorial, hot, wet climate is found between 5 degrees and 10 degrees north and south of the equator. Its greatest extent is found in the lowlands of the Amazon, the Congo, Malaysia, and the East Indies. Further away from the equator, the influence of the onshore trade winds gives rise to a modified type of equatorial climate with monsoonal influences. Within the tropics, the equatorial highlands have a distinctively cooler climate, modified by altitude, such as the Cameron Highlands in Malaysia, the northern Andes, and the Kenyan Highlands in East Africa. Figure 132 shows the regions of the world which experience the hot, wet equatorial climate. Climate. Temperature. The most outstanding feature of the equatorial climate is its great uniformity of temperature throughout the year. The mean monthly temperatures are always around 80 degrees Fahrenheit, with very little variation. There is no winter. Cloudiness and heavy precipitation help to moderate the daily temperature, so that even at the equator itself, the climate is not unbearable. In addition, regular land and sea breezes assist in maintaining a truly equable climate. The diurnal range of temperature is small, and so is the annual range. Figure 133a and 133. Figure 133a and 133b show the RYHDHM of climate experienced in 2 different equatorial regions, one on a lowland, Kuala Lumpur, and the other on a highland, Bogota. The uniformity in temperature is apparent at once. Kuala Lumpur has its hottest month with 80 degrees Fahrenheit 26.6 degrees Celsius, and its coolest month with 78 degrees Fahrenheit 25.5 degrees Celsius. The annual range is not more than 2 degrees Fahrenheit or 1.1 degrees Celsius. The mean monthly temperatures for Bogota are comparatively low because of its altitudinal differences. It is located in the Andes, 8,730 feet, 2,661 meters, above sea level. Re 9132 The hot, wet equatorial regions. The hot, wet equatorial climate Q. Data, 1991 to 2021. JFMMJAS0ND. Average, temp. CC 25.1, 25.7, 26, 26.1, 26.3, 26.2, 26.1, 26, 25.8, 25.7, 25.2, 25.1. F77.278.378.878.978.379.278.978.878.578.277.4 77.2 Precip 209,173,4billion,268,243,174,303,205,305,373,284 and 86,10,11,96,789,12,14,11. Place Kuala Lumpur, 3 degrees north, 102 degrees east, altitude L to the power of J. For 1771. Asterisk annual precipitation I 2,981 millimeters, or 117.4 inch. Annual temperature range III. ZU, ZB.3U, ZO, IU. Figure 133A, Equatorial Climate A Lowland Station. Data, 1991 to 2021. JFMAMJJASN. Average, Tomp. Degree C 12.7, 12.9, 13, 12.9, 12.9, 12.8, 12.8, 13.2, 13.3, 12, 7, 12.5, 12.6. Degree F 54.9, 55.3, 55.4, 55.2, 55.2, 55, 55, 55.8, 56, 54.9, 54.6, 54.7 Precip. MM 81,101,141,152,103 54 48 31 41,110,133 6 and 3 3554 2111453. Figure 133, B, Equatorial Climate, a highland station. Place altitude annual precipitation. Bogota, for degrees. 38 foot S, 74 degrees 15 minutes west, 2,586 m, or 8,485 feet 1,091 millimeters, or 43.0 inch. Annual temperature range 1, for degree F 56.0 to 54.6 degrees Fahrenheit, or 0.8 degrees Celsius, 13.3 to 12.5 degrees Celsius. Its annual range is equally small, also 2 degrees Fahrenheit or 1.1 degrees Celsius, 59 to 57 degrees Fahrenheit or 15 to 13.9 degrees Celsius. The dotted line in the temperature graph shows its temperature reduced to sea level. Statistics taken from the various equatorial stations indicate that the annual range of temperature is small. Singapore, 2.8 degrees Fahrenheit or 1.6 degrees Celsius. Jakarta 2.7 degrees Fahrenheit or 1.5 degrees Celsius, Quito 0.6 degrees Fahrenheit or 1.1 degrees Celsius, Colombo 3.0 degrees Fahrenheit or 1.7 degrees Celsius. Over the oceans, the range is even smaller, e.g. Majuro in the Marshall Islands in the Pacific Ocean records a range in temperature of only 0.6 degrees Fahrenheit or 0.3 degrees Celsius. Precipitation. Precipitation is heavy, between 60 inches and 100 inches, and well distributed throughout the year. There is no month without rain, and a distinct dry season like those of the savanna or the tropical monsoon climates is absent. Instead, there are 2 periods of maximum rainfall, in April and October as shown in Figure 133A and 133B, which occur shortly after the equinoxes. Least rain falls at the June and December solstices. The double rainfall peaks coinciding with the equinoxes are a characteristic feature of equatorial climates not found in any other type of climate. But this simple pattern may be upset by local conditions. E.g. Kota Baru, Kelantan, Malaysia, receives most of its rainfall from the northeast monsoon at the end of the year, and Yangon, Myanmar, from the southwest monsoon between June and September. As one goes further north and south of the equator, particularly in coastal districts open to the influences of the trades, the tendency is towards a monsoonal pattern with the heaviest rainfall coming in the summer months, i.e. June, July, and August. In the northern hemisphere, in December, January, and February in the southern hemisphere. Due to the great heat in the equatorial belt, mornings are bright and sunny. There is much evaporation and convectional air currents are set up, followed by heavy downpours of convectional rain in the afternoons from the towering cumulonimbus clouds. See Chapter 13. Thunder and lightning often accompany the torrential showers, and the amount of rainfall recorded in one single afternoon may be as much as the deserts receive for the entire year. Besides the convectional rainfall, mountainous regions also experience much orographic or relief rain. In addition, there are some intermittent showers from cyclonic atmospheric disturbances caused by the convergence of air currents in the doldrums. 124 Part 2, Weather, Climate, and Vegetation. Forested slopes of Mt. Kinabalu. The lower slopes have been cleared in places for cultivation and settlements. The vegetation on the higher slopes gradually changes in response to lower temperatures. The relative humidity is constantly high, over 80%, making one feel sticky and uncomfortable. The monotonous climate, oppressive and enervating, taxes one as mental alertness and physical capability, though along the coast refreshing sea breezes do bring some relief. As a result, most of the white settlers, whose bodies are attuned to cooler and more varied conditions, take to the cooler highlands whenever they can. Equatorial vegetation. High temperature and abundant rainfall in the equatorial region support a luxuriant type of vegetation, the tropical rainforest in the Amazon lowlands. The forest is so dense and so complete in its vegetational extravagance that a special term selvace is used. Unlike the temperate regions, the growing season here is all the year round. Seeding, flowering, fruiting, and decaying do not take place in a seasonal pattern. So some trees may be in flower while others only a few yards away may be bearing fruit. There is neither drought nor cold to check growth in any part of the year. The characteristic features of the equatorial vegetation may be summarized as follows. 1. A great variety of vegetation. The equatorial vegetation comprises a multitude of evergreen trees that yield tropical hardwood, e.g. mahogany, ebony, greenheart, cabinet woods, and dyewoods. There are smaller palm trees, climbing plants like the lianas or rattan, which may be hundreds of feeding, and epiphytic and parasitic plants that live on other plants. Under the trees grow a wide variety of ferns, orchids, and lolong. 2. A distinct layer arrangement. From the air, the tropical rainforest appears like a thick canopy of foliage, broken only where it is crossed by large rivers or cleared for cultivation. All plants struggle upwards for sunlight, resulting in a peculiar layer arrangement. The tallest trees attain a height of over 150 feet, or about 45 meters, figure 134. Their slender trunks pierce skywards with widespread branches at the top. The smaller trees beneath form the next layer, and the ground is rooted with ferns and herbaceous plants which can tolerate shade. Because the trees cut out most of the sunlight, the undergrowth is not dense. 6 feet interrectal. Layer 30 feet lower layer. 0. 150 feet. Upper layer. Figure 134 sketch to show the 3 distinct layers of an equatorial forest. 3. Multiple species. Unlike the temperate forests, where only a few species occur in a particular area, the trees of the tropical rainforest are not found in pure stands of a single species. It has been estimated that in the Malaysian jungle as many as 200 species of trees may be found in an acre of forest. This has made commercial exploitation of tropical timber a most difficult task. Many of the tropical hardwoods do not float readily on water, and this makes haulage an expensive matter. It is therefore not surprising that many tropical countries are net timber importers. 4. Forest clearings. Many parts of the virgin tropical rainforest have been cleared either for lumbering or shifting cultivation. When these clearings are abandoned, less luxuriant secondary forests, called belukar in Malaysia, spring up. These are characterized by short trees and very dense undergrowth. In the coastal areas and brackish swamps, mangrove forests thrive. The hot, wet equatorial climate 125. Life and development in the equatorial regions. The equatorial regions are generally sparsely populated. In the forests, most primitive people live as hunters and collectors, and the more advanced ones practice shifting cultivation. Food is so abundant in such a habitat that many people worry very little about the life of the next day. There are numerous animals, birds, and reptiles that can be hunted to serve the needs of the community. The ever-flowing rivers and streams provide an inexhaustible supply of fish that the people spear or trap. From the forest, they gather leaves, fruits, nuts, and other forest products. In the Amazon basin, the Indian tribes collect wild rubber. In the Congo basin, the pygmies gather nuts, and in the jungles of Malaysia, the Orang Asli make all sorts of cane products and sell them to people in villages and towns. In the clearings for shifting cultivation, crops like manioc, tapioca, yams, maize, bananas, and groundnuts are grown. When the fertility is exhausted, the clearing is abandoned and they move on to a new plot. Such farming practices are becoming more and more widespread even among backward tribes. With the coming of the Europeans, many large plantations have been established, especially in Java, Sumatra, Malaysia, West Africa, and Central America. The climate has proved to be very favorable for the cultivation of certain crops that are highly valued in the industrial West. The most outstanding is natural rubber, called Hevea brasiliensis. Though it was first discovered in its wild state as para rubber in the Amazon basin, it has since been transplanted to other parts of the equatorial lands and is grown very profitably on large estates. Malaysia and Indonesia are the leading producers, each accounting for more than a third of the world production. The home country, Brazil, exports practically no natural rubber. The problems of tree diseases and the lack of commercial organization of the Indians in the Amazon lowlands have brought about this unexpected shift of rubber cultivation. Another tropical crop that has achieved an amazing success is cocoa. It is most extensively cultivated in West Africa, bordering the Gulf of Guinea. The 2 most important producers are Ghana and Nigeria. There is a keen demand for the crop, and acreages are rapidly on the increase. Most of the crop leaves West Africa for Europe or harvesting oil palm fruits in Malaysia. North America for the cocoa and chocolate industry. From the same area, another crop, oil palm, has done equally well in many countries outside Africa have now taken to its cultivation. Other crops that have been found suitable for the hot, wet equatorial climate and are extensively cultivated are coconuts, sugar, coffee, tea, tobacco, spices, cinchona, bananas, pineapples, and sago. Factors affecting the development of equatorial regions. 1. Equatorial climate and health. Under conditions of excessive heat and high humidity, people are subject to serious physical and mental handicaps. They perspire profusely and lose vigor and energy. In such an enervating environment, they expose themselves to such dangers as sunstroke and to such diseases as malaria and yellow fever. Consequently, their capacity for active work is greatly reduced and their resistance to diseases is much weakened. Unless there is adequate provision for satisfactory sanitation, physical and mental health are bound to be affected. Nowadays, malaria eradication schemes are in progress. In most tropical areas, and vaccines have been developed to counteract other diseases. 2. Prevalence of bacteria and insect pests. The hot, wet climate, which stimulates rapid plant growth, also encourages the spread of insects and pests, as germs and bacteria are more easily transmitted. Through moist air, equatorial conditions are ideal for the survival of such organisms. Insects and pests not only spread diseases but are injurious to crops. They plague both men and animals. 126 Pale 2. Weather, climate, and vegetation. Market gardening in Malaysia. In many parts of the equatorial zone, intensive farming to supply city dwellers with vegetables is profitable. 3. Jungle hinders development and maintenance. The jungle is so luxuriant that it is quite a problem to clear a small patch of it, and even more difficult to maintain it. Long tall grass and thick undergrowth spring up as soon as the shade trees are cut, and unless they are weeded at regular intervals, they may choke crops and overwhelm estates. In the same way, roads and railways constructed through the equatorial lands have to cut through forests, dense thickets, and swamps, and those who build and maintain them encounter wild animals, poisonous snakes, and insects. Once completed, they have to be maintained at a high cost. Many remote parts of the Amazon basin, the Congo, and Borneo are without modern communication lines. The rivers form the only natural highways. 4. Rapid deterioration of tropical soil. It is a misconception that tropical soils are rich in its virgin, untouched state due to heavy leaf fall and the decomposition of leaves by bacteria. A thick mantle of humus makes the soil fairly fertile. This is clear from the shifting cultivators' heavy croppings and their newly cleared ladangs. But once the humus is used and the natural vegetative cover is removed, the torrential downpours soon wash out most of the soil nutrients. The soil deteriorates rapidly with subsequent soil erosion and soil impoverishment. One may quote the Indonesian island of Java as an exception because of its rich volcanic ashes and the energetic local people. In Malaysia, Singapore, and eastern Brazil, much progress has also been made in the development of the tropical lands through systematic planning and the will of the people to succeed. Difficulties in lumbering and livestock farming. As mentioned earlier, but the tropics have great potential in timber resources. Commercial extraction is difficult. The trees do not occur in homogeneous stands. There are no frozen surfaces to facilitate logging, and the tropical hardwoods are sometimes too heavy to float in the rivers, even if these flow in the desired directions. Livestock farming is greatly handicapped by an absence of meadow grass, even on the highlands. The few animals like bullocks or buffaloes are kept mainly as beasts of burden. Their yield in milk or beef is well below those of the cattle in the temperate grasslands. The grass is so tall and coarse that it is not nutritious. In Africa, domesticated animals are attacked by tsetse flies that cause ndana, a deadly disease. The hot, wet equatorial climate. 127. 1. The above two graphs taken from two different stations, Alor Setter in West Malaysia and Mumbai in India, show two different types of climate. A. Name the type of climate experienced in each of the stations. B. Describe the major differences in temperature and precipitation between the two stations. C. In what ways are the rainfall of the two stations similar? 2. What type of climate is characterized by two periods of maximum rainfall? Explain why this is so. What local conditions may upset this normal pattern? 3. Outline the characteristics of the equatorial climate and vegetation, and for any one equatorial region, describe how the inhabitants overcome some of the difficulties posed by the environment. 4. Write brief notes on any three of the following statements about the equatorial regions. A. Cloudiness and heavy precipitation moderate the temperature of the equatorial regions. B. The most prominent feature of the tropical rainforest is its layer arrangement. C. Large-scale livestock farming is unknown in the hot, wet equatorial areas. D. The greatest single drawback to commercial lumbering in equatorial regions is inaccessibility. E. The equatorial environment is best suited to plantation agriculture. 5. On the map of the world, locate the hot, wet equatorial forests. Relate their vegetational characteristics to the climate of the regions. The tropical monsoon and tropical marine climates. Distribution. We have learned in Chapter 13 that some parts of the world experience seasonal winds like land and sea breezes, but on a much larger scale. These are the tropical monsoon lands with onshore wet monsoons in the summer and offshore dry monsoons in the winter. They are best developed in the Indian subcontinent, Myanmar, Thailand, Laos, Cambodia, parts of Vietnam, and South China and northern Australia. Outside this zone, the climate is modified by the influence of the onshore trade winds all the year round and has a more evenly distributed rainfall. Such a climate, better termed the tropical marine climate, is experienced in Central America, West Indies, northeastern Australia, the Philippines, parts of East Africa, Madagascar, the Guinea Coast, and eastern Brazil. Figure 135. Climatic conditions in tropical monsoon lands. The basic cause of monsoon climates is the difference in the rate of heating and cooling of land and sea. In the summer, when the sun is overhead at the Tropic of Cancer, the great land masses of the northern hemisphere are heated. Central Asia, backed by the lofty Himalayan ranges, is more than 15 degrees Fahrenheit hotter than its normal temperature, and a region of intense low pressure is set up. The seas, which warm up much slower, remain comparatively cool. At the same time, the southern hemisphere experiences winter, and a region of high pressure is set up in the continental interior of Australia. Winds blow outwards as the southeast monsoon to Java, and after crossing the equator are drawn towards the continental low-pressure area, reaching the HIG. 135. The tropical monsoon and marine regions. The tropical monsoon and tropical marine climates. 129. Figure 136. A. Summer conditions in Asia. Southwest monsoon in Indo-Pakistan is onshore in the rainy season July. Seasons are distinguishable, as illustrated in Figure 137. A. 1. The cool, dry season, October to February. Temperatures are low 76 degrees Fahrenheit 24.4 degrees Celsius in Mumbai, and only 50 degrees Fahrenheit 10 degrees Celsius in Punjab, with heavy sinking air. Frost may occur at night in the colder north. The center of high pressure is over the Punjab. Outblowing dry winds, the northeast monsoon, bring little or no rain to the Indian subcontinent. However, a small amount of rain falls in Punjab from cyclonic sources, and this is vital for the survival of winter cereals. Where the northeast monsoon blows over the Bay of Bengal, it acquires moisture and thus brings rain to the southeastern tip of the peninsula at this time of the year. For instance, in Chennai, 50 inches, 1,270 millimeters, of rain falls during October and November, accounting for half its annual rainfall. 2. The hot dry season, March to mid-June. As can be seen from Figure 137. A. The temperature rises sharply with the sun's northward shift to the Tropic of Cancer. Mumbai has a mean May temperature of 84 degrees Fahrenheit 29 degrees Celsius, which is considered moderate. For many parts of India, are even hotter. The heat is so great that schools and colleges are closed. The stifling heat and the low relative humidity make Figure 136. B. Winter conditions in Asia. Northeast monsoon in Indo-Pakistan is offshore in the cool, dry season, January. Indian subcontinent as the southwest monsoon, as shown in Figure 136. A. In the winter, conditions are reversed. The sun is overhead at the Tropic of Capricorn. Central Asia is extremely cold, resulting in rapid cooling of the land. A region of high pressure is created. Without blowing winds, the northeast monsoon. On crossing the equator, the winds are attracted to the low-pressure center in Australia and arrive in northern Australia as the northwest monsoon, Figure 136. B. In other parts of the world which experience a tropical monsoon climate, a similar seasonal reversal of wind directions occurs. The seasons of tropical monsoon climate. In regions like the Indian subcontinent which have a true tropical monsoon climate, 3 distinct. Data 1991 to 2021. Figure 137. A. Tropical monsoon climate. Place Mumbai, India, ISSN, 73 inch. Altitude 12 m or 39 feet. Annual precipitation 2.012 none or 79.2 inch. Annual temperature range 9.1 carat, 84.2 to the power of -75, RF, or 5.1 foot C, 29.0 to 0, 23.9 to 0. 130 Part 2, Weather, Climate, and Vegetation. Outdoor life, almost unbearable. Day temperatures of 95 degrees Fahrenheit 35 degrees Celsius are usual in central India, and the mean temperature in Sindh, Pakistan may be as high as 11.0 degree F, 43 degrees Celsius. Coastal districts are a little relieved by sea breezes. There is practically no rain anywhere. By May, the temperature is so high that an intense low-pressure zone is set up in northwest India. Dust storms are frequent, followed by long-awaited rainstorms that break by the middle of June. The transitional period between no rain and plenty of rain is over. 3. The rainy season, mid-June to September. With the burst of the southwest monsoon in mid-June, torrential downpours sweep across the country to the delight of everybody. Almost all the rain for the year falls within this rainy season. For example, in Mumbai, 19 inches, 487 millimeters, are recorded in June. 26 inches, 661 millimeters, in July, 18 inches, 459 millimeters. In August, and a further 11 inches, 300 millimeters, in September. As much as 95% of the annual rainfall is concentrated within 4 months. This pattern of concentrated heavy rainfall in summer is a characteristic feature of the tropical monsoon climate. The torrential downpours have an immediate impact on the local temperature. They lower the temperature considerably. The mean Temperature for Mumbai is 84.2 degrees Fahrenheit or 29 degrees Celsius in May, but only 78.6 degrees Fahrenheit or 25.9 degrees Celsius in July. In the north, the drop is even greater, as much as 13 degrees Fahrenheit, 10.5 degrees Celsius. Some of the windward stations on the Himalayan foothills have very heavy rainfall, though this is partly orographic. Cherrapunji has an average annual rainfall of 425 inches, 10,795 millimeters, and a record of 1,042 inches, 26,467 millimeters, in 1861. The retreating monsoon. The amount and frequency of rain decreases towards the end of the rainy season. It retreats gradually southwards after mid-September until it leaves the continent altogether. The Punjab plains, which receive the southwest monsoon earliest, are the first to see the withdrawal of the monsoon. The skies are clear again and the cool, dry season returns in October, with the outblowing northeast monsoon. The role of monsoons in India is vital in its economy. A late monsoon, or one that ends far too early, will condemn large stretches of agricultural land to drought. There will be widespread famine from crop failure, and thousands will perish. When there is too much water from the rainy monsoons, severe floods occur, destroying both crops and lives and disrupting communications. In no part of the world has the climate affected people's way of life so profoundly as in the monsoon lands. The tropical marine climate. This type of climate is experienced along the eastern coasts of tropical lands, receiving steady rainfall from the trade winds all the time. The rainfall is both orographic, where the moist trades meet upland masses as in eastern Brazil, and convectional due to intense heating during the day and in summer. Its tendency is towards a summer maximum as in monsoon lands, but without any distinct dry period. Figure 137b shows the rhythm of climate as experienced in Cairns, on the eastern coast of Queensland, under the constant influence of the southeast trade winds, and in summer. Also affected by the tropical monsoons. Its wettest months are in January, 9.7 inches or 246 millimeters, February, 10.2 inches or 259 millimeters, March, 8.7 inches or 222 millimeters, and April, 4.3 inches or 108 millimeters, which is summer in the southern hemisphere. Approximately 70% of the annual rainfall is concentrated in the 4 summer months. Data, 1991 to 2021. XJFM AMJ JAS 0 ND. Average, asterisk C 25.9, 25.9, 25.1, 23.8, 22.1, 20.5, 19.7, 20.2, 21.8, 23.3, 24.6, 25.6 temp. Degree F 78.6, 78.6, 77.2, 74.8, 71.8, 68.9, 67.5, 68.4, 71.2, 73.9, 76.3, 78.1 per mm, 246 billion, 259 million, 222,108.50. For 37, 33, 29, 20, 38, 66, 159. 110 VIP. In 910 84 21 110126. Figure 137b, tropical marine climate. Place altitude, annual precipitation. Place altitude, annual precipitation. Cairns, Australia, 17 QS. 145 degrees 42 minutes east, coastal lowland, about 7 m or 22 feet, 1,271 millimeters or 50.0 inches. Annual temperature range 11.rf. 78.6 cf, 67.5 degree F, or 6.2 degrees C, 25.9 to 19.7 degrees Celsius. The tropical monsoon and tropical marine climates 131. There is no month without any rainfall. The range of temperature is typical of the tropical latitudes, with a maximum of 82 degrees Fahrenheit 27.8 degrees Celsius in January and a minimum of 70 degree F 21.1 degrees Celsius in July. A range of 12 degrees Fahrenheit 6.7 degrees Celsius for the year. Due to the steady influence of the trades, the tropical marine climate is more favorable for habitation, but it is prone to severe tropical cyclones, hurricanes or typhoons, as mentioned in Chapter 13. Tropical monsoon forests. The natural vegetation of tropical monsoon lands depends on the amount of the summer rainfall. Trees are normally deciduous because of the marked dry period, during which they shed their leaves to withstand the drought. Where the rainfall is heavy, e.g. in southern Myanmar, peninsular India, northern Australia and coastal regions with a tropical marine climate, the resultant vegetation is forest. The forests are more open and less luxuriant than the equatorial jungle, and there are far fewer species. Most of the forests yield valuable timber and are prized for their durable hardwood. Amongst these, teak is the best known. Myanmar alone accounts for as much as 3/4 of the world's production. It is such a durable timber that it is extensively used for shipbuilding, furniture, and other constructional purposes. Other kinds of timber include sal, acacia, and some varieties of eucalyptus in northern Australia. Together with the forests are bamboo thickets, which often grow to great heights, figure 138. With a decrease in rainfall in summer, the forests thin out into thorny scrubland or savanna with scattered trees and tall grass. In parts of the Indian subcontinent, rainfall is so deficient. Figure 138 main features of a monsoon forest. That semi-desert conditions are found. Monsoonal vegetation is thus most varied, ranging from forests to thickets and from savanna to scrubland. Agricultural development in the monsoon lands. Much of the monsoon forest has been cleared for agriculture to support the very dense population. The cultural landscape throughout the length and breadth of the monsoon lands deeply reflects the intensity of people's quest for subsistence. Wherever possible, crops are grown. The plains are plowed, and the hills are terraced to provide farmland. Farms are small and the people are forever land hungry. In their quest for land, they have removed the natural vegetation sometimes, wantonly resulting in acute soil erosion. This is particularly serious in the Indian subcontinent, which has a very high density of population with a rapid rate of growth. But in the plains, the same piece of land may have been tilled for generations with little or no replenishment, and yet able to yield fairly reasonable returns. Tropical agriculture, dependent on natural rainfall and a large labor force, reaches its greatest magnitude in the monsoon lands. The soil provides the basis for the livelihood of millions. Farming is not only the dominant occupation of the greater part of the people, but also forms the mainstay of the economy of the Indian subcontinent. China, Southeast Asia, Eastern Brazil, and the West Indies. The following types of agriculture are recognizable. 1. Wet paddy cultivation. Rice is the most important staple crop and is grown in tropical lowlands wherever the rain exceeds 70 inches, 1,778 millimeters. It is perhaps the most characteristic crop of the monsoon lands, and its total acreage far exceeds that of any other crop. In fact, very few areas outside the influence of the monsoons ever take to the cultivation of paddy. There are two main varieties. The wet paddy, which is mainly grown on lowlands and flooded fields or in terraced uplands, and the dry paddy grown in regions of lower rainfall. A minimum of 50 inches, 1,270 millimeters, of rainfall is required during the growing season. Droughts and floods that are almost inseparable from a monsoonal type of climate can be very detrimental to its cultivation. Irrigation water from rivers, canals, dams, or wells is extensively used in the major rice. 132 Part 2. Weather, climate, and vegetation. Producing countries. Other food crops like maize, millet, sorghum, wheat, gram, and beans are of subsidiary importance. They are cultivated in the drier or cooler areas where rice cannot be grown. 2. Lowland cash crops. A wide range of lowland tropical cash crops are cultivated for the export market after local needs have been met. The most important crop in this category is sugarcane. As much as 2/3 of the world's sugar production comes from tropical countries. Sugar is either grown on plantations or on small holdings wherever rainfall and sunshine are abundant. Some of the major producers include India, Java, Taiwan, Cuba, Jamaica, Trinidad, and Barbados. Jute is confined almost entirely to the Ganges, Brahmaputra Delta, in India and Bangladesh. It has long been a leading hard fiber for the manufacture of sacks gunny. Manila hemp abaca is a product of the Philippines, particularly of Mindanao. It is used to make high-quality rope. Other crops include indigo, still cultivated in India and Java, cotton, a major export of the Indian subcontinent, and bananas, coconuts, and spices. Harvesting sugarcane in Queensland, Australia. 3. Highland plantation crops. The colonization of tropical lands by Europeans gave rise to a new form of cultivated landscape in the cooler monsoonal highlands. This is the cultivation of certain tree crops in tropical plantations. Thousands of acres of tropical upland forest were cleared to make way for plantation agriculture, in which tea and coffee are the most important crops. These were luxuries in Europe in the 18th century, and the products of the plantations were originally meant only for export to the mother countries where there was a great craze for the beverages. Later, the local people also got into the habit of drinking them, and they fast became necessities. Both the beverages became so popular in and out of the tropics that there was great expansion in their acreages, both in regions with a tropical monsoon climate and the tropical marine climate. Coffee originated in Ethiopia and Arabia, where it is still grown, but Brazil now accounts for about 40% of the world's production of coffee. It is mainly grown on the eastern slopes of the Brazilian plateau. The crop is also cultivated on the highland slopes between 2,000 feet, or about 600 m, and 4,500 feet, or about 1,400 m, in the central American states, India, and eastern Java. Tea picking in a plantation in Sri Lanka. Tea originated in China and is still an important crop there, but as it requires moderate temperatures, about 60 degrees Fahrenheit or about 15 degrees Celsius, heavy rainfall, over 60 nbs or 1,500 millimeters, and well-drained highland slopes, it thrives well in the tropical monsoon zone, but preferably at a higher altitude. The best regions are thus the Himalayan foothills of India and Bangladesh, the central highlands of Sri Lanka and western Java, from all of which it is exported. In China, tea is grown mostly for local consumption. 4. Lumbering. Wherever there are tropical forests which still have not been felled to make way for the plow, lumbering is undertaken in the more accessible areas. This is particularly important in continental Southeast Asia. Of the tropical deciduous trees, teak, of which Myanmar is the leading producer, is perhaps the most sought after. It is valuable on account of its great durability, strength, immunity to shrinkage, fungus attack, and insects. It is grown in hilly districts up to 3,000 feet, about 900 m, in altitude with a moderate rainfall. Under government supervision, teak trees which are cut have to be replaced. This is the only way. The tropical monsoon and tropical marine climates 133. To ensure the steady supply of the timber, which is the second greatest money earner for Myanmar after rice. In northern Myanmar, in the region of the Chindwin River, there are large teak plantations. It takes as long as 100 years for a teak tree to mature into commercial timber. Green teak logs are so heavy that they will not float readily on water. It is therefore necessary to poison the tree several years before actual felling, so that it is dry and light enough to be floated down the Chindwin and the Irrawaddy to reach the sawmills at Yangon. The individual logs are tied in rafts and guided downstream by crews of men and tugboats. Teak logs are also floated downstream and loaded on trucks to be transported to various destinations. In some places, elephants are still used for logging and carrying timber in the forests. It takes something like 18 months or another season for a log of teak to reach Yangon to be sawn into planks for export. 5. Shifting cultivation. This most primitive form of farming is widely practiced. Instead of rotating the crops in the same field to preserve fertility, the tribe's people move to a new clearing when their first field is exhausted. The clearing, or field, in the midst of the jungle is usually made by fire, which destroys practically everything in its way. After planting, little attention is paid to the field either. Questions and exercises. In weeding or manuring, the crops are left entirely to the care of nature. The farmers use simple hoes and sticks for plowing and seeding. Draft. Animals are unknown and labor is exclusively manual. Their needs are so basic that every farmer produces much the same range of crops as their neighbors. Maize or corn, dry paddy, yams, tapioca, sweet potatoes, and some beans are the most common crops. Farming is entirely for subsistence, i.e. everything is consumed by the farmer's family. It is not traded or sold. As tropical soils are mainly laticolic, rapidly leached, and easily exhausted, the first crop may be bountiful, but the subsequent harvests deteriorate. A few years later, the field has to be abandoned and a new patch cleared elsewhere. This system of a short period of cultivation alternating with long periods of fallowing is probably the best V/I of using land in many parts of the tropics where manuring is unknown. Shifting cultivation is so widely practiced amongst indigenous peoples that different local names are used in different countries. For example, Ladong in Malaysia, Tanya in Myanmar, Tamrai in Thailand, Kainjin in the Philippines, Huma in Java, China in Sri Lanka, and Milpa in Africa and Central America. 1. The climate of India is characterized by 3 distinct seasons. Explain why this is so. 2. With the aid of diagrams or sketch maps, explain any 3 of the following statements. A. The east coasts of continents within the tropics have much heavier rainfall than the interiors or the west coasts. B. The tropical monsoon climate is, in fact, land and sea breezes on a continental scale. C. Near the equatorial latitudes, the period of maximum rainfall is closely related to the movements of the overhead sun. D. There is a marked difference in temperature between the east and west coasts of countries in latitudes 20 degrees to 35 degrees north. 3. In which parts of the monsoon lands has the natural vegetation been removed by men? Describe and explain the uses made of the cleared lands. 4. Name the types of climate which have A. Rain mainly in winter, B. Rain only in summer, C. Rain throughout the year. I. Describe the characteristic climatic features of any 2 of the types you have named. 2. For any one of them account for its rainfall distribution. 5. Contrast the essential characteristics of plantation agriculture and shifting cultivation. The savanna or Sudan climate. Distribution. The savanna or Sudan climate is a transitional type of climate found between the equatorial forests and the trade-wind hot deserts. It is confined within the tropics and is best developed in the Sudan where the dry and wet seasons are most distinct, hence its name the Sudan climate. The belt includes West African Sudan and then curves southwards into East Africa and Southern Africa north of the Tropic of Capricorn as shown in Fig. 139. In South America, there are 2 distinct regions of savanna. North and south of the equator, namely the Llanos of the Orinoco Basin and the Campos of the Brazilian highlands. The Australian savanna is located south of the monsoon strip, running from west to east north of the Tropic of Capricorn. Climate of the Sudan type. Rainfall. The Sudan type of climate is characterized by an alternate hot, rainy season and cool, dry season, as illustrated in Figure 140a. In the Northern Hemisphere, the hot, rainy season normally begins in May and lasts until September, as in Kano, Nigeria. The rest of the year is cool and dry. The annual rainfall for Kano, which is located at a height of 1,588 feet, 484 meters, above sea level, is 26.5 inches, 674 millimeters, and is almost entirely concentrated in the summer. But the amount varies from 48 inches, 1,220 millimeters, at Banjul, earlier known as Bathurst, in Gambia on the coast to only 2.8 inches, 70 millimeters, at Khartoum, in Sudan in the interior. Both the length of the rainy season and the annual total rainfall decrease appreciably from the equatorial region polewards towards the desert fringes. On the whole, the annual precipitation is Figure 139 regions of Sudan climate with savanna or tropical grasslands. The savanna or Sudan climate 135. F degree C 10440. Inch degree F degree C. 3595. 30. 86. 2568 2059 1550 10. Temperature 245 9.6. 210 8.3 175 6.9 145.5 105 4.12.8. 70. 0 JFM AM JJ Assant. 3077 2568 2059 1550 1041 5. Temperature precipitation 86. 200 160 120 8040. ASOND. FM AMJ. MM. 240 inch. 9.47.96.3 4.73.11.6. 1.4. 41.5. 0.0. 0. 32. 35. JFM AMJ JASOND. Average C 21.6, 24.6, 28, 30.9, 30.9, 28, 8, 26.2, 25.1, 26.1, 26.9, 25.1, temp. Degree F 70.9, 76.3, 82.4, 87.5, 87.7, 83.9, 79.1, 77.1, 79.1, 80.4, 77.2, 71.6 precip. MM 000 436 75 billion 171 million 242,122 2400. In 00001 269 4000 data 1991 to 2021. 000.032. 1 JF AJJIASOND. Average degree C 20.2 20.1 I9 data 18.1 16.3 143 13.9 16.6 19.9 21.8 21.5 20.6 temp. Degree F 68.3 68.2 67.3 64.66 T.4 57.7 57.160 1.9 67.8 71.2 70.3 69 1. Preculp. MM 229,153,132 72 21 322 33 135 in 96 31000000 037. Data 1991 to 2021. Place Harare, Zimbabwe, 17 foot 45 s, 31 altitude 1,479 m or 4,852 feet. Annual precipitation 824 mm or 32.4 inches, 14.1 degree F, 71.2 to 57.1 degrees Fahrenheit, or annual temperature range G, C, 21 to the power of 13 G, C. Place Kano, Nigeria, 11 degrees 58 minutes north, 8 degrees 20 minutes east, altitude 484 m or 1,588 feet. Annual precipitation 674 millimeters or 26.5 inches. Annual temperature range 16.8 degrees Fahrenheit, 87.7 to 70.9 degrees Fahrenheit, or 9.3 degrees Celsius, 30.9 C, 21.6 degrees Celsius. Figure 140, A, the savanna or Sudan climate in the northern hemisphere. Figure 140, B, the savanna or Sudan climate in the southern hemisphere. Less than that of the tropical monsoon climate, and the length of the wet and dry seasons differs with the locality. In the southern hemisphere, the rainy season is from October to March, the southern summer, as shown in Figure 140, B, of Harare, earlier known as Salisbury, in Zimbabwe, earlier known as Rhodesia. Its annual precipitation of 32.4 inches, 824 millimeters, also varies much from year to year. The monthly temperature hovers between 70 degrees Fahrenheit and 90 degrees Fahrenheit, 21 to 32 degrees Celsius, for lowland stations. An annual temperature range of 20 degrees Fahrenheit 11 degrees Celsius is typical, but the range increases as one moves further away from the equator. It is, however, interesting to note that the highest temperatures do not coincide with the period of the highest sun, e.g. June in the northern hemisphere, but occur just before the onset of the rainy season, i.e. April in Kano and October in Harare, earlier, Salisbury. There is also a distinct drop in temperature in the rainy period due to the overcast sky and the cooler atmosphere. Days are hot, and during the hot season, noon. Temperatures of over 100 degrees Fahrenheit, about 37 degrees Celsius, are quite frequent. When night falls, the clear sky, which promotes intense heating during the day, also causes rapid radiation in the night. Temperatures drop to well below 50 degrees Fahrenheit, 10 degrees Celsius, and night frosts are not uncommon at this time of the year. This extreme diurnal range of temperature is another characteristic feature of the Sudan type of climate. Winds. The prevailing winds of the region are the trade winds, which bring rain to the coastal districts. They are strongest in the summer, but are relatively dry by the time they reach the continental interiors or the western coasts of the continents, so that grass and scattered short trees predominate. In West Africa, the northeast trades, in fact, blow offshore from the Sahara Desert and reach the Guinea coast as a dry, dust-laden wind, called locally the harmattan, meaning the doctor. It is so dry that its relative humidity seldom exceeds 30%. The doctor provides a welcome relief from the damp air of the Guinea lands by increasing the rate of evaporation with resultant cooling effects, but it is such a dry, dusty wind that, besides ruining the crops, it also stirs up a thick, dusty haze and impedes inland river navigation. 136 Part 2 Weather, Climate, and Vegetation. Natural vegetation. Tyne savanna landscape is typified by tall grass and short trees. It is rather misleading to call the savanna tropical grassland, because trees are always present with the luxuriant tall grass. The terms parkland or bushveld perhaps describe the landscape better. Trees grow best towards the equatorial humid latitudes or along riverbanks, but decrease in height and density away from the equator, figure 141. They occur in clumps or as scattered individuals. The trees are deciduous, shedding their leaves in the cool, dry season to prevent excessive loss of water through transpiration, e.g. acacias. Others have broad trunks, with water-storing devices to survive through the prolonged drought, such as baobabs and bottle trees. Trees are mostly hard, gnarled and thorny, and may exude gum, like gum arabic. Many trees are umbrella-shaped, exposing only a narrow edge to the strong winds. Palms which cannot withstand the drought are confined to the wettest areas or along rivers. Vegetative luxuriance reaches its peak in the rainy season, when trees renew their foliage and flower. In true savanna lands, the grass is tall and coarse, growing 6 to 12 feet, 1.8 to 3.6 m, high. The elephant grass may attain a height of even 15 feet, 4.5 meters. The grass tends to grow in compact tufts and has long roots which reach down in search of water. It appears greenish and well-nourished in the rainy season, but turns yellow and dies down in the dry season that follows. The grass lies dormant throughout the long, rainless period and springs up again in the next rainy season. In between the tall grass are scattered short trees and low bushes. As the rainfall diminishes towards the deserts, the savanna merges into thorny scrub. In Australia, this scrubland is particularly well represented by a number of species: mallee, mulga, spinifex grass, and other bushes. Giraffes in the savanna. The vegetation is of grass and scattered trees. Animal life of the savanna. The savanna, particularly in Africa, is the home of wild animals. It is known as the big game country, and thousands of animals are trapped or killed each year by people from all over the world. Some of the animals are tracked down for their skins, horns, tusks, bones, or hair. Others are captured alive and sent out of Africa as zoo animals, laboratory specimens, or pets. There is such a wealth of animal life in Africa that many of the animal films that we see at the cinema are actually taken in the savanna. There are, in fact, two main groups of animals in the savanna: the grass-eating herbivorous animals and the flesh-eating carnivorous animals. The herbivorous animals are often very alert and move swiftly from place to place in search of green pastures. They are endowed with great speed to run away from the savage flesh-eaters that are always after them. The leaf and grass-eating animals include the zebra, antelope, giraffe, deer, gazelle, elephant, and okapi. Many are well camouflaged species, and their presence amongst the tall greenish-brown grass cannot be easily detected. The giraffe with such a long neck can locate its enemies a great distance away, while the savanna. Why 141 changes in vegetation from savanna to desert. The savanna or Sudan climate 137. Elephant is so huge and strong that few animals will venture to come near it. It is well equipped with tusks and trunk for defense. The carnivorous animals like the lion, tiger, leopard, hyena, panther, jaguar, jackal, lynx, and puma have powerful jaws and teeth for attacking other animals. Their natural colorings of light yellowish-brown, often with stripes like the tiger or spots like the leopard, match perfectly with the tawny background of the savanna. They often hide themselves in shady spots up in the branches or amidst the tall bushes, and many wild animals, as well as hunters themselves, are caught unawares. In this manner, along rivers and in marshy lakes are numerous species of reptiles and mammals, including crocodiles, alligators, monitors, and giant lizards, together with the larger rhinoceros and hippopotamus. In such an animal paradise, there are many diverse species of birds, snakes, butterflies, moths, and insects. In many parts of East and South Africa, national parks have been set up which control the killing of animals. This is a necessity if many of the rare species of animals are to be preserved and protected from wanton shooting. In Kenya, there are large hotels and viewing towers built in the heart of the savannah with special transport arrangements to bring tourists in to see the animals in their natural settings. This is a progressive step made in conserving animal life of the savannah and should be encouraged. Human life in the savannah. Within the savannah lands of the tropics live many different tribes who are either cattle pastoralists like the Maasai of the East African Plateau or settled cultivators like the Hausa of northern Nigeria. We shall examine the life of these two groups of people more closely and see how they adapt themselves to the savannah environment. The Maasai, cattle pastoralists. The Maasai are a nomadic tribe who once wandered with their herds of cattle in the central highlands of East Africa, in Kenya, Tanzania, and Uganda. At the height of their power, in the mid-19th century, the Maasai occupied most of the Great Rift Valley and adjacent lands. In Kenya, the British evicted the Maasai with a treaty in 1904, followed by another treaty in 1911. This led to a cut down in Maasai lands by 60%, thus confining them to Narok and Kajiado districts of the present day. In the 1940s in Tanzania, the Maasai were forced to leave their fertile lands between Mount Kilimanjaro and Mount Meru, as well as areas close to the Ngorongoro. The Maasai also had to give up more grazing land for the creation of wildlife parks and national reserves. But today, after a century's tribal clashes, epidemics, natural deaths, and displacements, they are now mainly confined to the 15,000 square miles, 38,850 square kilometers, of Maasai reserves in Kenya and Tanzania. Their numbers are now estimated to be 900,000. Their old grazing grounds in the Kenyan highlands were taken over first by the immigrant white settlers for plantation agriculture, coffee, tea, cotton, and dairy farming, and later, after independence, by African farmers. They now occupy the less favored areas of savanna in which are graze something like 1 million cattle and perhaps twice as many sheep and goats. On the lower slopes of the East African Plateau, where rainfall is as low as 20 inches, 508 millimeters, and there are long periods of drought, the grass seldom reaches a foot high and is not nutritious. When there is a drought, the Maasai move upwards to the higher and cooler plateau regions in which their herds can graze on the better pastures. They build circular huts with sticks, bushes, and mud for temporary shelter. The cattle are kept in a special enclosure at night and are protected from attack by wild animals by a strong fence. The cattle kept by the Maasai are the zebu, cattle with humps and long horns. They are treated with great respect and affection and are never slaughtered for food or for sale. The meat from cattle is only consumed when they die a natural death from old age or disease. They are never used as draft animals and are kept entirely for the supply of milk and blood. Milking is done by women before daybreak and at dusk. The yield is extremely low by any standard, and usually not more than 2 pints are obtained at a single milking. The milk is drunk either fresh or sour. Cheese making is still not known to the Maasai. Blood from both bulls and cows is drunk. This is obtained by tying a leather cord around the neck of an animal until the veins swell. A vein is then punctured by a special arrowhead, and the blood gushes out and is collected and drunk fresh or clotted. 138 Part 2. Weather, Climate, and Vegetation. Traditional Maasai people's lifestyle concentrates on their cattle, which make up the primary source of food. Cattle are kept by every Maasai family. They are considered far more valuable than anything else and are symbols of wealth. The richest man has the largest herds of cattle, leaving aside the sheep and goats which, to the Maasai tribes, are of little significance. Cattle are used in payment for wives, and when the father of a family dies, the mother divides the livestock among the sons. The Maasai will not slaughter the cattle for food, so from the agricultural tribes such as the Kikuyu of Kenya, they obtain a small amount of millet, bananas, groundnuts, and vegetables. Because the number of cattle is more important to the Maasai than their quality, the Maasai will not willingly sell their cattle. So, the large area of land which they occupy in East Africa is not used profitably. Great efforts are being made to get the Maasai to care for their animals properly and raise them for sale, keeping only as many animals as the pasture can support. Many Maasai are responding to modern techniques, but the majority stubbornly continue in their old ways. Amongst most of the other African tribes, pastoralism exists side by side with agriculture. The Hausa, settled cultivators. The Hausa are a tribe of settled cultivators who inhabit the savanna lands of the Bachi Plateau of northern Nigeria. They number almost 6 million and have been organized in settled agricultural communities for hundreds of years. They are more advanced in their civilization and ways of life than many of the other African Negroes. The Hausa live in towns or villages. The ancient Hausa city of Kano, with a population of 135,000, has long been a focus of routes and trade. They do not practice shifting cultivation as many tribes do. Instead, they clear a piece of land and use it for several years, growing a wide range of crops like maize, millet, guinea corn, groundnuts, bananas, and beans. Some Hausa also cultivate non-food crops, e.g. cotton and tobacco. When the fertility of the plot declines, they plant a new field and allow the old one to lie fallow. This enables natural forces to act on it until fertility is restored. New crops are then sown in the old plot again, and the harvests are good. In this manner, the Hausa rotate their crops between different fields at different parts of the year, which is a technique employed in advanced agricultural societies. The Savannah or Sudan climate 139. Besides cultivation, the Hausa also make use of domesticated animals. Herds of cattle and goats are kept for both milk and meat, but they are only subsidiary to crop cultivation. Though they do not contribute much to the income of the Hausa, because of their small numbers, their manure is used to fertilize the fields. Poultry are raised by the villagers, and both eggs and chicken are consumed. The farming year is very closely related to the season of rainfall. In Nigeria, the rainy season begins in May and lasts till September. The annual precipitation is about 40 inches, 1,016 millimeters, falling entirely in summer. The Hausa sow the seeds in late April when sufficient rain has fallen. The seedlings sprout with the heavy rain and grow rapidly throughout the rainy season. Weeding with traditional hoes is done at regular intervals till the crops are ripened and harvested in September, the beginning of the cool, dry season. The tall brown bushes are burnt down by the farmers in preparation for new fields for the following year. Sometimes fires may be caused by the dry, dusty harmattan. Problems, prospects, and development of the savanna. There is little doubt that in years to come, world population pressure and the need for greater food production will necessitate greater economic development of the savanna. The deserts or the freezing tundra form climatic barriers too formidable for large-scale human intervention to take place. But the savanna lands with an annual rainfall of over 30 inches, 762 millimeters, and without any severe cold, should be able to support a wide range of tropical crops. Pioneer settlements in Central Africa, Northern Australia, and Eastern Brazil have shown that the savannas have immense agricultural potential for plantation agriculture of cotton, cane sugar, coffee, oil palm, groundnuts, and even tropical fruits. Tropical Queensland, despite its scarcity of labor force, has been very successful in its attempts to develop its huge, empty land. The newly independent states of Kenya, Uganda, Tanzania, and Malawi have already taken to large-scale production of cotton and sisal hemp. Both crops thrive well in savanna conditions. In West Africa, the commercial cultivation of groundnuts, oil palm, and cocoa have been gradually extended into the savanna lands. New drought-resistant varieties will have to be introduced into these newly emergent countries to increase their foreign earnings and such. Tropical raw materials. In the cooler highlands, temperate crops have been successfully raised. But farming in the savanna land is not without natural hazards. Droughts may be long and trying, as rainfall is often unreliable, unless countermeasures can be taken in the form of adequate provision for irrigation, improved crop varieties, and scientific farming techniques suitable for the tropical grasslands. Crop failures can be disastrous for the people, who have very little to fall back on. The Sudan climate, with distinct wet and dry periods, is also responsible for the rapid deterioration of soil fertility. During the rainy season, torrential downpours of heavy rain cause leaching, in which most of the plant nutrients, such as nitrates, phosphates, and potash, are dissolved and washed away. During the dry season, intense heating and evaporation dry up most of the water. Many savanna areas therefore have poor lateritic soils which are incapable of supporting good crops, unless the soil is properly conserved through regular manuring, weeding, and careful maintenance. Crop yields are bound to decline. The savanna is said to be the natural cattle country, and many of the native people are, in fact, herdsmen or pastoralists. Cattle are kept in large numbers and fed on the tall grass or the bushes. They provide the people with milk, blood, and meat. Unfortunately, the native zebu cattle are bony and yield little meat or milk. They often fall victim to tropical diseases, e.g. the ngana or sleeping sickness earned by the tsetse fly in Africa. The export of either beef or milk from the tropical grasslands is so far not important. It seems necessary to introduce temperate cattle, such as the English Shorthorn, Frisian, or Guernsey, to cross with the tropical zebu if cattle rearing is to be successful in the savanna. In fact, a start has already been made in tropical Queensland, which has become Australia's largest cattle-producing state. Both meat and milk are exported. In other regions, such as the Campos and Llanos of South America, though cattle ranching has been carried out for centuries, little progress has been made so far. The quality of the grass needs to be improved, and a better network of communications is essential. Above all, cattle breeding and disease control must be carried out on a scientific basis. In the African savanna, the attitude of such native herdsmen as the Maasai who treat cattle as prestige animals, not for slaughtering, will pose many difficulties towards the commercialization of the cattle industry. But as an agricultural region, the savanna holds great promise for the future. 140 Part 2, Weather, Climate, and Vegetation. Questions and exercises. 1. The following are brief descriptions of 3 different types of climate. A very large temperature range with summer rain. B. Distinct wet and dry seasons with concentrated summer rain. C. High uniform temperature with well-distributed heavy rainfall. I. Name the type of climate. 2. For any two of them, give a fuller description of the climate and the factors which give rise to it. 2. Explain why. A. The savanna lands have a parkland type of natural vegetation. B. The savanna is the natural home of cattle. C. The savanna grass increases in height and luxuriance further away from the equator. D. Rainfall in the Sudan climate is concentrated in the summer. 3. Write a descriptive account of either the Maasai, pastoralists of East Africa, or the Hausa, food growers of northern Nigeria. You should bear in mind the environmental influence on their mode of living. 4. It is said that the savanna land holds great promise for the future. Do you think so? Why? Outline some of the probable difficulties that may be encountered in their development. 5. Write brief notes on the following. A. The effects of harmattan in West Africa. B. The savanna is the big game country. C. Tropical grasslands have great potential for the cultivation of tropical hot crops, e.g. cotton, coffee, fruits. D. The savanna is a transition zone between the equatorial forests and the hot deserts. The hot desert and mid-latitude desert climates. Distribution. Deserts are regions of standing rainfall, which may be hot like the hot deserts of the Saharan type, or temperate as are the mid-latitude deserts like the Gobi. The aridity of the hot desert is mainly due to the effects of offshore trade winds, hence they are also called trade wind deserts. The temperate deserts are rainless because of their interior location in the temperate latitudes, well away from the rain-bearing winds. The major hot deserts of the world are located on the western coast of continents between latitudes 15 degrees east, 30 degrees north, and S, as shown in Fig. 142. They include the Sahara Desert, the largest single stretch of desert, which is 3,200 miles from east to west and at least 1,000 miles wide. Its total area of 3.5 million square miles is larger than all the 50 states of USA put together. The next biggest desert is the Great Australian Desert, which covers almost half the continent. The other hot deserts are the Arabian Desert, Iranian Desert, Kalahari, and Namib deserts. In North America, the desert extends from Mexico into USA and is called by different names in different places, e.g. the Mojave, Sonoran, California, and Mexican deserts. In South America, the Atacama or Peruvian Desert is the driest of all deserts with less than 0.5 inches of rainfall annually. Amongst the mid-latitude deserts, many are found on plateaus and are at considerable distance from the sea. These are the Turkestan and Patagonian deserts. The Patagonian Desert is more due to its rain shadow position on the leeward side off the Andes than to continentality. 142 Part 2, Weather, Climate, and Vegetation. Climate. Rainfall. Few deserts, whether hot, mid-latitude, have an annual precipitation of more than 10 inches, 254 millimeters. For example, William Creek in Australia has 5.4 inches, 137 millimeters. Jasper in India has 6.9 inches, about 176 millimeters, whereas Korea, Rajasthan, India has 28.4 inches, about 720 millimeters of annual precipitation. Yuma, Arizona, USA has 3.43 inches, about 90 millimeters. In Sella, Algeria, in the mid-Sahara, or Chile, in the mid-Atacama have practically no rain at all. In the latter, less than 0.02 inches, 0.5 millimeters, fell within a period of 17 years through light showers. In another station, less than 150 miles, about 240 kilometers away, Chile, not a single drop of rain was recorded for 4 years, and then a torrential downpour suddenly came one afternoon in which 2.5 inches, 63.5 millimeters of rain fell. The aridity of deserts is the most outstanding feature of the desert climate. We shall examine more closely why they are so dry. The hot desert lies dry north latitudes or the subtropical high-pressure belts where the air is sending, a condition least favorable for precipitation of any kind to take place. The rain-bearing trade winds blow offshore and the west tropics that are onshore blow outside the desert limits. Whatever winds reach the desert is low for cooler to warmer regions, and their relative humidity is lower, making condensation almost impossible. There is scarcely a single cloud in the continuous blue sky. The relative humidity is extremely low, decreasing from 60% in the coastal district to less than 30% in the desert interiors. Under such conditions, every bit of moisture is evaporated in the desert thus. Egypt's permanent drought. Precipitation is both scarce and most. Unreliable coastal stations like Massawa also, spelled Mitsawa on the Red Sea, is illustrated on IG 143a, receives light scattered showers from onshore winds, amounting to 77.3 inches, 439 millimeters for the year. On the west coast, the presence of cold currents, indicated by arrows in Figure 142, gives rise to mist and spots by chilling. Beyond the oncoming air, this air is later more contact with hot land and little rainfalls. The designating effect that cold overview current along the coast is so pronounced that the annual rainfall for the Atacama Desert is not more than half an inch. Rain normally occurs as data 1991 to 21. JAFMA 0 average. Temp CC 24.5 0.77.0 29.0 31.0 33.5 35.0 34.0 33.0 4.55 27.55 26.0 degrees Fahrenheit 76.177.0 80.6 84.2 87.8 99.3 99.0 93.2 91.4 86.9 81.577 8.8 33.5 8 4 0 9 11 4 16 33 33 in 1.3 1.0 0.30.4 Place time is Massawa, mid-sea, area 16 degrees north, 39 degrees east, altitude 6 m or 20 feet, precipitation equals 180 millimeters or 7.2 inches. Asterisk 88.99 degrees Fahrenheit, 95.0 to 76.1 degrees Fahrenheit, or annual temperature range 105 inches C, 35.0 C 20 carat. Figure 143a, hot desert climate. Violent thunderstorms of vegetation type. It bursts suddenly and continuously for a few hours over small areas. An inch or more may be recorded in one single shower. The thunderstorm is so violent and comes so sudden it has disastrous consequences of desert forms. Temperature. The deserts are some of the hottest spots on Earth can have hot temperatures throughout the year. There is no cold season in hot deserts, and the average temperature is around 86 degrees Fahrenheit, 30 degrees Celsius. The highest temperature recorded was 136 degrees Fahrenheit, 58 degrees Celsius on September 13th, 1922 at Al-Azizia, 25 miles about 25 kilometers south of Tripoli, Libya, in the Sahara. Days are unbearably hot, and the open barren sands. 177 degree F, 77 degrees Celsius is often recorded. The reason high temperatures are obvious: a clear, cloudless sky, intense insolation, dry air, and a rapid rate of evaporation. Coastal deserts by virtue of their maritime influence and the cool effect of cold currents have much lower temperatures, e.g. Arica, Chile, has a mean annual temperature of 66 degrees Fahrenheit, 18 degrees Celsius. Iquique, Chile, 65 degrees Fahrenheit, 18 degrees Celsius. Walvis Bay, Namibia. Southwest Africa, only 60 degrees Fahrenheit, 17 degrees Celsius. The hottest months seldom rise beyond 70 degrees Fahrenheit, 1 degrees Celsius, and the annual temperature range is equally small. The hot desert and mid-latitude desert climates 143. EG 16 degrees Fahrenheit, 9 degrees Celsius. In Arica, 10 degree F, or 6 degrees Celsius. In Iquique, and 10 degree F, 5 degrees Celsius. In Walvis Bay. The desert interiors, however, experience much higher temperatures, and the winter months are rather cold. For example, in Sulla, in the Sahara, has a temperature of 99 degrees Fahrenheit, 37 degrees Celsius in the hottest month, but only 55 degrees Fahrenheit, 13 degrees Celsius in the coldest month. The annual range is 44 degrees Fahrenheit, or 24 degrees Celsius. The range for Yuma, Arizona, USA, is 36 degrees Fahrenheit, or 21 degrees Celsius, and for Jacobabad, Sindh, Pakistan, is 41 degrees Fahrenheit, or 22 degrees Celsius. In comparison, the station Massawa, illustrated in Figure 143a, located near the coast, facing the Red Sea, has only a moderate range of 19 degrees Fahrenheit. Its hottest month is July, 95 degrees Fahrenheit, or 35 degrees Celsius, and its coldest month is January, 76 degrees Fahrenheit, or 24.5 degrees Celsius. The diurnal range of temperature in the deserts is very great. Intense insolation by day and region dry air, no clouds causes the temperature to rise with the sun. The barren ground is so intensely heated that, by noon, particularly in summer, a reading of 120 degrees Fahrenheit, about 48 to 49 degrees Celsius, is common. But as soon as the sun sets, the land loses heat very quickly by radiation, and the mercury column. And the thermometer drops to well below the mean. Temperature. A daily temperature range of 30 degrees to 40 degrees Fahrenheit, 20 to 25 degrees Celsius, is common, though in the Death Valley of California, an exceptionally great diurnal range of 74 degrees Fahrenheit, about 30 to 35 degrees Celsius, has been recorded. Frosts may occur at night in winter. These extremes of temperature make desert living most trying. This explains why the desert people wear thick gowns all day long, to protect themselves from the glaring heat by day and chilling frost by night, not to mention the sand grains that are carried by the wind. Climatic conditions in the mid-latitude deserts. The climatic conditions of the mid-latitude deserts are in many ways similar to those of the hot deserts. Aridity is the keynote. These inland basins lie hundreds of miles from the sea and are sheltered by the high mountains all around them. As a result, they are cut off from the rain-bearing winds. Occasionally, depressions may penetrate the Asiatic continental mass and bring light rainfall in winter, or unexpected convectional storms may bless the parched lands with brief showers. In summer, for example, Kashgar, Xinjiang, in western China in the Gobi Desert, as illustrated in degree F 4 degrees Celsius, 40 inch, 35, 30, 25, 20, 59, 10, 5, 0, minus 5, 95, 86, 77, 68, 15, 50, 41, 32, 23, 14, to 10, 5, minus 15. Dash asterisk. Temperature, I precipitation. Schmamgesond. 50, 45, 40, 35, 30, 25, 20, 15, 10, 5, 0. 2.0, 1.8, 1.6, 1.4, 1.2, 1.0, 0.8, 0.6, 0.4, 0.2, 0.0. Data, 1991 to 2021. Month FM AM JJ SOD. Average, temp degree C minus 5.2, 0.4, 8.8, 15.9, 2023.7, 25.5, 24.1, 19.8, 13.1 minus 2.7, 12.4. Degree F, 22.6, 32.6, 47.9, 60.5, 68.1, 74.7, 77.8, 75.4, 67.6, 55.6, 41, 27.1, 54.5. Precip. MM3, 475, 11, 9986, 6, 2270, in 0.10.10, carat 0.20, 40.40.40.30.30.20, 0.2020.123. Figure 143, B, the mid-latitude desert climate. Place Kashgar, Xinjiang, China, 39 degrees north, 76 foot E. Altitude 1,300 m, or 4,265 feet. Annual precipitation 70 millimeters, or 28 inches. Annual temperature range 55.2 degrees Fahrenheit F 77.8 degree F, 22.6 equals F, or 30.7 degrees Celsius, 25.53 C, 5.2 equals C. Figure 143, B, has most of its 3.5 inches of annual precipitation in the summer. Due to their coldness and elevation, snow falls in winter. From figure 143, B, it is clear that summers are very hot, 77.8 degrees Fahrenheit or 25.5 degrees Celsius, in July at Kashgar, and winters are extremely cold with 2 months below freezing point. The annual range of temperature is 55.2 degrees Fahrenheit or 30.7 degrees Celsius, much greater than that of the hot deserts. Continentality accounts for these extremes in temperature. Winters are often severe, freezing lakes and rivers, and strong cold winds blow all the time. When the ice thaws in early summer, floods occur in many places. The greatest inhibiting factors to settlement are the winter cold and the permanent aridity, besides remoteness from the sea. Desert vegetation. All deserts have some form of vegetation such as grass, scrub, herbs, weeds, roots, or bulbs. Though they may not appear green and fresh all the time, they lie dormant in the soil awaiting rain, which comes at irregular intervals or once in many years. The environment, so lacking in moisture and so excessive in heat, is most unfavorable for 144 Part 2 weather, climate, and vegetation. Plant growth and a significant vegetation cannot be expected, but very rarely are there deserts where nothing grows. The predominant vegetation of both hot and mid-latitude deserts is xerophytic or drought-resistant. Scrub. This includes the bulbous cacti, thorny bushes, long-rooted wiry grasses, and scattered dwarf acacias. Trees are rare except where there is abundant groundwater to support clusters of date palms. Along the western coastal deserts washed by cold currents, as in the Atacama Desert, the mists and fogs, formed by the chilling of warm air over cold currents, roll inland and nourish a thin cover of vegetation. Plants that exist in deserts have highly specialized means of adapting themselves to the arid environment. Intense evaporation increases the salinity of the soil so that the dissolved salts tend to accumulate on the surface, forming hard pans. Absence of moisture retards the rate of decomposition, and desert soils are very deficient in humus. Plants, whether annuals or perennials, must struggle for survival against both aridity and poor soil. Most desert shrubs have long roots and are well spaced out to gather moisture and search for groundwater. Plants have few or no leaves, and the foliage is either waxy, leathery, hairy, or needle-shaped to reduce the loss of water through transpiration. Some of them are entirely leafless, with pricks or thorns. Others, like the cacti, have thick succulent stems to store up water for long droughts. There are still others that shed their leaves during droughts. The seeds of many species of grasses and herbs have thick, tough skins to protect them while they lie dormant. Desert plants in Arizona, USA, germinate at once when their seeds are moistened by the next rain. In short, all plants must adapt themselves to survive in such an inhospitable region as the desert. Life in the deserts. Despite its inhospitality, the desert has always been peopled by different groups of inhabitants. They struggle against an environment deficient in water, food, and other means of livelihood. Some, like the Egyptians, have attained a high level of civilization. Others, like the Bedouin Arabs, have fared quite well with their flocks of sheep, goats, camels, and horses. The Bushmen of the Kalahari and the Bindabu of Australia remain so primitive in their mode of living that they barely survive. They are, in fact, a relic of the old Stone Age in the modern world. The desert inhabitants may be grouped under the following categories. 1. The primitive hunters and collectors. Of the primitive tribes, the Bushmen and the Bindabu are the best known. Both the tribes are nomadic hunters and food gatherers, growing no crops and domesticating no animals. The Bushmen roam the Kalahari Desert with their bows and poisoned arrows, spears, traps, and snares. They are not only skillful and strong, but also have great endurance. In order to capture their prey, they have to be very patient and, if necessary, run many miles to track down the wounded animals. In this way, they hunt antelope and other smaller animals. The women and children collect insects, rodents, and lizards, and gather honey, roots, grass, and grubs. Great skill is required in obtaining water in the desert. Dew is carefully gathered from leaves early in the morning and stored in ostrich shells. Very often, it is necessary to dig a hole in damp sand and suck the water up from the ground through a hollow reed. This is often a very slow process. Bushmen either wear a loincloth or go virtually naked. They travel in small family groups and live together in open sherms. This is a hollow dug beneath a thorn tree, surrounded by bushes. At night, a fire is lit to keep the family warm. The Bindabu or Aborigines of Australia live in very much the same way as the Bushmen. They are lean and dark, but healthy. They are skilled trackers, and some of them use wooden throwing sticks or boomerangs and spears. They also domesticate the dingo, a wild dog that assists them in tracking. The Hoi Desert and mid-latitude desert climates 145. Down kangaroos, rabbits, and birds. The women gather grass, roots, seeds, berries, moles, and insects to supplement their diet. Like the wandering Bushmen, the Bindabu move in family groups in search of fresh hunting grounds. But one distinct difference is that they always stay close to a water supply, as they still have not devised a means of tapping and storing water. They live in wurleys, simple shelters made of branches and tufts and grass. 2. The nomadic herdsmen. These people represent a more advanced group of desert dwellers who pursue a livestock economy. They ride on animals instead of walking and are heavily clad against the blazing sun, the stormy winds, and the chilly nights. The Bedouin of Arabia ride on horses and live in tents. The Tuaregs of the Sahara are camel riders and dwell in grass zareba, while the Gobi Mongols ride on horses to herd their yaks and live in portable yurts, a kind of tent. The Bedouin are the best examples of a desert group who have fared well as nomadic herdsmen. Besides keeping large flocks of animals, they are also engaged in trade with the caravan merchants and the oasis people. All around the year, the Bedouin wander with their herds in search of water and green pastures. Their wealth is their animals: sheep, goats, camels, and perhaps a few horses. The animals provide them with all that they require: daily milk and cheese, and on occasions meat as well. Their skin is used for hides or leather, for making tents, clothing, belts, footwear, and water bags. From the hair and wool, the Bedouin make clothes, mats, ropes, rugs, and carpets. These can also be exchanged at trading stations or oases for other necessities of life, which the desert herdsmen cannot produce, like dates, grain, beverages, medicines, firearms, and other manufactured articles. The Bedouin move in groups of about 100. They follow a regular pattern of routes, along which are scanty patches of pastures, wells, or springs. In this manner, one group rarely clashes with the Other in their search for new grounds to pitch their tents. Since they move so often, they always travel light, and only the essentials are carried along. 3. The caravan traders. These were the traveling merchants of the desert. Their journeys across the wastes of the Sahara or Russian Turkestan, currently part of Kazakhstan, Kyrgyzstan, Tajikistan, Uzbekistan, and Turkmenistan, sometimes lasted months or even years. They traveled at night as a team and were well armed. They carried a wide range of goods into remote interiors where their merchandise was highly sought after. These goods were sold or exchanged for hides, rugs, carpets, and other valuable products of the deserts. Though profits were high, the risks were equally great. The pack animal used by the caravans to carry their goods across the deserts was the camel, aptly described as the ship of the desert. Unlike horses which have sharp hooves that sink readily in the sandy desert, the camel has broad padded feet that will not slip in the sand. A pack camel, adequately fed, can carry a load of 350 pounds, 160 kilograms approximate, and travel 50 miles, 80 kilometers, a day. And a racing camel can do twice the distance when ridden. The camel has several other advantages. It provides milk and hair. It can store up water in its stomach and fat in its hump, so that it can go for long periods without either food or water. With the introduction of modern air, road, and rail transport, the role of the caravan traders is greatly reduced. Goods can be conveyed much more cheaply and with greater security by desert jeeps, vans, or trucks. But between the interior oases and scattered outposts beyond the reach of roads, the caravan routes remain the only form of available transport. 4. The settled cultivators. For crops to be cultivated in the desert, irrigation is indispensable. This is obtained either from oases, rivers, or dams, through a network of canals. In Egypt, the Nile supports a population of 25 million, mainly concentrated in the Nile Valley and Delta. The life-giving waters of the Nile made it possible for the Egyptians to raise many crops as early as 5,000 years ago. When the Nile flooded in summer, the overflowed water was caught in basins with raised banks and led into the fields to irrigate the crops. This was basin irrigation, which was widely practiced by the ancient Egyptian farmers and is still employed by the Egyptians today. Rice and cotton are cultivated in summer, followed by wheat, barley, beans, and other minor crops in winter. Modern concrete dams constructed across the Nile, e.g. Aswan and Sennar dams, are even more effective for extensive irrigation works. The floodwater can be held back and controlled and then released at any part of the year to feed the fields that yield 2, 3, or even more crops a year. In the same way, desert cultivators rely on the Indus in Pakistan, the Tigris-Euphrates in Iraq, and 146 Part 2, weather, climate, and vegetation. The Colorado in the Imperial Valley of California, and are able to irrigate millions of acres of arid land for crop production. In the deserts, wherever there are oases, some form of settled life is bound to follow. These are depressions of varying sizes, where underground water reaches the surface. Some of them are abnormally large, like the Tafilalet, also spelled Tafilat, oasis in Morocco, which measures 5,000 square miles, 12,950 square kilometers, supporting many settlements, including large towns. Others may be so small that they are no bigger than the mining pools that we are so familiar with, e.g. the Gadam's oasis of Libya is only 1 square mile in size. Life in an oasis is secure and well organized. A wall is usually constructed around the oasis to keep out the violent dust storms called samums. The oasis people live in mud brick houses with flat roofs, closely packed together. The streets are narrow and winding, and the heart of the settlement is dominated by the Souk, central marketplace. The oasis in the Algerian Sahara, the dunes are gradually encroaching on the date palms. Mosque, school, and shopping blocks. Souks may also be set up miles from anywhere, and people come from a number of surrounding settlements on special days to trade. Around the settlement are the agricultural lands. Water is led to the fields by irrigation channels, or drawn up from wells by camels or mules. The most important tree is the date palm, which is grown in dug-out hollows so that its roots can penetrate deep into the ground in search of water. The fruit is consumed locally and also exported. Other crops cultivated include maize, barley, wheat, cotton, sugarcane, fruits, and vegetables. With the development of motor routes across the deserts, many sophisticated foreign goods can now reach the oases. 5. The mining settlers. The lure of mineral wealth has attracted many immigrants into the desert. Mining camps and isolated settlements have sprung up following the discovery of certain mineral deposits. It was gold that brought immigrants scrambling into the great Australian desert. Water and food supplies have to be brought 300 miles, 482 kilometers, from Perth to keep the mines going. Some of them, like Kalgoorlie and Coolgardie, have become towns of considerable size. In the Kalahari Desert, the discovery of diamonds and copper has brought many white men to the thirst land, as it is called. Even in the most arid Atacama, in northern Chile, large mining camps have been established for the mining of caliche, cemented gravels, from which sodium nitrate, a valuable fertilizer, is extracted and exported to all parts of the world. The mines are worked by local Indian laborers and supervised by foreign technicians. Besides nitrates, copper is also mined. These two products have directly or indirectly contributed to the growing size of the Chilean towns of Arica, Iquique, Antofagasta and Chuquicamata. The last named is the world's largest copper town. Similarly, in the deserts of North America, silver is mined in Mexico, uranium in Utah, and copper in Nevada. A host of other minerals and their byproducts have, in fact, greatly altered the landscape and the economy of such arid regions. In recent years, the discovery of oil in many parts of the Saharan and Arabian deserts has transformed this forgotten part of the globe. In Algeria, oil wells have been sunk 2 miles deep to tap oil. In the Middle East, pipelines over 1,000 miles, 1,610 kilometers, long have been laid to the whole desert and mid-latitude desert climates 147. Bring oil from the shores of the Persian Gulf across Saudi Arabia to Sidon, Lebanon, and Beni, Syria, on the Mediterranean coast. With still half of the world's reserves of oil untapped in this region, the deserts here will virtually be paved with gold. In Iraq, Kuwait, and Saudi Arabia, the desert landscape is fast changing. New roads, huge palaces, ultra-modern hospitals, air-conditioned apartments, and swimming pools are examples of a thriving new era created entirely by oil, liquid gold. Questions and exercises. 1. Explain how the aridity of the desert is related to A. Offshore trade winds, B. The subtropical high-pressure belts, the horse latitudes, C. Cold ocean currents 2. Bring out any distinct differences between the hot deserts and mid-latitude deserts in A. Climate, B. Vegetation, C. Way of life. 3. With reference to actual examples, describe the activities and modes of living of the different groups of people that inhabit the deserts. Attempt to account for their differences. 4. Explain any 3 of the following. A. The hot deserts of the world are located on the western coast of continents. B. Patagonia is a desert in the rain shadow of the Andes. C. The annual range of temperature is much greater at Kashgar, Gobi, than at Iquique, Atacama. D. Desert plants must adapt themselves to survive. E. Camels are the ships of the desert. 5. Write brief notes on any 3 of these topics. A. The Bendibu of the Great Australian Desert. B. Date palm cultivation in an oasis. C. The role of oil in the development of desert economy. D. The Bedouin, the wandering herdsman. E. Agricultural development of any selected desert region. The warm temperate western margin. Mediterranean climate. Distribution. The warm temperate western margin climate is found in relatively few areas in the world. They are entirely confined to the western portion of continental masses, between 30 degrees and 45 degrees north and south of the equator, figure 144. The basic cause of this type of climate is the shifting of the wind belts. Explained in Chapter 13. Though the area around the Mediterranean Sea has the greatest extent of this type of winter rain climate and gives rise to the more popular name Mediterranean climate, the best developed form of this peculiar climatic type is, in fact, found in central Chile, figure 145a. Valparaiso, a Chilean locale characterized by a Mediterranean climate, experiences the majority of its rainfall during the winter months, figure 145b. Other Mediterranean regions include California, around San Francisco, the southwestern tip of Africa, around Cape Town, southern Australia, in southern Victoria and around Adelaide, bordering the St. Vincent and Spencer Gulfs, in southwest Australia, Swanland. Climate. The Mediterranean type of climate is characterized by very distinctive climatic features. 1. A dry, warm summer with offshore trades, as illustrated in figure 146a, and B. The summer months have a relatively high temperature. 77 degrees Fahrenheit or 25 degrees C in July in Rome, and about 68 degrees Fahrenheit or 20 degrees Celsius in February in Cape Town. The highest temperatures are, however, experienced further away from the coast in the more continental eastern Mediterranean, in the interiors of the Balkan Peninsula, the Anatolian Plateau, and Mediterranean Middle East. For example, the July mean for Athens is 82 degrees Fahrenheit or 28 degrees Celsius. Larissa, Greece, 82 degrees Fahrenheit or 28 degrees Celsius, and Beirut. Figure 144 regions with Mediterranean climate. The warm temperate western margin, Mediterranean, climate 149. Figure 145a, central Chile, a region with a typical Mediterranean climate, showing the shifting of the wind belt with most rain falling in winter. Figure 145b, Valparaiso, Chile, known for its Mediterranean climate, receives the majority of its rainfall during the winter months. Data, 1991 to 2021. JFMAMJAS. 0. ND. RO. Average, degree C 7.2, 7.8, 10.6, 13.8, 17.9, 22.5, 25.2, 25.4, 21.1, 12.6, 8.5. Temp degree F 45, 46, 51.1, 56.9, 64.2, 72.5, 77, 377.7, 70, 62.8, 54.7, 47.3. MM 67, 75, 77, 83, 60, 34, 24, 23, 84,122,135, 94. Precip. In 223321003463. Data, 1991 to 2021. Place Romo, Italy, 42 degrees north, 12x. Altitude 32 m or IPS feet. Annual precipitation, J878 mm or 34.6 inches. 7 to the power of 7 foot. T32.7 T, 77, 7-7 or annual temperature range I1 2 degrees Celsius, 25 4x, 7.2 degrees Celsius. Figure 146A, Mediterranean climate in the Northern Hemisphere. Place Cape Town. South Africa, 34 18 feet 3 inches. Altitude annual precipitation. 27 m or 88 feet 621 mmcr 24.4 inches. Annual temperature range. L2, F 68.rf. 55.50 AR 7.qx 0.1 pounds asterisk C, 13.0x1. B. Mediterranean climate in the Southern Hemisphere. 150 Part 2, Weather, Climate, and Vegetation. Lebanon, 79 degrees Fahrenheit or 26 degrees Celsius. Elsewhere in central Chile, South Africa and Mediterranean Australia, due to their coastal position, the influence of the sea has modified the temperature in the January means. Southern summer are normally around 70 degrees Fahrenheit or 21 degrees Celsius. In summer, when the sun is overhead at the Tropic of Cancer, the belt of influence of the westerlies is shifted a little polewards. Rain-bearing winds are therefore not likely to reach the Mediterranean lands. The prevailing trade winds are offshore and there is practically no rain. The air is dry, the heat is intense, and the relative humidity is low. Days are excessively warm and in the interiors, prolonged droughts are common. At night, there is rapid radiation but frosts are rare. 2. A concentration of rainfall in winter with onshore westerlies. The Mediterranean lands receive most of their precipitation in winter when the westerlies shift equatorwards. In the Northern Hemisphere, the prevailing onshore westerlies bring much cyclonic rain from the Atlantic to the countries bordering the Mediterranean Sea. This is the rainy season and is the most outstanding feature of the Mediterranean climate. In almost all other climatic types, maximum rain comes in summer. The mean annual rainfall is normally taken as 25 inches, 635 millimeters. Again, this differs greatly from place to place, depending on relief, continentality, and the nassage of the passing cyclones. The annual rainfall for the two selected stations, Rome and Cape Town, is 33 inches, 838 millimeters, and 25 inches, 635 millimeters, respectively, which are quite typical of the regions. They represent the rain comes in heavy showers, and only on a few days with bright sunny periods between them. This is another characteristic feature, or the Mediterranean winter rain. With a little more caution in relating the relief of the Mediterranean lands to the rainfall distribution, you will notice that the Mediterranean regions are often backed by mountains of some kind. In Iberia, the central Meseta and other sierras of the peninsula present an effective barrier to the oncoming westerlies. As a result, the Portuguese coast is much wetter than eastern Spain. Lisbon has an annual rainfall of nearly 25 inches, 635 millimeters, while Cartagena, along the eastern coast of Spain, does not receive even half as much. Much heavier precipitation has been recorded in the highlands on windward slopes facing the westerlies. The steep hills of the eastern Adriatic are the rainiest part of Europe, with 182 inches, 4,622 millimeters, recorded at Kirkvice, about 3,600 feet, about 1,100 m above sea level. Rain in Mediterranean Europe normally begins in September, reaching its peak somewhere in October-November, 4 and 5 inches respectively. In Rome, though the downpours are infrequent, they are often very torrential, and in mountainous districts, destructive floods occur. The floods come so suddenly that there is practically no time to do anything about it. The disastrous flood of Lisbon in 1967 came in the middle of the night and caused great damage and loss of life in a few hours. Snow rarely occurs on lowlands and coastal districts, and even if it does fall on the highlands, it is moderate and is a source of water supply for hydroelectric power generation and for irrigation. 3. Bright, sunny weather with hot, dry summers and wet, mild winters. Considering its mid-latitude position, the Mediterranean regions have a very favorable climate, unrivaled by any other climatic regions. The climatic features are transitional between those of the trade wind hot desert in the south and the cool temperate maritime climate. In the north, summers are warm and bright and winters are so mild and cool that many tourists come at all times of the year. The sky is almost cloudless and sunshine is always abundant. In July, Rome has as much as 11 hours of sunlight. And with the Mediterranean palm trees around, tourists feel very much as if they are in the tropics. Even in midsummer, the intense heat is never sultry. The combined effects of onshore winds and the maritime breezes keep the temperature down to about 50 degrees Fahrenheit, 10 degrees Celsius in winter, and not often exceeding 75 degrees Fahrenheit or 24 degrees Celsius in summer. The climate is so mild that many of the local people sleep in the open air. The annual temperature range is between 15 degrees and 25 degrees Fahrenheit, annual average air temperature of 16.3 degrees Celsius. The Mediterranean regions are famous for their health and pleasure resorts, frequented by millions all around the year. 4. The prominence of local winds around the Mediterranean Sea. Many local winds, some hot, others cold, are common around the Mediterranean Sea. The causes are many and varied. The Topography of the region with the high Alps in the north, the Sahara Desert in the south, continental interiors in the east, and the open Atlantic on the west give rise to great differences in temperature. The warm temperate western margin, Mediterranean, climate 151. Figure 147 local winds of the Mediterranean Sea. Pressure and precipitation. The passing cyclones. From the Atlantic, the anticyclones from the north. And the cold air masses from the continental interiors are often interrupted or channeled by relief features, resulting in the birth of local winds around the Mediterranean. These winds varying in strength, direction, and duration affect the lives, crops, and activities of the people there. Figure 147 indicates the location and direction of some of these local winds, and the more important ones are described below. A. Sirocco. This is a lot, dry, dusty wind which originates in the Sahara Desert. Though it may occur at any time of the year, it is most frequent in spring and normally lasts for only a few days. The Sirocco blows outwards in a southerly direction from the desert interiors into the cooler Mediterranean Sea. It is usually associated with depressions from the Atlantic passing from the coast eastwards inland. After crossing the Mediterranean Sea, the Sirocco is slightly cooled by the absorption of the water vapor. Even then, it is still hot and dry with a temperature of over 105 degrees Fahrenheit or 40 degrees Celsius. Its scorching breath withers vegetation and crops. The damage is particularly serious when it comes at the times during which vines and olives are in blossom. The Sirocco is so prominent that it is called by many other local names, such as Chile in Tunisia, Gibli in Libya, Lavesh in Spain, Khamsin in Egypt and Malta. In the Adriatic and Aegean Sea, this hot wind, better known as garbi, gathers much moisture causing fog, heavy dew, and rain. This may be blood rain because the wind is carrying the red dust of the Sahara Desert. B. Mistral. In contrast, the Mistral is a cold wind from the north, rushing down the Rhone Valley in violent gusts between 40 and 80 miles per hour, 64 to 128 kilometers per hour. The velocity of the Mistral is intensified by the funneling effect in the valley between the Alps and the Central Massif, and in extreme cases trains may be derailed and trees uprooted. In winter when the Mistral is most frequent, the temperature of the wind may be below freezing point, though the sky may be clear and cloudless. As a protective measure, many of the houses and orchards of the Rhone Valley and the Riviera have thick rows of trees and hedges planted to shield them from the Mistral. A similar type of cold northeasterly wind experienced along the Adriatic coast is called the Bora. Like the Mistral, it is caused by a difference in pressure between continental Europe and the Mediterranean. This usually occurs in winter, when the atmospheric pressure over continental Europe is higher than that of the Mediterranean Sea. The Bora thus blows outwards into the Mediterranean. This dry, icy wind is even more violent than the Mistral, and speeds of over 100 miles per hour, 160 km/h, have been recorded. During strong Boras, ships may be blown aground, and agricultural land devastated. Tramontana and Gregale are similar. Cold winds of the Mediterranean Sea. Natural vegetation. In a land where half the year is dry, one cannot expect the natural vegetation to be luxuriant. Trees with small broad leaves are widely spaced and never very tall. Though there are many branches, they are short and carry few leaves. The absence of shade is a distinct feature of Mediterranean lands. Growth is slow in the cooler and wetter season, even though more rain comes in winter. Growth is thus almost restricted to autumn. In spring, when the temperature is higher and moisture is just sufficient, the long summer drought checks the growth. One fact is clear: plants, whether trees or shrubs, evergreen or deciduous, have to devise ways of adapting themselves to a climatic environment with such a marked rhythmic recurrence of rain and drought. In many ways, the vegetational responses to climatic demands in the Mediterranean are similar to those of the adjacent deserts and the savanna. Further south, plants are in a continuous struggle against heat, dry air, excessive evaporation, and 152 Part 2, Weather, Climate, and Vegetation. Prolonged droughts. They are, in short, xerophytic, a word used to describe the drought-resistant plants in an environment deficient in moisture. Types of Mediterranean vegetation. Various kinds of vegetation are found in the Mediterranean regions. 1. Mediterranean evergreen forests. These are open woodlands with evergreen oaks, of which the cork oaks of Spain and Portugal are the best known. They are found only in the climatically most favored regions with a rainfall of well over 25 inches, 635 millimeters. The trees are normally low, even stunted, with massive trunks, deeply fissured barks, small leathery leaves, and a wide-spreading root system in search of water. The cork oaks are specially valued for their thick barks used for making wine bottle corks and for export around the world. In Australia, the eucalyptus forest replaced the evergreen oak. The jarrah and cherry trees are commercially the most important. The giant sequoia or redwood is typical of the Californian trees. 2. Evergreen coniferous trees. These include the various kinds of pines, firs, cedars, and cypresses which have evergreen, needle-shaped leaves and tall, straight trunks. They appear more on the cooler highlands and where droughts are less severe. Deforestation has reduced their numbers considerably. 3. Mediterranean bushes and shrubs. This is perhaps the most predominant type of Mediterranean vegetation. Summers are so dry and hot that in places forests give place to short, evergreen shrubs and bushes. The low bushes grow in scattered clumps and are often thorny. The more common species are laurel, myrtle, lavender, arbutus, and rosemary, of which a number are strongly scented or perfumed. In many areas, due to people's interference in forest depletion or to overgrazing, the original woodlands degenerate into a scrub vegetation with scattered, stunted trees and tall bushes. They are so different from the ordinary woodland or the true desert scrubland that special names have been given to them to distinguish their location in different parts of the Mediterranean lands. This type of vegetation is called maquis in southern France and macchia in Italy. In California, the term chaparral is used, and in Australia, mallee scrub. In limestone uplands, where the soil is extremely thin and the scrub deteriorates into highly xerophytic ground creepers, a more exact term, garriga, is used. 4. Grass. Conditions in the Mediterranean do not suit grass, because most of the rain comes in the cool season when growth is slow. Slow-growing vegetation, which cannot replenish its foliage readily, and which is without deep penetrating roots, is least suited here. Even if grasses do survive, they are so wiry and bunchy that they are not suitable for animal farming. Cattle rearing is thus unimportant. In the Mediterranean, the grass, which is replaced by certain drought-resistant varieties of shrubs and flowering herbs, can however support sheep or goats. Even this form of grazing has done more harm than good, for it has promoted soil erosion and impoverished the hill slopes of the Mediterranean. Animal fats are not important here, and the chief cooking oil is obtained from olives. Dairy products are net import items. Economic development of the Mediterranean regions. Despite the semi-arid conditions over many parts of the Mediterranean lands, the climate as a whole is favorable. Its warm, bright summers and cool, moist winters enable a wide range of crops to be cultivated. One must not forget that the Mediterranean shorelands were once the cradle of world civilization. Nowadays, the area is important for fruit cultivation, cereal growing, winemaking, and agricultural industries, as well as engineering and mining. We shall deal with some of them in greater detail below. 1. Orchard farming. The Mediterranean lands are also known as the world's orchard lands. A wide range of citrus fruits, such as oranges, lemons, limes, citrons, and grapefruit, are grown. The fruit trees have long roots to draw water from considerable depths during the long summer drought. In exceptionally dry areas, irrigation helps to relieve the lack of moisture. In the Great Valley of California, the Vale of Chile, the Negev Desert of Israel, and the northern shores of Mediterranean Europe, an elaborate system of irrigation canals enables both fruits and cereals to be successfully raised. The thick, leathery skin of the citrus fruits prevents excessive transpiration, and the long, sunny summer enables the fruits to be the warm temperate western margin, Mediterranean, climate 153. Ripened and harvested. The various Mediterranean oranges are so distinctive in their shape, size, taste, and quality that they are called by different names in their area of production. Of the Mediterranean oranges, perhaps, the best known are the sun-kissed oranges from California, exported for table consumption and for making orange squash. The Seville oranges of Spain are small but very sweet, and are particularly suitable for making marmalade. Those from Israel, the Jaffa oranges, are equally delicious and are specially grown for export. In Tangiers, the tangerine is of great local importance. In the temperate monsoon lands of China and Japan, which were, in fact, the native home of the orange, commercial cultivation of the fruit is less significant, and only in recent years has there been any serious effort made to popularize their export. As mandarin oranges, the Mediterranean lands account for 70% of the world's exports of citrus fruits. The olive tree is probably the most typical of all Mediterranean cultivated vegetation. It is so hardy and long-rooted that it can survive even on very poor limestone soils with less than 10 inches of annual rainfall. Like our coconut palm, the olive tree is very versatile and has many uses. The olive can be eaten fresh or pickled with spices. The fleshy part can be crushed and olive oil extracted. A valuable source of cooking oil in a region deficient in animal fat. Soap and margarine can also be made with the oil. Besides olives, many nut trees like chestnuts, walnuts, hazelnuts, and almonds are grown, and the nuts picked as fruits, or for the chocolate industry. Other important fruits are peaches, apricots, pears, plums, cherries, and figs. 2. Crop cultivation. Besides orchard fruits, the Mediterranean climate also supports many field crops. Cereals are by far the most important. Wheat is the leading food crop. Though conditions for extensive wheat cultivation are not as ideal as those of the cool temperate regions, the Mediterranean farmers have utilized the seasonal climatic rhythm to their best advantage. The wheat grown is mainly hard, winter wheat. It is suitable for both bread making and other food products such as macaroni, spaghetti, and vermicelli. The farmers. Olive cultivation in Andalusia, Spain. The small, gnarled trees are typical of the Mediterranean. 154 Part 2. Weather, climate, and vegetation. Usually sow the seeds in autumn, so that they germinate and grow steadily with the coming winter. Usually sow the seeds in autumn, so that they germinate and grow steadily with the coming winter. Rain. By spring there is still sufficient moisture for the wheat to mature. The sunny weather of early summer ripens the grains and the wheat is harvested in almost guaranteed rainless weather. Barley is the next most popular cereal. Summer crops are raised only where irrigation is possible. The water comes mainly from the melting snow that feeds the many rivers whose sources are in the highlands. Lowlands are intensively cultivated and the hill slopes are terraced. In Spain and Italy, the edges of the terraces are firmly piled with stones to prevent any soil from being washed away. Generally speaking, farms are small, but there are also large holdings called haciendas in Spain which engage large numbers of paid laborers to work the farms. In a few localities, e.g. the Ebro Basin in Spain, the Po Valley in Italy, and in California, rice has been successfully cultivated and their yields are some of the highest in the world. In the more fertile plains, vegetables, especially beans, and flowers are grown for the local market. A little cotton and tobacco are also grown. The mountain pastures, with their cooler climate, support a few sheep, goats, and sometimes cattle. Transhumance is widely practiced. 3. Wine production. This is another speciality of the Mediterranean countries, because the best wine is essentially made from grapes. Some 85% of grapes produced go into wine. The long, sunny summer allows the grapes to ripen and then they are handpicked. Viticulture is by tradition a Mediterranean occupation and the regions bordering the Mediterranean Sea account for 3/4 of the world's production of wine. In Spain, Portugal, France, and Italy, wine is the national drink. The average wine consumption of the Mediterranean countries is about 15 gallons per head per annum, whereas in USA it is not even 1/20th as much. Although grapes may be grown in many parts of the temperate lands, commercial viticulture is almost entirely confined to the Mediterranean regions. It has been estimated that 80% grapes are grown in many Mediterranean countries. In Turkey, a portion of these grapes undergoes a unique and traditional process. Selected grapes are sun-dried to make sultanas, raisins, and molasses. The warm temperate western margin, Mediterranean, climate Q. Of the world's total production of 70 million tons of grapes annually are being processed into wine. The quality of the fermented grape juice is decided by a number of factors including the types of vines grown, the quality of the soil, the climate of the region, the method and extent of fermentation. The fragrance, taste, and quality of the final product is so varied that the price range is tremendous. Wine may be as cheap as any soft drink or as expensive as brandy. To differentiate the various kinds of wine, the principal wine areas of the world maintain their exclusive names. The wine from southern Spain is called sherry, from Portugal port wine. Chianti, Asti, and Marsala come from different parts of Italy. In France, the greatest wine regions are located further north, e.g. Champagne in the Paris Basin, Bordeaux in the Garonne Basin, Burgundy in the Rhone-Saône Valley. The world trade in fresh grapes is comparatively small, mainly from Mediterranean South Africa. Most of the inferior grapes are preserved as dried grapes and exported. They are known by several names, e.g. currants from the Levantine grapes, raisins from California, and sultanas from Asia Minor. The other industries associated with Mediterranean agriculture are fruit canning, flour milling, and food processing. Questions and exercises. 1. What is meant by the index plant of a climatic type? In what ways are the following index plants representative of the type of climate indicated? A. Teak, tropical monsoon climate. B. Olive, Mediterranean climate. C. Cactus, hot desert climate. D. Spruce, cool temperate continental climate. 2. The following statistics of the annual rainfall and annual temperature ranges of 4 Mediterranean lowland stations are taken from the Mediterranean shorelands. Attempt to explain their differences. 3. Outline the various types of natural vegetation found in the Mediterranean regions. Relate this to climate, soil, and human interference. 4. Give an explanatory account of the following statements about economic activities of the Mediterranean lands. A. Orchard farming is the predominant occupation. B. The chief cereal cultivated is hard, winter wheat. C. Pastoral farming is of little importance. 5. Write geographical notes on any three of the following. A. The Mediterranean climate is typified by dry, sunny summers and wet, mild winters. B. Hot, dusty Sirocco and cold stormy Mistral. C. Mediterranean woodlands, shrubs and scrub. D. 3/4 of the world's wine comes from the Mediterranean regions of Europe. The temperate continental, steppe climate. Distribution. Bordering the deserts, away from the Mediterranean regions and in the interiors of continents are the temperate grasslands. Though they lie in the westerly wind belt, they are so remote from maritime influence that the grasslands are practically treeless. These grasslands are so distinctive in their natural vegetation that, although those which occur in the southern hemisphere have a much more moderate climate, they are often dealt with together. In the northern hemisphere, the grasslands are far more extensive and are entirely continental. In Eurasia, they are called the steppes and stretch eastwards from the shores of the Black Sea across the Great Russian Plain to the foothills of the Altai Mountains, a distance of well over 2,000 miles, 3,218 kilometers. They are broken in a few places, being interrupted by the highlands. There are isolated sections in the Pustas of Hungary and the plains of Manchuria, also called as Northeast China Plain. In North America, the grasslands are also quite extensive and are called prairies. They lie between the foothills of the Rockies and the Great Lakes astride the American-Canadian border, figure 148. In the southern hemisphere, due to the narrowness of the temperate portions of the southern continents, the grasslands are rather restricted and less continental. In the case of the pampas of Argentina and Uruguay, the grasslands extend right to the sea and enjoy much maritime influence. In South Africa, the grasslands are sandwiched between the Drakensberg and the Kalahari Desert and are further subdivided into the more tropical bushveld in the north and the more temperate highveld in the south. The word veld is a Dutch word given by the early pioneer Dutch farmers who came to settle here. It means field and is pronounced as veld. In Australia, figure 148, the temperate grasslands. The temperate continental steppe climate 157. The grasslands are better known as downs and are found in the Murray-Darling Basin of southern Australia. Climate. Temperature. Their location in the heart of continents means that they have little maritime influence. Their climate is thus continental with extremes of temperature. Summers are very warm. Over 68 degrees Fahrenheit, 20 degrees Celsius in Winnipeg for July, as illustrated in figure 149a. And 72 degrees Fahrenheit, 22 degrees Celsius for January for Pretoria, as shown in figure 149b. Winters are very cold in the continental steppes of Eurasia because of the enormous distances from the nearest sea. The winter months are well below freezing, and in Winnipeg the January reading is 3.7 degrees Fahrenheit minus 15.7 degrees Celsius, 36 degrees below freezing point. In contrast, the steppe type of climate in the southern hemisphere is never severe. The winters are so mild that the mean temperature for any of the winter months is usually between 35 degrees and 55 degrees Fahrenheit, 2 to 13 degrees Celsius, temperatures below freezing point even. In midwinter, July in the southern hemisphere are exceptional. Pretoria, the station chosen to illustrate the steppe type of climate in the southern. Data, 1991 to 2021. JFMAMJJASOND average. Degree C minus 16.7 minus 14.1 minus 5.64.1 11.117, 220.4 19.4 14.26 minus 2.8 minus 12.2. Temp degree F 3.76.6 21.9 39.3 52.1 62.9 68.8 67 57.6 42.7 26.9 10.1 precip. MM 21 18 30 38 83 106 91 78 72 50 33 26. In 001134332111. Figure 149A, steppe climate in the northern hemisphere. Place Winnipeg, Canadian prairies, 50 degrees north, 97 degrees west. Altitude 234 m or 768 feet. Annual precipitation 646 millimeters or 25.4 inch. Annual temperature range 65 VF 68.8 to 37 degrees Fahrenheit or 36 1 degree C 20.4 to minus 15.7 degrees Celsius. Pretoria, Transvaal, Republic of South Africa. Place J 25 degree S 28 AE. Altitude I 1,280 m or 4,200 feet. Annual precipitation I 661 millimeters or 26.0 inch. Plus I 18.5 degrees Fahrenheit, 72.1 degree F, 53.6 SF, or annual temperature range. Figure 149, B, steppe climate in the southern hemisphere. Hemisphere has 53.6 degrees Fahrenheit, 12 degrees Celsius in midwinter, July, the coldest month of the year. Statistics from other parts of the southern continents also show a mild winter. For example, the July mean, midwinter, for Johannesburg is 49 degrees Fahrenheit 9.5 degrees Celsius, for Buenos Aires, 51 degrees Fahrenheit 10.5 degrees Celsius, and for Mildura, Murray-Darling Basin, 51 degrees Fahrenheit 10.5 degrees Celsius. These statistics establish the moderating effects of oceans on the climates of the southern hemisphere. The annual range of temperature is great, a direct result of continentality. Winters are so cold that parts of the Eurasian steppes are snow-covered for several months. The snow melts with the return of spring, and by midsummer, temperatures soar to over 65 degrees Fahrenheit 18 degrees Celsius. It is really hot for its latitude. For example, the midsummer temperatures for Kiev is 67 degrees Fahrenheit 19 degrees Celsius. The stations in the southern hemisphere record even higher temperatures, e.g. 67 degrees Fahrenheit 19 degrees Celsius in Johannesburg, 74 degrees Fahrenheit 23 degrees Celsius in Buenos Aires, and 77 degrees Fahrenheit 25 degrees Celsius in Mildura. It is clear from the two selected stations given that there is a tremendous difference between the annual temperature range of the northern and southern hemispheres, again a factor of continentality. The range in Winnipeg, figure 149A, is 65 degrees Fahrenheit 36 degrees Celsius, over 3 times as great as that. 158 Part 2, Weather, Climate, and Vegetation. Of Pretoria, figure 149B, at 18 degrees Fahrenheit, 10 degrees C. Readings taken in various other stations of the northern and southern hemispheres confirm this trend. The annual range for Shinyang, Mukden, and Manchuria is 69 degrees Fahrenheit, 20.5 degrees Celsius. In comparison, the annual range of the more maritime stations of Johannesburg, Buenos Aires, and Mildura in the southern hemisphere are very much smaller, 18 degrees Fahrenheit, 10 degrees Celsius. 25 degrees Fahrenheit, 14 degrees Celsius, 28 degrees Fahrenheit, 17 degrees Celsius respectively. Precipitation. In its continental position, the annual precipitation of the steppe climate can be expected to be light. The average rainfall may be taken as about 20 inches, about 500 millimeters, but this again varies according to location from 10 inches to 30 inches, about 250 to 750 millimeters. Winnipeg, in Figure 149a, has 25.4 inches, 646 millimeters, with a distinct summer maximum from convectional sources when the continental interiors are intensely heated. The heaviest rain comes in the middle of the year with 4.0 and 3.0 inches, 106 and 91 millimeters, each in June and July. Most of the winter months have about an inch of precipitation brought by the occasional depressions of the westerlies and coming in the form of snow. In many other continental stations, the annual precipitation is even less, though the general pattern remains the same, with most of the rain falling in the summer. The maritime influence in the steppe type of climate of the southern hemisphere is even better, brought out by the rainfall regime. Its annual precipitation is always more than the average 20 inches, or 500 millimeters, because of the warm ocean currents that wash the shores of the steppe lands here. Pretoria, in Figure 149b, has an annual precipitation of 26 inches, 661 millimeters, with the wettest months in November, December, January, and February, the summer season of the southern hemisphere. There are 3 months, June, July, and August, without any rain. This is the period of drought that may have such a disastrous effect on the sheep-rearing industry here. The dry season is particularly pronounced in temperate grasslands, adjoining deserts, for example, in Australia. Mildura, on the fringe of the mallee scrub of the Great Australian Desert, and also in the rain shadow area of the Great Dividing Range, has an annual rainfall of only 10.8 inches, 274 millimeters. Irrigation is essential. The other southern hemisphere stations have moderate rainfall, e.g. 30.9 inches, 784 millimeters, in Johannesburg and 43.8 inches, 1,112 millimeters, in Buenos Aires. On the eastern slopes of the Rockies in Canada and USA, a local wind, similar to the Fin in Switzerland, called the Chinook, comes in a southwesterly direction to the prairies and has a considerable effect on the local pastures. It actually comes with the depressions in winter or early spring from the Pacific coast ascending the Rockies and then descending to the prairies. It is a hot wind and may raise the temperature by 40 degrees Fahrenheit, about 4 to 5 degrees Celsius, within a matter of 20 minutes. As it melts the snow cover in the pastures, animals can be driven out of doors to graze in the open fields. The agricultural year is thus accelerated. Local farmers welcome the Chinook, for frequent Chinooks mean mild winters. Natural vegetation. Though the term steppe vegetation geographically refers to the scanty vegetation of the subarid lands of continental Eurasia, many authors, including the late Professor Sir Dudley Stamp, have extended the term to include the temperate grassland all over the world. In this connection, our reference to steppe grassland is taken to mean the temperate grasslands of the mid-latitudes, the steppes, prairies, pampas, veldt, and downs. It is natural to expect the steppes to be grass-covered, differing only in the density and quality of the grass. Their greatest difference from the tropical savanna is that they are practically treeless and the grasses are much shorter. Where the rainfall is moderate, above 20 inches, the grasses are tall, fresh, and nutritious and are better described as long prairie grass. This is typical of the grass of the wheatlands in North America, the rich black earth or Chernozem areas of Ukraine, and the better watered areas of the Asiatic steppes. Where the rainfall is light, less than 20 inches or 500 millimeters, or unreliable, where the soil is poor, as in the continental interiors of Asia, the short steppe type of grass prevails, Figure 150. The grasses are not only shorter but also wiry and sparse, often found in discontinuous clumps with bare soil exposed between them. These areas are less suitable for arable farming and are used for some form of ranching, as in the high plains of USA. The climatic requirements of grass are quite different from those of trees. They require less moisture than trees, and an annual precipitation of 10 to 20 inches, about 250 to 500 millimeters, is adequate. The temperate continental, steppe, climate 159. Figure 150. The Black Earth region of Ukraine, part of the Eurasian steppes. Their growth is not abruptly checked by summer droughts or winter cold. The steppe grass can lie dormant throughout the prolonged drought. They sprout and come to life as soon as the temperature is warm enough for plant growth, 43 degrees Fahrenheit or 6 degrees Celsius, and grow steadily with very little moisture. The appearance of the temperate grasslands varies with seasons. In spring, the grass begins to appear green, fresh, and blooming with small, colorful flowers. The light rainfall that comes in late spring and early summer greatly stimulates their growth, and there is plenty for the animals to graze. The herdsmen are busiest at this time. In summer, there is so much heat and evaporation that the grass is scorched. The carpet of bluish-green grass turns yellow and soon brown. Towards autumn, the grass withers and dies, but the roots remain alive and lie dormant throughout the cold winter. The winter is harsh and long, but the snow. The prairies, Saskatchewan, Canada. Notice the grain elevators by the railway line. Is never of great depth. Everything is quiet, but with the next spring, the cycle is repeated and the steppe is alive again. Trees are very scarce in the steppes because of the scanty rainfall, long droughts, and severe winters. The rolling plain is an endless stretch of grass, whether green or brown, except along the watercourses where a few low willows, poplars, or alders break the monotony. Polewards, an increase in precipitation gives rise to a transitional zone of wooded steppes where some conifers gradually appear. Even then, the trees are very scattered and few in number. Towards the equator, the steppe grass becomes shorter and sparser, till it merges into the desert with thorny scrub. In the cultivated regions, such as the wheat farms of the prairies, double rows of trees are planted around the house to shield the occupants from the strong winds which come unobstructed across miles of level ground. This provides the greatest contrast in a land which is essentially grass. There are no hedges and few fences, and the rows of planted trees form an unusual landmark from the air. Economic development. The temperate grasslands were once the home of grazing animals, wild horses in the Asiatic steppes, swift-footed bison in the prairies, and untamed buffaloes in the pampas. Even as recently as the last century, these grasslands were dominated by nomadic and semi-nomadic people like the Kyrgyz of the Asiatic steppes. They roamed far and wide with their herds and earned a precarious living from whatever pastures they could find. The Red Indians of North America were mostly hunters who moved around after the bison and other animals. Cultivation was unknown, and the region was one of the most sparsely populated parts of the world. In recent years, great changes have taken place. In the grasslands, and few areas, in fact, have managed to retain their original landscape. The grasslands have been plowed up for extensive mechanized wheat cultivation and are now the granaries of the world. Besides wheat, maize is increasingly cultivated in the warmer and wetter areas. The tufted grasses have been replaced by the more nutritious lucerne or alfalfa grass for cattle and sheep rearing. These temperate grasslands are now the leading ranching regions. 160 Part 2 Weather, Climate, and Vegetation of the globe. We shall now describe more closely each of these economic activities. 1. Nomadic herding. This type of migratory animal grazing has almost disappeared from the major grasslands. The herders were wandering tribes, e.g. the Kyrgyz, the Kazakhs, and the Kalmucks, also spelled Kalmyks. They used to travel over long distances like the Bedouin of the Arabian desert in search of grass and water for their animals: cattle, sheep, goats, and horses. From these domesticated animals they obtained meat, milk, wool, hides, bones, and horn. You would be surprised at the number of things they made out of these. The wool was woven into felt for tents and garments. The leather was used for making boots, saddles, and belts, which were very essential in a country where the chief riding animal was the horse. The bones and horns were not wasted but made into tools, utensils, and weapons. Many of their homemade products were exchanged at trading posts or with the caravans for guns, canned food, grains, tea, coffee, sugar, medicines, and other essential goods. The harsh environment of the nomads, with long droughts and unreliable showers, made the Kyrgyz a tough and fearless people, the Tartars, and they long resisted subjugation by the Russians. Now, however, under the communist regime, they are being forced to settle down. The steppes which they used to wander have been made into huge collective farms and state farms for ranching or producing cereals. 2. Extensive mechanized wheat cultivation. The temperate grasslands are ideal for extensive wheat cultivation. The cool, moist spring stimulates early growth, and the light showers in the ripening period help to swell the grains to ensure a good yield. The warm, sunny summer is not only advantageous for harvesting, but also enables the straw to be dried for farm use. In addition, the levelness of the steppes and other temperate grasslands all over the world makes plowing and harvesting a comparatively easy job. Mechanical plows loosen the soil and get the fields ready for sowing in the shortest possible time. In the prairies, the Argentinian pampas, the Ukrainian steppes, and the downs of Australia combine harvesters reap, thresh, winnow, and sack the grains almost as soon as the stalks are gathered. One distinct drawback of this form of extensive mechanized farming is the consequent low yield. For example, the average yield of wheat in the prairies is about 23 bushels per acre. 1 bushel is approximately equivalent to 60 pounds in weight or 8 gallons in volume. In the pampas and the Australian downs, the yields are even lower, not more than 20 bushels per acre. In comparison, the wheat yield in countries that practice intensive farming are much higher, at times almost thrice the yield. It is 50 bushels per acre in the United Kingdom, 57 bushels in Denmark, and almost 59 bushels in the Netherlands. This is attributed to the greater attention given to a smaller piece of land, which is not practicable in the extensive wheatlands where a farmer owns anything from 600 to 40,000 acres as in the prairies. But if we consider the yield per man, this is very much higher in the extensive farms. In this respect, the sparsely populated temperate grasslands of the mid-latitudes produce the greatest quantity of wheat per capita amongst the world's wheat-growing nations. They are, naturally, the greatest wheat exporters. 3/4 of Canada's 10 million tons of annual wheat production is exported, mainly to Europe, which does not produce sufficient wheat to feed the very dense population, despite the high wheat yield. Europe's wheat needs are so great that shipments of wheat and flour arrive at the ports from almost every part of the temperate grasslands, from the USA, Argentina, Uruguay, Australia, and Russia. Three-quarters of the world's wheat is winter wheat, i.e. wheat sown in winter or late autumn. It is a hard wheat with a low moisture content, being ripened in the hot, sunny, continental summer. It is best for bread making and is extensively traded. Polewards, where the winter temperatures are too cold for the wheat seedlings to survive, spring wheat is grown. It is the less important soft wheat, more suitable for making cakes, biscuits, and paste rather than bread. In North America, winter wheat is dominant south of the Great Lakes in USA, while spring wheat is sown mainly in the Canadian prairie provinces of Alberta, Saskatchewan, and Manitoba, Figure 151. Scientific plant breeding has now devised cold-resistant varieties that can mature within 110 days. This has resulted in the northward extension of the wheat cultivation into the Peace River region in Canada. In the warmer, wetter regions, maize is increasingly grown. 3. Pastoral farming. When pioneer settlers first moved into the temperate grasslands, the temperate continental, steppe, climate 161. A cargo ship loading grain for export at Port of Thunder Bay, Ontario. Figure 151 wheat production and ranching in the North American grasslands. Figure 152 sheep, cattle, wheat, and maize production in southern South America. Were very few animals. The natural conditions suit animal farming. Subsequently, cattle, sheep, pigs, and horses were introduced, and they proved very successful. With the development of refrigerated ships in the late 19th century, the temperate grasslands became major pastoral regions, exporting large quantities of beef, mutton, wool, hides. Milk, butter, cheese, and other dairy products are also important in some parts of the North American grasslands. The development was particularly spectacular in the southern hemisphere, figures 152, 153, and 154, where the winters are milder and the rainfall is more evenly distributed. The original tuft grass was plowed up and replaced by sown alfalfa. The semi-wild cattle in the pampas were either crossed with or replaced by the imported pedigree stock from Europe. Soon the pampas became so involved with the pastoral industry that it took the lead in the world's export of beef. Large estancias ranches were established, linked to the frigorificos meat packing factories in the coastal ports by a dense network of roads and railways. The growth was rapid in towns like Buenos. Wheat, cattle, sheep, maize. Figure 153 agriculture in the veld of southern Africa. Figure 154 the wheat, maize, cattle, and sheep producing areas of Australia. Note the import the downs. 162 Part 2. Weather, climate, and vegetation. Aries, Bahia Blanca, Fray Bentos, and Montevideo became known throughout the world. This is also true of other temperate grasslands. Much beef is produced in the Great Plains of USA, and Australia became the world's leading wool exporter, accounting for a third of its total production. In the Eurasian steppes, too, increasing emphasis is being placed on the ranching of animals for meat production. Questions and exercises. 1. Compare and contrast tropical and temperate grasslands in respect of a. Their seasonal responses to climatic changes, b. Their economic importance too. Each of the following temperate grasslands is paired with an important aspect of its economic life. For any three of them, give a reason to count. A. Asiatic steppes, nomadic herding. B. Canadian prairies, spring wheat cultivation. C. Argentine pampas, beef cattle ranching. D. S. African veldt, maize growing. E. Australian downs, sheep grazing. 3. Explain why. A. The annual temperature range of Winnipeg, Canada is much greater than that of Pretoria, South Africa. B. When Chinooks are more frequent in the prairies, the winters are milder. C. Wheat yields in the pampas are much lower than those of Denmark. 4. The temperate grasslands are the granaries of the world. To what extent this is true? Account for the geographical factors that make this possible. 5. Write a geographical account of the international trade in wheat. The warm temperate eastern margin. China type climate. Distribution. This type of climate is found on the eastern margins of continents in warm temperate latitudes, just outside the tropics, figure 155. It has comparatively more rainfall than the Mediterranean climate in the same latitudes, coming mainly in the summer. It is, in fact, the climate of most parts of China, a modified form of monsoonal climate. It is thus also called the temperate monsoon or China type of climate. In southeastern USA, bordering the Gulf of Mexico, continental heating in summer induces an inflow of air from the cooler Atlantic Ocean. Though less pronounced, the overall climatic features resemble those of the China type. It is sometimes referred to as the Gulf type of climate. In the southern hemisphere, this kind of climate is experienced along the warm temperate eastern coastlands of all the three continents, in New South Wales with its eucalyptus forests, and Natal, where sugar cane thrives, and in the maize belt of the Parana-Paraguay-Uruguay basin, as the regions are influenced by the onshore trade winds all year round. Without any monsoon variations, the climate cannot be described as temperate monsoon. It is sometimes referred to as the natal type of climate. The warm temperate eastern margin climate is typified by a warm moist summer and a cool, dry winter. The mean monthly temperature varies between 40 degrees Fahrenheit and 82 degrees Fahrenheit, 5 degrees Celsius and 28 degrees Celsius, and is strongly modified by maritime influence. Occasionally, the penetration of cold air from the continental interiors may bring down the temperature to freezing point. Though frosts are rare, they occasionally occur in the colder interiors. For most of the time, it is pleasantly warm. The relative humidity is a little high. 164 Part 2, Weather, Climate, and Vegetation. In midsummer, when the heat becomes oppressive and can be very trying to the white settlers, e.g. in Natal, rainfall is more than moderate, anything from 25 inches to 60 inches, 635 millimeters to 1,525 millimeters. This is adequate for all agricultural purposes, and the warm, temperate eastern margin climate supports a wide range of crops. Areas which experience this climate are very densely populated. Another important feature is the fairly uniform distribution of rainfall throughout the year. There is rain every month, except in the interior of central China, where there is a distinct dry season. Rain comes either from convectional sources or as orographic rain in summer, or from depressions and prolonged showers in winter. Local storms, e.g. typhoons and hurricanes, also occur. There is a good deal of variation in detail within the eastern margins, and it is essential to examine them by reference to specific areas where the local factors affect the climates. We shall subdivide them into three main types. 1. The China type, Central and North China, including southern Japan, temperate, monsoonal. 2. The Gulf type, Southeastern United States, slight monsoonal. 3. The Natal type, all the warm temperate eastern margin, non-monsoonal areas of the southern hemisphere, including Natal, eastern Australia and southern Brazil, Paraguay, Uruguay, and northern Argentina. 1. The China type. This is the most typical climate of the warm temperate eastern margin. The Great Land mass of the Asiatic continent with its mountainous interior induces great pressure changes between summer and winter. Intense heating in the heart of Asia sets up a region of low pressure in summer, and the tropical Pacific airstream is drawn in as the rain-bearing southeast monsoon. Heavy precipitation occurs in most parts of China, decreasing inland. As illustrated in Figure 156a, the wettest months of Nanjing are in summer, with half of its annual rainfall falling in June, July, and August. 22 inches out of 44 inches, though the monsoon does not burst as suddenly, nor pour as heavily as in India. In winter, a steep pressure gradient is set up between the cold interiors of Mongolia and Siberia and the warmer Pacific coastlands. Data, 1991 to 2021. JFMAMJJASOND range/total. Temp degrees C 3.15.410.316.121.124.628.027.223.811.55.07. F 37.541.750.661.069. 976.3 by 82.4, 81.8.154.152.641.045. Precip. MM 5660 83 98 trillion 125 billion 222 million 203,178 84 55 56 36 12 56. In 22334 87322 144. Figure 156a, warm temperate eastern margin climate in the northern hemisphere, China type. Place Nanjing, China, 32 degrees north, 119 degrees east, altitude 12 meter or 39 feet, annual temperature range 45 degrees Fahrenheit or 7 degrees Celsius, annual precipitation 49 inches or 1,256 millimeters. The continental polar airstream flows outwards as the northwest monsoon, bitterly cold and very dry. There is little rain but considerable snow on the windward slopes of Shandong as the cold winds are warmed and moistened. In fact, less than 8.4 inches are recorded in Nanjing during the cold season from October to February. Another characteristic feature of the China type of eastern margin climate is the great annual temperature range. As shown in the temperature graph of Nanjing, there is a difference of about 45 degrees Fahrenheit or 25 degrees Celsius between July, 82.4 degrees Fahrenheit or 28 degrees Celsius, and January, 37.5 degrees Fahrenheit or 3.1 degrees Celsius. Further north, the range is even greater, 47 degrees Fahrenheit or 26 degrees Celsius in Xianchang'an, and about 56 degrees Fahrenheit or 31 degrees Celsius in Beijing. In the warmer south and along the coast, the temperature differences are much less, e.g. about 25 degrees Fahrenheit or 14 degrees Celsius in Guangzhou, 24 degrees Fahrenheit or 13 degrees Celsius in Shantou, and only 22 degrees Fahrenheit or 12 degrees Celsius in Hong Kong. Another climatic feature associated with the China type of climate in southern China is the occurrence of typhoons, intense tropical cyclones that originate in the Pacific Ocean and move westwards to the coastlands bordering the South China Sea. They are most frequent in late summer, from July to September, and can be very disastrous. The winds blow with the warm temper 8 eastern margin, China type, climate 165. Tremendous strength, the sky is overcast and there are torrential downpours, as much as 24 inches. 610 millimeters in a day have been recorded, and flooding is widespread. Millions of people across large parts of eastern China were affected by Typhoon Wifa, which hit the area in September 2022. 2. The Gulf type. The Gulf Atlantic regions of the United States experience a type of climate similar to that of central China, except that the monsoonal characteristics are less well established. There is no complete seasonal wind reversal, for the pressure gradient between mainland America and the Atlantic Ocean is less marked. As can be seen from the graph in Figure 156b, for Miami, Florida, the difference in temperature between midsummer, July, 82 degrees Fahrenheit or 28 degrees Celsius, and midwinter, January, 68 degrees Fahrenheit, or 20 degrees Celsius, is only 14 degrees Fahrenheit or 8 degrees Celsius. The warm Gulf Stream and the onshore trade winds help to bring about this narrow range of temperature. Data, 1991 to 2021. JFMAMJ JAS degree ND range / total. Temp degree C 20.5 21.4 22.3 24.0 25.6 27.0 27.8 28.0 27.2 25.8 23.4 22.07.5 degree F 68.8 70.5 72.2 75.3 78.1 80.7 82.0 82.3 81.0 78.4 74.2 71.6 13.5 Precip MM 5240 153 57 93 trillion 163 billion 119 million 155,162 118 55 for 511 13 in 21223646642144. Fig. I56b, warm temperate eastern margin climate in the northern hemisphere, Gulf type. Place Miami, Florida, USA, 26 degrees north, 80 degrees west. Altitude 11 m or 36 feet. Annual temperature range 13.5 degrees Fahrenheit or 7.5 degrees C. Annual precipitation 44 inches or 1,113 millimeters. Summers are warm and pleasant, Miami being an important holiday resort, and it rarely snows in winter. The annual rainfall is heavy with 44 inches or 1,113 millimeters in Miami, 54 inches or 1,183 millimeters. In New Orleans, 45.6 inches or 1,159 millimeters in Montgomery, and 48 inches or 1,219 millimeters in Charleston. There is no distinct dry period as in monsoon lands, and the abundant moisture has stimulated extensive cultivation of cotton and maize, in the cotton and corn belts, both of which are the world's leading areas for these crops. From the rainfall pattern in Figure 156b, it is clear that there is a tendency towards a summer maximum, brought by the onshore trade winds which swing landwards from the Atlantic. The amount of rain is increased by frequent thunderstorms in summer and by hurricanes in September and October. Some stations, e.g. Montgomery and Alabama, also show a secondary maximum in late winter when cyclonic activities are greatest. Sometimes, violent tornadoes occur due to intense local heating on land. Though these whirling storms follow only a narrow path in the Central Plain, Mississippi Basin, they leave behind a trail of destruction. 3. The natal type. There are 3 distinct areas on the eastern coast of the southern continents, lying just south of the Tropic of Capricorn, which experience this type of climate. The narrowness of the continents and the dominance of maritime influence eliminate the monsoonal elements which characterize the corresponding climates of the northern hemisphere. The southeast trade winds bring about a more even distribution of rainfall throughout the year, as illustrated by the climatic graph for Sydney, Australia. It has a mean monthly precipitation of 4 inches, which is adequate for most agricultural activities. The annual amount of 48 inches is fairly representative of this climatic type in the southern hemisphere. The annual precipitation of Durban and Natal is 35 inches, or 890 millimeters, and that of Asunción in Paraguay is 64 inches, or 1,630 millimeters. The osage of depressions across the southern edges of the warm, temperate eastern margins results in a slight autumn or winter maximum, typified by Sydney. Figure 156c, which has its wettest months in March, April, May, June, and July, the autumn-winter part of the year. The rain comes in prolonged showers. Much of the water seeps into the ground, and there is little runoff, so the regions are well suited to agriculture and are some of the best settled parts of the southern continents. Another feature to note is the small annual temperature range, without any really cold month. The annual range for Sydney is 18 foot F, 10 degrees Celsius, and the 166 Part 2, Weather, Climate, and Vegetation. JF Mamjasint RF ** 7 CC 22. 822.621.3 18.8 15.8 13.6 12,713.5 16.0 18.0 19.7 21.4 10.1 temp 1 colon T TJ colon FI asterisk F 73.1 72.670 for 65.9 60.4 56.5 54.9 56.4 60.8 64.5 67 for 70.6 18.2 I 1 ILJ. In 3:4333 feet 3 inches 22 feet 2 inches 232 feet 36 inches. Data, 1991 to 2021. mm 79 105 86 89 85 101 57 59 54 59 feet 77 inches 61 912 precip. I1 1. Place altitude. Sydney, New South Wales, Australia, 34 degrees south, 151 degrees east. 27 m or 89 feet. Annual temperature range 18.2 C for 10.1 cc. Annual precipitation 35.9 inches or 912 millimeters. Figure 156C, warm temperate eastern margin climate in the southern hemisphere, natal type. Coldest month is 23 degrees Fahrenheit above freezing, about 55 degrees Fahrenheit or 12.7 degrees Celsius in July. The range is smaller for Durban, only 13 degrees Fahrenheit 7 degrees Celsius, with July, the coldest month at 63 degrees Fahrenheit 17 degrees Celsius. In Asuncion, the range is 19.3 degrees Fahrenheit, 10.7 degrees C, and the climate is pleasantly warm all the time. However, the southern continents also have violent local storms, which, though not as severe as the typhoon, hurricane, or tornado, are nevertheless quite significant. The southerly burster, a violent cold wind blowing along the coast of New South Wales, leads to a sudden fall in temperature. It is most frequent in spring and summer. The corresponding cold wind in Argentina and Uruguay is the pampero, which is often accompanied by thunder and lightning besides the rain and dust. In southeastern Africa, a hot, dry wind called the berg wind comes down from the interior plateau. It is comparable to the Fin or Chinook and brings unpleasantly high temperatures and oppressive weather. Natural vegetation. The eastern margins of warm temperate latitudes have a much heavier rainfall than either the western margins or the continental interiors and thus have a luxuriant vegetation. The lowlands carry both evergreen broad-leaved forests and deciduous trees quite similar to those of the tropical monsoon forests. On the highlands are various species of conifers such as pines and cypresses, which are important softwoods. As the perennial plant growth is not checked by either a dry season as in the Mediterranean or a cold season as in the cool temperate regions, conditions are well suited to a rich variety of plant life including grass, ferns, lianas, bamboos, palms and forests. The well-distributed rainfall all the year round makes the regions look green at all times. It is interesting to note that the warm temperate eastern margins are the homes of a number of valuable timber species. In eastern Australia, the most important are eucalyptus trees with scanty foliage and thick fern undergrowth. Some of the eucalyptus are very tall, over 250 feet, and they make hardy timber. The Australian Alps of Victoria and the Blue Mountains of New South Wales have great reserves of temperate eucalyptus forests that make a part of the timber exports of Australia. From the forests of southeastern Brazil, eastern Paraguay, northeastern Argentina come valuable warm temperate timbers such as the Parana pine and the quebracho axebreaker, an extremely hardwood used for tanning, and wild yerba mate trees, from which the leaves are gathered for making Paraguay tea. Today, large yerba mate plantations have been established to produce Paraguay tea, an increasingly important export item of Paraguay. In Natal, the warm Mozambique current encourages heavy precipitation along the coast, and many species of palm trees thrive. The highlands yield extensive forests of chestnuts, ironwood, and blackwoods. An unusual occupation is the commercial cultivation of wattle trees and plantations for tanning extracts and for use in Natal's coal mines as pit props. The forests of China and southern Japan also have considerable economic value and include oak, camphor, camellia, and magnolia. Unfortunately, the tremendous population pressure in the two countries has caused much of the original forest to be cleared for fuel or crop cultivation. Deforestation has resulted in many barren hill slopes that are still feeling the impact of soil erosion. The Gulf states of USA have lowland deciduous forests. The trees grow close together. The warm temperate 8 eastern margin, China type, climate 167, with thick undergrowth and leafy branches. Walnut, oak, hickory, and maple are some of the more common species, while in the more sandy regions grow pines. Much of the forest cover has given way to the cultivation of subtropical crops like cotton, maize, and fruits. Economic development. The warm temperate eastern margins are the most productive parts of the middle latitudes. There is adequate rainfall, no prolonged drought, and the cold season is warm enough for most crops to survive. Thus, the growing season is almost continuous, though summer is the busiest part of the farming year. Monsoon China, together with southern Japan and other parts of the eastern margin climatic zone, accounts for almost a third of the world population. Food has to be raised to feed the teeming population. The hills are terraced, fields are irrigated, and agriculture is extended to the limits of production. It is no exaggeration to say that the temperate monsoon lands are the most intensively tilled parts of the earth. Besides the widespread cultivation of maize and cotton in the corn and cotton belts of USA, fruit and tobacco are also grown. Rice, tea, and mulberries are extensively grown in monsoon China. Elsewhere are found other products of economic importance, e.g. cane sugar in Natal, coffee and maize in South America, and dairying in New South Wales and Victoria. Let us now examine some of the regions more closely. 1. Farming in monsoon China. Undoubtedly, this is the world's greatest rice-growing area. About a third of the world's rice is grown in China, though the huge population of 1,410 million leaves very little for export. In fact, in normal years, imports of rice and other food grains are essential. The Chinese peasants raise wet paddy or swamp rice in flooded fields that call for endless hard labor for the greater part of the year. It is said that nowhere else is there so much manual labor devoted to raise a food crop that gives so little economic return. Farming is usually on a subsistence basis. Despite increasing mechanization and paddy cultivation, very few farmers actually make use of new machines because they are expensive and may be impractical in some areas. The only progress that has been made is towards double or treble cropping, which has increased the annual total rice production. Terraced land for rice farming in Japan. When compared with the rapid population growth/th of the rice-eating nations, the increased production has in no way relieved the critical food problem of monsoon Asia. Furthermore, milled rice, which forms the staple food of the Orient, is a seriously deficient diet. The people are therefore not only inadequately fed, also physically undernourished. Monsoon China has all the ideal conditions for paddy cultivation: a warm climate, moderately wet throughout the year, and extensive lowlands with fertile moisture-retentive alluvial soil, which, if necessary, can be easily irrigated. The land has been tilled from generation to generation, and yet there is little deterioration in soil fertility. The muddy irrigation water from the river basins is silty and constantly brings new soil to the fields. The water is greatly enriched during floods, though these are far less frequent now, with the improvement made in flood control by the communist regime. In practice, the Chinese peasants add all kinds of organic waste to enrich their fields: rice straw, ashes, clippings, animal dung, refuse, and last but not least, human manure. The most intensively farmed areas are the basins of the Sikiang, Yangtze, and Huang Ho, which are also the most densely peopled areas. The eastern coastlands are equally important. As the flatlands are insufficient for rice cultivation, farmers move up the hill slopes and grow paddy on terraced uplands. The artificial terraces retain the excess water as it flows down the slope. Besides rice, the other important crops are tea, grown for home consumption, and mulberry leaves gathered for feeding silkworms, though sericulture is declining. 2. Agriculture in the Gulf states. Agriculture in the Gulf states of America differs from that of monsoon China, though they have a similar climate. 168 Part 2. Weather, climate, and vegetation. Lack of population pressure and the urge to export make rice cultivation a relatively unimportant occupation. It is grown only in a few areas in the southern coastlands of the Mississippi Delta. Americans are bread eaters, and one can well imagine how insignificant is rice in the economy of the Gulf states. The most important crops are corn, cotton, and tobacco. A. Corn. The chief food crop raised is, in fact, corn or maize. The humid air, the sunny summer, and the heavy showers suit the crop well. It is grown right from the Gulf Coast to the Midwest south of the Great Lakes, with the greatest concentration in the corn belt of Nebraska, Iowa, Indiana, and Ohio. The region accounts for more than half the world's production of corn, but only 3% of the world's export. This is because most of the corn is used for fattening animals, mostly farm animals. The fattened animals are then sold to the meat plants in Chicago and Cincinnati. Very little corn is consumed as a staple food in America, though the cereal originated in America as the food crop of the native Indian people. Apart from its ease of cultivation, in respect of soil, climatic, and labor requirements, corn's most outstanding feature is its prolific yield. It gives almost twice as much food, mainly starch, per acre as wheat or other cereals. This explains why it is so widely cultivated in both the warm temperate and the tropical latitudes. B. Cotton. Of the cash crops grown in the Gulf states, none is comparable with cotton. In the Deep South, the fiber is so vital to the USA is not the only important cotton producer. India has a flourishing cotton textiles industry. This image showcases a large-scale fabric spool used in an Indian factory to facilitate the meticulous process of dyeing textiles. Economic well-being of the Southerners that cotton is king. It shapes the destiny of the Southern states, being directly responsible for their trade, prosperity, and politics. In the early days of America, millions of black people were brought from Africa as slave labor for the cotton plantations because the climate was too hot for the white settlers to harvest the cotton themselves. Although slavery was abolished in the 19th century, a large number of the black people are still poor and underprivileged. The Gulf type of climate is undoubtedly the best for cotton growing. It's long, hot growing season, with 200 days frost-free and a moderately high temperature of about 75 degrees Fahrenheit 24 degrees Celsius permits the crop to grow slowly and mature within 6 months. Like most fibers, cotton likes ample rain, and an annual precipitation of around 40 inches or 1,016 millimeters is essential. In fact, an adequate moisture supply coming from frequent light showers, with bright sunshine between them, gives the highest yield. Fine quality cotton also comes from irrigated fields, and the drier west provided sufficient water is supplied during the growing season. The Cotton belt is thus limited by the 20-inch isohyet on the west and 77 degrees Fahrenheit or 25 degrees Celsius isotherm in the north, within which there are at least 200 days without frost. In the very south, in the Gulf lands, the heavy rainfall damages the lint. This area is therefore less suitable for cotton and is devoted to citrus fruits, cane sugar, and market gardening, as in Florida. The commercial cultivation of cotton is now concentrated only in the most favorable areas, which are the Mississippi floodplains, the clayey Atlantic coastlands of Georgia and South Carolina, the black prairies of Texas, and the red prairies of Oklahoma. Figure 157 shows the chief cotton areas of the USA. Generally speaking, the best cotton comes from the maritime districts where the sea breezes and the warming effect of the ocean are most strongly felt. The sea island cotton grown in the islands off the coast of Georgia and South Carolina is long stapled. The fibers are between 1 to 5 and 2 to 3 inches in length and is the best in the world. Further inland, the staples are shorter, about an inch long. This is typical of the bulk of the American cotton. Besides the problem of soil exhaustion and erosion caused by prolonged cotton cultivation, the most dreaded enemy of the cotton belt is the boll weevil. The warm temper ale eastern margin, China type, climate 169. Figure 157 the cotton belt of the USA. The pest multiplies so rapidly that a pair of boll weevils, if left unchecked, will breed over 10 million grubs within a single season. The pest is responsible for the westward migration of the cotton belt. When it first appeared in 1892 in the eastern USA, it attacked the sea island cotton. Aerial spraying with insecticides and a thorough burning of old cotton stalks have been found effective in eliminating the boll weevil. C. Tobacco. Another interesting crop closely associated with the Gulf type of climate is tobacco, which incidentally is also a native crop of America. Though it is cultivated in many parts of the world, and the finished products range from Turkish tobacco to Havana cigars and Malaysian cheroots, there is none so universally known as the Virginia tobacco. It is the raw material from which most of the world's cigarettes are blended to suit the smoker's taste. The humid atmosphere, the warmth, and the well-drained soils of the Gulf states enable tobacco to be successfully cultivated in many of the eastern states of USA, e.g. Virginia, Maryland, Georgia, North and South Carolina, Kentucky, and Tennessee. No less than half the tobacco that enters international trade comes from these states. 3. Crop cultivation in the eastern margins of the southern hemisphere. A close look at the economic map of the southern hemisphere will at once reveal the agricultural importance of its eastern margins, which experience a natal type of climate. The warm, moist summers and frost-free winters not only support many crops but also animals. In the coastlands of natal, sugarcane is the dominant crop, followed by cotton and tobacco in the interior. Recent expansion of these crops has come about with improved irrigation. Maize is extensively cultivated for use both as mayalai, an important food item for Africans, and silage, an animal fodder for cattle rearing. But in comparison with the maize yield of the corn belt of USA, the African yield is rather low, often only half. Improvements can be made if farmers attempt some form of crop rotation to arrest the rapid rate of soil exhaustion in regions of maize monoculture. Scientific manuring and better methods of cultivation would raise yields. In South America, where rainfall is less than 40 inches, there is much grassland on which many cattle and sheep are kept for meat, wool, and hides. It is the continuation of the Argentinian pampas. The mild winters mean that the animals can be kept out of doors all the time. The extensive natural pastures provide valuable forage for both cattle and sheep. The products from these two kinds of domesticated animals account for over 3/4 of the annual exports of Uruguay. The remaining exports come mainly from wheat and flax. Further north in southern Brazil, the rainfall increases to more than 40 inches, 1,016 millimeters, and forest gradually replaces grass. Here the important occupations are the cultivation. 170 Part 2, Weather, Climate, and Vegetation of yerba mate Paraguay tea, and the lumbering of Araucaria or Parana pine. Cattle and sheep are reared, and maize and cane sugar are grown. In eastern Australia, the moist trade winds bring heavy rainfall to the coastal districts, and these are thickly wooded. Giant eucalyptus trees rise one above the other right up the eastern highlands. But with the influx of European immigrants, much of the forest has been cleared for settlement and dairying. The eastern margin of New South Wales was, in fact, the earliest part of the continent to be colonized, beginning with Port Jackson, the present site of Sydney. The region is now the chief source of Australia's milk, butter, and cheese, besides cotton, sugarcane, and maize, which are increasingly grown in the north. Questions and exercises. 1. What do you understand by the China type of climate? Locate on a world map the regions which experience this type of climate, and describe the broad pattern of their agricultural activities. 2. Describe the main factors which affect the climate and vegetation of any three of the following regions. A. The Gulf states of USA. B. The Iberian Peninsula. C. Borneo. D. Tasmania. E. Ceylon. 3. Give a reasoned account of any two of the following. A. Cotton cultivation in the United States of America. Give a reasoned account of any two of the following. A. Cotton cultivation in the United States of America. B. Paddy growing in monsoon China. C. Dairying in eastern Australia. D. Lumbering in Canada. 4. Analyze, in relation to latitude and other geographical factors, the following climatic figures. LOC 3 Yuan Outli UUC. Temp. Mean July a Key Qfi. IPI to the power of IKJ. HHHB Singapore 1 foot in, 104 degrees east 50 feet 78.4, F 80.6 degrees Fahrenheit 2.2 degrees Fahrenheit 93.1 inches. Santiago 33 foot 5, 71 carat 1,700 feet 71 to 9, F 48.1, F 23.8 degrees Fahrenheit 204 inches Shanghai 31 degrees north. 121 degrees east 20 feet 40.7 inch F 82.5 degrees Fahrenheit 41.8 degrees Fahrenheit 52.2 inches. 5. Give an explanatory account of any three of the following. A. Local storms e.g. typhoon, hurricane, pampero, are often associated with the warm, temperate eastern margin climate. B. The predominant forest trees of eastern Australia are eucalyptus. C. The USA is the world's largest corn producer and exporter, contributing 31% of the world's total corn production and nearly 38% of the world's total corn exports. D. Farming in monsoon China is usually on a subsistence basis, and the peasants are permanently land-hungry. The cool temperate western margin, British type climate. Distribution. The cool temperate western margins are under the permanent influence of the westerlies all round the year. They are also regions of much cyclonic activity, typical of Britain, and are thus said to experience the British type of climate. From Britain, the climatic belt stretches far inland into the lowlands of North West Europe, including such regions as northern and western France, Belgium, the Netherlands, Denmark, western Norway, and also northwestern Iberia. There is so much oceanic influence on both the temperature and the precipitation that the climate is also referred to as the Northwest European maritime climate. In North America, high Rockies prevent the onshore westerlies from penetrating far inland, and the British type of climate is confined mainly to the coastlands of British Columbia. In the southern hemisphere, the climate is experienced in southern Chile, Tasmania, and most parts of New Zealand, particularly in South Island. The surrounding large expanses of water have increased the maritime nature of the climate here. Figure 158. Climate. Temperature. The mean annual temperatures are usually between 40 degrees Fahrenheit and 60 degrees Fahrenheit, 4.4 degrees Celsius and 15.6 degrees Celsius. The warmest month in London, as illustrated in the temperature graph of London figure 159a, is 64 degrees Fahrenheit, 17.8 degrees Celsius, and the coldest month is just around 40 degrees Fahrenheit, 4.8 degrees Celsius, thus giving an annual temperature range of only 23.4 degrees Fahrenheit, 13 degrees Celsius, which is comparatively small for its latitude. 51 degrees north summers are, in fact, never very warm. Monthly temperatures of over 65 degrees Fahrenheit, 18.3 degrees Celsius, even in midsummer, are rare. Heat waves, as they are popularly called, that is a short spell of warm summer days, are a welcome feature in such cool temperate latitudes, where people do not often see enough of the sun. The climate is Figure 158 regions with cool temperate western margin climate, British type. 172 Perry 2, weather, climate, and vegetation. Chmam Jason D. Degree C 4.8 4.9 6.79.4 12.7 15.7 17.8 17.3 15 11.8 7.8 5.3 temp. I F 1 T colon J diamond suit. T 46 48 44 48.9 54.8 60.3 64 63.1 59.1 53.2 46 41.6 MM 59 50 47 54 57 60 59 65 51 60 67 61 Precip in 21122222222. Data 1991 to 2021. Place AJ Wuda annual precipitation. Annual temperature range. London, British Isles 51 CN 0 CW 5.4 m or 18 feet. 670 millimeters or 26.4 inches 23.4 T 647 F 40.6 degree F or 13 degrees Celsius 17.8 cc 4.8 cc. Southern Hemisphere is even more equable. Lack of continental land masses in Tasmania, New Zealand, and southern Chile means that extremes of temperature are not likely at all. Hobart has midsummer temperatures of not more than 61 degrees Fahrenheit 16 degrees Celsius, while its coldest month in July. Winter in the southern hemisphere is barely below 44 degrees Fahrenheit 6.6 degrees Celsius. The annual temperature range is reduced to only 16.3 degrees Fahrenheit 9 degrees Celsius, which is unusual for the middle latitudes. This is in fact the average figure for all the maritime stations in the southern continents where insularity overrides all other factors. The annual ranges of other southerly stations are Dunedin 15.8 degrees Fahrenheit 8.9 degrees Celsius, Christchurch 19.7 degrees Fahrenheit 11 degrees Celsius, Valdivia 16 degrees Fahrenheit 9 degrees Celsius, and Punta Arenas 14 degrees Fahrenheit 7.6 degrees Celsius. The last two stations, Valdivia and Punta Arenas, are in southern Chile. The oceanic influences not only keep the winters very mild but also keep the summers cool. Some geographers have described these southerly islands as the favored isles, which has much truth in it. Precipitation. The British type of climate has adequate rainfall throughout the year with a Figure 159, a British type of climate in the Northern Hemisphere. Ideal for maximum comfort and mental alertness. People can work for long hours without feeling drowsy and lethargic as they do in the tropics. There appears to be some direct relationship between climate and people's output of work. It is no wonder that the cool temperate regions are some of the most advanced parts of the world. Winters are abnormally mild, and no stations actually record mean January temperatures below freezing point. In northwestern Europe, this is attributable to the warming effect of the warm North Atlantic drift and the prevalence of the southwesterlies. It has been estimated that the marine stations of the region are almost 25 degrees Fahrenheit minus 3.8 degrees Celsius warmer in January than corresponding stations of the same latitude in the interiors. Night frosts do occur and snow falls in winter too. Sometimes, unusual cold spells, caused by the invasion of cold polar continental air from the interiors, may hit the western margins for a number of weeks. The climate of the maritime regions as a whole may be described as equable with moderately warm summers and fairly mild winters. It is quite apparent from Figure 159b of Hobart, Tasmania that the British type of climate in the data, 1991 to 2021. Place altitude annual precipitation. Annual temperature range. Hobart, Tasmania, 43 degrees south, 147 degrees east, I 17 m or 56 feet. 670 millimeters or 26.4 inches. 16.3 f, 60.1 f, 43.8 f, or 9 degrees Celsius, 15.6 to 6.6 degrees Celsius. Figure 159, B, British type of climate in the southern hemisphere. The cool temperate western margin, British type, climate 173. Tendency towards a slight winter or autumn maximum from cyclonic sources. Since the rain-bearing winds come from the west, the western margins have the heaviest rainfall. The amount decreases eastwards with increasing distance from the sea. Though both the quoted stations, London and Hobart, have 26 inches, 670 millimeters of precipitation a year, the actual amount varies quite considerably from place to place. Relief can make great differences in the annual amount. For example, the western slopes of the southern Alps of South Island, New Zealand, have as much as 200 inches, 5,080 millimeters of rainfall, mainly orographic rain, while the Canterbury Plain, in the rain shadow area, has as little as 25 inches, 635 millimeters. Similarly, the Lake District of Britain has well over 100 inches, 2,540 millimeters, in contrast to only 24 inches, 609 millimeters, in East Anglia. It is therefore difficult to say how much annual rainfall is typical of the British type of climate. Perhaps, a useful guide would be to confine ourselves to lowland regions which normally have 20 to 40 inches, 500 to 1,000 millimeters, a year. E.g. 28 inches, 710 millimeters, in Paris, 36 inches, 914 millimeters, in Dublin, 54 inches, 1,370 millimeters, in Seattle, and 31.7 inches, 806 millimeters, in Dunedin. Generally, western coastal stations are wetter. Vancouver has 92.6 inches, 2,351 millimeters, of rain, Valdivia 77.6 inches, 1,972 millimeters, and Bergen 97 inches, 2,464 millimeters. They are exceeded in the annual amount only by the highland stations as mentioned earlier. The seasons. As in other temperate regions, there are 4 distinct seasons in the British climate type. Light snowfalls can be expected in the winter months, normally only of short duration because of the comparatively mild weather. But over the highlands, such as the Scandinavian mountains and the American Rockies, snowfall is heavy and feeds the mountain glaciers that move down the valleys. Winter is the season of cloudy skies, foggy and misty mornings, and many rainy days from the passing depressions. Out at sea, gales are frequent and can be dangerous to shipping. Spring is the driest and the most refreshing season when people emerge from the depressing winter to see everything becoming green again. This is followed by the long, sunny summer. Sunbathers, picnickers, and sightseers are out in the open to enjoy themselves. With the roar of gusty winds and the fall of golden leaves, autumn is ushered in, and the cycle repeats itself. This type of climate with its 4 distinct seasons is something that is conspicuously absent in the tropics. Natural vegetation. The natural vegetation of this climatic type is deciduous forest. The trees shed their leaves in the cold season. This is an adaptation for protecting themselves against the winter snow and frost. Shedding begins in autumn, the fall season, during which the leaves fall and are scattered by the winds. The golden brown leaves and the naked branches present a very interesting scene. When they are in leaf, the deciduous trees have typical rounded outlines with thick trunks and outspreading branches that yield valuable temperate hardwood. Some of the more common species include oak, elm, ash, birch, beech, poplar, and hornbeam. In the wetter areas grow willows, alder, and aspen. Elsewhere are found other species, e.g. chestnut, sycamore, maple, and lime. Oak, beech, elm. 1. Poplar. Some deciduous trees. Unlike the equatorial forests, the deciduous trees occur in pure stands and have greater lumbering value from the commercial point of view. The open nature of the forest with sparse undergrowth is useful in logging operations. Easy penetration means much cost can be saved in the movement of the logs. The deciduous hardwoods are excellent for both fuel and industrial purposes. In Tasmania, the temperate eucalypts are also extensively felled for the lumbering industry. Higher up the mountains in the Scandinavian highlands, the Rockies, southern Andes, and the southern Alps of New Zealand, the deciduous trees are generally replaced by the conifers, which can survive a higher altitude, a lower temperature, and poorer soils. 174 Part 2. Weather, climate, and vegetation. Economic development. A very large part of the deciduous woodlands have been cleared for fuel, timber, or agriculture. The dense population necessitates the removal of the lowland forests, particularly for the plow. In Britain, there is only 13% of the original forest left. A large range of cereals, fruits, and root crops are raised, mainly for home consumption rather than for export. Northwest Europe, which includes some of the most crowded parts of the globe, has little surplus for export. It is, in fact, a net importer of food crops, especially wheat from almost all parts of the wheatlands for bread making and other food items. The region differs from many others in its unprecedented industrial advancement. The countries are concerned in the production of machinery, chemicals, textiles, and other manufactured articles rather than agriculture. Fishing or lumbering, though these activities are well represented in some of the countries. Fishing is particularly important in Britain, Norway, and British Columbia, since the manufacturing aspect of industrial geography will be dealt with in much greater detail in Chapter 23, we shall deal here with the agricultural development of the region. 1. Market gardening. Though market gardening is practiced throughout the world wherever there is a large urban population, nowhere else is it so highly specialized as in Northwest Europe. Several factors account for this. All the Northwestern European countries, Britain, France, Germany, Benelux, and Denmark, are highly industrialized and have high population densities. There are more towns and cities than in other continents despite its small size. It is understandable that the demand for fresh vegetables, green salads, eggs, meat, milk, and fruits will be tremendous. The city dwellers, the factory workers, and the civil servants who make up the bulk of the urban population consume large quantities of fresh provisions daily, and these must be provided by local farmers if freshness of the produce is to be ensured. In Northwestern Europe, intensive market gardening is carried out in many specialized areas, e.g. the valleys of York and Evesham in the UK, where climatic, soil, and other factors best suit this form of agriculture. Farms are normally small, located near large cities or industrial areas. Soils, whether silty, loamy, or podzolic, are carefully maintained at a high degree of fertility. Very selective fertilizers are applied depending on the type of crops and cultivation. Farming is carried out intensively, aiming at high yield and maximum cash returns. As the crops are perishable, a good network of transport is indispensable. The produce such as lettuces, cabbages, cauliflowers, tomatoes, onions, peas, and fruits are seldom shipped but conveyed by high-speed conveyances such as trucks or vans. Perhaps a more appropriate term to use is truck farming, which is commonly used in the United States. In a few instances, warmer weather or better soils, as in southwest England, Devon, and Cornwall, can also induce farmers to take to market gardening despite their remoteness from the more populated districts. Early vegetables. Early potatoes and tomatoes reach London from the Canary Islands, the Channel Islands, and from Brittany, in northwest France. Similarly, bulbs and flowers from the polderlands of the Netherlands and eggs, bacon, and other dairy products from Denmark are sent to most of the major industrial centers of Europe in almost perfect condition for household consumption. The horticultural industry in the Netherlands is so highly specialized that Dutch tulips and bulbs are flown by the KLM Royal Dutch Airlines to Rome, Paris, Zurich, and London. In Australia, high-speed boats ply across the Bay Strait daily from Tasmania to rush vegetables, tomatoes, apples, and beans to most of the large cities in mainland Australia. It is no wonder the Australians nicknamed Tasmania the Garden State. 2. Mixed farming. Throughout Britain and North Western Europe, farmers practice both arable farming, cultivation of crops on plowed land, and pastoral farming, keeping animals on grass meadows. Crops may be raised for cash sales or as fodder for cattle or sheep. The proportion of crops and animals in the farm at any time depends to a great extent on the type of soil, the price of the cereals, and the demand for animals and animal products. The farmers also plant a few fruit trees, apples, pears, plums, rear animals for meat, keep poultry, mainly for eggs, and even have bees for honey. There is such a great variety in the farms that the term mixed farming is most aptly applied. Amongst the cereals, wheat is the most extensively grown, almost entirely for home consumption because of the very dense population. The cool temporal western margin, British type, climate 175. In northwestern Europe. At one time, some of the European countries, France, Denmark, and the Netherlands, used to be wheat exporters. But the keen competition from the new wheatlands of the New World forced most of the farmers to divert their interest to other more profitable uses of their land, such as market gardening, dairying, or an intensive form of mixed farming. With the rise of industry, more arable farms are being devoured by factories and wheat is now a net import item in Europe. The next most important cereal raised in the mixed farm is barley. The better quality barley is sold to the breweries for beer making or whiskey distilling and is raised preferably in the drier areas. Malting barley is thus grown in southeastern Britain near the hop-growing area. Hops are also used for beer, where rainfall is less than 30 inches, 762 millimeters. On heavy soils or wetter regions, barley is grown mainly as an animal fodder, sometimes mixed with oats as dredge corn. Both are raised in crop rotations with a leguminous crop, beans or clover, and a root crop, turnips or beet sugar. The most important animals kept in the mixed farm are cattle. Northwestern Europe was originally the home of many world-renowned cattle breeds, e.g. Guernsey, Ayrshire, and Friesian, which are first-class dairy cattle for milk production. The countries bordering the North Sea, Britain, Denmark, the Netherlands, are some of the most advanced dairying countries where cattle are kept. On a scientific and intensive basis, Europeans drink more milk than anybody else except the New Zealanders. In the UK, a person drinks almost a pint of milk a day. For milk, other important. An English farm. Notice the well-wooded countryside. Dairy products are derived. These are butter, cheese, cream, and skimmed milk or casein, a raw material for making plastics, paper, and drugs. The temperate western margin type of climate is almost ideal for intensive dairying. Cheese is a specialized product of the Netherlands, from Edam and Gouda. From Denmark comes high-quality butter, of which Denmark ranks with New Zealand as one of the world's greatest exporters. In Devon and Cornwall, clotted cream is made, which is less perishable than fresh milk. It can be sent over longer journeys without being contaminated. The Swiss have also made excellent use of their alpine pastures for keeping dairy cattle. Fresh milk is converted into various forms of condensed or evaporated milk and exported around the world for baby feeding, confectionery, ice cream, and chocolate making. Besides dairying, some cattle are kept as beef cattle, e.g. the Hereford and Aberdeen Angus, but their numbers are very small in comparison with those of Argentina or Australia, where meat production is the primary concern. TNE high rate of per capita meat consumption in Europe, about 68 kilograms per year, necessitates large imports of frozen and chilled meat. In the mixed farms in Europe, farmers keep cattle also with a view of enriching their fields with the animal dung. The pigs and poultry act as scavengers that feed on the leftovers from root crops and dairy processes. In this way, Denmark is able to export large quantities of bacon from pigs that are fed on the skimmed milk, a byproduct of butter making. Fresh chickens' eggs from the farms and more recently, from large poultry yards also form part of the export products of Denmark. Sheep are kept both for wool and mutton. In British Columbia, mixed farming is restricted only to the most favored parts of the western lowlands, the region being so mountainous and thickly forested. 3. Sheep rearing. This is well developed in some parts of the British type of climate. Britain is the home of some of the best-known sheep breeds, e.g. Leicesters, Lincolns, and Southdowns, which are dual-purpose, noted for mutton as well as wool. With the greater pressure exerted on land by increased urbanization, industrialization, and agriculture, sheep rearing is being pushed further and further into the less favored areas. The principal sheep areas are on foothills, drained uplands, chalk and limestone scarplands, 176 pale 2-foot weather, climate, and vegetation, and the light, sandy coasts. In the UK, the major sheep areas are the Pennines, Swaledale breeds, Scottish Highlands, the Blackface, the southern uplands, Cheviot, the Wales Mountains, Black Welsh, and the scarplands of southeastern England, Romney Marsh. In 2020, UK was the 4th largest exporter of wool in the world. In the southern hemisphere, sheep rearing is a major occupation of New Zealand, with its greatest concentration in the Canterbury Plain. However, the sheep population in the country has declined significantly in the last few decades. The 2020 estimates showed that for every New Zealander, there were only 5 sheep, whereas in 1982 there were about 22 sheep for every New Zealander. Many factors were responsible for the growth of the sheep population during the past century, including extensive meadows, a mild temperate climate, well-drained level ground, scientific animal breeding, and last, but most vital, the development of refrigeration, which enabled frozen or chilled Canterbury lamb and Corriedale mutton to reach every corner of the globe. Today, New Zealand has about 2% of the world's sheep population. In Tasmania and southern Chile, sheep rearing has always been a predominant occupation, with surplus sheep products for the international trade. 4. Other agricultural activities. Apart from market gardening and mixed farming, which have been singled out for greater individual treatment, the British type of climate also supports a number of other important crops. Amongst the food crops, potatoes feature prominently in the domestic economy of the cool temperate regions. It is the staple food in supplementing wheat or bread for millions of people. In terms of starch, it yields far a sheep station near Hawke's Bay, New Zealand, more food than any cereals, and can be cultivated over a wide range of climatic and soil types. But normally a cooler and more northerly latitude is preferred because the crop will be less prone to the attack of blight, a virus disease that is particularly infectious in warm and humid countries. Since the Introduction of the crop by the Spanish conquerors from the Andean states of Peru and Bolivia in the 16th century. Potato growing has spread far and wide in Europe. Today, almost one-fourth of the world's annual production of potatoes comes from Europe, of which Ukraine, Germany, France, Poland, and the Netherlands are the major producers. Besides its principal use as a substitute for bread, large quantities of potatoes are also consumed as animal fodder and as a source of industrial alcohol. Potato is also as an important source of chips and pancakes in these countries. Another interesting crop that is found almost exclusively in northwestern Europe, including European Russia and parts of the USA, is sugar beet. The need for such a crop was greatly felt during the Napoleonic Wars around 1800 when military blockades caused a scarcity of sugar. High prices of imported tropical sugar from sugar cane drove many governments of the temperate lands to think seriously about the vital importance of securing a certain amount of self-sufficiency in their sugar requirements. The first sugar beet factory in Europe was established in 1801. Farmers were given subsidies, aids, or allowances to induce them to devote at least part of their farm to the crop. Since then, sugar beet has become an integral part of many European farms. It is grown either on special beet farms for cash sales or in conjunction with cereals and crop rotation. The beet is crushed for sugar and the green tops are used as animal fodder. The crop thrives best in the warmer and drier east of the UK and in mainland Europe. The highest sugar yield is obtained when the autumn is both dry and sunny. The European Union (EU) is the world's largest producer of sugar beet, with about half of the total output. However, sugar beet contributes only about a fourth of the world as sugar production. Over three-fourths of the sugar output comes from sugar cane. The major sugar beet growing areas of the EU lie in northern France, Germany, the Netherlands, Belgium, and Poland. The EU also has an important refining industry that processes imported raw sugar cane. The cool temperate western margin, British type, climate 177. Questions and exercises. 1. The following statements attempt to describe a type of climate. Westerlies come all the year round. There is a tendency towards an autumn or winter maximum of rainfall. Light snow falls in winter. Ports are never frozen, but frosts do occur on cold nights. The seasons are very distinct, and the climate is very favorable for maximum human output. A. Name the type of climate that it describes. B. Locate with the aid of a sketch map a region where such a type of climate is best represented. C. Explain why such a type of climate is ideal for human habitation. 2. Describe and explain with the aid of sketch maps the essential differences between the various climatic types found within the cool temperate zone. 3. A. What are the characteristic features of temperate deciduous forests? B. Name the various species of deciduous forests and account for some of their industrial uses. C. Explain why there is comparatively little of the original forest left. 4. Write a geographical account of any three of the following economic activities. A. Mixed farming. B. Sugar beet cultivation. C. Cool temperate orchard farming. D. Sheep rearing. E. Woolen textile industry. 5. Give an explanatory account of any two of the following. A. The Netherlands is a major exporter of butter and cheese. B. Sheep outnumber the population of New Zealand by 5. C. No country produces and exports more wool than Australia. D. Market gardening is a product of urbanization. The cool temperate continental Siberian climate. Distribution. The cool temperate continental Siberian climate is experienced only in the northern hemisphere where the continents within the high latitudes have a broad east-west spread, figure 160. On its poleward side, it merges into the Arctic tundra of Canada and Eurasia at around the Arctic Circle. Southwards, the climate becomes less severe and fades into the temperate steppe climate dealt with in Chapter 19. The predominant vegetation of this Siberian or subarctic type of climate is evergreen coniferous forest. It stretches in a great, continuous belt across North America, Europe, and Asia. The greatest single band of the coniferous forest is the taiga, a Russian word for coniferous forest, in Siberia. In Europe, the countries that have a similar type of climate, forest, are mainly found in Northern Europe, Sweden, and Finland. There are small amounts of natural coniferous forest due to high altitude in Germany, Poland, Switzerland, Austria, and other parts of Europe. In North America, this subarctic belt stretches from Alaska across Canada into Labrador and is found on the high Rocky Mountains. Farther south, the Siberian climate is conspicuously absent in the southern hemisphere because of the narrowness of the southern continents and the high latitudes. The strong oceanic influence reduces the severity of the winter, and coniferous forests are found only on the mountainous uplands of southern Chile, New Zealand, Tasmania, and southeast Australia. Figure 160. The cool temperate coniferous forest. The cool temperate continental Siberian climate 179. Climate. The climate of the Siberian type is characterized by a bitterly cold winter of long duration and a cool brief summer. Spring and autumn are merely brief transitional periods. The isotherm of 50 degrees Fahrenheit or 10 degrees C for the warmest month forms the poleward boundary of the Siberian climate, and the winter months are always below freezing. The stations chosen to illustrate this type of climate are Moscow in continental Europe and Churchill in northern Canada, bordering Hudson Bay. The coldest month in Moscow is January with 18 degrees Fahrenheit, 14 degrees below freezing point, or minus 10 degrees Celsius. The warmest month, July, is as high as 68 degrees Fahrenheit, 20 degrees Celsius, thus there is an annual range of 50 degrees Fahrenheit, 30 degrees Celsius, which is common in the Siberian type of climate. In comparison, the annual temperature range for Churchill is even higher, reaching 67 degrees Fahrenheit or 19 degrees Celsius, minus 13 degrees Fahrenheit or minus 25 degrees Celsius in January, and 54 degrees Fahrenheit or 12 degrees Celsius in July. This is due to the more northerly position of Churchill. The extremes of temperature are so great in Siberia that it is often referred to as the cold pole of the Earth. Some of the lowest temperatures in the world are recorded in Verkhoyansk, 68 foot in 113 degrees east and only 415 feet in altitude, where minus 90 degrees Fahrenheit minus 67.8 degrees Celsius was once recorded. This is, in fact, 17.0 degree F minus 76 degrees Celsius, colder than Kuala Lumpur. It is almost unimaginable. In North America, the extremes are less severe because of the continent's lesser east-west stretch. The lowest midwinter means in the cold Mackenzie Valley are not lower than minus 70 degrees Fahrenheit minus 57 degrees Celsius. With such low temperatures in the cold season, heavy snowfall can be expected. Frosts occur as early as August, and by September lakes and ponds are already icebound. All over Russia, nearly all the rivers are frozen. The number of days in which the rivers are frozen increases from south to north. In normal years, the Volga is ice-covered for about 150 days, while those further north, e.g. the lower courses of the Ob, Lena and Yenisei, are ice-covered for more than 210 days or 7 months. Occasionally cold, northerly polar winds such as the blizzards of Canada and Buran of Eurasia blow violently at 50 miles per hour, 80 kilometers per hour, or more, and at a temperature of 50 degrees Fahrenheit 10 degrees Celsius below freezing point. The powdery snowflakes are blown around in the lower atmosphere and visibility is greatly reduced. Conditions are so unbearable that Siberia is very sparsely populated, but it is gradually being developed. Precipitation, the interiors of the Eurasian continent are so remote from maritime influence that annual precipitation cannot be high. Generally speaking, a total of 15 to 25 inches, 380 to 500 mm, is typical of the annual precipitation of this subarctic type of climate. It is quite well distributed throughout the year, with a summer maximum from convectional rain when the continental interiors are greatly heated, midsummer temperatures of 60 degrees to 75 degrees Fahrenheit, 15 to minus 25 degrees Celsius, are quite usual, and the maximum recorded in Siberia is a real surprise 102 degrees Fahrenheit 39 degrees Celsius. In winter the precipitation is in the form of snow, as mean temperatures are well below freezing all the time. The precipitation rhythm can best be grasped from the two representative stations chosen, in Fig. 161a and 161b. Moscow, with an annual precipitation of 26 inches 660 millimeters, has most of the rainfall concentrated in the warmer months. May-October. There is no month without some form of moisture. In a region where overall temperature is low, evaporation is not rapid, and the relative humidity is high, this small amount of precipitation is adequate for tree growth. The conifers, which require little moisture, and place altitude annual precipitation. Annual temperature range. Moscow, Rusa, 56*H, 37T 150 m or 480 feet 660 millimeters, or 26 inches 50 f 68 foot f. 1 SJR, or 28*0, 20*0. Figure 161. A. Siberian climate in Eurasia. 180 Part 2. Weather, climate, and vegetation. JFM, MJJS, OND. C-24.3-24.2-17.5-8.6-0.7. 6.9 112.312 2.7.4-0-11.3 J114 U4 temp. F135 116 0.5 16.6 30.7 44.4 54.1 9 45.3 J31.9 J11.65 to 6.1. IT 1 L J 1 1 1 mm 18 15 24 26 40 49 68 feet 93 inches 78 66 35 22 precip 1 1 1 1 colon in 0 0 0 11 J 12 I 3 13 1212. Data 1991 to 2021. Place. Altitude. Annual precipitation. Annual temperature range. Churchill, Manitoba, Canada, 58 degrees north, 94 equals W. 10 m, or 33 feet 534 millimeters, or 21 inches. 67.5 T, 54 degree F, 13.5 cf, or 13 cc, 12.3 foot C, 25.3 degrees C. Figure 161. B. Siberian climate in Canada. Transpire in equally small amount, are best suited to this type of subarctic climate. In Churchill, Figure 161, B, the annual precipitation is just 21 inches, 534 millimeters, with a distinct summer maximum. The total precipitation of the Siberian climate is determined by such factors as altitude, latitude, proximity to the poles, amount of exposure to influences by westerlies on western parts of continents, temperate monsoons on the eastern parts of continents, and the penetration of the cyclones. European Russia usually has more than 20 inches, 500 millimeters, of annual precipitation because of some oncoming westerlies in the periodic penetration of cyclones. Eastern Siberia also has over 20 inches, 500 millimeters, being moistened by the SE monsoon from the Pacific Ocean. Central Siberia and Canada have about 15 inches, 380 due to their continentality and lack of sea influence. Polewards and southwards, the amount again decreases to only 12 inches, 300 millimeters, or less. The cold, dry air of the north is incapable of holding moisture, and in the south are the semi-arid steppes. Snow falls nearly everywhere in Russia in the long, cold winter. The amount varies from place to place. It is heaviest in the northern tundra and in the Siberian taiga, where a thickness of several feet is common. Permanent snowfields like those of the Alps or the Himalayas are absent, because any accumulation of snow is melted with the return of spring and the warm summer. Frozen rivers are thawed, causing a rise in the water level, and extensive floods occur. The lower courses of the Ob, Lena, and Yenisei are marshy and ill-drained. On the other hand, the presence of a thick mantle of snow is not without its blessings. Snow is a poor conductor of heat and protects the ground from the severe cold above, which may be as much as 30 to 50 degrees Fahrenheit, L degrees C, 10 degrees C, colder. It also provides moisture for the vegetation when the snow melts in spring. When the ground is plowed and the leached, acidic podzolic soil is improved, the continental interiors of the coniferous forest belt are capable of supporting some agriculture. Natural vegetation. No other trees are so well adapted as the conifers to withstand such an inhospitable environment as the Siberian type of climate. The coniferous forest belts of Eurasia and North America are the richest sources of softwood for use in building construction, furniture, matches, paper and pulp, rayon, and other branches of the chemical industry. The world's greatest softwood producers are Russia, USA, Canada, and the Finno-Scandian countries, Finland, Norway, and Sweden. In the production of wood pulp, by both chemical and mechanical methods, the USA is second largest leader after China. But in the field of newsprint, Canada has outstripped all other producers, accounting for almost one-third of the world's total annual production. The more accessible coniferous forests have reached the limit of production, but the relatively inaccessible taiga of Siberia will remain the richest reserve of temperate softwood. There are 4 major species in the coniferous forests. 1. Pine, e.g. white pine, red pine, Scots pine, jack pine, lodgepole pine. 2. Fir, e.g. Douglas fir and balsam fir. 3. Spruce. 4. Larch. Their presence in pure stands and the existence of only a few species are a great advantage in commercial forest exploitation. The cool temperate continental, Siberian climate 181. Coniferous forests on the Rockies of Canada. Coniferous forests. 1. Coniferous forests are of moderate density. Unlike the equatorial rainforests, which are luxuriant and contain trees of various heights, the coniferous forests are more uniform and grow straight and tall, up to a height of about 100 feet. Where the poleward limit of tree growth is approached, the trees are widely spaced and give way to tundra vegetation, figure 162. 2. Almost all conifers are evergreen. The low annual temperature with more than half the year below the growing point temperature of 43 degrees Fahrenheit, about 6 degrees Celsius, means that evergreens are at an advantage. Growth can begin as soon as growing point is reached in spring. The conifer has a 2-year fructification cycle. The seeds are pollinated in 1 year and dispersed in the following year. There is no annual replacement of new leaves as in deciduous trees. The same leaf remains on the figure 162 diagram to show changes in vegetation and journey polewards from the taiga zone. 182 Part 2. Weather, climate, and vegetation. Tree for as long as 5 years. Food is stored in the trunks, and the bark is thick to protect the trunk from excessive cold. 3. Conifers are conical in shape. This is another adaptation to survive the subarctic climate. The sloping branches prevent snow accumulation, which may snap the branches. It also offers little grip to the winds. 4. Leaves are small, thick, leathery, and needle-shaped. This is to check excessive transpiration. The leaf surface is reduced to the minimum, as transpiration can be quite rapid in the warm summer due to intense continental heating. 5. There is little undergrowth. The podzolized soils of the coniferous forest are poor. They are excessively leached and very acidic. The evergreen leaves provide little leaf fall for humus formation, and the rate of decomposition of the leathery needles in a region of such low temperature is slow. All these factors are deterrents to the growth of much undergrowth. Absence of direct sunlight and the short duration of summer are other contributory factors to a sparse undergrowth, but where trees are widely spaced near the tree line, heath and tundra plants cover the intervening ground. Besides the continental interiors of the higher latitudes, coniferous forests are also found in other climatic regions wherever altitude reduces the temperature. The conifers are, in fact, the dominant trees of the mountainous districts in both the temperate and tropical countries. But on very steep slopes where soils are immature or non-existent, even the conifer cannot survive. Economic development. The coniferous forest regions of the Northern Hemisphere are comparatively little developed. In Canada, Eastern Europe, and Asiatic Russia, large tracts of coniferous forests are still not exploited. Only in the more accessible areas are the forests cleared for lumbering or timber harvesting under strict laws and sustainable forest management practices. The various species of pine, fir, larch, and spruce are felled and transported to the sawmills for the extraction of temperate softwoods. There is little agriculture, as few crops can survive. In the subarctic climate of these northerly lands, the long, cold winter, the frozen soils, and the low mean annual temperature throughout the year exclude all but the hardiest crops. Only in the more sheltered valleys and the lands bordering the steppes are some cereals, barley, oats, rye, and root crops, potatoes, raised for local needs. Many of the Samoyeds and Yakuts of Siberia and some Canadians are engaged in hunting, trapping, and fishing. We shall deal with two of the major activities in greater detail. 1. Trapping. Many fur-bearing animals inhabit the northerly lands of Canada and Eurasia. Wherever the cold is keenest, the quality and thickness of the fur also increases. Consequently, the most severe winters produce the finest furs which fetch the highest prices. Nowadays, the trapping of fur-bearing animals in Canada is licensed and regulated by provincial and territorial governments whose wildlife experts have framed regional management plans to ensure healthy fur-bearer populations. Trapping activities are generally consistent with international agreements such as CITES, Convention on International Trade in Endangered Species, the Convention on Biological Diversity, CBD, and the IUCN, International Union for Conservation of Nature. Beaver, badger, muskrat, bobcat, fox, lynx, wolverine, etc. are the most important fur-bearing animals sought after in Canada. In the past, the Hudson Bay Company had many stations scattered in the northern regions to trade in furs with the Canadian trappers and hunters. 2. Lumbering and timber harvesting. This is probably the most important occupation of the Siberian type of climate. The vast reserves of coniferous forests provide the basis for the lumbering industry. The trees are felled for many purposes but on specific conditions. A. Sawmilling. This processes the logs into sawn timber, plywood, planks, hardboard, and other constructional woods. B. Paper and pulp industry. Timber is pulped by both chemical and mechanical means to make wood pulp the raw material for paper making and newsprint. The development of the printing industry has made paper and pulp indispensable. Canada and USA are amongst the leading producers of the world's supplies of newsprint and wood pulp. C. As a fuel. Less than a quarter of the world's softwood is burnt as fuel because the cool temperate continental Siberian climate. 183. A lumberjack hewing a log at the Grouse Mountain, North Vancouver, British Columbia, Canada. Its industrial uses are far more significant. In contrast, almost 3/4 of the world's hardwoods are burnt as fuel, particularly tropical hardwoods where the trees occur in mixed stands. D. As an industrial raw material. Timber has a wide range of uses. In Sweden, matches form a major export item. In other temperate countries, timber is used for making furniture, wood carvings, toys, crates, and packing cases. From the byproducts of the timber, many chemically processed articles are derived such as rayon turpentine, varnishes, paints, dyes, liquid resins, wood alcohols, disinfectants, and cosmetics. The coniferous forests are characterized by the following features. 1. The conifers are limited in species. Pine, spruce, and fir are the most important in the northern forests, while larch is more predominant in the warmer south. They occur in homogeneous groups and not mixed as in the tropical forests. This not only saves time and costs, but also enhances the commercial value of the felled timber. 2. In these northerly latitudes, agriculture is almost impossible and lumbering or timber harvesting replaces farming in the continental interiors. Even where crops are cultivated, farmers are idle in the winter months and can supplement their loading of logs on wagons in Canada. 184. Part 2. Weather, climate, and vegetation. Income by doing part-time lumbering in the forests, as they do in most parts of Europe. 3. Lumbering is normally carried out in the winter when the sap ceases to flow. This makes felling much simpler. The snow-covered ground also makes logging and haulage a relatively easy job. Earlier, the logs were dragged to the rivers and floated to the sawmills downstream when the rivers thawed in spring. However, the use of modern techniques and transportation methods have helped to load and transport timber to the sawmills easily. This has greatly assisted the development of the lumbering industry in eastern Canada and Sweden. Unfortunately, over the greater part of Siberia, all the rivers drain polewards into the Arctic Ocean, which is frozen for 3/4 of the year, and there are few sawmills there. With the use of the Northern Sea Route, which links Murmansk and Vladivostok via the Arctic Ocean, development is increasing. Many sawmill operators are now venturing into Siberia. Cheap hydroelectricity for driving the sawmills is harnessed in the mountainous uplands of North America and Europe and has greatly assisted the lumbering industry. Questions and exercises. 1. Compare and contrast deciduous forests and coniferous forests in respect of the following. A. Distribution. B. Vegetational characteristics. C. Climatic influence. D. Economic development. 2. Distinguish between hardwoods and softwoods. What industrial uses are made of them? Account for their large-scale production for export in any one country. 3. Give a reasoned account of any three of the following. A. The annual temperature range of Moscow is 50 degrees Fahrenheit or 12 degrees Celsius. B. The annual precipitation of St. Petersburg is not more than 28 inches or 710 millimeters. C. The lower courses of the Siberian rivers are frozen for as long as 7 months. D. One of the coldest spots on the globe is Verkhoyansk with a record lowest temperature of 90 degree F minus 67.8 degrees Celsius. 4. What is meant by A. The taiga, B. The veldt, C. The selvis? Account for the distribution and characteristics of any two of them. 5. Describe the role played by forest products in the economy of either Canada or Sweden. 6. Describe the modern-day trapping methods and policies associated in this regard in Canada. The cool temperate eastern margin, Laurentian. Distribution. The cool temperate eastern margin, Laurentian, climate is an intermediate type of climate between the British and the Siberian type of climate. It has features of both the maritime and the continental climates. It is apparent from Figure 163 that the Laurentian type of climate is found only in two regions. One is northeastern North America, including eastern Canada, northeast USA, i.e. maritime provinces, and the New England states, and Newfoundland. This may be referred to as the North American region. The other region is the eastern coastlands of Asia, including eastern Siberia, North China, Manchuria, Korea, and northern Japan. It may be referred to as the Asiatic region. In the southern hemisphere, this climatic type is absent because only a small section of the southern continents extends south of the latitude of 40 degrees south. The only possible location is in eastern Patagonia, south of Bahia Blanca, lat. 39 degrees south, to Tierra del Fuego, lat. 54 degrees south. But the climatic barrier of the southern Andes is so complete that the west 54 degrees south. But the climatic barrier of the southern Andes is so complete that the westerlies hardly ever reach Patagonia. The region is subjected to aridity rather than continentality. Its annual precipitation is not more than 10 inches, 250 millimeters, so that it is a rain shadow desert. Elsewhere in the southern hemisphere, the climate is so equable and the oceanic influence is so profound that neither the continental nor the eastern margin type of climate exists. Climate. The Laurentian type of climate has cold, dry winters and warm, wet summers. Winter temperatures may be well below freezing point and snow falls to quiet. Figure 163 regions with a cool temperate eastern margin climate, Laurentian type. 186 Part 2, Weather. Climate and vegetation. A depth. Summers are as warm as the tropics, 70 to 80 degrees Fahrenheit or 21 to 27 degrees Celsius, and if it were not for the cooling effects of the offshore cold currents from the Arctic, the summer might be even hotter. The rain falls throughout the year. There is a distinct summer maximum from the easterly winds. From the oceans. Of the annual precipitation of 30 to 60 inches, 762 to 1,524 millimeters, 2/3 come in the summer. Winter is dry and cold because the winds are dry westerlies that blow out from the continental interiors. We shall now examine in closer detail the variations of the Laurentian type of climate between the North American region and the Asiatic region. The North American region. The most remarkable characteristic of the Laurentian climate of the North American region is its uniformity in precipitation, about 3 to 4 inches or 75 to 100 millimeters monthly with a late summer maximum. New York in Figure 164a has an annual precipitation of about 45 inches, 1,140 millimeters, with the wettest months in June, July, and August, 4.0 inches each. No month is really dry, and the driest month, November, has 2.0 inches, 76 millimeters, of rain. This uniformity of precipitation is largely due to the Atlantic influence and that of the Great Lakes. The warm Gulf Stream increases the moisture content of easterly winds from the open Atlantic. The prevailing westerlies which penetrate across the Rockies carry depressions over the Great Lakes to the New England states. These winds thus promote wet conditions especially in winter, which are vital for the agricultural activities of northeastern North America. The meeting of the warm Gulf Stream and the cold Labrador Current on coastal waters off Newfoundland produces dense mist and fog and gives rise to much precipitation. St. John's, its capital, has as much as 54 inches, 1,372 millimeters, of annual precipitation. It is said that Newfoundland experiences more drizzles than any other part of the world. In summer, the westerlies bring less depressions and extend their continental influence to the coast. Temperatures are normally high in summer for the latitude. New York has a mean July temperature of 76 degrees Fahrenheit, 24.5 degrees Celsius, and sometimes even as high as 90 degrees Fahrenheit, 32 degrees Celsius. Once, on July 9, 1936, the absolute maximum of 106 degrees Fahrenheit, 41 degrees Celsius was reached. Such high temperatures in a cool temperate maritime region, where the relative humidity is high, can be very trying. Prolonged heat waves cause discomfort and frustration in crowded cities. Data, 1991 to 2021. JFMAM J3S0N0. Average. C minus 1 4.1 10.4 16 21.3 24.5 23.6 20.1 13.7 7.7 2.5 temp. T 30.3 32, I 9 foot 4 50.8 60.9 70.3 76 74.5 68.1 56.6 45.8 36.5. Pre-Sci P. MM 86 78 106 92 9 2 103,105,106 95 97 76 103. In 33334443324. Figure 164, A. Laurentian type of climate in North America. Place Nev/York, USA, 41 degrees north, 74 degrees west. Altitude 20 m or 66 feet. Annual precipitation 44.8 inches or 1,139 millimeters. Annual temperature range 45.8 degree F, 76.0 to 30.2 degrees Fahrenheit, or 25.4 degrees Celsius, 24.5 to minus 1.1 degrees Celsius. Figure 164, B. Laurentian type of climate in Asia. JFMAMJJASOND average. C minus 3.7 minus 0.36.3 14.4 21.6 25.9 27.3 25.5 20.9 13.2 minus 2.4 temp. IOP 25.3 31.4 43.4 370.9 78.7 81.1 78 69.6 55.8 38 9 27.8. MM 46 10 22 37 79 170,125 61 33 15 4 Precip. IN 00003 42100 data, 1991 to 2021. Place Beijing, North China, 40 degrees north, 116 degrees east. Altitude 51 m or 167 feet. Annual precipitation I 22.3 inches or 566 mm. Annual temperature range I 55.8 degrees Fahrenheit, 81.1 to 25.3 degrees Fahrenheit, or 31, 0 degrees C, 27.3 degrees C. The cool temperate eastern margin, Laurentian, 187. In winter, the temperature drops and snow falls. New York has 2 months below freezing point and an annual temperature range of 45.8 degrees Fahrenheit, 25.4 degrees Celsius. Away from the maritime influence, the cold increases. The mean January temperatures for Quebec, Ottawa, and Montreal are about 12 degrees Fahrenheit minus 11 degrees Celsius, 15 degrees Fahrenheit minus 9 degrees Celsius, and 15 degrees Fahrenheit minus 9 degrees Celsius, respectively. The temperature ranges widen accordingly. The Asiatic region. In contrast, the rainfall distribution of the Asiatic region is far less uniform. Winters are cold and very dry while summers are very warm and exceptionally wet. Beijing, a typical station of the Laurentian climate in northern China, as shown in Figure 164, B, will bring out these facts very clearly. It has 8 dry months from October to May with a total rainfall of about 2.0 inches, 50 millimeters, which is only 1/11 of the annual total of 22 inches, 566 millimeters. The remaining 4 months receive more than 2 inches a month, with 6.0 inches, 170 millimeters, in July alone. The rainfall regime is, in fact, similar to that of the tropical monsoon type in India, where the whole year's rainfall is concentrated in the 3 summer months. The mountainous interior of China has such pronounced continental effects that the intense heating in summer creates a region of extreme low pressure and moisture-laden winds from the Pacific Ocean and the Sea of Japan blow in as the southeast monsoon. The Laurentian type of climate here is often described as the cool temperate monsoon climate. It has a very long, cold winter and a big annual range of temperature. The July mean for Beijing is 81 degrees Fahrenheit 27 degrees Celsius, while that of January is only 25 degrees Fahrenheit minus 3.5 degrees Celsius. The temperature range is therefore more than 55 degrees Fahrenheit 31 degrees Celsius. The dry, cold wind that blows out from the heart of Asia in winter carries fine, yellowish dust and deposits. It has a thick mantle of loess in Shanxi, and other neighboring provinces at the bend of the Huanghe. Much of the winter precipitation in northern China, Korea, and Hokkaido, Japan, is in the form of snow. In the mountainous districts, the snow piles to a depth of 5 to 10 feet, 1.5 to 3.0 m. The climate of Japan is modified by its insularity and also by the meeting of warm and cold ocean currents. It receives adequate rainfall from both the southeast monsoon in summer and the northwest monsoon in winter. The latter is the dry, cold wind from mainland Asia, but after crossing the Sea of Japan it has gathered sufficient moisture to give heavy relief rain or snow on the western coast of Japan. The rainfall is more evenly distributed. As in Tokyo, with 2 maxima, 1 in June, the plum rain, 6.3 inches or 161 millimeters, and the other in September-October, the typhoon rain, 7.7 to 8 inches or 195 to 207 millimeters. On the windward slopes of the Japanese Alps on the west, some stations, e.g. Kanazawa have more than 92 inches, 2,338 Kanazawa have more than 92 inches, 2,338 millimeters of rain, much of it falling as snow. The maritime influence also effectively moderates the temperature range. Tokyo has a range of 40 degrees Fahrenheit or 22 degrees Celsius, 79 degrees Fahrenheit in August and 39 degrees Fahrenheit in January, with none of the months below freezing point. The warm Kuroshio has played an important part in making the climate of Japan less extreme. In meeting the cold Oyashio from the north, it also produces fog and mist, making North Japan's second Newfoundland. Fishing replaces agriculture as the main occupation in many of the Ident coastlands. Natural vegetation. The predominant vegetation of the Laurentian type of climate is cool temperate forest. The heavy rainfall, the warm summers, and the damp air from fogs all favor the growth of trees. Generally speaking, the forests tend to be coniferous north of the 50 degrees north parallel of latitude. The increase in the length and severity of the winter excludes forests that are not adaptable to cold conditions. In Asiatic region, eastern Siberia and Korea, the coniferous forests are, in fact, a continuation of the great coniferous belt of the taiga. Lumbering has always been a major occupation of this sparsely populated part of Eastern Asia, and timber is a leading export item. Much of the original coniferous forests of fir, spruce, and larch have been cleared as a result of lumbering rather than agriculture. Eastern Canada, along the banks of the St. Lawrence River, is the heart of the Canadian timber and wood pulp industry. South of latitude 50 degrees north, the coniferous forests give way to deciduous forests. Oak, beech, maple, and birch are the principal trees. Like their counterparts on the western margins, the deciduous forests are fairly open. A long growing season of over 6 months and an adequate supply of moisture from maritime sources encourage rapid growth of ferns and other temperate undergrowth. The occurrence of trees in almost pure stands and the predominance of only a handful of species greatly enhance the commercial value of these forests. As a result, they have been extensively 188 Part 2, Weather, Climate, and Vegetation, felled for the extraction of temperate hardwood. In many parts of Manchuria, Korea, and Japan, the forests have made way for the plow. Both food and cash crops are raised. In Canada, due to the greater reserves of coniferous softwoods and their overriding importance in industrial uses, the annual production of deciduous hardwood is much less significant. Economic development. Lumbering and its associated timber, paper, and pulp industries are the most important economic undertaking. Details of lumbering have already been dealt with in Chapter 22. Agriculture is less important in view of the severity of the winter and its long duration. Fortunately, the maritime influence and the heavy rainfall enable some hardy crops to be raised for local needs. Potatoes thrive over large areas of the podzolized soils, while hardy cereals like oats and barley can be sown and successfully harvested before the onset of the cold winter. A number of other interesting crops are produced. In the Asiatic region, such as soybeans, northern China, Manchuria, and Korea are amongst the world's leading producers, groundnuts, sesame, rapeseeds, tung oil, and mulberry. In the North American region, arable farming is not carried out on a sizable scale, except in the more favored localities. Farmers are engaged in dairy farming, hay cultivation, and, in mild maritime areas, fruit growing. The fertile Annapolis Valley in Nova Scotia is the world's most renowned region for apples. Fishing is, however, the most outstanding economic activity of the Laurentian climatic regions. Fishing. Fishing off Newfoundland, the Maritime Provinces, and New England. This is one of the world's largest fishing grounds, particularly on the Grand Banks of Newfoundland, figure 165. The reasons for its importance are geographical. Fish feed on minute marine organisms, collectively called plankton, which is present in abundance only in shallow waters adjacent to land masses, where sunlight can penetrate through. The gently sloping continental shelves, less than 600 feet or 183 meters deep, which stretch for over 200 miles, about 322 kilometers, southeast of Newfoundland and off the coasts of the Maritime Provinces and New England contain a rich collection of microscopic plankton. Fish of all types and sizes feed and breed here and support a thriving fishing industry not only in Canada and USA, but also in countries like Norway, France, Britain, Portugal, Denmark, Russia, and Japan, who send fishing fleets to the Grand Banks. As less than 1% of Newfoundland is cultivated, fishing provides employment for almost the entire population. It is not only the chief source of wealth to Newfoundland, but also a major export item of all the maritime provinces. Both pelagic fish which live near the surface and demersal fish which live near the bottom of shallow seas are caught. The chief fish caught is cod, which is consumed fresh or dried, salted, smoked, canned, or packed in ice for export to mainland America, Central and South America, and Southern Europe. Cod liver oil is exported too. Other fishes caught are haddock, halibut, hake, herring, plaice, and mackerel. Various kinds of fishing craft and techniques are employed to obtain maximum harvest from the sea. Modern trawlers, dragging large conical-shaped nets, and drifters, carrying curtain-like rectangular nets, operate extensively off the Atlantic coasts. They are Equipped with radio and radar devices to navigate through the dense fog, avoid collision with icebergs, and also maintain contact with their headquarters on land. Offshore fishermen also use traps, lines, and nets to catch crabs, lobsters, and shrimps for home consumption and increasingly for export. Further inland, in lakes and rivers, such as the St. Lawrence and the Great Lakes, freshwater fish, e.g. salmon, trout, eels, and sturgeons are caught. In Newfoundland and along the Atlantic coasts are many fishing ports. St. John's, chief port of Newfoundland with a population of nearing 100,000, is the headquarters of the Grand Banks. Fishing industries. It also had interest in sealing and whaling, but these have declined. In the fishing ports of Halifax and Yarmouth in Nova Scotia and in the New England ports are processing plants that cut, clean, salt, pack, or preserve fish for disposal by refrigerated boats, trains, or trucks to all parts of the continent. They are bases for large fleets of trawlers. A modern trawler may well cost anything around $1 million and have men stay on board in floating factories far out at sea for days and even weeks. Fishing in this part of the world is highly specialized and very efficient. The cool-temperate eastern margin, Laurentian, 189. Figure 165 fishing, the North American region. In fact, overfishing is a growing problem. The United States government and international fishing bodies are now contemplating strict measures in fish conservation if this major source of protein food is to be sustained for regular supply in the years to come. Fishing off Japan. In the Northwest Pacific, surrounding the islands of Japan is another major fishing area of the world. Nowhere else in the world are there so many people engaged in fishing as in this part of the Northwest Pacific. The mountainous nature of Japan and parts of mainland Eastern Asia have driven many to seek a livelihood from the sea. The scarcity of meat, there is little pasture in Japan for livestock farming of any kind, and religious reasons have popularized fish as the principal item of diet and the chief protein food of the Japanese and the Chinese as well. Large quantities of fish and fish products are either canned or preserved for export to neighboring countries. The Japanese also make use of fish wastes, fish meal, and seaweeds as fertilizers in their farms. Japan is one of the few countries that has taken to seaweed cultivation. Coastal farms that are submerged in water grow weeds for sale as fertilizers, chemical ingredient, and even as food. Another interesting aspect of Japanese fishing is pearl culture. The divers of southern Japan dive down into the coastal waters and bring to the surface shellfish called pearl oysters and extract the highly prized pearls for sale as ornaments. The lining of the oyster shells, called mother of pearl, is used for the 190 Part 2, weather, climate, and vegetation. A fishing settlement in Newfoundland, much of the fish is dried for export. Manufacture of pearl buttons and other decorative articles. As natural pearls and oysters are difficult to obtain in large numbers, the Japanese have begun to breed the young oysters. By injecting tiny seeds into them, the oysters are made to secrete the pearl material, which accumulates to form cultured pearls. These are collected and exported. The Japanese interest in fishing is not confined to their own territorial waters. They venture far and wide into the Arctic, Antarctic, and the Atlantic waters. Large whaling fleets complete with processing plants and experienced crews stay out in the open seas and return only occasionally for refueling or replenishment of fresh provisions. As a nation, Japan accounts for 1/8 of the world's total annual catch. Japan is one of the world's greatest fishing nations today with about 8% of the global captures. Its active participation in international fishing enterprises and advanced fishing techniques speak well of Japan's relentless drive to make good from the seas what it lacks on land. Let us find out why this is possible. 1. Japan is not well endowed with natural resources, for as much as 80% of the land is classed non-agricultural. It has to take the help of the sea if it wants to survive. This has compelled the people to develop the seas, and fishing has for centuries been the traditional occupation of many coastal Japanese. 2. The continental shelves around the islands of Japan are rich in plankton, due to the meeting of the warm Kuroshio and the cold Oyashio currents, and provide excellent breeding grounds for all kinds of fish including herring, cod, mackerel, bonito, salmon, sardine, and tuna, as well as crabs and lobsters. 3. The indented coastline of Japan provides sheltered fishing ports, calm waters, and safe landing places, ideal for the fishing industry. In Hokkaido, where the Laurentian type of climate is too cold for active agriculture, fishing takes first place. Hakodate and Kushiro are large fishing ports, complete with refrigeration facilities. 4. Lack of lowlands and pastures means that only a few animals can be kept to supply meat and other protein food. Fish, in all its varied forms: fresh, canned, dried, frozen, and in the form of fish pastes, fish sauce, and spiced condiments takes the place of meat as Japan's primary source of protein food. There is a great demand for it locally. And 4. Export to other East Asiatic neighbors which lack the techniques of large-scale commercial fishing. The cool-temperate eastern margin, Laurentian, 191. A cultured pearl farm in Japan. 5. The Japanese fishermen began with small fishing boats, using nets, traps, and lines. With the progress made in industries, fishing has also become more scientific, aiming at heavy hauls, high returns, and economy of time, effort, and money. Though three-quarters of the fishermen practice offshore pelagic fishing either full-time or part-time, in small boats, most of the commercial deep-sea demersal fishing is now highly mechanized. Powered trawlers and modern refrigeration plants backed by sound financial organizations have greatly increased the annual fish yield. Japan is now not only a major producer and exporter of fish and marine products, but also a center for marine and fishing research. Questions and exercises. 1. A. Locate on a world map the extent of the cool temperate eastern margin, Laurentian, climate. B. Explain why this type of climate is confined to the northern hemisphere. C. Describe its climate. 2. Compare and contrast the climate of any two of the following pairs of areas. A. Laurentian climate in the North American region and the Asiatic region. B. Tropical monsoon climate of India and the warm temperate eastern margin, China type, climate in S. China. C. The steppe type of climate in Eurasia and the Siberian type of climate in northern Canada. D. The tundra climate of Greenland and trade wind desert climate of Central Australia. 3. A. Name the major fishing areas of the world. B. What types of fishing can normally be distinguished in such major fishing grounds? C. Name a few methods used to catch the fish. D. For any one major fishing area you have selected, explain the geographical factors which have contributed to its importance. 4. Write brief notes on any three of the following. A. The economy of the forests of the Laurentian regions. B. Fishing in Japan. C. Soya bean cultivation in Manchuria. D. Fruit growing in the maritime provinces of Canada. 5. The following statistics are a guide to 4 different types of climate in the northern hemisphere. A. Name the type of climate that each of them represents. B. Locate a probable station for each. C. For any two of them, describe their climatic characteristics. Stations: July. Temp. January. Temp. Annual temp. Range. Annual. Rainfall. Month of max rainfall. A 81 F 78 degrees Fahrenheit, 3T96 inch April, and October B 55 degrees Fahrenheit, 12 degrees Fahrenheit 43 foot FS Loon. July August. C 91 degrees Fahrenheit, 56 degrees Fahrenheit, 35 seconds F 3M irregular. I0. 74 degrees Fahrenheit, 30 foot F 44 inch F 41 July. August. September. The Arctic or polar climate. Distribution. The polar type of climate and vegetation is found mainly north of the Arctic Circle in the northern hemisphere. The ice caps are confined to Greenland and to the highlands of these high-latitude regions, where the ground is permanently snow-covered. The lowlands, with a few months ice-free, have tundra vegetation. They include the coastal strip of Greenland, the barren grounds of northern Canada and Alaska, and the Arctic seaboard of Eurasia. Figure 166. In the southern hemisphere, the virtually uninhabited continent of Antarctica is the greatest single stretch of ice cap where the layers of permanent ice are as thick as 10,000 feet. Climate. Temperature. The polar climate is characterized by a very low mean annual temperature, and its warmest month in June seldom rises to more than 50 degrees F, 10 degrees Celsius. In midwinter, January, temperatures are as low as minus 22 degrees Fahrenheit to minus 13 degrees Fahrenheit, minus 30 degrees Celsius to minus 25 degrees Celsius, and much colder in the interior. Normally not more than 4 months have temperatures above freezing point. Winters are long and very severe. Summers are cool and brief. Within the Arctic and Antarctic circles, there are weeks of continuous darkness. At the North Pole, there are 6 months without light in winter. Despite the long duration of sunshine in summer, when the sun does not set, temperatures remain low because the sun is low in the sky and much of the warmth of its. Figure 166 Ice cap and tundra. The Arctic or polar climate 193. Faint rays is either reflected by the ground snow or used up in melting the ice. It has little power left to raise the air temperature. Water in the soil is frozen to great depths in the summer heat. Can only thaw the upper 6 inches of the soil. The ground remains solidly frozen for all but 4 months, inaccessible to plants. Frost occurs at any time in blizzards, reaching a velocity of 130 miles an hour, about 210 kilometers per hour, is not infrequent. They can be very hazardous for the polar inhabitants. In coastal districts, where warmer water meets cold land, thick fogs may develop. They last for days, and in many instances it is not possible to see for more than a few feet. Precipitation is mainly in the form of snow, falling in winter and being drifted about during blizzards. Snowfall varies with locality. It may fall either as ice crystals or large, amalgamated snowflakes. As it takes 10 to 12 inches of snow to make 1 inch of rain, precipitation in polar regions can be expected to be light, not more than 12 inches, 305 millimeters, in a year. Convectional rainfall is generally absent because of the low rate of evaporation and the lack of moisture in the cold polar air. There is normally a summer maximum, and the precipitation is then in the form of rain or sleet. In regions where winds blowing out from the large anticyclones developed over the ice caps are prevalent, rain comes in summer, when more evaporation is possible. But in coastal areas, where cyclones are more strongly felt, the tendency is towards a winter maximum, for that is when cyclonic activity is greatest. In such regions, the annual rainfall of 10 to 12 inches, about 250-305 millimeters, for the tundra may be exceeded. Much heavier rainfall has been recorded, especially in areas where the cyclones are most frequent, e.g. Jan Mayen, 71 degrees north, 8 degrees west, has 15 inches, 380 millimeters. Vardo, 70 degrees north, 31 degrees east, has 26 inches, 660 millimeters. And Tasiilaq, formerly Ang Magsalak, 66 degrees north, 38 degrees west, has over 37 inches, 940 millimeters. Figure 167 shows the rhythm of temperature and precipitation of a tundra region taken at Upernavik, Greenland, 72 degrees north, 56 degrees west. Its winter temperature is minus 10 degrees Fahrenheit, 23 degrees Celsius, while its warmest month in July is only about 43 degrees Fahrenheit, 6 degrees Celsius, giving an annual range of about 54 degrees Fahrenheit, 30 degrees Celsius. Precipitation is low, only 15.4 inches, 390 millimeters, falling mainly in the second half of the year, both as rain and snow. Figure 167 Tundra climate. Place Upernavik, Greenland, 723 in, 56 to the power of W. Altitude 1 m or 3.2 feet. Annual precipitation 15.4 inches or 390 millimeters. Annual temperature range 53.7 degrees Fahrenheit, 43.6 to minus 102 degrees Fahrenheit, or 29.8 degrees Celsius, 6.4 degrees Celsius, 23.4 foot C. Tundra vegetation. In such an adverse environment as the tundra, few plants survive. The greatest inhibiting factor is the region's deficiency in heat. With a growing season of less than 3 months and the warmest month not exceeding 50 degrees Fahrenheit, the tree survival line, there are no trees in the tundra. Such an environment can support only the lowest form of vegetation, mosses, lichens, and sedges. Drainage in the tundra is usually poor, as the subsoil is permanently frozen. Ponds and marshes and waterlogged areas are found in hollows. In the more sheltered spots, stunted birches, dwarf willows, and undersized alders struggle for a meager existence. Climatic conditions along the coastal lowlands are a little more favorable. Here are found some hardy grasses and the reindeer moss, which provide the only pasturage for the herbivorous animals like reindeer. In the brief summer, when the snows melt and the days are warmer and longer, berry-bearing bushes and Arctic flowers bloom. Though short-lived, they brighten the monotonous tundra landscape into Arctic prairies. In the summer, the tundra is full of activities. Birds migrate north to prey on the numerous insects which emerge when the snow thaws. 194 Part 2, Weather, Climate, and Vegetation. Mammals like the wolves, foxes, muskox, Arctic hare and lemmings also live in tundra regions. Human activities. Human activities of the tundra are largely confined to the coast, where plateaus and mountains increase the altitude. It is uninhabitable, for these are permanently snow-covered. The few people who live in the tundra live a semi-nomadic life and have to adapt themselves to the harsh environment. In Greenland, northern Canada, and Alaska live the Eskimos, numbering around 160,000 today. In the past, they used to live as hunters, fishermen, food gatherers. However, in recent times, more of them have been making permanent huts for settling. Their economy now relies somewhat less on traditional activities and more on gathering plant products. Whales, seals, caribou, various kinds of fish, and many animals with fur, along with birds, provide them with everything they need for food and clothing. These resources also play a significant role in supplying materials for tools, weapons, and everyday items or utensils. The polar Eskimos, living around Thule in northwest Greenland, still lead an uncertain life, not very much different from their forefathers. The seasonal changes in climate necessitate a nomadic way of life. During winter, they live in compact igloos, and in summer, when they move out to hunt, they pitch portable tents of skins by the side of streams. Their food is derived from fish, seals, walruses, and polar bears. Other Eskimos hunt caribou, the name given to reindeer in America, and other animals to secure a steady supply of their daily meat, milk, fat, skins, and bones. In the last 60 years, through their contact with the Europeans, the way of life of the Eskimos has undergone tremendous changes. Coastal villages have permanent wooden houses complete with modern facilities. Speedboats are replacing frail kayaks. Deadly rifles instead of traditional harpoons are used to track down animals and seals. Fur-bearing animals are being reared on a commercial scale, and fishing, too, is being commercialized. In some more accessible parts of Canada and Alaska, schools have been established, and the Eskimo children are being taught the skills which will allow them to fit into the modern way of life. In the Eurasian tundra are other nomadic tribes such as the Lapps of northern Finland and Scandinavia, the Samoyeds of Siberia from the Ural Mountains and the Yenisei Basin, the Yakuts from the Lena Basin, and the Koryaks and Chukchi of northeastern Asia. They wander with their herds of reindeer across the Eurasian tundra where there are pastures. Many of them have taken to a more settled life. In Russia, large farms have been established for raising reindeer and for breeding fur-bearing animals. The importance and recent development of the Arctic region. The Arctic region, once regarded as completely useless, is now of some economic importance. Apart from the efforts of the various governments in assisting the advancement of the Arctic inhabitants, the Eskimos, Lapps, Samoyeds, etc., new settlements have sprung up because of the discovery of minerals. Gold is mined in Alaska, nickel near Petsamo, Russia, petroleum in the Kenai Peninsula, Alaska, and copper at the Rankin Inlet, Canada. Coal has been mined in Spitsbergen for a long time and also in Alaska. With the declining reserves of iron or around Lake Superior, the Great Lakes industrial concerns are using more and more iron from large iron ore deposits in Labrador. New railway lines have been constructed to bring the ores to the St. Lawrence River for subsequent shipment to the major industrial districts. Rich deposits of iron ores at Kiruna and Gallivare in Sweden have made it possible for Sweden to enjoy a prosperous export trade in iron and steel and other metallurgical products. With the establishment of ports on the Arctic seaboard of Eurasia, it is now possible to ship timber and fur from Siberia. Though the ports, such as Agarka at the mouth of the Yenisei, are not ice-free, modern icebreakers keep the passage open most of the time. On the Arctic lowlands where the growing season is lengthened by warm currents or higher temperatures, experiments have been the borderlands between the taiga and the tundra. The Arctic or polar climate 195 carried out to devise varieties of hardy cereals for worth consideration for future colonization. Local needs. It may not be long before the tundra scientists, meteorologists, and explorers have lived is brought under greater agricultural, especially in the Arctic and Antarctica, making studies of their geology, weather conditions, plant and animal life. Pastoral use. The healthy air and its preservative qualities, it is practically germ-free, are factors that will be of great significance in years to come. Questions and exercises. 1. Draw separate sketch maps to show the area covered by each of the following. A. Tundra in Eurasia. C. Hot desert in Australia. B. Savanna in South America. D. Equatorial forest in Africa. For any three of them, describe their characteristic features of natural vegetation, and for any one of them, explain how the features are related to the climate of the area. 2. The following are representative of plants found in different climatic zones: spruce, olive, teak, reindeer moss, date, oak, eucalyptus, and bamboo. For any six of them, A. Name the type of climate in which each of them thrives. B. State the sort of natural vegetation with which they are associated. C. Describe very briefly the role each of them plays in the economy of a named country in which they are found in abundance. 3. Explain briefly any four of the following terms connected with the Arctic climate and the tundra vegetation: blizzards, permafrost, midnight sun, ice cap, snow blindness, kayaks, international deep freeze. 4. Make a comparative study of the polar Eskimos of Greenland and the orang asli, e.g. Sainois or Sangwa, under the following headings. A. How they obtain their food. B. How they shelter themselves. C. What significant changes have taken place in their environment and their way of life. 5. Statistics of rainfall and temperature for three towns are given below. For any two of them, A. State their season of maximum rainfall. C. Suggest a possible location of the town. B. Name the type of climate. D. Describe their climatic rhythm. J. F. MAMJJASON. D. Range slash. Dot dash. Dot A. Total. Town A altitude, 207 feet temp. Degree F, 47, 49, 51, 57, 64, 71, 76, 76, 70, 62, 53, 46, 30. I precip. Inches, 3.22.7, 2.9, 2.62.2, 1.60.7, 1.02.55, 5.04.4, 33, 32.7 altitude, 65 feet temp. Degree F, -8, -9, -6, 25, 35, 41, 41, 34, 34, 25, 14, 10, 49. Precip. Inches, 0.4, 0.5, 0.7, 0.6, 0.6, 0.5, 0.9, 0.1, 1.1 K at 1.1 is 9.1 altitude, 9,350 feet temp. Degree F, 55, 55, 55, 55, 55, 55, 55, 55, 55, 55, 55, 54, 1.0. Precip. Precip. Inches, 3.23.9, 4.87.0, 4.6, 1.5, 1.12, 0.22.6, 33, 4.0, 3.6, 423. 6. A. With the aid of sketch maps to show one major region where each type is found, describe the main features of vegetation of tropical grassland, savanna, and coniferous forest. B. For either tropical grassland, savanna, or coniferous forest, show how the main features of the vegetation are influenced by climate. Index. Abrasion, 50, 53, 59 absence of shade, 151 absence of surface drainage, 65 absolute humidity, 102 absorb, 36 abyssal plain, 91 acid, 14, 31 active, 24 adapt, 144 adobe, 63 advanced, 9 afternoon, 111 age, 14 agriculture, 131,188 a hook or recurve spit, 80 air, 101 air in motion, 103 alcohol, 101 Aletsch Glacier, 50 algae, 85 alluvial cone or fan, 63 alluvial plains, floodplains and deltaic plains, 20 alpine, 15 altimeter, 100 altitude, 182 anemometer, 103 aneroid barometer, 100 a net importer. Of food crops, 174 angular distance, 8, 9 animal fodder, 176 annual range, 123,157 annual temperature range, 171 anticlines, 16 anticyclones, 193 aquifer, 36 arable farming, 174 arch, 78 archipelagos, 84 arctic prairies, 193 arcuate deltas, 46 area of lowland, 19 aerates, 50 aridity, 57,142 to 143 artificial embankments, 44 artificial lakes, 72 artificial reservoirs, 74 sins, 100 ash and cinder cones, 24 to 25 Asiatic region, 185 a spring, 37. Atmosphere, 13 atolls, 86 to 88 attrition, 59, 76 Australia, 128,129 autumn, 159,173 average, 97. SI Happy Face Z Happy Face CJ. Backwash, 76, 79 Badlands, 58, 63 Bahada, 64 Bamboo Thickets, 131 Bar, 80 Barconts and Seefs, 62 Barogram, 100 Barometer, 99 Barren, 67 Barrier Lakes, 72 Barrier Reef, 86, 87 Basaltic Rocks, 13 Base of the Regolith, 34 Basin Irrigation, 145 Basin Shape, 38 Batholith, 23 Bayous, 45 Beaches, 79 Beaufort Wind Scale, 104 Beavers, 72 Bedding Plains, 66 Bedouin, 145 been weakened by the action of chemical weathering, 31 Belooker, 124 Benches or Alps, 55 Benguela Current, 94 Bergschrund, 51 Berg Wind, 166 Bindabue or Aborigines, 144 Birdsfoot Delta, 46 Black People, 168 Blizzards, 179,193 Blowhole, 79 Blue Sky, 108 Boll Weevil, 168 Bora, 151 Borax, 74 Boulder Clay, 54 Braided Stream, 44 Brazilian Current, 94 Breakers, 76. Breccia, 14 Bright Sunny Periods, 150 Building, 67 Buran, 179 Bushman, 144 Bushveld, 156 Buttes, 60. Cacti, 144 Calcareous, 14 Calcium Carbonate, 65, 85 Caldera, 24 to 25 Caledonian, 15 Caliche, 146 Californian Current, 95 Calm, 117 Camel, 145 Camouflaged, 136 Camphor, 166 Canaries Current, 94 Canyons, 42, 60 Carbonaceous, 14 Caribou, 194 Carnivorous, 136 Cataracts, 43 Catchment Areas, 40 Cattle, 138, 175 Cattle Breeding and Disease Control, 139 Cattle Country, 139 Caves, 67, 78 Cement, 67 Cereals, 153 Chaparral, 152 Characteristics, 14 Chepka, 63 Chemically Processed Articles, 183 Chemical Ore, Solvent, 41 Chief Highway, 47 China Type, 163 Chinook, 158, 166 Chocolate Making, 175 Cinder Cones, 24 Circular, 86 Circum-Pacific Fold Mountain System, 17 Circum-Pacific Region, 27 Cirques or Cories, 50, 70 Citrus Fruits, 152 Classification of Clouds, 105. Index 197. Clay, 14 Cliffs, 76 to 77 Climate, 30, 31, 35, 97, 108 Climatic Zones, 120 Climatology, 97 Clints, 65 Cloud Cover, 105 Cloud Formation and Precipitation, 109 Cloudiness and Precipitation, 74,122 Clouds, 105, 111 Cloud Type, 105 Coal, 15 Coast, 194 Coastal Plain, 20 Cocoa, 125 Cod Liver Oil, 188 Coffee, 132 Cold Currents, 57, 93,142 Cold Spells, 172 Cold Waters, 93 Cold Winter, 179 Collective Farms and State Farms, 160 Colonization, 132 Commercial Deep Sea, 191 Common Salt, 74 Composite Cones, 25 Compressed and Warmed, 117 Compressional Forces, 18 Concordant, 82 Condensation, 105, 109 Condense, 111 Conduction, 108 Conduit, 25 Confluence, 43 Conglomerate, 14 Coniferous Forest, 178, 187 Conifers, 166, 173, 180 Consequent Stream, 40 Continental, 157,185 Continental Blocks, 19 Continental Interiors, 57 Continentality, 143, 157, 180 Continental Shelves, 188, 190 Convection, 108 Convectional Rain, 123, 179 Convectional Storms, 143 Convection Current, 111 Converge at the poles, 9 Convergence. 112,114 cool brief summer, 179 cooled, 112 cooling effect, 102,135 cool temperate forest, 187 cool temperate monsoon climate, 187 coombs, 68 copper, 146. Coral reefs, 85, 88 core samples, 89 cork oaks, 152 corn or maize, 168 corrasion, 76 corrections, 100 corridors, 60 Corey lake or tarn, 50 cotton, 132,168 crabs, lobsters and shrimps, 188 crag, 53, 54 crater or caldera lake, 25, 71 crescentic, 62 crest, 62, 76 crevasses, 52 crop rotation, 169 crustal disturbances, 23 crystalline, 14 crystals, 14 currents, 155 currents, 76 cuspate deltas, 46 cutoffs or bayous, 45 cyclones, 180,193 cyclonic activities, 112,165,171. Dairy cattle, 175 dairying, 170 dairy products, 175 dampness of, 102 dams, 145 darkness, 5 date palms, 144, 146 dawn, 7 deciduous forest, 131,136, 173,187 decomposition, 30 deepening, 50 deficiency in heat, 193 deficient in humus, 144 deflation, 20 deflation hollows, 59 deflects, 93,114 deforestation, 166 degree of concentration, 92 degree of variability, 97 deltaic fans, 82 deltas, 46 to 47 demersal, 188 dendritic drainage, 40 denser, 93 denudation, 15, 18, 30, 59 deplete groundwater, 39. Deposition, 20, 44, 90 depressions, 118,143,151,158, 164, 186 depth of the water, 85 descending, 142. Desert interiors, 143 desert pavement, 61 deserts, 57 desiccating effect, 142 deteriorates rapidly, 126 dew point, 102 differential heating, 116 diffused or refracted light, 7 dilution, 92 discovery of minerals, 194 diseases, 125 dissected, 19 dissolved, 30 distributaries, 46 diurnal range, 116,143 diurnal range of temperature, 102, 122 diverts, 93 divide or watershed, 40 doldrums, 113,123 doline, 66 dolomite, 65 domesticated animals, 139.160 dominant influence, 93 dormant, 24,136,143 double or treble cropping, 167 double rainfall peaks, 123 down cutting, 46 downs, 157 downward, 41 down warping, 87 drainage, 193 dredging, 47 Drakender, 61 drifters, 188 drizzles, 186 drought, 158 drumlin, 70 dry dusty wind, 151 dry potty, 131 dry period, 131 dry season, 134 dry winds, 117 dry winter, 163 dual purpose, 131 dry season, 134 dry winds, 117 dry winter, 163 dual purpose, 175 dune belts, 80 dunes, 62 durable hardwood, 131 dust storms, 146 dikes, 14.22. L, Z, 11 Earth, 1. Earth movements, 16, 19 earthquakes or volcanic disturbances, 34 earth temperatures, 100 earth tremors, 2S East Australian current, 95, 198 index, East coasts, 114 easterly winds, 186 ecliptic, 6 economy, 130 eddies, 62 edge of a plateau, 43, 91 edge of the ice sheet, 55 efficient, 59 eighths Soractas, 105 elbow of capture, 43 elliptical orbit, 6 entrenched or incised meanders, 47 epicenters, 29 epiphytic and parasitic plants, 124 equable, 172 equinoxes, 7,123 desert, 62 erosion, 19, 40, 53 erosional, 50 erratics, 54 escarpments, 37 eskers, 54 Eskimos, 194 estuaries, 82 estuarine deltas, 46 eucalyptus forests, 152,166 evaporation, 35,109 evergreen trees, 124 excessive heat and high humidity, 125 exfoliation, 59 exotic streams, 63 expands and cools, 32, 59,117 extensive, 159,160 external forces, 30 extinct, 24 extreme diurnal range of temperature, 135 extremes of temperature, 157 extrusive, 14 extrusive landforms, 22. Faintly, 7 fallowing, 133 far less uniform, 187 fast changing, 147 fat, 145 fattening animals, 168 faulting, 17, 43, 67, 69 faults, 18, 28 fermentation, 155 ferns, 187 Farrell's law of deflection, 114 fertile alluvium, 74 fertility, 174 fertilizers, 189 festoons, 84 few species, 180 fjords, 53, 81. Farren, 49 fish breeding, 74 fish conservation, 189 fishing, 48,174 fishing grounds, 90 fishing industry, 188 fishers, 28 fixed dunes, 62 flash floods, 63 fleet, 80 flood plains, 44, 47 fog and mist, 187,193 fan, 158,166 folding, 16 foliage, 136 force, 100 forecast, 97 fossils, 14 free from sediment, 85 free mixing of water, 92 friction, 50 fringing reefs, 86, 87 from the direction they blow, 103 frontal rain, 112 frosts, 32, 58 trillion, 143 billion, 150 million, 179,193 frozen, 193 funnel cloud, 118 fur-bearing animals, 182 furious 50s, 115 furniture, 183 future colonization, 195. FEZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZZ gains, 11 gaps, 86, 28,108 geos, 79 garbi, 151 ghibli, 151 giant sequoia, 152 glacial control theory, 88 glacial drifts, 55 glacial troughs, 52 glaciation, 88 glaciers, 49 glup, 79 gneiss, 15 good pastures, 55 gorges, 42, 47 graben or rift valleys, 17 graduated cylinder, 98 granaries of the world, 159 granites, 13, 14 grapes, 154 graphite, 15 grass temperatures, 101 gravel, 14 gravity, 41 great dust bowie, 61. Great Lisbon earthquake, 28 green pastures, 145 grikes, 65 ground moraine, 53 groundwater, 35 grubs, 169 Gulf Stream, 94 Gulf type, 163 gullies, 63 gypsum, 74. HTTTZZ, carat halves, 72, 80. Hail or hailstones, 111 hanging valleys, 43, 52 hard pans, 144 hardwood, 173 hardy cereals, 195 harmattan, 135,139 haze, mist or fog, 111 headlands, promontories or capes, 77 head of water, 74 heat waves, 186 heavy precipitation, 122 heavy rainfall, 114 heavy showers, 150 heavy snowfall, 179. Herbivorous, 136. Hercynian, 15. Herders, 160 high altitude, 178 higher in the sky, 7 high in summer, 186 highly fluid, 23 highly specialized, 188 highly viscous, 24 high pressure, 116, 118, 128,129 high salinity, 93 high felt, 156 hill fogs, 107 hose and sticks, 133 holds great promise for the future, 139 hollows, 69 homogeneous groups, 183 hops, 175 horizontally, 22 horse latitudes, 113. 142 horse or block mountains, 17 horticultural industry, 174 hot springs, 28 humid atmosphere, 169 hummocks, 54 humus, 126,182 hurricanes, 117, 165 hydroelectricity, 184 hydroelectric power, 47, 56 hydrosphere, 13 hygrometer, 102. Index 199. Iberia, 115 icebergs, 49, 53, 93 icebreakers, 194 ice caps, 49, 192 ice-scoured plains, 20, 55, 70 ice sheets, 49 ice shelves, 49 igloos, 194 igneous rocks, 22 impermeable, 36 indented coastline, 190 indigo, 132 individual soil particles, 33 industrial, 174 industrial alcohol, 176 industrial uses, 183 inlets, coves or bays, 77 insequent streams, 40 insolation, 108. 143 insularity, 172, 187 intense heating, 135 interlocking spurs, 43 intermediate, 185 interment plateaus, 19 internal forces, 30. 63 interrupted or channeled, 151 intersection, 8 intrusive landforms, 22 inwards, 118 ionosphere, 108 irrigation, 74, 131, 139, 145, 154 irrigation canals, 47 isobars, 100 isohalines, 92 isohels, 105 isohyet, 99 isolated residual hills, 60 isonefs, 105 isotherms, 102, 168. Jaffa, 153 Japan, 187 June or summer solstice, 7 Jute, 132. Kiziars LZZ. Kames, 55 Karst regions, 38, 65 Kettle Lakes, 55 Kamseen, 151 Nick Point, 46 Combe, 58 Kuroshio, 95. LZJ Labrador Current, 94 Lakalith, 23 Ladangs, 126. Lagoons, 71, 87 Lakes, 56 Lalong, 126 Land Breeze, 116 Land Hungary, 131 Landslides, 34, 41 Lapse Rate, 110 Large Farms, 194 Lateral Corrosion, 42, 43, 44 Lateral Moraines, 53 Lateritic Soils, 139 Late Summer, 164 Latitudes, 8,100 Latisolic, 133 Lava Bridges, 25 Lava Domes or Shield Volcanoes, 24 Lava Flow, 71 Lava Plains and Basalt Plateaus, 24 Lava Plateau, 19 Lavas, 14, 23 Lava Tongues, 25 Lava Tunnels, 25 Leaching, 139 Leeward Slope, 112 Leguminous Crop, 175 Lavesh, 151 Levees, 44 Lianas, 124 Lie Dormant, 159 Lignite, 15 Limestone Gorge, 66 Limestone Pavement, 65 Limestones, 14 Limon, 63 Line of Bluffs, 43 Lines of Weakness, 16 Liquid, 34,108 Lithosphere, 13 Little Agriculture, 182 Little Attention, 133 Little Vegetation, 63 Live Dunes, 62 Livestock Economy, 145 Livestock Farming, 126 Load, 41 Local Time, 9 Local Winds, 150 Lus, 20, 55, 63,187 Lus Region, 29 Logging and Haulage, 184 Longitude, 8 Long Prairie Grass, 158 Long Roots, 136, 144 Longshore Drift, 79 Long Stapled, 168 Look Green at all times, 166 Lopalith, 23 Lower parts of the valleys, 81 Lower Strata, 107 Lower the temperature, 130. Low humidity, 106 Lowland deciduous forests, 166 low pressure, 116 to 118,128,129 low yield, 160 lubricating action, 34, 41 lucerne or alfalfa, 159 lumbering, 170,182,187 to 188 lure of mineral well. Low humidity, 106 lowland deciduous forests, 166 low pressure, 116 to 118,128,129 low yield, 160 lubricating action, 34, 41 lucerne or alfalfa, 159 lumbering, 170,182,187 to 188 lure of mineral wealth, 146, lying close to the shore, 86. Makia, 152 McKinsey Valley, 179 Magma, 14, 22 Magnificent Scenery, 56 Maze, 160,169 Malaspina Glacier, 50 Mali Scrub, 152 Man, 30 Mandarin Oranges, 153 Mangrove Forest, 124 Manila Hemp, 132 Mantle, 13 Mini Tourists, 150 Maki, 152 Marble, 15 Marine and Fishing Research, 191 Marine Dunes, 80 Marine Erosion, 88 Maritime Influence, 163,165.185 Maram Grass, 80 Mars, 2 Marshy and ill-drained, 180 Mass Movement, 35, 41 Maximum and Minimum Thermometers, 101 Mean Annual Rainfall, 99 Mean Annual Temperature, 92 Meanders, 43 Means, 97 Meat Plants, 168 Mechanical, 41 Mechanical Grinding, 41 Mechanized Wheat Cultivation, 159 Medial Moraine, 53 Mediterranean, 27 Melting, 70 Mercury, 1 Meridians, 9 Mesas and Buttes, 19, 60 Metamorphic or Changed Rocks, 1 Meteorology, 97 Middle, 49 Migration, 62 Milled Rice, 167 Millet Seed Sand, 59 Millibar, MB, 100 Mineral Composition, 14 Mining Activities, 72. Misfit, 43. 200 Index. Mist and Fog, 107,186 Mixed Farming, 174 Moderating, 74 Monsoonal Pattern, 123 Monsoon, 116 Monsoon Winds, 93 Morainic Debris, 70 Most Intensively Tilled, 167 Most Sparsely Populated, 159 Most Varied, 131 Mountain Barrier, 112 Mountain Pastures, 154 Mountains, 150 Mountains of Accumulation, 18 Mountains of Denudation, 19 Mountains of Elevation, 17 Mud, 63 Mudstone, 14 Mushroom Rocks or Gore, 59. RC, T7 Nap, 16 Narrowness, 165,178 Natal Type, 163 National Parks, 137 Natural Rubber, 125 Navigable, 47 Negative Movement, 46. Narungs, 80. Neptune, 2 Net Gain, 7 In Carat V, 49 Never Overhead, 7 Ghana, 139 Nigeria, 138 nitrates, 50 nomadic and semi-nomadic people, 159 non-agricultural, 190 no perceptible current, 94 northeast monsoon, 96,129,130 northern hemisphere, 6,178 north Pacific drift, 95 northwest European maritime climate, 171 northwest monsoon, 164 northwest Pacific, 189 no strong current, 46 notch, 77 not found in pure stands, 124 nunataks, 49 nut trees, 153 pt happy face oak, 166 oases or swamps, 61,146 oats and barley, 175,188 oblique rays, 7 ocean deep, 91 oceanic influence, 171 oceanography, 89 offshore, 57 offshore cold currents, 186 offshore dry monsoons, 128 offshore terrace, 78 offshore terrace, 79 oil, 146 olive oil, 153 olive tree, 153 olivine, 13 onshore westerlies, 150 onshore wet monsoons, 128 opaque, 109 open woodlands, 152 oranges, 153 organic wastes, 167 ornamental lakes, 72 orogenesis, 30 orographic or relief rain, 123,164 outcrops, 40 outwards, 118 outwash plain, 20 overfishing, 189 overfold, 16 overthrust fold, 16 oxbow lake, 45, 71 oyashio, 95. Pack ice, 93 palm trees, 124,166 pampas, 156 pampero, 166 parallel, 8, 62 piranha pine, 166 parasitic cones, 25 part-time lumbering, 184 pastoral, 174 pastoralism, 138 pearl culture, 189 pearl oysters, 189 peat, 14 pebbles, 41, 61 pediment, 64 pediments or pediplanes, 20 pelagic, 188 pelagic deposits, 91 perch blocks, 54 percolation, 69 perishable, 174 permanent drought, 142 permeable or pervious, 36 Peruvian current, 95 Peruvian desert, 141 pervious, 36 facalith, 23 Piedmont glacier, 50 pigs. In poultry, 175 pines, firs, cedars and cypresses, 152,167. Planetary winds, 93 plankton, 90, 188 plantation agriculture, 139 plantations, 125, 132 plateaus, 19,141 playas. Salinas or salas, 64 plowing, 133 plucking, 50 plum rain, 187 plunge pool, 43 platonic rocks, 22 polewards, 184 political boundaries, 48 polges, 67, 71 polyps, 85 porous, 35 portable tints, 194 positive movement, 47 potash, 15 potatoes, 176, 188 prairies, 156 precipitation, 98, 179, 193 prevailing winds, 109 previous day, 102 prime meridian, 9 printing industry, 182 prolific yield, 168 prolonged droughts, 150 prolonged showers, 165 promontories, 77 proportions, 92 protein food, 190 protruding headland, 86 pure stands, 173,180 pustas, 156 pyramidal peak, 51 pyroclasts, 25 quartzite, 15 quartz, mica, feldspa, 14, 32 quebracho, 166 radar sounding, 89 radiation, 107 to 108, 143 rainfall regime, 158 rain gauge, 98 rain or sleet, 111, 193 rain shadow, 112, 141, 173 rain shadow desert, 185 raised beach, 83 ranching, 158 rapid radiation, 135 rapids, 43 ravines, 58 recessional moraines, 53 recumbent fold, 16 reflected, 108 refracted, 76. Index 201. Refreshing sea breezes, 124 refrigerated ships, 161 refrigeration facilities, 176, 190 refrigeration plants, 191 reg, 20. 58 reindeer, 194 rejuvenation, 46 relative humidity, 102,109,124, 142, 179 relief, 30. 36, 173 relief rain, 112 reptiles and mammals,